Grab a standard 12-inch wooden ruler, if you have one handy. Just, hold it in your hands. It feels completely solid, right?
Yeah.
Like dependable.
Yeah, very fixed.
You trust it. It's a foot long, no matter what you do with it. But step into the world of theoretical physics, and that permanence just completely vanishes. Because if you were to throw that ruler like a spear, while it is flying through the air, it actually shrinks. Like it physically becomes shorter than 12 inches.
Which is pretty much the absolute definition of an intuitive nightmare. I mean, the fundamental reality is that the faster you throw that ruler, the shorter it becomes.
Wow.
Right. We base our entire perception of reality on this idea that space and distance are fixed, measurable facts. So to hear that the universe alters the physical dimensions of objects based simply on how fast they are moving, well, it feels almost like a glitch in the matrix.
It really does. Well, welcome to the deep dive. Today we are exploring the ultimate intellectual mystery. What happens when the unbreakable rules of the universe suddenly break?
It's a big one.
It is. For you listening, our goal today is to fundamentally alter how you view the physical world around you. We're looking at Chapter 15 of Richard Feynman's iconic lectures on physics. The mission is to take Albert Einstein's 1905 special theory of relativity,
Which is just a gorgeous piece of science.
this mind-bending framework where space shrinks, time slows down, and mass literally explodes, and make it deeply, truly intuitive. No PhD in mathematics required. So, okay, let's unpack this. Where do we start?
Well, to really appreciate how radical Einstein's ideas were, we have to establish the foundation he was shaking up. For over 200 years, Isaac Newton's laws of motion were basically untouchable. I mean, they perfectly described everything humans could observe.
Yeah, how planets orbit the sun, how apples fall from a tree, how steam engines drive trains.
Exactly. But as we'll see in Feynman's text, when things start moving at speeds close to 186,000 miles per second.
The speed of light.
Right, the speed of light in a vacuum, which physicists designate with the letter c. When you hit those speeds, Newton's physics completely spectacularly falls apart.
So we basically have a clash of titans here. The core contradiction that struck the theory of relativity is this fight between how solid objects move and how light moves. Feynman illustrates this in his lectures by setting up a scenario with two observers.
Yeah, this is a great thought experiment.
Let's imagine you, the listener, are standing completely still on Earth. You are our stationary observer. Meanwhile, a friend of yours is flying past you in a spaceship at a uniform, steady speed.
And according to Newton's principle of relativity, if your friend is inside that ship and has no windows and it's moving in a perfectly straight line at a constant speed, well, everything inside feels like it's standing still.
Right, there's no sense of motion.
Exactly. Your friend can pour a cup of coffee, bounce a ball, or juggle, and the physics inside that ship operate exactly as they do for you standing on the ground. The laws of mechanics are identical for both of you. You can never really feel absolute steady motion.
That part aligns perfectly with how our brains work. Like if I'm on a smooth train ride, I don't feel like I'm moving. And if I'm on that train and it's going 100 miles per hour and I throw a baseball forward at 50 miles per hour.
Someone standing outside sees something very different.
Right. Someone on the ground sees that baseball flying at 150 miles per hour. The speeds just add together. That's a simple Galilean transformation.
Right.
But the text introduces a massive wrench in the gears here.
Oh, a huge wrench. In the 19th century, James Clerk Maxwell's equations for electromagnetism proved that the speed of light is always a constant, 186,000 miles per second. And that's regardless of the motion of the source emitting it.
It just doesn't change.
No. The speed of light is fiercely independent. It simply does not care how fast the flashlight or the star or the spaceship emitting it is moving.
I have to push back here because this is where the mechanics of it seem to break down. Are we really saying that if my friend is in a spaceship going 100,000 miles per second and they turn on a laser pointer facing forward, the light from that laser doesn't go 286,000 miles per second?
It does not.
It doesn't get a, 100,000 mile per second speed boost from the fact that it was fired from a speeding ship.
The math states unequivocally that it does not get a boost. The light from that laser leaves the ship traveling at exactly 186,000 miles per second.
That is just...
And to you on the ground, measuring that beam of light as it streaks past Earth, it is going 186,000 miles per second. To your friend inside the wildly fast spaceship, measuring that exact same beam of light racing away from their ship, it is also moving at 186,000 miles per second.
That fundamentally breaks how our brains are wired to understand motion. It's like throwing a 50-mile-per-hour baseball from a 100-mile-per-hour train, and the person on the ground measures the ball at 50, and you on the train also measure it moving away from you at 50. I mean, the arithmetic simply doesn't add up.
Which meant the physics community of the late 1800s was facing a profound crisis. Maxwell's equations said light was a constant. Newton's equations said speeds must add up. They could not both be right.
So our basic equations of physics were housing this deep, unresolved contradiction. So rather than rewriting the laws of physics immediately, scientists decided to test it in the real world. They assumed that light waves had to travel through some kind of invisible physical medium in space, right? The same way sound waves travel through air, or ocean waves travel through water.
Right. They called this invisible fabric the ether. They reasoned that since the Earth is hurtling through space, we must be flying through this ether, creating an ether wind.
And measuring the physical effect of this ether wind on the speed of light would resolve the contradiction and prove Newton right. So, to do this, two scientists, Albert Michelson and Edward Morley, conducted a really famous experiment in 1887.
Yeah, using a highly sensitive piece of equipment called an interferometer. It used a light source, some mirrors, and a half-silvered glass plate that acted as a beam splitter.
Let me see if I can visualize the mechanics of this for the listener. The setup basically forms a cross, right? You shoot a single beam of light into the center. The splitter cuts the beam in two.
Yep, straight down the middle.
So half the light continues straight ahead to a mirror on the far right. The other half is reflected at a 90-degree angle to a mirror straight up. Both of these mirrors are placed at the exact same distance from the center. The light hits the mirrors, bounces back to the center, recombines, and heads to a detector.
The brilliance of the experiment lies in the Earth's motion. The Earth is orbiting the Sun at about 18 miles per second. So this entire contraption is moving through the hypothesized ether at 18 miles per second. Think of it like swimming in a river. The beam of light moving parallel to the Earth's motion is like a swimmer fighting the current, swimming up the river against the current and then back down with it. The beam going perpendicular is like a swimmer just crossing the river side to side.
And the math of fluid dynamics tells us that swimming up and down a flowing river always takes slightly longer than just swimming across and back, even if the absolute distances are identical. So Michelson and Morley fully expected the light going parallel to the Earth's motion to take a tiny fraction of a second longer. When the two beams recombined at the center, they should have been slightly out of phase, arriving at different times.
But the result was the most famous failed experiment in scientific history. A complete null result. There was absolutely zero difference in the arrival times.
None at all.
None. They rotated the heavy machine on a bed of liquid mercury to eliminate friction. They tested it day and night. They tested it in summer and winter to account for different points in Earth's orbit. The light always took the exact same amount of time. It was as if the Earth wasn't moving through space at all.
Man, they must have been scrambling to figure out why their highly precise machine wasn't detecting the obvious motion of the planet.
Oh, they were. What's fascinating here is the sheer desperation to save the old Newtonian physics. A physicist named Hendrik Lorentz proposed a radical, almost absurd solution. He suggested that the physical arm of the machine pointing in the direction of the Earth's motion was actually contracting. He argued that the pressure of moving through the ether literally compressed the atoms of the apparatus just enough to shorten the distance the light had to travel.
Wait, perfectly compensating for the extra time it should have taken?
Yes. This physical shrinking became known as the Lorentz contraction.
I mean, that is quite the mental gymnastic routine. Instead of admitting that the speed of light is a bizarre constant, they decided the universe actively alters the physical dimensions of solid objects.
Shrinks them down.
Yeah, shrinks them down, specifically to hide the absolute motion of the Earth from us.
The mathematician Henri Poincaré observed this and realized how profound it was. He argued that if nature has designed a complete, flawless conspiracy to prevent you from ever measuring your absolute velocity, well, then that conspiracy isn't just an experimental error.
It's a feature.
Right. That conspiracy is a fundamental law of nature. The laws of physics conspire to ensure you can never detect your own absolute motion.
So if space actually shrinks, if the physical length of a ruler or a machine contracts just to keep the speed of light constant, then we have to look at the other side of the equation. Speed is just distance divided by time.
Exactly.
If the distance part of that equation is physically warping, the time part must be warping as well to balance it out.
Time is indeed the other victim of relativity. And to explain how time warps, Feynman introduces one of the most elegant thought experiments in all of physics. The light clock. Imagine a clock that uses light instead of gears.
Okay, let's build this in our minds. It's a rigid stick, exactly 1 meter long. At the top end, there's a mirror. At the bottom end, there's a light bulb and a detector.
Simple enough.
The bulb flashes, the light travels 1 meter up the stick, bounces off the top mirror, and travels 1 meter back down to hit the detector. Tick. Because the speed of light never changes and the stick is always a meter long, that up and down journey takes an absolutely precise, unvarying amount of time. Tick, tick, tick.
It's the perfect infallible clock. So we build 2 of these exact same clocks. You keep one here on Earth. We give the second clock to your friend, who takes it onto their spaceship.
Okay.
They place the clock standing straight up and down, perpendicular to the direction the ship is going to fly. Your friend takes off, accelerating to a massive fraction of the speed of light. Inside the ship, your friend looks at the clock. The light is going straight up, bouncing, and coming straight down. Tick, tick, tick. Everything seems totally normal.
But the whole point of this deep dive is that our perspectives are different.
Yeah.
Let's picture what you see, standing on Earth, watching that spaceship fly past at hundreds of thousands of miles a second.
This is where it gets weird.
Right. The light leaves the bulb at the bottom of the clock, but the ship is moving forward rapidly. So by the time the light reaches the top of the clock, the top mirror has moved several miles to the right. The light has to aim on a forward diagonal to hit it.
And as the light bounces off the top mirror and heads back down, the bottom detector is also continuously moving to the right. So the light has to angle forward again to catch the detector.
So to the observer on Earth, the light in the spaceship's clock isn't going straight up and down. It's traveling in a massive diagonal zigzag path. It's tracing the long hypotenuse of a triangle through space.
The light is traversing a demonstrably longer physical distance through space to complete one tick. But here is the mechanism that breaks reality. The speed of light cannot increase to cover that extra distance.
It's capped.
It is fiercely capped at 186,000 miles per second. So if the light is forced to travel a longer physical distance, and it is strictly forbidden from traveling any faster, there is only one logical mathematical conclusion.
It has to take more time. The tick itself takes longer to happen. To you, standing on Earth, watching your friend fly past, the light in their clock takes longer to complete its journey. Your friend's clock is literally ticking slower.
The flow of time has stretched. The time it takes for light to traverse that zigzag path is longer than the time it takes to go straight up and down in your stationary clock on Earth.
Okay, I need to clarify something crucial here. Is this just a mechanical illusion? Like, is the clock just behaving weirdly because we constructed it out of light beams? Or does time, as a concept, fundamentally slow down for the human being in the ship?
It is the biological and physical reality of the universe. Time itself slows down. Everything in that moving spaceship slows down from the perspective of the observer on Earth.
Everything.
Everything. Your friend's pulse rate drops, their digestion slows, the rate their brain processes thoughts drops, the rate their cells age, everything. If their biological functions didn't slow down at the exact same rate as the light clock, your friend would notice their heart beating faster than the clock ticking, and they would instantly realize they were moving. And the principle of relativity explicitly forbids that.
That is a lot to accept just from a thought experiment about a stick and a mirror. But Feynman provides actual observable proof of this happening in nature, doesn't he? I mean, we don't have spaceships going that fast, but we do have subatomic particles.
We do. The universe provides a perfect natural laboratory with a particle called a muon. Muons are created when high-energy cosmic rays strike the Earth's upper atmosphere, about 10 kilometers above our heads.
Okay.
Now, a muon is highly unstable. From the moment it is created, it begins decaying, and it disintegrates in an incredibly short lifespan, about 2.2 microseconds on average.
That's 2.2 millionths of a second. That is practically nothing. Even if a muon is hurtling downward at 99% of the speed of light, well, distance equals rate times time. At that speed, in 2.2 microseconds, it should physically only be able to travel about 600 meters before it ceases to exist.
Which means not a single muon should ever reach the surface of the Earth. They should all vanish high in the stratosphere. Yet physicists detect them easily in laboratories down on the ground, 10 kilometers below where they were born.
So how do they make it?
The mechanism that allows them to survive the trip is time dilation. Because the muons are traveling so close to the speed of light, their internal clocks slow down drastically relative to us.
So from the muon's perspective, it only lives for 2.2 microseconds. It experiences a very short normal life. But from our perspective on Earth, watching this fast-moving particle, its internal clock is ticking so slowly that its 2.2 microsecond lifespan gets stretched out immensely.
Exactly.
We see it live long enough to cover 10 kilometers. We are literally watching its time run in slow motion.
If my clock ticks differently than your clock simply because we are moving at different speeds, it forces us to discard the idea that time is a universal metronome ticking steadily in the background of the cosmos. Time is profoundly personal.
That's wild.
And if time is personal, it destroys another core intuition we rely on, the concept of simultaneity, the illusion of now.
Let's dissect the illusion of now. How can two events that happen at the exact same time not actually happen at the exact same time? Let's go back to your friend in the spaceship. They want to synchronize two regular clocks, one mounted at the absolute front of the ship, one at the absolute rear.
Okay, setting the scene.
To be precise, your friend stands exactly in the dead center of the ship. They hold up a flashbulb and trigger it. The light bursts outward, traveling forward and backward. Since the ship's length is constant to the person inside it, and light speed is constant, the light travels the exact same distance to the front and back.
Right.
It hits both clocks at the same moment, and boom, they're synchronized. To the person in the ship, the clocks were struck simultaneously.
That is the reality within their reference frame. But consider your perspective, watching from Earth. You see the spaceship moving forward at a high velocity. When the flashbulb goes off in the middle of the ship, the light starts moving toward the front and back.
Right.
But the rear clock is attached to a ship that is moving toward the backward traveling light flash.
And the front clock is physically running away from the forward traveling light flash. So from the Earth's perspective, the backward traveling light has a shorter physical distance to travel because the back of the ship is rushing up to meet it.
Precisely.
But the forward traveling light has to play catch-up with a front wall that is speeding away.
Since the speed of light is absolutely constant in both directions for you on Earth, the light that has to travel the shorter distance must arrive first. To you, the light hits the rear clock before it hits the front clock.
Wow.
The events were not simultaneous. Your friend thinks the clocks are perfectly synced. You observe that the rear clock is running ahead of the front clock.
So who holds the objective truth? Did the light hit the clocks at the same time, or did one happen first?
They are both objectively right within their own reference frames. There is no master clock in the universe to declare who is truly correct. If we connect this to the bigger picture, it reveals the ultimate architecture of reality. Time and space are not separate, independent arenas where events unfold. They are fundamentally entangled.
Feynman dives into this by introducing the concept of four vectors, which is where the math of relativity actually becomes highly visual. The idea is that we don't live in a 3D universe with a separate clock ticking. We live in a 4D universe, 3 dimensions of space, and 1 dimension of time.
To understand how a four-vector works, think about what a vector is. It's an arrow with a specific length and a specific direction. In our four-dimensional space-time, every object has a velocity vector, an arrow representing its speed through space-time.
Okay.
And the stunning realization of Einstein's math is that the length of this arrow through space-time is always exactly the speed of light. Everything in the universe is constantly moving through 4D space-time at the speed of light.
Okay, let me visualize this with an analogy for you listening. Imagine you're looking at a 3D object, like a long rectangular shoebox. If you look at it perfectly straight on, you might measure it as being purely width. You see zero depth. But if you rotate that box slightly, what used to be entirely width is now a mix of width and depth. The dimensions bleed into each other depending entirely on the angle of your perspective.
The mathematics of relativity, the equations describing space shrinking and time slowing, act exactly like that rotation. If you are standing completely still in space, your entire velocity arrow is pointing directly through time. You're moving through time as fast as possible.
Right.
But when you start moving in a spaceship, you tilt that arrow. You divert some of your speed away from time and into space.
Because the total length of the arrow can never exceed the speed of light. If you spend more of your speed moving through space, you literally have less speed available to move through time. Time slows down. Speed is just an angle in a four-dimensional block.
It is a breathtakingly elegant way to understand the universe. What one observer perceives entirely as a distance in space, an observer moving at a different velocity perceives as a mixture of space and time.
Here's where it gets really interesting, though. If space and time will bend over backward, shrinking and slowing down, just to ensure that the speed of light remains perfectly constant. What happens if I refuse to accept that limit?
Ah, trying to break the rules.
Exactly. Let's say I build a massive, incredibly powerful nuclear engine on a spaceship, and I just keep pouring on the thrust. If I just keep pushing with infinite force, why can't I brute force my way past that 186,000 mile per second barrier?
To answer that, we have to look at Einstein's profound modification to the rules of mechanics, relativistic dynamics. In Newton's universe, the equation for momentum is mass times velocity. If you apply a constant force to an object, its mass stays the same, so its velocity just keeps increasing forever. There is no speed limit.
Well, yeah, there is one.
Right. In relativistic mechanics, because the velocity is strictly capped at the speed of light, the energy you pour into accelerating the object has to go somewhere else.
So if the energy can increase the speed, how does it manifest?
The energy transforms into inertia. It increases the object's mass. The faster you push an object, the physically heavier it becomes.
So the kinetic energy I'm pumping into the engine literally condenses into physical mass. Feynman brings up a staggering real-world example of this happening at the Caltech synchrotron.
Oh, that's a great example.
A synchrotron is a particle accelerator that uses immense magnetic fields to whip electrons around in a circle, pushing them faster and faster. Now, an electron at rest is almost weightless. It has practically zero mass.
But when the scientists at Caltech accelerate these electrons to just a microscopic fraction of a percent below the speed of light, their mass explodes. The electrons become 2,000 times heavier than normal. A near weightless electron suddenly possesses the mass of a proton.
And that immense localized gravity, that mass, is the universe's braking system. The heavier those electrons get, the more energy it takes to accelerate them, even a tiny fraction more. Feynman proposes a hypothetical race to prove the point.
I love this rate.
Right. If you took those incredibly heavy, highly energized electrons from the synchrotron and raced them against a standard beam of light over a 700-foot distance.
The light beam wins. It always wins. But the margin of victory is what is so revealing. Over a 700-foot race, the light would beat those highly accelerated electrons by only 1/1000th of an inch.
Wow.
That is a quarter of the thickness of a standard sheet of paper. The electrons are traveling at astonishing velocities. Their masses have ballooned to 2,000 times their normal state. But the physical laws of the universe dictate they absolutely cannot cross that final millimeter of speed.
This mechanism, this undeniable pipeline where kinetic energy converts directly into physical mass, leads to the most famous equation in human history.
E equals mc squared. Energy equals mass times the speed of light squared. What the synchrotron demonstrates in real time is that mass and energy are not separate phenomena.
They're the same.
They're essentially two forms of the exact same thing. You can convert kinetic energy into mass, creating heavier electrons.
Yeah.
And, far more consequentially, you can convert mass back into energy.
The deep dive in the text gives a chilling reality check on the math behind this. We know how much energy is released in an atomic bomb. If you take an explosion with the destructive force equivalent to 20 kilotons of TNT.
The kind of energy that levels an entire city in seconds.
Yeah, and you somehow manage to gather up every single microscopic particle of dirt, ash, gas, and fallout left over after the detonation.
If you weighed all of that debris, the total mass remaining would be exactly 1 gram lighter than the mass of the reacting material you started with.
That's 1 single gram of physical matter, converted entirely into the raw energy that wipes out a city. Because the speed of light squared is such an astronomically huge number, multiplying even 1 tiny gram of mass by that number yields a terrifying amount of energy.
It really does.
That is the raw, undeniable proof of E equals mc squared. It's not just a clever theory written on a chalkboard. It is the fusion fire that powers the sun and the devastating weapons that shape the history of the 20th century.
It forces us to accept that the solid matter around us is essentially just congealed energy, locked away by the constants of space and time.
Let's pull all of this together. We start with one single, unbreakable assumption discovered in the 1800s. The speed of light is a constant 186,000 miles per second for everyone, everywhere, no matter how fast they are moving.
And simply by following the math of that one fact, we had to abandon everything our human intuition tells us about reality.
We had to accept that the physical dimensions of objects shrink when they move, that time itself slows down to compensate for distance.
That the concept of now is a localized illusion, with simultaneous events disagreeing depending on who is watching.
And finally, that trying to force an object past the speed limit literally turns energy into heavy mass, locking the speed of light as the absolute immovable boundary of reality.
It's incredible.
For you listening to this deep dive right now, you need to know this isn't just science fiction operating in a lab. You are hurtling through space-time at this very second because you are sitting in a moving car or walking down the street or even just sitting on a planet that is rotating. Your personal clock is ticking at a microscopic fraction of a second differently than the GPS satellites orbiting high above you.
Exactly.
The engineers who built your phone literally have to program Einstein's equations into the software to account for the fact that time is moving faster for the satellite than it is for you on the ground. The universe is actively compensating for your daily motion.
Which leaves us with a truly profound implication to ponder. If we accept that your now is different from my now, depending entirely on how we are moving relative to each other, the implications for time are staggering.
Yeah, they are.
If we are moving differently, my present moment might mathematically contain what you consider to be the distant future. Or my present might contain what you consider the established past.
That completely upends the concept of a linear reality.
So the question to ask yourself is this. Is the past truly gone? Is the future actually waiting to happen? Or, from the perspective of an observer flying past our galaxy at near the speed of light, are the past, the present, and the future all existing simultaneously right now?
Are they all just different angles, different rotations of the exact same unchangeable four-dimensional block of space-time?
That's the real mystery.
The idea that every moment in history and every moment yet to come already exists in this four-dimensional block.
Yeah.
That is going to keep me awake tonight. The next time you pick up a 12-inch wooden ruler, just remember, it's only 12 inches long because you happen to be holding it still. The moment you move it, you are interacting with the deepest, strangest mechanics of the cosmos. Thank you for joining us on this deep dive into the architecture of relativity. Keep questioning, keep exploring, and we'll see you next. Usually, when we think about tracking a moving object, there is this massive expectation of overwhelming complexity. Just imagine throwing a standard baseball.
Right.
If you really zoom in and think about it, that ball isn't just a simple white sphere.
Yeah.
It's a cluster of countless billions of individual atoms. And they're all vibrating and spinning and interacting with each other in real time.
Oh, yeah. It's a mess.
Exactly. So if you had to calculate the physics of every single atom just to figure out where that baseball is going to land in a catcher's mitt, it would be utterly impossible.
It would be an absolute computational nightmare. I mean, even our most powerful supercomputers would just completely freeze up trying to track the individual quantum states of a trillion atoms just for a simple game of catch. The math is completely paralyzing.
But physicists don't do that. They don't track every atom.
Yeah.
Instead, they perform this incredible magic trick to just entirely cheat complexity. And today we are going deep into exactly how they pull that off.
Which is such a fun topic.
It really is. We've got an incredible stack of notes and diagrams sourced straight from Chapter 19 of the legendary Feynman Lectures on Physics. And the mission for this deep dive is to basically figure out how chaotic, oddly shaped objects can be mathematically simplified into single, solitary points.
Yeah, and we're also going to explore how those objects resist spinning. Plus, why simply moving in a rotating world summons these bizarre, phantom forces out of thin air.
Right. Because the underlying theme of Feynman's 19th chapter is that the physical rules governing a simple spinning rod on a laboratory table are the exact same rules that explain why a spinning ice skater can seemingly create energy out of nowhere just by pulling their arms in.
It's kind of wild. The universe is incredibly consistent, but it uses that consistency to mask some deeply strange behavior, as you'll see.
So to understand that weirdness, we have to start with the ultimate physics shortcut, which Feynman identifies as the center of mass. From the notes, the center of mass is basically the average position of all the mass in an object.
Right, the average.
And the trick is that if all the external forces hit that one single point, the object accelerates as if its entire mass were concentrated right there. You get to just ignore the chase completely.
It functions as this mathematical balancing act. Imagine you have a broom, right? And you want to support it with just one finger so that it perfectly balances parallel to the floor.
Okay. Yep.
The point where you place your finger, which is obviously going to be much closer to the heavy bristle end than the handle, is effectively the center of mass. And what often trips people up is that this magical point doesn't even have to be physically located inside the material of the object.
Oh, like a hula hoop. That's the perfect example of that.
Yes.
Exact, because the center of mass of a hula hoop is right in the dead center of the empty air. I mean, there is no plastic there at all, but mathematically, that is where the object lives.
Right. And if we look at figure 19:1 from the source text, Feynman provides this brilliant example of how physicists weaponize this concept to avoid doing terrible math.
Oh, the L-shaped thing.
Yeah. So suppose you have the wildly complex asymmetrical object. Let's say it looks like a bulky, uneven L shape made of two distinct parts, piece A and piece B.
Right, so instead of calculating the physics for the whole chaotic shape all at once, you just shatter the problem into smaller, bite-sized pieces.
Exactly. You find the center of mass for piece A alone, and you just pretend all of piece A's weight is a single, tiny, infinitely dense dot at that specific location.
Just a single point.
Yep. Then you do the exact same thing for piece B. Suddenly, your completely chaotic, asymmetrical object has been conceptually reduced to just two tiny dots connected by an invisible line.
Oh, that's so clean.
Oh.
And then the center of mass for the entire object is simply the balanced average between those two dots.
Right. You never have to start from scratch. You just build the physics up from simpler, manageable pieces.
Well, I have to admit, reading through this section, I hit a massive philosophical roadblock.
Oh, what was it?
Well, Feynman points out that we can use Newton's famous law of force equals mass times acceleration on a macro object like a baseball by just looking at its center of mass.
But wait, so Newton's law applies to a giant baseball exactly as it applies to an individual atom. Like, is that a fundamental law of the universe, or is that just some giant cosmic coincidence?
That is such a good question, and Feynman anticipates that exact confusion. His answer is honestly one of the most profound insights in the entire chapter. It turns out Newton's laws are not the fundamental laws of the universe.
Wait, really?
Yeah.
Yeah.
What we are experiencing is an incredibly lucky self-reproducing quirk of scale.
A self-reproducing quirk. You're going to have to break that down for me because that sounds like sci-fi.
Right, so the fundamental rules that govern the universe at the microscopic level of atoms, the realm of quantum mechanics, they're totally weird and completely alien to the physics we experience every day. Atoms do not act like tiny baseballs.
Right.
They teleport, they exist in multiple states at once, they behave like waves, they do their own spooky quantum thing, which just makes no intuitive sense to a human being.
Exactly. But when you take billions and billions of those atoms, all obeying these bizarre, jittery quantum rules, and you lump them all together to form something big enough for us to see those quantum weirdnesses average out.
Oh, like statistical noise.
Yes, the statistical noise cancels itself out perfectly. What emerges from that massive collective average is Newton's laws. And once Newton's laws emerge at that microgram scale, they have this unique mathematical property. They reproduce themselves perfectly at every scale above it.
Meaning, once the mathematical law averages out and works for a single grain of sand, it works exactly the same way for a rock, and then a mountain, and then an entire planet.
Exactly. Feynman notes that human beings were essentially guaranteed to discover Newton's laws first, precisely because they are the laws that survive when you zoom out to our human-sized world. If the universe didn't have this specific property where the laws of motion reproduce themselves on a macro scale, the world would be an unpredictable, chaotic mess. We might never have figured out physics at all because a thrown rock would behave entirely differently than a thrown boulder.
That is genuinely mind-blowing. We are only seeing the smoothed-out tail end of the atomic laws, extrapolated to a giant size.
Yeah.
Okay, so we know what the center of mass is, and we know why it's such a brilliant universe-breaking shortcut that allows our brains to comprehend motion. But practically speaking, how do you actually find that center point for a weirdly shaped object?
Ah, right.
Because looking at the source material, Feynman casually mentions that finding this point is usually the province of integral calculus. And I don't know about you, but mind-numbing calculus is not how anyone wants to spend their afternoon.
Definitely not. Fortunately, Feynman introduces an ancient geometric trick to bypass all that heavy calculus. It's called the theorem of Pappus.
Pappus.
It is a phenomenal way to use three-dimensional geometry to cheat a two-dimensional problem.
Right, the text lays out the theorem like this. If you take a flat two-dimensional shape, like a piece of paper cut into a triangle,
Yeah.
and you sweep it through empty space to make a 3D solid object.
Right.
The volume of that newly created solid equals the area of your original flat shape multiplied by the distance that its center of mass traveled during the sweep.
Yeah, and Feynman asks us to imagine a specific scenario using figure 19:2. Think of a flat right triangle shaped exactly like a wedge of cheese sitting flat on a table.
Okay.
It has a flat base and a tall vertical height. If you stick a pin in that tall vertical side and physically spin the flat triangle all the way around in a full 360-degree circle, it sweeps out a solid shape in the air.
It makes a right circular cone.
Exactly. Because of basic geometry taught in grade school, we already know the formula for the volume of a solid cone. And we already know the formula for the area of a flat triangle. Pappus's theorem links these two known numbers together with the one thing we don't know: the exact distance the center of mass traveled during that 360-degree spin.
Oh! And because the shape spun in a perfect circle, the distance the center of mass traveled is literally just the circumference of its circular path.
You got it.
So you plug in the cone's volume, you plug in the triangle's area, and you just do some basic middle school algebra backward to solve for the exact spot where the center of mass has to be. The math cleanly spits out that the center of mass is located exactly 1/3 of the way across the base.
It is incredibly elegant. You didn't have to slice the triangle into an infinite number of tiny rectangles and integrate them using advanced calculus. You just mentally spun it into a cone and the answer fell right out.
That's amazing.
And Feynman also notes you can use the exact same mental trick on a flat, semicircular disk. If you spin a half circle around its flat, straight edge, it creates a solid 3D sphere.
Oh, right.
By comparing the sphere's total volume to the half-circle's flat area, the formula reveals the center of mass is sitting out in the material, specifically at a distance of 4 times the radius over 3 pi.
Which is, what, roughly 42% of the way out from the center? I love this concept so much. It's like trying to find the exact nutritional value of a single thin slice of bread by baking an entire massive loaf,
Right.
measuring the entire loaf's calories, and then working backward to figure out what was in the slice. It's just a wild mental leap to say, I need to know something about this flat shape, so I'm going to summon a 3D ghost object to find the answer for me.
That analogy captures the essence of theoretical physics perfectly. Physicists are always looking for these hidden symmetries and conservation principles to avoid brute forcing the math. I mean, why do the hard works when the geometry of the universe has already done it for you?
Seriously. But the center of mass only works perfectly if the object is just sliding straight forward, like a hockey puck on perfectly smooth ice.
Sure.
The second that baseball or that asymmetrical L shape starts to tumble and spin, treating it as a single floating dot completely breaks down. The source notes make it very clear that the moment an object starts to rotate, knowing the center of mass just isn't enough anymore.
Right, because when things spin, a whole new physical property takes the wheel. The center of mass tells you where the object balances, but when it rotates, we have to understand how the rest of the object's physical weight is distributed around that center point.
Oh, yeah.
This introduces the concept of the moment of inertia.
Okay, so inertia is just an object's natural resistance to changing what it's already doing. So the moment of inertia is an object's resistance to rotational motion. It dictates how hard it is to get something spinning from a dead stop, or, how hard it is to break it once it's already whirling around.
Exactly. And the crucial detail to focus on here is the formula governing it. The moment of inertia depends on 2 factors: the total mass of the object and the square of its distance from the axis of rotation.
Wait, I'm stuck on the math here. Why is the distance squared? Because if I take a long wooden stick and I tape a heavy weight 1 foot away from my hand, it's a little hard to swing. But if I move that exact same weight to be 2 feet away, shouldn't it just be twice as hard to swing? Why does the universe penalize me by making it mathematically 4 times harder to turn?
That's a great question. It goes back to the fundamental rules of kinetic energy. Think about the physical reality of what happens when you rotate that stick. A point that is further out from your hand has to travel a much larger, wider circle than a point close to your hand.
Yeah, the outer edge is covering way more ground in the exact same amount of time as the inner edge.
Exactly. So to keep up with the rotation and not break the stick, the weight that is further out isn't just moving, it is forced to move much faster. Velocity increases linearly with distance from the center. Now remember the fundamental formula for kinetic energy.
1/2 mass times velocity squared.
Right. It's 1/2 the mass times the velocity squared, because the velocity itself is squared in the energy equation, and the velocity depends directly on the distance from the center. That distance factor gets squared in the final tally. It's a massive compounding effect.
Oh, so it's not just sitting further away, it's actively demanding exponentially more energy because it's being forced to act like a race car speeding around the outer lane compared to the slow-walking mass near your hand.
Yes.
That makes total intuitive sense.
Feynman illustrates this beautifully with figure 19-3. He compares a straight, uniform rod being spun from its very extreme end, like swinging a baseball bat, versus being spun right from its dead center, like an airplane propeller.
Right, and the source material shows the proportional math on this. When you calculate the moment of inertia for swinging the rod from the very end, compared to spinning it from the exact center, the math proves that spinning it from the end is functionally 4 times harder than swinging it from the middle.
Yep. Because when you hold it in the center, half the mass is on the left side, half is on the right side, and importantly, none of the mass is sitting at the extreme far end of the total length. The mass is tucked in much closer to the axis of rotation, so you completely avoid that massive distance squared energy penalty.
And if you don't want to calculate this penalty from scratch, every single time you move your hand to a different spot on the stick, Feynman gives us another incredible escape hatch, the parallel axis theorem.
Oh, the parallel axis theorem is a massive time saver. It states that if you already know how hard it is to spin an object around its perfect center of mass, you can easily calculate how hard it is to swing it around any other parallel axis.
How did that work?
You take that original center of mass inertia, and you simply add the total mass multiplied by the distance you shifted the axis squared.
Oh, wow. So if I know the exact mathematical resistance of a bicycle wheel spinning nicely on its central axle, and I suddenly decide I want to know how hard it is to grab the rim of the wheel and swing the whole thing around my head.
Which would look ridiculous, by the way.
Totally. But I don't have to start over. I just add the mass of the wheel times the radius squared. Boom. Done.
Exactly.
Feynman also mentions the perpendicular axis theorem for flat, two-dimensional plates, where the inertia spinning around the z-axis is just the sum of the x and y axes. Physicists have really built an entire architecture of shortcuts.
They absolutely have. But what happens when the shape changes while the object is already actively spinning?
Oh, right.
This relationship between mass, distance, and spin isn't just a static trick for rigid sticks and wheels. It leads to one of the most counterintuitive, almost magical phenomena in all of physics.
This is where the physics gets deeply weird. We're talking about the turntable and the phantom forces. This explains something that has, always bothered me when watching Olympic ice skaters.
The spin, right?
Yeah. A skater starts spinning with their arms outstretched. They are moving fast, but nothing crazy. Then they pull their arms in tight to their chest, and suddenly they turn into a human blur, spinning at a terrifying speed.
We can explain exactly why using what we just learned about the moment of inertia. By pulling their arms in tight, the skater has drastically reduced the distance of their body's mass from the axis of rotation.
Right, moving the mass closer to the center.
Exactly. Their overall moment of inertia drops like a rock. But because of a strict universal rule called the conservation of angular momentum, the total amount of spin in the isolated system cannot change. If the resistance to spin goes down, the speed of the spin must violently increase to balance the cosmic ledger.
Okay, the fact that they spin faster makes intuitive sense.
Yeah.
You lower the resistance, the speed shoots up. But the source text points out a paradox here that completely broke my brain.
The kinetic energy part.
Yes. If you sit down and actually calculate the rotational kinetic energy of the skater, the raw physical energy of their motion when they pull their arms in, their kinetic energy actually increases.
It goes up significantly. They possess physically more motion energy than they did a second ago.
But energy cannot just be created out of nothing. If angular momentum is perfectly conserved and there are no, hidden motors attached to this ice skater,
Right.
how can they suddenly possess more kinetic energy? Where is that extra magical energy coming from?
The answer is sweat.
Sweat.
Yeah, you have to think about the physical reality of how those arms got pulled in. If you were just standing perfectly still in your living room and you pull your arms to your chest, you aren't doing any meaningful work. But when you are spinning rapidly on ice, there is a powerful outward centrifugal force trying to throw your arms away from your body.
Oh. Like when you spin a heavy bucket of water on a rope.
Yep.
The water desperately wants to fly outward in a straight line, and the rope is the only thing hauling it in a circle.
Right. So to pull those arms inward, the skater's muscles have to actively fight against that massive outward centrifugal force. They are physically doing heavy work. They are burning calories to haul that mass inward against an incredibly strong outward pull. That intense muscular effort doesn't just evaporate. The universe takes the chemical energy the skater burned from their breakfast and converts it directly into the extra rotational kinetic energy of the faster spin.
That is amazing. The skater is literally acting as their own biological engine, injecting physical work into the system. And that shifting mass inside a spinning system introduces us to the final concept in Feynman's chapter, the Coriolis force.
Right. And Feynman uses figure 19.24 to ground this concept. He asks us to imagine a massive rotating turntable, like a playground merry-go-round or a carousel. If you are standing safely on the solid ground watching this carousel spin, and someone riding the carousel tries to push an object straight outward from the dead center toward the outer edge, something very weird happens.
Yet to the observer standing on the grass, the object doesn't look like it's moving in a straight line across the floor of the carousel at all. It curves heavily.
Because the wooden floor of the carousel is physically rotating underneath the object while it moves outward.
But to the person actually riding on the carousel, the experience is totally different. It feels like an invisible hand is aggressively pushing the object sideways as they try to slide it outward. They have to actively lean and fight this phantom sideways push just to make the object walk in a straight line toward the edge.
That phantom sideways push is the Coriolis force. Feynman explains that the magnitude of this invisible push scales up based on three specific things: the mass of the object, the rotational speed of the carousel, and how fast you are walking toward the edge.
But why does nature summon this sideways force out of nowhere? Like if I'm just walking in a straight line on a flat wooden disc, why am I being shoved from the side?
Well, Coriolis force is actually a physical necessity to maintain the laws of physics. Let's think about a giant treadmill or a running track. When you are standing at the very center of the carousel, you are spinning, but your distance from the center is 0.
Right, so I'm not really moving very fast through space.
Exactly. But as you walk outward toward the edge, the outer rim of the carousel is covering way more distance. It is moving much, much faster. To keep up with the floor beneath your feet, you need to gain angular momentum. You need to physically speed up your sideways motion.
Because if I don't speed up sideways, the faster moving floor at the outer edge is just going to sweep my feet out from under me.
Exactly. And angular momentum doesn't just increase on its own. You need a torque, a twisting force to create it. If you tried to slide perfectly outward on frictionless ice, you would lag behind the rotation of the carousel and curve backward.
Oh, I see.
The Coriolis force you feel is the physical manifestation of that required torque. It is the sideways push required to accelerate your body tangentially so you can perfectly match the faster speed of the outer edge.
Oh, wow. So when I feel that sideways pressure pushing against me on the playground, it's actually just my own inertia, resisting the fact that the outer part of the merry-go-round is trying to force my body to travel at a much faster velocity?
Yep. You are feeling the strict physical cost of changing your angular momentum. It's categorized as an apparent force, meaning it only exists because you are trapped inside a rotating frame of reference. But the physical effort your muscles have to exert to fight it is very, very real.
Yeah, your muscles don't know it's an apparent force.
Right. And this isn't just a playground novelty. This exact phantom force is why massive weather systems and hurricanes rotate the way they do.
Oh, sure. Because of the Earth.
Yeah, as air currents move outward or inward across the surface of the Earth, which is basically just a giant spinning carousel, they are shoved sideways by the Coriolis force, creating those massive swirling vortexes we see from space.
Man, that perfectly ties together everything we've pulled from Feynman's notes today. We started with the static, mathematically perfect balance of the center of mass.
Right.
Then we realized that the moment things actually start to rotate, we have to account for the moment of inertia and how mass further out penalizes us and resists that spin exponentially more.
The distance squared.
Exactly.
Yeah.
And finally, when you try to change where that mass is while you are actively spinning, the universe demands you pay a stripped toll in energy and torque, which we experience as real-world centrifugal and Coriolis forces.
It truly is the hidden architecture of motion. The complex math isn't just abstract numbers, it's a way of codifying what the universe rigorously demands to keep everything balanced.
It's incredible. The physics of a spinning skater, a baseball bat, and a Category 5 hurricane all stem from the exact same geometric rules.
It's beautiful, really.
It really is. Well, before we go, there's a final thought I want you to mull over, drawing directly from Feynman's challenge in the text. He notes that if you try to walk a perfectly straight line from the center of a spinning carousel to the edge, you physically have to lean over and push sideways to fight the Coriolis force just to stay straight.
Right.
Well, right now, you are standing on the surface of a giant spinning rock called Earth, and it's rotating at about 1,000 miles an hour at the equator. So next time you take a walk down the street, think about those hidden phantom forces acting on you right now.
Yeah.
How much of your daily intuition about moving in a straight line is actually a massive illusion? completely masked by the fact that you've just grown so incredibly accustomed to the spin of the planet. Keep questioning, keep exploring, and we'll see you on the next deep dive.
If I handed you the mathematical equations governing a simple metal spring bouncing up and down,
Okay.
and then right after that, I handed you the equations for a boom and bust cycle of foxes and rabbits in a forest, you'd probably assume they look entirely different.
Oh, absolutely. I mean, one is rigid mechanics and the other is just, messy biology.
Right. But our mission today in this deep dive is to look at a stack of notes that proves they are mathematically identical.
It's pretty wild.
It is. The physical universe isn't a series of locked rooms with different rules for mechanics and electricity and optics. There is like a master blueprint.
Yeah. And we're looking at Chapter 21 of the Feynman lectures on physics today, which zeroes in on the harmonic oscillator.
Which sounds incredibly technical, but
It's really just demonstrating how understanding one specific mechanical example, like a mass hanging on a spring,
Right.
equips you with the foundational vocabulary to understand sound waves, alternating currents, atoms, and, even predator-prey dynamics.
so it's basically the mathematical master key to almost everything.
Exactly. And it all traces back to the behavior of linear differential equations with constant coefficients.
Okay, let's unpack this. Because in physics, you usually study things in isolation, right? But this strange thing happens where the exact same equations pop up everywhere.
Right, which brings us to what a linear differential equation actually is. I know it sounds like a lot of jargon,
A little bit, yeah.
but it's essentially just a sum of terms involving a variable and its derivatives, all multiplied by constants. It's really the mathematical heartbeat of the universe.
So if I'm understanding this right, learning this one mathematical pattern is like learning a master blueprint that lets you instantly read the architecture of 100 different buildings.
That is a brilliant way to put it, yeah.
Awesome. So let's look at the anatomy of this thing. The notes start with the simplest physical example, figure 21:1. We've got a mass, which we'll call hanging on a perfectly linear spring.
Right. And first, the spring just stretches to balance out gravity.
So it just hangs there.
Exactly. Once it's balanced, we just track the upward displacement from that resting point, and we call that x.
Okay. So what happens when we pull it?
Well, because it's a perfectly linear spring, the force pulling it back is exactly proportional to how far you stretch it. So force equals negative k times x.
And that minus sign is there because...
Because it reminds us it's a restoring force. It's always pulling back toward the center.
Yeah.
So if you set that equal to mass times acceleration, you get the foundational equation. Mass times the second derivative of x with respect to time equals negative k times x.
Okay, but wait. Let me push back on this for a second.
Sure.
If I pull this mass down twice as far, it has twice the physical distance to cover to get back to the middle, right?
Right.
So does it take twice as long to complete a cycle? I mean, my intuition says yes.
Oh, I totally get that. It is a super common misunderstanding. But the answer is no.
Wait, really?
Yeah. If you pull it twice as far, the force is twice as strong, which means the acceleration is twice as great and the velocity is twice as fast.
Oh, I see.
Because of that perfect linearity, it takes the exact same time to complete a cycle. The time pattern remains identical regardless of amplitude.
That is wild.
It is. And there's some specific terminology we should break down here.
Okay, lay it on me.
So amplitude, or A, is the maximum displacement, how far you pull it.
Got it.
Then there's the phase shift, usually a delta symbol, which is where the motion starts from a defined zero. And angular frequency, omega zero, is how fast the phase changes.
And the notes point out a trap here, right? Something people get wrong in the literature.
Yes, a huge point of confusion. Some people call delta the phase, but the true phase is actually the entire quantity, omega zero times t plus delta. Delta is just the shift.
Okay, that makes sense.
Oh, yeah.
But here's where it gets really interesting for me, and honestly, a bit confusing.
Okay, what's throwing you?
When physicists solve this spring equation, the answer they get is a cosine function, like x equals cosine of omega zero t. Why are we talking about cosines? Cosines are for circles and angles. This mass is literally just bouncing straight up and down. There is no circle here.
I know, it feels like a total mismatch. But this is exactly why figure 21.2 is in the text.
Okay, walk me through it.
Imagine a particle moving in a perfect circular path at a constant speed. Got it in your head?
Yeah, just spinning in a circle.
Now, if you track just the horizontal exposition of that object, ignoring the vertical entirely.
Like looking at it perfectly edge on.
Exactly. The acceleration of that horizontal component is exactly proportional to its distance from the center. It's mathematically identical to our bouncing spring.
Oh, wow. So the straight line motion is just a circle viewed from the side.
Precisely. And there's this amazing physical demonstration of it, figure 21-3. Imagine an arc light projecting shadows onto a blank screen.
Okay.
Side by side, it projects the shadow of a vertically bouncing mass on a spring and the shadow of a crank pin spinning in a circle on a motor shaft.
And since they're shadows, they both just look like dots moving up and down.
Right. And if you match the frequencies and drop the mass at the exact right moment, the two shadows move up and down together in perfect, inseparable lockstep.
That is such a cool visual, but I mean, why do we care? What's the point of pretending a spring is a circle?
Well, what's fascinating here is that by artificially pretending the one-dimensional spring is a projection of circular motion, physicists get a massive shortcut.
A shortcut for the math.
Yeah. They can avoid solving incredibly difficult differential equations and just use circular math complex variables instead. It makes the impossible possible.
Okay, so that handles the math side. But what does this all mean for the poor person who actually has to pull the spring?
What do you mean?
Like, how does this bouncing actually begin? How are all these constants decided in the real world?
Okay. So that comes down to initial conditions. The equation dictates the period, how long a cycle takes based on the mass and stiffness.
Right.
But the amplitude and the phase shift are entirely dictated by how you start the motion.
So, like, do I just pull it down and let go?
Yeah, exactly. That would be an initial displacement. Or do you push it as you let go, giving it an initial velocity?
So the spring's stiffness and mass dictate the rhythm of the dance, but the initial conditions dictate how wide you're swinging your arms on the dance floor.
I love that analogy.
Yeah.
Yes. And assuming there's no friction, energy is perfectly conserved throughout this entire dance. It's just a constant tug of war.
Between potential and kinetic energy.
Exactly. The potential energy is stored in the stretch of the spring, and the kinetic energy is all in the speed of the mass.
So how do they fluctuate?
Well, when the spring is fully stretched, at maximum x, the velocity is 0 for a split second, right?
Yeah, as it changes direction.
Right. So at that moment, it's 100% potential energy. But when it zooms back through the middle, where x is 0, it's moving at its absolute fastest, so then it's 100% kinetic energy.
They just trade off back and forth forever.
Precisely. The total energy remains constant. But here's the crucial takeaway for the listener.
Okay, what is it?
The total energy depends on the square of the amplitude.
Wait, the square.
Yes. So if you double the amplitude of the bounce, you aren't just doubling the energy, you're multiplying it by 4.
Wow. Okay, so pulling it twice as far is 4 times the work. That's huge.
It's a fundamental property of the harmonic oscillator.
Okay, so far we've just talked about pulling it once and letting it bounce. But what if we don't just let the spring bounce on its own?
Oh, now we're getting into forced oscillations.
Right. What if we continuously apply an external oscillating force? So the equation becomes mass times acceleration equals negative k times x plus an external force f of t.
Yes. And if we connect this to the bigger picture, we now have two competing frequencies. The applied frequency, which is just omega, and the natural frequency of the spring, omega 0.
And the notes say when you first start doing this, it's kind of chaotic, right?
Very. It's called the transient response. The spring wants to bounce at its natural frequency, but you're forcing it at a different one. It clashes.
But that eventually dies out.
Exactly. Friction eventually kills that initial chaos, leaving only the steady-state response. That's where the mass ultimately surrenders and oscillates at the exact same frequency as your external force.
The text has a great, really relatable analogy for this. Pushing a child on a swing.
Yes, the perfect example of a harmonic oscillator.
Because if you close your eyes and push at random speeds, sometimes you push when you should pull, and the swing goes absolutely nowhere.
You're fighting the natural frequency.
Right. But if you match the natural frequency of the swing exactly, so omega equals omega 0, you achieve resonance.
And that's where the amplitude really starts to build. The equation for amplitude under a forced oscillation is fascinating here. It's the force divided by the mass times the quantity omega 0 squared minus omega squared.
Okay, wait a second. Let me look at that math.
Do you see the trap?
I think so. If my pushing frequency omega is exactly the same as the natural frequency omega 0,
Yeah,
then omega 0 squared minus omega squared just becomes 0.
it does.
We are dividing by 0. Doesn't that mean the amplitude becomes mathematically infinite?
It does. The math literally says the amplitude goes to infinity.
But that's impossible. A kid on a swing isn't going to launch into orbit just because I push him at the right time.
No, of course not. And this is a super common misunderstanding of how the equation applies to reality. Friction, which isn't in this basic idealized equation, eventually steps in to balance things out.
Oh, right. Air resistance, heat in the swing chains, stuff like that.
Exactly.
Mm.
Or, as Feynman points out with his classic dry humor in the text, the amplitude doesn't reach infinity because, well, the spring just breaks.
Right. Materials have limits. The linear rule only works up to a point.
Exactly.
Well, this has been an amazing journey. For you listening at home, we've gone from a simple mass on a spring to the hidden geometry of circles, to the flawless transfer of energy, and finally, the explosive mathematical reality of resonance.
All perfectly connected by linear differential equations.
And the reason this was worth your time today is because understanding this one bouncing weight gives you the foundational framework for how energy and motion interact across the entire physical universe.
It really is a master key. And, I want to leave the listener with one final, mind-bending application of this exact same math. It's mentioned briefly in the text, but we haven't touched on it yet.
Oh, let's hear it.
What if the oscillators aren't weights on a spring, but populations in an ecosystem?
Wait, like animals?
Yes. The exact same equations govern the growth of a colony of bacteria or a predator-prey dynamic. Think about foxes eating rabbits and rabbits eating grass.
Okay.
As the rabbit population booms, they become abundant food for the foxes. So then the foxes boom.
Which means they eat too many rabbits.
Right, causing the rabbit population to plummet, which leads to the foxes starving, so their population plummets, which relieves the pressure on the rabbits, causing them to boom again.
It's just a perpetual mathematical oscillation, a boom and bust cycle.
Exactly. It's a perfect biological spring. So next time you look out your window, try to spot the hidden springs bouncing everywhere in nature. They really are all around us.
Welcome to today's deep dive. If you've ever played a video game, you probably know the power of, like, a developer cheat code.
Oh yeah, like entering a button combination and suddenly you're walking through walls.
Exactly. You input this sequence and suddenly the normal physics of the game, they no longer apply. You can bypass totally frustrating obstacles, bend the rules, completely to your advantage.
Right, it totally breaks the reality of the game.
Yeah, well, today we are looking at the universe's version of a cheat code.
I love that framing. It really is a cheat code.
It is, and our sources for this are centered around Chapter 25 of the legendary Feynman Lectures on Physics. It's titled Linear Systems and Review.
Which sounds a bit dry, I admit, but I promise it's not.
No, not at all. Our mission today is to uncover how this seemingly abstract mathematical concept, linear equations, how it acts as a universal master key for physicists.
Yeah, because we're going to explore how a single structural property of math connects, well, everything. The swing of a pendulum, how your car radio works, even how engineers simulate complex suspensions.
Right, because math in this context, it isn't just like a descriptive tool. It's basically the structural scaffolding of reality.
Absolutely. And we should probably establish right away why physicists dedicate so much of their careers to these linear systems.
Oh, definitely. Because the universe isn't actually linear, right?
No, not at all. The universe is incredibly chaotic. It's highly nonlinear in most places.
So why the obsession with linear math?
Well, simply put, there are the systems we can actually solve, like without relying entirely on just, numerical brute force from massive supercomputers.
Right, it's the math we can actually do on paper.
Exactly. When we can approximate a complex physical phenomenon as a linear system, we suddenly have this rigorous framework to untangle it.
Okay, let's unpack this. Let's lay out the ground rules for this framework. In the text, they use this specific mathematical shorthand, right?
Yeah, they use the operator, which is denoted as this cursive letter L of x.
Right, L of x. And that represents whatever physics formula or force we're hitting our system with.
That's right. And for a system to officially qualify as linear, it strictly has to obey two foundational rules.
Only two.
Just two. The first is additivity. Basically, the operator of x plus y must perfectly equal the operator of x plus the operator of y.
Got it. And the second one?
Homogeneity. If you scale your input by a constant, say, the letter A, the output is scaled by that exact same constant.
Okay, so if I push twice as hard, it goes twice as far.
Exactly. And those two simple algebraic rules unlock what physicists call the principle of superposition.
Superposition. That sounds like a sci-fi movie title.
It does, but it's incredibly practical. It dictates that if you have an incredibly complicated set of forces acting on a system, you are mathematically allowed to just, break that complex force down into separate pieces.
So you simplify it.
Right. You solve for each piece independently, as if the other forces don't even exist, and then you just sum the separate solutions together.
And that works.
Yeah, the final result is a perfectly accurate description of the total system.
That's wild. It's like, think of throwing two pebbles into a still pond at the exact same time.
Oh, that's a great visual.
Right. You have two distinct sources creating ripples. And when the wave from pebble A intersects with the wave from pebble B, they don't, like, crash into each other and create some chaotic new shape.
No, they pass straight through one another perfectly intact.
Exactly. The water's surface right at that point of intersection is just the simple geometric sum of wave A's height and wave B's height.
Yeah, that pond analogy perfectly captures the mechanism of independent variables. And it works because the laws governing the water's surface, at least in that regime, are linear.
So it's not just water, right? What about other areas of physics?
Oh, we see the exact same behavior in electrostatics.
Yeah.
Say you need to calculate the total electric field at a specific point in space.
Right.
You calculate the field vector generated by charge A,
Yeah.
then you calculate the field from charge B completely separately, like charge A is totally gone.
And then you just add them up.
Exactly, you add the vectors. The underlying physics, which are Maxwell's equations, are linear differential equations. So it legally permits this perfect, interference-free addition.
You know, it's like if baking were a linear system. You could
Yeah.
bake the flour, bake the eggs, and bake the sugar in separate ovens, mash them together on the counter, and you'd have a perfect cake.
I mean, it sounds totally absurd in the kitchen, but mathematically, that is exactly how reality works in physics.
That is just crazy. And the sources also talk about how this lets us stack what they call transient and forced solutions, right?
That's a huge part of it.
So if you have a pendulum that's already swinging freely on its own, that's the transient behavior, right?
Yep, the inherent unbothered motion.
And then you start continuously pushing it, which is the forced behavior. You don't have to calculate a brand new complicated motion from scratch.
Not at all. Superposition guarantees that you can just take the free motion, mathematically add it to the motion caused by your pushing, and boom, you have an exact model.
So the system's natural properties and its reaction to what we do to it, they just operate independently.
Independently and cumulatively. The transient solution usually decays over time due to friction, but they just stack perfectly.
Okay, because superposition allows us to independently stack forces, it means we can conceptually separate the forces we care about from the ones we don't.
Yes, and this is exactly how your car radio works.
This is the part that blew my mind. So we're moving from like abstract math into a real-world thing you use every day.
Right, highly dynamic.
So imagine you're driving and two local radio stations are broadcasting at the exact same time. Say station A is at 780 kilocycles and station B is at 550.
Okay.
Both of those invisible electric fields are physically hitting your car's antenna and driving the electrons inside it simultaneously.
Right, the antenna doesn't get to choose which wave hits it.
Exactly. But wait, if the rule of superposition insists that both forces are independently active in the system, how do we ever hear just one song?
It's a great question.
Why isn't it just a garbled mess of two stations overlapping? Does the radio circuit somehow physically block the 550 signal?
What's fascinating here is, no, it doesn't block it at all. Superposition hasn't been violated. Both signals are fully present in your radio.
Wait, really? The unwanted song is in there?
It is entirely in there. The trick lies in resonance. Every radio circuit has a natural frequency, which we call omega 0. It's the frequency the electrons inherently want to oscillate at.
Okay, so when I turn the dial on my dashboard,
You're actually physically adjusting the capacitance or the inductance inside the radio. You are shifting that natural frequency to match the station you want.
so I tune it to 780.
Right. And that creates a very sharp resonance curve. The electrical response spikes massively when the incoming wave aligns perfectly with the circuit's tune frequency.
So it amplifies it.
Exactly. And the response to the off-tune frequency, the 551, it gets no such amplification.
So it's still there pushing the electrons, but it's just tiny.
Microscopic. It's a victory of proportion, really. The station you want is mathematically amplified to a scream, drowning out the microscopic whisper of the one you don't.
Wow. So the unwanted song is literally playing in my speakers. It's just operating at a magnitude so infinitesimally small that my ears just can't hear it.
Yeah, your equipment can't detect it. It's a perfect illustration of how predictable oscillating forces work.
But I mean, physics rarely deals with perfect sine waves, right?
Oh, almost never outside a lab.
Right. So what happens when a system gets hit by a force that is completely chaotic, like, I don't know, a sudden impact or a crazy gust of wind?
Well, the sources outline two profound mathematical methods to handle exactly that. and both rely entirely on this linearity cheat code.
Okay, what's the first one?
The first is Fourier analysis. It's this mathematical proof that any complicated, jagged, irregular curve can be perfectly reconstructed by summing together an infinite number of simple sine waves.
Infinite sine waves. That sounds exhausting.
It is, conceptually. But if your system is linear, you only have to figure out how it responds to one simple sine wave. Then you scale that response and add up the infinite series.
Ah, because L of x plus y equals L of x plus L of y.
Precisely. The sine waves don't interact or warp each other, they just stack cleanly.
Okay, so you build the messy curve out of clean ones. What's the second method? The text mentioned the Green's function method.
Yes, Green's function. Instead of continuous sine waves, this method treats a messy force as a rapid succession of sharp, instantaneous impulses.
Right, the text described it like a succession of blows with a hammer.
Exactly. We know how an object responds to a single, isolated hammer strike, right? It rings out in a damped oscillation.
Like hitting a bell.
Right. So if a force is continuous and messy, the math just models it as a relentless drum roll of tiny hammer strikes.
Oh, wow. So you just figure out the ringing from one tiny strike and then what? Add up all the overlapping rings?
Yep. Using superposition, you just integrate or sum up the overlapping delayed ringing from every single subsequent impulse over time.
And that gives you the exact motion of the messy force. That's brilliant.
It is. And we lean heavily on Fourier and Green's functions because, honestly, if a system is non-linear, these methods completely fall apart.
Why? Wouldn't the hammer blows just add up anyway?
In a non-linear system, the hammer blows would actually influence each other. The sine waves would modulate one another and create unpredictable new frequencies.
Oh, right. They wouldn't stack cleanly.
Exactly. Without linearity, you are forced to step through the problem moment by moment using computer simulations.
Okay, so that brings us to the physical reality of what causes these oscillations in the first place. Like, why do they ring and eventually stop?
The mechanics are pretty clear. Oscillations exist entirely because of inertia.
So, like, a mass on a spring, I pull it down and let go, the spring pulls it back to the center.
Right. But by the time it reaches the center equilibrium point, it's gathered momentum. It literally cannot stop instantly.
So it overshoots.
It overshoots, stretches the spring in the opposite direction, and the cycle continues.
Until friction stops it.
Yes, damping. And the math is particularly elegant when friction is exactly proportional to velocity.
Meaning, the faster it moves, the harder friction pushes back.
Exactly. When you have that kind of damping, the system's amplitude drops by the exact same fraction during every single cycle.
Which creates a perfect exponential decay curve.
Spot on.
But wait, I want to challenge this theoretical extreme for a second.
Yes, go for it.
So, looking at these resonance curves, if I'm reading this right, if we have a system with absolute zero friction and we tap the pendulum perfectly in time, well, the math says the curve goes up to literal infinity.
Yes, it does.
But we can't have infinite energy in the real world, or that's impossible.
You're totally right. You are looking at the mathematical limit. In a theoretical frictionless vacuum, the equation really does run away to infinity because every cycle injects new energy, and there's no mechanism to bleed it out.
But in reality, friction is everywhere.
Exactly. Friction rounds off the peak of that curve. The system's amplitude will only climb till the energy you inject per cycle perfectly matches the energy lost to friction as heat.
So more friction means a lower, wider peak.
Yep. And if the friction is severe enough, it doesn't even oscillate. It just oozes back to zero without a single overshoot.
Okay, so we've got this rigorous understanding of mechanical oscillators. Masses carry inertia, springs provide restorative force, friction bleeds energy.
Right. The fundamental differential equation for that is mass times acceleration plus friction times velocity plus spring stiffness times position equals the driving force.
Here's where it gets really interesting. The profound twist here is that this exact differential equation, letter for letter, governs the behavior of invisible electrical circuits.
It really is one of the most powerful unifiers in classical physics, the direct translation between mechanical parts and electrical components.
So let's look at this dictionary. Inertia, which is mass in a mechanical system, what is that electrically?
That is mathematically identical to inductance. An inductor is just a coil of wire. Once current starts flowing through it, it resists any change in flow.
So it has electrical momentum, just like a heavy block of steel.
Precisely.
And mechanical friction.
That's analogous to electrical resistance. Ohm's law shows that resistance causes a drop in voltage, bleeding energy out as heat.
Exactly how physical friction heats up a brake pad.
Right. And then you have the mechanical spring stiffness, which maps perfectly to the inverse of electrical capacitance.
So a capacitor stores charge between plates the same way a stretched spring stores kinetic energy?
Yes. And finally, the mechanical force is the equivalent of electrical voltage.
The implications of this are just staggering because the equations are identical. The circuit doesn't just approximate the physical thing, it undergoes the exact same mathematical experience.
A circuit with an inductor, resistor, and capacitor will exhibit resonance, overshoot, and decay identically to a mass bouncing on a spring.
And this gave rise to the analog computer. This is so cool. So imagine you're engineering a complex suspension for a heavy military vehicle.
Right, a very non-trivial problem.
You need to know how violently the chassis will shake over rugged terrain. Before digital computers, you couldn't easily calculate that.
No, you'd have to physically build the thing, weld the steel, install heavy springs and hydraulic shocks, and drive it over a track.
And if it fails, you go back to the foundry and start over.
Which is incredibly expensive and slow.
But the analog computer bypassed all of that. Engineers just wired up an electrical circuit on a desk.
They used the mathematical dictionary we just talked about.
Yeah.
They built a circuit where the inductance perfectly matched the mass of the vehicle.
And they picked capacitors to match the stiffness of the steel springs.
And resistors for the hydraulic shock absorbers. Then they just generated a fluctuating voltage to represent the physical bumps of the road.
So if they wanted to test a stiffer shock absorber, they didn't call a mechanic, they just turned a dial to increase the electrical resistance.
Exactly. By reading the voltage on a meter, they knew exactly how the physical steel would perform out in the field.
It just proves nature uses the same underlying logic across vastly different domains. A physical shock absorber is mathematically indistinguishable from a tiny carbon resistor.
It's incredible. But, when engineers build these analog computers or any electrical grid, they deal with massive webs of components.
Right, hundreds of overlapping wires. How do they track the behavior without getting totally lost?
This is where impedance comes in. It's denoted as a Z with a little hat on it. Impedance generalizes resistance, capacitance, and inductance into one mathematical framework.
Okay, so how do they piece it all together?
Well, there are rigorous rules. If components are wired in series in a row, the total impedance is just the simple sum of the parts.
So they just add up.
Yeah, the voltage drops across each piece add up, but the current flowing through that path stays exactly the same.
And if they are side by side?
In parallel, the relationship inverts. The voltage across parallel branches is identical, but the total current splits and divides based on their individual impedances.
To track all those splitting and merging currents, they use Kirchhoff's laws, right? Yeah.
Kirchhoff's first law says the sum of all currents flowing into any junction must perfectly equal the currents flowing out. Electrons can't just disappear.
And the second law?
The net voltage change around any closed loop is always zero. The energy supplied by the source is fully dissipated by the impedances by the time it completes the loop.
So what does this all mean? It sounds to me like it turns circuit analysis into basically a Sudoku puzzle.
That's a perfect analogy.
You take this overwhelmingly complex schematic and methodically step through it. You reduce parallel branches and series loops until the whole board is simplified into a single number.
But we have to remember why this Sudoku puzzle is solvable at scale.
Linearity, right.
Exactly. The ability to break it down step by step is guaranteed by the linearity of the components. Because superposition holds true, the rules of cause and effect are strictly proportional.
So doubling the voltage precisely doubles the current, no matter how many components there are.
Yes. If the components were nonlinear, adding just one more resistor could unpredictably alter the entire grid. Analytical simplification would be impossible.
Wow. Linearity isolates the complexity. It ensures the sum of the parts always equals the whole.
Which is really how we built the entire modern electrical infrastructure.
Okay, let's summarize this journey. We started with a fundamental structural rule of math. If a system is linear, you can dismantle a complex force, solve its pieces, and add them back together.
Right, the principle of superposition.
We saw how that exact mechanism allows a radio to pull one specific broadcast out of a sea of noise. We talked about smashing irregular forces into manageable hammer blows using Green's functions.
And we translated the mechanics of a swinging pendulum directly onto a circuit board.
So linearity really isn't just a trick. It's the scaffolding that makes half of all physics and engineering possible.
It reveals a profound order beneath the surface chaos of the world. Once you grasp it, you see the same equations everywhere. Acoustics, thermodynamics, electronics.
Yet we do have to acknowledge the boundaries here. Feynman explicitly points out that if you pull a physical spring too far, it deforms.
Right, it breaks the cheat code. The force is no longer proportional to the distance.
The mathematical beauty just shatters, and it descends into nonlinear chaos. We really do rely on this small displacement approximation for almost everything we build.
It definitely highlights a tension in physics. Our mathematical tools are incredibly powerful, but they operate within strict physical limits.
Which brings us to a final, slightly provocative thought to leave you with. While macroscopic objects like springs eventually break linearity, Feynman notes that the foundational laws of the universe, like quantum mechanics and electromagnetism, are strictly linear.
To the best of our knowledge, yes.
There is no known amplitude where Maxwell's equations suddenly become nonlinear. So are we simply living in a macroscopic, small displacement universe?
That's a deep question.
Right. Our linear models work perfectly for the sliver of reality we can manipulate. But what if there's a threshold? Could the fundamental fabric of reality itself have a breaking point?
What happens if we pull the ultimate spring too hard?
Exactly. Consider the fragility of that mathematical perfection the next time you tune your car radio. Thanks for joining us on this deep dive. Until next, imagine for a second that you're just looking at a really breathtaking sunset.
Or maybe driving on a hot summer afternoon and seeing one of those, shimmery water mirages on the road.
Yeah, exactly. Or honestly, just think about looking at your own reflection in the bathroom mirror this morning.
Right, something totally mundane.
We take all of those visual experiences completely for granted. But what if the light creating those images wasn't just blindly, ricocheting through space?
Oh, this is where it gets wild.
Right. What if that light is actively choosing the absolute most efficient path to get to your eyes?
That's a huge concept to wrap your head around.
Welcome to today's deep dive, everyone. I'm your host, and I'll be guiding us through this mind-bending topic.
And I'm the resident physics expert, here to help unpack the actual science behind the magic.
Today, our mission is to peel back the curtain on everyday reality. We're using Richard Feynman's legendary optics notes, specifically Chapter 26 of his lectures, to figure out how a simple beam of light seems to, possess a mind of its own.
Yeah, we are definitely going to change the way you perceive something as ordinary as a glass of water.
So to even begin wrapping our heads around this, where do we start?
Well, it's such a staggering shift in perspective that we have to start with a deliberate oversimplification. Physicists call it geometrical optics.
Okay, geometrical optics, meaning what exactly?
Basically, for the first part of this discussion, we are going to completely ignore the fact that light acts as a wave, or that it's made up of individual quantum particles called photons.
So we're just ignoring the really complicated quantum stuff for a minute.
Exactly. We are just going to look at the macro scale. We're treating light like a solid, continuous ray shooting out in a straight line.
Which, makes sense because if I shine a flashlight or a laser pointer, it definitely looks like a straight, solid line.
Right. It feels very linear.
And as long as nothing gets in its way, it just keeps going. Even if I cross two laser beams, they don't crash into each other.
No, they pass right through.
Yeah, they pass right through. The weirdness only really starts when that straight line actually hits something.
And the rules seem deceptively simple at first, like take your bathroom mirror.
Okay, looking in the mirror.
When light hits a flat reflective surface, the geometry is perfectly symmetrical. The angle at which the light ray strikes the mirror is, mathematically identical to the angle at which it bounces off.
Right. Angle of incidence equals angle of reflection. Pretty basic physics.
Exactly. But the real headache for early scientists began when light didn't just bounce, but traveled through a new medium.
Like going from empty air into a dense pool of water?
Yes, the light bends. This is called refraction, and it drove some of the greatest minds of the ancient world absolutely crazy.
Oh yeah, the source material highlights this guy, Claudius Ptolemy, the Greek mathematician from around 140 AD.
Yeah, Ptolemy.
This guy was incredibly meticulous. He just sat there shining light from air into water at countless different angles.
Just measuring over and over.
Right, carefully measuring exactly how much the light bent each time. And he compiled this massive, highly accurate table of raw data.
He had all the numbers right in front of him.
But he could not figure out the underlying mathematical rule. Okay, let's unpack this. Why did it take over a millennium, like a millennium and a half, just to find a pattern in a table of numbers?
It's frustrating, right? But that's the scientific process. First you observe, then you quantify it perfectly. But finding the hidden architecture, tying it all together, that's a monumental leap.
So humanity just sat on Ptolemy's table of numbers for 1,500 years.
Pretty much. The math required a completely different way of thinking about proportions. It wasn't until 1621 that a Dutch mathematician named Wilbert Snell finally cracked it.
Oh, Snell's law?
Yep, Snell's law. Instead of just looking at the raw angles, Snell realized the relationship was tied to trigonometry. He discovered that for any given material, there's a strict speed limit exchange rate.
A speed limit exchange rate. I like that.
Yeah. If you take the sine of the angle the light makes in the air and compare it to the sine of the angle in the water, the ratio is always a specific, unchanging constant.
So for water, that constant, the refractive index is roughly 1.33.
Exactly.
So Snell essentially gave us the ultimate cheat code. We finally had the formula to predict exactly how light would bend in any situation.
He did, but here's the thing. A formula is incredibly useful, but it isn't the true glory of science.
What do you mean?
A formula tells us the what. It lets us predict the outcome, but it leaves us completely in the dark about the why.
Ah, right. Why does light care about this specific ratio of 1.33?
Exactly. To find the physical mechanism behind the math, humanity had to wait another 30 years.
Enter Pierre de Fermat.
Yes. A French mathematician who stepped in and delivered what has to be one of the most elegant conceptual leaps in the history of physics.
Fermat drops this absolute bombshell in 1650, the principle of least time.
Such a beautiful idea.
He argues that out of the infinite number of possible paths light could theoretically take to get from point A to point B, it always takes the path that requires the shortest amount of time.
And that distinction is crucial.
Right, because he doesn't say the shortest distance, he says the shortest time.
That subtle distinction literally changes the entire universe. You can see Fermat's principle at work with a really clever geometric trick involving that simple bathroom mirror we talked about.
Okay, paint a picture for us.
Imagine you want to get a beam of light from a bulb near the ceiling, bounce it off a mirror on the wall, and have it hit your eye in the shortest possible time.
Okay, I'm picturing it.
How do you find the exact spot on the mirror where the light should bounce? You imagine a fake artificial version of the light bulb located directly behind the mirror.
Wait, behind the mirror?
Yeah, the exact same distance into the wall as the real bulb is out from the wall.
Oh, I see. So if I draw a straight line from that fake bulb behind the mirror directly to my eye, the spot where my line intersects the physical mirror, that's the perfect mathematically shortest time path.
You nailed it. And because the light ray arriving at your eye is following that exact trajectory, your brain is completely fooled.
My brain assumes light always travels in a straight line.
Right, so it literally perceives a three-dimensional room and a real bulb existing on the other side of the glass.
That's wild. The illusion of a mirror is just our brain misinterpreting Fermat's principle.
Exactly. But the illusions get even more profound when we apply Fermat's principle to refraction, light bending as it enters water.
Feynman has a great analogy for this in his lectures, right? The lifeguard scenario.
Oh, the lifeguard analogy is brilliant for explaining why light chooses to bend.
Set the scene for us.
Imagine you're a lifeguard standing on a sandy beach. Out in the water, diagonally down the shoreline from you, someone is drowning. You need to reach them in the absolute minimum amount of time.
Well, I mean, I definitely wouldn't run in a direct straight line to the swimmer.
Why not? That's the shortest distance.
Yeah, but a straight diagonal line would plunge me into the water almost immediately. And swimming is vastly slower than running. I'd spend way too much time fighting the resistance of the water.
Exactly. The straight line is a terrible strategy for time. So what do you do instead?
I'd run much further down the beach on the dry sand. I'm taking a longer path geographically, but I can sprint on sand.
Right, you're maximizing your speed.
Exactly. By running further down the shoreline, I minimize the total distance I have to desperately paddle through the slow water. I'd try to find that perfect sweet spot where my fast running balances out my slow swimming.
And that is exactly how light behaves. Light travels faster in the thin air than it does in dense water.
So when a beam of light hits the surface of a pond,
It doesn't go straight. It adjusts its path to spend more time in the fast medium of the air and less time in the slow medium of the water.
that makes perfect sense.
And if you mathematically calculate that exact sweet spot on the shoreline, the one point that results in the absolute minimum overall time, you organically derive Snell's law.
Wow. So the geometry of the lifeguard's shortest time perfectly matches the refractive index.
Exactly. The math and the principle perfectly align.
Wait, so light is actively negotiating a detour? It's looking for the fastest highway to avoid traffic.
What's fascinating here is,
Yeah.
yes, That's exactly what it's doing.
So if we take this out of the laboratory and into the real world, this greediness for time must create some wild phenomena in nature.
Oh, it creates spectacular phenomena. Consider shining a light through a thick rectangular block of glass at an angle.
Okay, glass is much denser than air.
Right, so light moves significantly slower inside it. Rather than plowing straight through on a diagonal, the light beam steepens its angle once it enters the glass.
It takes a sharper, more direct path to get out of the slow glass as quickly as possible.
Yes. And once it bursts back out into the fast air on the other side, it resumes its original angle. The entire beam essentially takes a sideways step just to save a fraction of a nanosecond.
That is amazing. And we actually see this happening on a massive planetary scale every single evening.
We do, with the atmosphere.
Right. The Earth's atmosphere isn't a uniform density. The air down here near the surface is relatively thick and dense, but as you go higher up into the stratosphere, the air gets thinner and thinner.
And because the air is denser at the bottom, light travels slightly slower near the ground than it does in the thin air high above.
So when you watch a sunset, the light from the sun is coming in at a very low angle.
And if that light traveled in a perfectly straight line to your eyes, it would have to slog through thousands of miles of thick, slow air near the Earth's surface.
But the light acts like the lifeguard. It refuses to take the slow path.
Exactly.
Instead, the sunlight takes a higher route through the thin, fast air of the upper atmosphere and then gently curves down through the thicker air right at the end to meet your eyes.
Which leads to a pretty incredible realization.
Yeah. It means when we are watching a beautiful romantic sunset on the beach, the sun isn't actually there. It is already below the physical horizon.
Right. The light is bending over the curve of the Earth to reach us because the high road is simply faster. We are quite literally seeing over the horizon.
It's a breathtaking realization. And what about mirages, like those shimmery water mirages you see on hot asphalt?
They work on the exact same principle, just inverted.
Okay, so how does the inversion work?
Well, black asphalt absorbs the summer sun and gets incredibly hot, which intensely heats the thin layer of air immediately above the road.
And hot air expands, making it much less dense than the cooler air higher up.
Right, so we have a fast lane of hot, thin air right near the ground.
Okay, I see where this is going.
Light from the blue sky is angling down toward the road. But right before it hits the blacktop, it encounters that super fast hot layer. It dips down into the hot air to speed up and then curves back up to hit the driver's eye.
Wow. Because that light from the blue sky is now curving upward at you from the pavement, your brain falls for the same trick it plays with the bathroom mirror.
Yep, it assumes light travels in a straight line.
So your brain firmly believes there is a patch of blue sky physically sitting on the asphalt. And a shimmering patch of blue sky on the ground looks remarkably like a puddle of water reflecting the sky.
Nature accidentally creates these illusions just by bending light through hot and cold air.
But humans figured out how to intentionally trap light and force it to do what we want. We engineered mazes to trick light into arriving exactly where we need it.
Which is the entire basis of lenses, glasses, and telescopes.
So what does this all mean for optics?
In optics, the ultimate goal is achieving a perfect focus.
Yeah.
You want to take light that is spreading out from one specific point and manipulate it so that every single ray converges back together flawlessly at a second point.
But Fermat's rule presents a massive obstacle there, right? Light is greedy. It will only take the path of least time. Right. If I want light to take multiple different routes at the exact same time, say, one ray going straight down the middle, one arching way up high, and one dipping low, and I want them all to arrive at a sensor at the exact same millisecond, the light is going to fight me.
It absolutely will.
If one of those paths is even a fraction of a nanosecond faster than the others, all the light abandons the other routes and just takes the fast one.
Yep. The only way light will agree to take multiple paths simultaneously is if every single one of those paths is tied in a dead heat. They must all take the exact same amount of time.
So to build a functional lens, you have to design a system that brutally penalizes the shortest path.
You hit the nail on the head. You have to equalize the time it takes to travel the short, straight route with the time it takes to travel the long, angled routes.
So a lens isn't just a piece of curved glass. It is a literal time equalizer, like a highly engineered traffic jam.
Think about a standard magnifying glass. It's thick in the middle, and it tapers down to very thin edges.
The geometrically shortest path goes dead center through that lens.
Right. And to stop the light from winning the race on that short path, we intentionally place a massive speed bump in its way.
Glass is a dense, slow medium.
Exactly. By making the center thick, We force the light on the short path to slog through a lot of slow glass, deliberately delaying it.
Meanwhile, the light rays taking the longer angled paths on the outside edge have further to go, but they only have to pass through the razor-thin glass at the borders.
They spend almost their entire journey in the fast air.
So the curve of a lens is meticulously mathematically shaped, so that the thick glass in the middle perfectly compensates for the extra distance on the edges.
Every single path becomes a mathematically identical tie in terms of time.
That is just wow.
And this elegant leveling of the playing field applies to massive telescopes, too.
Oh, like the famous 200-inch Palomar telescope mentioned in the notes.
Yeah, but it doesn't use thick glass to slow light down. It uses the geometry of mirrors. Its primary mirror is shaped like a parabola.
Okay, a parabola.
A parabola is a very specific mathematical curve designed so that if light bounces off any point on its surface toward a single focal point, the total geometric distance is identical.
And because the light is traveling entirely through air, an equal distance guarantees an equal time.
Exactly. The engineering is brilliant.
It really is. But Fermat's principle didn't just explain the tools we built right. It predicted things we couldn't even measure.
It did. At the time Fermat proposed this in the 1600s, nobody had the technology to measure the speed of light in water.
Yet his entire theory hinged on the bold prediction that light must travel slower in water than in air for the math to work.
It was a massive theoretical gamble that turned out to be completely accurate. However, Feynman points out that Fermat's principle introduces a deeply disturbing philosophical crisis into physics.
Okay, here's where it gets really interesting. This is the part of the source material that genuinely broke my brain.
It shatters our intuitive understanding of cause and effect.
Wait, let me explain why it broke my brain. With Snell's law, things make logical sense. A beam of light is traveling, it physically hits the water, the density of the water exerts a physical drag on it, and the light bends, cause and effect.
Right, very mechanical.
But Fermat's principle implies something entirely different. It suggests the light evaluates the entire environment, runs the math on all possible routes, and intentionally chooses the fastest path before it ever arrives.
It does sound like that.
You're telling me a mindless particle of light leaves a star, looks at a piece of glass on Earth millions of years later, and calculates the optimal trajectory. Does light have a brain? How can a photon possibly know where it's going?
Your skepticism is completely justified. This raises an important question. It sounds absurd to suggest that light has a brain or possesses foresight.
Right.
But does the light somehow smell the nearby adjacent paths to check which one is the fastest before it commits to a trajectory?
It physically cannot be doing that.
Well, it absolutely is doing that.
Wait, really?
The light is checking the adjacent paths. Feynman offers a beautiful, tangible way to prove this with a phenomenon called diffraction.
Okay, how does that work?
You can actually do this experiment yourself. Look at a distant, bright point of light, like a street lamp at night. Bring two fingers right in front of your eye and squeeze them incredibly close together, creating a microscopic slit for the light to pass through.
Okay, so I'm looking at a street lamp through a tiny gap in my fingers.
As you squeeze that gap tighter and tighter, the single distinct dot of the street lamp will suddenly blur and stretch out into a wide line with little colored fringes.
The light loses its sharp focus and smears across my vision. Why does squeezing it make it spread out?
Because by making the slit so incredibly narrow, you are building a physical wall that blocks the light from being able to smell or explore its adjacent paths.
Oh, wow.
When you strip away its ability to check the neighboring routes to find the absolute least time, the light loses its perfect, optimized trajectory. It gets confused and spreads out in multiple directions.
So to actually answer how the light is smelling these paths, we have to throw out everything we've talked about for the last 15 minutes.
We do. Geometrical optics, the idea of a solid, continuous ray of light, completely fails us here.
So where do we go?
We have to zoom all the way down to the fundamental nature of reality. We have to enter the realm of quantum mechanics.
Okay, let's go.
At the ultimate microscopic level, a ray of light doesn't actually exist. Light is composed of individual, discrete packets of energy called photons. When highly sensitive instruments detect them, they arrive one by one, like individual clicks on a Geiger counter.
So how does a single isolated photon run the math to find the fastest path?
It doesn't run the math to choose one path. In the bizarre reality of quantum mechanics, a single photon doesn't take the fastest path. It takes every single possible path simultaneously.
You mean it takes the straight path, but it also takes a path that loops around the moon, a path that bounces off the floor, and a path that zigzags through the room. Every single geometric possibility from A to B.
Every single possibility.
That is insane.
It is. And quantum mechanics gives us a fascinating way to visualize this. Imagine we assign a tiny mathematical vector. Think of it as a little arrow with a stopwatch attached to every single one of those infinite paths.
Okay, an arrow with a stopwatch. I'm with you.
As a photon supposedly travels a specific path, the hand on that path's stopwatch spins around and around. The final direction that the little arrow points is determined entirely by the exact millisecond the stopwatch stops when the path reaches the destination.
So a path that takes 1 second might have an arrow pointing up, while a path taking 1.5 seconds points down.
Exactly. And to find the final probability of the photon actually arriving at the destination, you have to take all those billions of arrows for all those billions of paths and add them up tip to tail.
Okay, let me walk through this because I think this is the ultimate aha moment.
Go for it.
We have all these crazy, highly inefficient paths, the ones looping around the moon or zigzagging through the room. Because their distances are wildly different, their travel times are completely random. Their stopwatches are stopping at vastly different times, meaning their arrows are pointing in totally chaotic directions.
Yes.
So when you add all those random arrows together, tip to tail, they just loop back on themselves in a giant tangled knot. They sum to zero.
Yes. The inefficient paths completely cancel each other out of existence.
But wait, what about the fast paths?
Consider the paths that are clustered immediately next to Fermat's path of least time. Because that specific route is the absolute mathematical minimum, the paths immediately adjacent to it take almost the exact same amount of time.
Oh, so their stopwatches are stopping at almost the exact same fraction of a millisecond.
Which means all of their tiny arrows are pointing in the exact same direction.
And when you add those specific arrows up tip to tail, they don't tangle or cancel out. They stack together, building a massive long line in one direction.
Exactly. That long line represents a huge statistical probability that the photon will be found there.
So light doesn't magically know the right path at all.
No, it doesn't. If we connect this to the bigger picture, Fermat's macroscopic principle of least time is really just the macroscopic shadow of this invisible, probabilistic quantum dance.
It literally travels every single conceivable path in the universe, but the vast majority of those paths perfectly annihilate each other. The only paths that survive the cancellation are the ones clustered around the fastest possible route.
You've got it. It forces us to abandon a purely mechanical, predictable universe. It introduces us to a reality governed by probability, interference, and time.
That is unbelievable. We went from Ptolemy pulling his hair out over a table of angles in ancient Rome to a lifeguard sprinting down a beach.
To engineering glass speed bumps in our telescopes.
Right. All the way down to quantum stopwatches canceling each other out across the cosmos. It's just a spectacular journey.
It really is. Feynman had a gift for taking you from the mundane to the profound.
He absolutely did. Well, I want to leave you, the listener, with a final thought to mull over as we wrap up this deep dive.
Oh, this should be good.
The next time you walk into your bathroom and catch your reflection in the mirror, remember what is actually happening in the space between you and the glass. The light bouncing off your face and into your eyes isn't just taking one simple geometric bounce.
Not at all.
From a quantum perspective, that light is actively exploring every single possible route across the entire room. It is mapping the cosmos, checking every corner, and canceling itself out everywhere except for the absolute most efficient path imaginable. All just to show you your reflection.
So, I actually want you to do something for me right now. Just take a look at your smartphone.
Always a good place to start.
Right. But take a second and try to really imagine the sheer, invisible, just completely chaotic web of signals passing right through your body at this very second.
Oh, it's an absolute hurricane.
It really is.
Mhm.
You've got Wi-Fi, cellular networks, radio broadcasts, Bluetooth. It is just an absolute hurricane of electromagnetic noise everywhere.
And we are just sitting right in the middle of it.
Exactly. And yet, somehow, when you click a video on your screen, A specific invisible signal weaves through all of that chaos, finds its way to your specific device, and just plays instantly without getting lost.
Which is, I mean, it feels like magic when you really stop to think about it.
How is that even possible?
Well, we take the modern world completely for granted, obviously, but the physical reality of how we target and, steer that energy is honestly one of the most elegant achievements in human history.
It totally sounds like magic. But the answer is actually a concept called interference.
Yes, interference.
So today, we are taking a deep dive into the mechanics of electromagnetic waves, and we're heavily inspired by the legendary lectures of Richard Feynman, Chapter 29 specifically.
Oh, it's such a classic text. It really breaks it down.
It does. Now, I know the word physics might sound, a bit intimidating to some of you listening, but our mission today is to strip away all the dense calculus.
Please, let's leave the calculus behind.
Yeah, we're going to build a crystal clear mental picture of how energy radiates through space and how scientists use clever spacing and timing to literally bend these invisible waves to our will.
Because that mental picture is everything, right?
Yeah.
We'll look at how a simple moving charge fundamentally alters the fabric of space around it.
And how engineers harness that exact behavior to connect an entire planet.
Exactly.
So I promise you, by the end of this deep dive, you will never look at a radio tower or even the Wi-Fi router sitting in your living room the exact same way again. It is going to be a massive aha moment.
I can't wait.
But, before we can talk about steering a massive wave to your smartphone, we really have to start at the very beginning. We need to understand how a single wave is born.
Right. So to visualize that, you just have to picture a single electric charge, let's say an electron, just sitting there in empty space.
Just floating there. Okay.
Yeah, just sitting there. Now imagine it suddenly gets bumped, so it starts vibrating up and down. That vibration creates a ripple in the electric field around it.
Like dropping a pebble in a pond.
Very much like that. But the crucial part to understand here is that this ripple doesn't happen everywhere in the universe instantaneously.
Okay, let's unpack this. If you bump an electron, the ripple doesn't instantly appear everywhere because there is a universal speed limit, right?
Exactly, the speed of light.
Right, the speed of light. So if you are measuring the electric field from, say, a mile away, you aren't measuring what the electron is doing at this exact second.
No, you're measuring what it was doing a tiny fraction of a second ago.
Okay, yeah, that makes sense.
Feynman uses a very specific term for this phenomenon. He calls it retarded acceleration.
Retarded meaning delayed.
Right. In physics, retarded simply means delayed. Because absolutely nothing can travel faster than the speed of light, that ripple has to physically cross the distance.
It's like my favorite analogy for this. You were standing on a hill watching a massive firework explode in the distance.
Oh, that's a perfect way to look at it.
Right. You see the flash of light almost instantly, but you just stand there waiting. You're waiting, and then boom, the physical sound wave finally hits your chest.
You feel it, yeah.
The shock wave you're feeling is just a delayed reflection of an event that is already completely over.
That is a brilliant way to visualize it. And physicists actually take this a step further with what we call the snapshot concept.
The snapshot concept.
Yeah. So if you could somehow freeze time across the entire universe, just take a snapshot and look at the shape of the electric field radiating outward from that charge. The wave's physical shape in space is literally a reverse timeline of the charge's past acceleration.
A reverse timeline. Wait, so if the charge vibrated really violently and then completely stopped and then vibrated softly,
Yep.
the wave spreading outward would show the soft vibration closest to the charge and the violent vibration much further away.
Exactly, because that violent shake happened first, so it had more time to travel outward.
Oh, well, okay, so it had a head start.
You've nailed it. The field at points further and further away is dictated by the acceleration at earlier and earlier times. It is a literal history of the electron's movement, just written into the space around it.
That is wild. But this makes me wonder, when we talk about these ripples, is the field actually physically moving outward like a solid wave of water on a pond? Or is that just, a helpful metaphor we use to make the math easier to swallow?
Well, what's fascinating here is that the physics reality is that they are mathematically identical.
Wait, really? Identical?
Yeah. To say that light propagates as waves is perfectly equivalent to saying that the effect of the electric field is simply delayed by the speed of light. As time ticks forward, that delay pushes the effect further out into space. The delay itself basically is the wave.
That is wild to think about.
Oh, yeah.
So we have this ripple. This wave of electric field is physically traveling outward at the speed of light.
Right.
But here's the problem my brain immediately runs into.
Yeah.
As this wave gets further and further away, expanding in all directions, it has to get weaker, right?
It does get weaker, yes. But we have to be incredibly careful about how we define getting weaker.
Okay, what do you mean?
Well, we need to contrast the electric field's amplitude, which is the actual physical push, with the energy the wave carries. They aren't the same thing.
Let's break that down. So the amplitude of the electric field drops off proportionally to the distance.
Yes,
So if you double the distance from the source, the physical push of the field is only half as strong.
exactly. But the energy that the wave carries, the actual power it has to work or move another charge that behaves differently. Energy is proportional to the square of the electric field.
Ah, okay. So if you double the distance, the energy doesn't just cut in half. It plummets to a quarter.
Right, it drops much faster.
And if you triple the distance, the energy plummets to a ninth. I mean, that sounds like the energy is just dying out, fading into absolute nothingness very quickly.
It sounds like it, sure, but the universe doesn't actually work that way. The energy is completely unlosable.
Unlosable.
Yeah, Feynman proves this with a really beautiful geometric concept using a cone.
Okay, picture a cone.
Right, imagine you draw a giant cone starting from that vibrating charge, projecting outward into deep space. If you measure the energy passing through a circular slice of that cone at, say, 1 mile away, you get a certain amount of energy per square inch.
And if you measure the slice at 2 miles away, the energy per square inch has plummeted to a quarter of what it was.
Exactly.
Yeah.
But because it's a cone expanding outward, the physical area of that circular slice at 2 miles away has grown by the exact same proportion.
Oh, it is 4 times larger in surface area.
Yes, so the total amount of energy passing through that wider slice is completely identical to the smaller slice.
It's like taking a fixed teaspoon of really thick fruit jam.
Okay, I like where this is going.
Right, so if you spread it on a tiny water cracker, you get a really thick, potent layer of jam.
Delicious.
But if you take that exact same single teaspoon and try to spread it over a giant slice of sourdough toast, the layer of jam gets incredibly thin.
You might barely taste it.
Exactly. But you haven't lost any jam. The total amount of jam in the universe remains constant.
That is a great analogy. And if we connect this to the bigger picture, this exact principle is how we are still able to communicate with deep space probes like the Voyager spacecraft.
Oh, wow, of course. Voyager 1 is currently over, 15 billion miles away from Earth?
Something like that, yeah. It is literally outside our solar system, just flying through interstellar space.
Wait, 15 billion miles? With a signal that drops by the square of the distance. That means the signal reaching Earth must be infinitesimally weak.
Oh, it is a whisper of a whisper. But because of what physicists call the wave zone, the energy isn't gone.
The wave zone?
Yeah, once a wave gets beyond a few wavelengths from its source, it enters this zone where it just expands outward forever. The radio wave Voyager sends back to Earth hasn't died.
The toast it's spread over has just gotten astronomically huge.
Exactly. The toast is the size of a solar system. But as long as NASA has a dish network sensitive enough to catch that incredibly thin layer of jam, the data is still there. The energy is forever.
Okay, my mind's a little blown right now, but that actually sets up our next massive problem.
Which is?
Well, if energy naturally spreads out in all directions forever, spreading thinner and thinner over the cosmic toast,
Yeah.
how do we target it?
Right.
Because if I'm a radio station in California trying to broadcast to a specific city, I don't want to waste 90% of my power sending energy straight up into empty space or backward into an ocean.
No, that would be terribly inefficient. And
Yeah.
that introduces the absolute magic of having two sources instead of just one.
Too soon.
This is the birth of the concept of interference. We stop looking at just one vibrating charge and we build two antennas.
Okay, let's visualize this. We build 2 giant metal towers and we space them a very specific distance apart, say exactly half a wavelength apart.
Right. And by doing that, their expanding ripples start to overlap. And when waves overlap, they basically do one of two things.
They either add together to make a bigger wave or they cancel each other out entirely.
Exactly.
Here's where it gets really interesting. Let's say our 2 towers are in California and the radio station wants to broadcast their show west, straight over the Pacific Ocean to Hawaii.
To achieve that, the engineers pulse the two antennas in perfectly the same rhythm. We call that being in phase.
In phase.
Right, because Hawaii is to the west, the waves from both antennas travel outward together in lockstep, and their peaks combine perfectly.
So the signal gets incredibly strong in that direction.
Yes.
But let's say tomorrow the radio station pivots.
Yeah.
They don't want to broadcast to Hawaii anymore. They want to broadcast north up to Alberta, Canada. Wait, hold on. I'm losing the thread here. Do they physically rebuild the towers? Do they bring in cranes to rotate these massive metal structures 90 degrees?
No, no, the towers never move a single inch.
So what do?
All the engineers do is tweak a clock.
Tweak a clock.
Yeah, they change the electrical phase of one of the antennas so it pulses exactly half a wave cycle behind the other one.
But how does changing a clock steer a physical wave north instead of west? I mean, that sounds impossible.
Think about the geometry, because the antennas are physically spaced half a wavelength apart, and now one is pulsing half a cycle late.
Okay.
The wave heading west from the first antenna completely crashes into the delayed wave from the second antenna. A peak hits a valley.
And they cancel out.
The result is dead silence. They destroy each other.
Oh, me. You.
But heading north, the waves are traveling side by side. The half wavelength physical distance sideways perfectly makes up for the time delay.
You got it.
So heading north, they sync up again. The signal beams north without a single moving part. That is incredible. It is entirely orchestrated by timing. And there is an even more clever, unsymmetrical trick engineers use.
Unsymmetrical.
Yeah, because in the Hawaii and Canada examples, you are still accidentally sending a mirror image of the signal in the opposite direction.
Oh, right. You're broadcasting north to Canada, but also south to Mexico.
Exactly, which is wasted power if your audience is only in Alberta.
Right. So how do you fix that?
To send power in only one direction, they use a brilliant combination of space and time. They physically space the antennas 1/4 of a wavelength apart.
Okay, a quarter wavelength.
Then they delay the timing of one antenna by exactly 1/4 of a period.
Let me puzzle this out. If I'm the wave traveling forward, the quarter wavelength physical head start I have is perfectly offset by the quarter-second delay of the second antenna.
Yeah, so you sync up perfectly forward.
But if I'm traveling backward...
The math flips.
Right. Traveling backward, the physical distance and the time delay stack together. A quarter plus a quarter equals a half. The waves end up exactly half a cycle out of sync. A peak meets a valley. Complete silence backward, maximum power forward.
A perfectly focused beam of energy in a single direction. It's beautiful. And I actually have to point out a quirky terminology issue physicists have here.
Oh, what's that?
Well, in plain English, the word interference sounds negative, right? Like someone running interference to block you.
Yeah, interference is usually a bad thing. It's static on the line or your Wi-Fi cutting out.
Right. But physicists stubbornly use the term constructive interference when the waves perfectly combine to make a stronger signal.
Constructive interference. It almost sounds like an oxymoron.
It really does to anyone else, but constructive interference is the holy grail of signal targeting. The opposite, when they cancel out to create that dead silence, is destructive interference.
Constructive interference. It's brilliant. Let's take a breath, though, because what we've described is already incredible.
It really is.
We are steering literal beams of invisible energy across continents just by changing a microchip's clock.
Yeah.
But two antennas are still relatively primitive, right?
They are, yes.
Because the beam might go mostly north, but it's still bleeding a lot of energy to the northeast and the northwest. It's essentially a floodlight. What if we want a laser pointer?
To sharpen the beam from a floodlight to a laser, we have to expand our array. 2 antennas are a great start, but 6 antennas are much better.
Okay, so we can space 2 antennas really far apart, say 10 wavelengths apart. That creates a very, very sharp beam in the exact direction you want.
It does, but it introduces a massive headache.
Unwanted lobes.
Yes, lobes. Lobes are basically the collateral damage of a wide array. They are extra intense bumps of energy shooting off in completely wrong directions.
Why does that happen?
Because the 2 antennas are so far apart, there are multiple weird geometric angles where the ripples accidentally line up perfectly in phase again.
So you think you are broadcasting a tight laser-focused beam to Canada, but because of these lobes, you're accidentally blasting a random town in Ohio with maximum radio power.
Exactly. And to fix the Ohio problem, engineers don't move the outer antennas. They fill the gap between them.
Fill the gap.
Yeah. They place an additional antenna every 2 wavelengths, creating a solid array of 6 antennas.
Oh, I see.
Because you filled the gaps, the overlapping ripples from the inner antennas end up destructively interfering with the outer antennas at those weird angles.
So they constructively interfere where you want them to in Canada and destructively interfere in those accidental side lobes, smoothing them out to zero.
You've got it. It's all about balancing it out.
So what does this all mean? How do engineers actually calculate 6 overlapping pulsing ripples? I know the source says physicists use 3 different mathematical languages to describe this chaos: trigonometry, an analytical method and a geometric method. But I am a visual learner. If you start throwing sine and cosine equations at me or complex numbers with imaginary variables, my eyes are just going to glaze over.
Well, the analytical method with complex numbers is powerful because the imaginary part of the number handles the wave's phase, while the real part represents the physical wave you actually measure.
Okay.
But you're right, the geometric method is much easier to visualize. Imagine we represent each antenna's wave as an arrow on a piece of paper.
Arrows on a paper. I can do that.
The length of the arrow is how strong the wave is,
Wow.
and the angle the arrow points is the wave's timing, its phase.
Okay, I can picture that.
Think of it like two people pushing someone on a playground swing. The swing is our radio signal.
Okay.
If both people push forward at the exact same moment, meaning their arrows point in the exact same direction, the swing goes twice as high, that is constructive interference.
Right. And if we draw that, we just place the second arrow at the tip of the first one, making a giant arrow pointing forward.
Exactly. And if they are out of phase, one person pushes forward while the second person pulls backward.
The swing doesn't move at all. Dead silence.
Right. On paper, one arrow points right, the other points left, and they cancel each other out to zero.
Now, imagine 6 people standing around the swing, all pushing at slightly different times.
Yes. To figure out where the swing is going to go, you just draw the 6 arrows tip to tail, each angled to represent their specific delay.
And wherever the final arrow ends up pointing, that's your beam.
That's your beam. It allows engineers to visually and perfectly balance an array of 6 or 60 or 600 antennas.
Wow. It isn't just an abstract math trick. It represents the literal lockstep phase relationship of the physical towers pushing out energy. You can literally draw arrows on a piece of paper, connect them tip to tail, and know exactly where your radio wave is going to hit hardest.
It is a phenomenal tool, but this raises an important question about unintended consequences.
Uh-oh. Unintended consequences.
There is a very strict warning in the physics of interference. Even with 6 perfectly tuned antennas, if the physical spacing between them is larger than one single wavelength, it is a mathematical certainty that at some extreme angle, the distance delay will exactly equal one full wave cycle.
Wait, if the delay is exactly one full cycle, that means the wave has completely reset.
Yeah.
They all accidentally realign again.
Yes. They will constructively interfere and create a massive, strong beam in a direction you absolutely did not intend.
For a radio station, this is a disaster. You are violating federal regulations and jamming someone else's signal.
It's a huge problem for radio, but what is terrible for a radio station turns out to be a superpower in other fields.
Oh, really? Like what?
We purposefully use this flaw in optics to build things called diffraction gratings.
Diffraction grating.
A diffraction grating is essentially an antenna array for visible light.
But because different colors of light have different wavelengths, they bounce off at slightly different extreme angles.
Exactly.
So it acts like a high-tech prism. It splits the light apart.
It does. And astronomers use these gratings to look at the light from distant stars, splitting it into a barcode of colors to figure out exactly what chemicals are burning inside a star millions of light years away.
And it's all using the exact same math that steers a radio wave to Canada.
It all comes back to the geometry of overlapping ripples.
That is just incredible. Let's bring this all home.
Oh.
Think about the massive journey we just went on. We started with a single, lonely vibrating electron, delaying space and time just to push a ripple outward.
Yeah.
We saw how that energy never dies.
Mhm.
It just spreads across the cosmos, carrying whispers to deep space probes.
And we learned how human ingenuity figured out that by placing multiple antennas near each other and simply tweaking the timing of their pulses, we can steer invisible beams of energy across continents without moving a single piece of metal.
So the next time you are sitting on your couch, streaming a high-definition video, or sending a text message, remember this. You aren't just magically receiving data.
No, not at all.
You're sitting directly inside a carefully orchestrated, mathematically precise, invisible matrix of constructive interference. Antennas miles away are literally timing their invisible ripples to peak at the exact moment they pass through the microchip in your hand.
It turns that hurricane of electromagnetic noise into a beautifully targeted delivery system.
It is absolutely mind-bending. But before we wrap up, I want to leave you with one final provocative thought built on all of this science.
So let's hear it.
We've been talking heavily about radio waves and Wi-Fi, but visible light, the light we see with our very own eyes, is the exact same thing. It is an electromagnetic wave, just with a much, much smaller wavelength.
Right. I think I see where you're going with this. Destructive interference on a visual scale.
Exactly. If we can perfectly control the phase of radio waves to cancel them out or steer them around, what if we could eventually do the exact same thing with the atoms emitting visible light?
Oh, wow.
Could we one day perfectly calculate the incoming light waves bouncing off an object and broadcast the exact opposite phase to perfectly cancel them out?
A peak meeting a valley, but for the light hitting your retina.
Could we literally make a physical object completely invisible to the human eye just by manipulating the physics of interference?
It sounds like pure science fiction.
It really does. But the math tells us it is exactly the same as steering a radio signal away from a town in Ohio.
When you look at the world around you, you're looking at a chaotic web of waves. And the better we understand the math, the more that chaos looks like a canvas we can paint on.
Something for you to ponder the next time you turn on the Wi-Fi.
So the next time you look in the mirror, you aren't just seeing a simple reflection. You're actually looking at the single surviving angle of this chaotic, microscopic wave war.
Yeah, wave war is a great way to put it, honestly.
Right. I mean, billions of tiny waves are constantly colliding, adding together, and, completely destroying each other, all just to project that seemingly solid image back at you. So welcome to the deep dive.
Thanks for having me. I'm excited to get into this one.
Me too.
Oh, yeah.
Because our mission today is to unpack a really legendary source, Chapter 30 of the Feynman Lectures on Physics, which is all about the concept of diffraction.
And look, if you just glance at the raw source material, it's incredibly dense.
Oh, totally. We're talking pages of, complex wave math, geometric diagrams, highly theoretical calculus. But our goal today is to translate all that math into a vivid, intuitive understanding of how waves actually shape the reality you see every single day.
Exactly. From, like, the rainbow sheen on a puddle of oil in your driveway to the very shadows you cast on the sidewalk.
Yeah, and it really fundamentally changes how you perceive the physical world. I mean, we tend to expect our reality to have these sharp, clean edges, right?
Right, like a shadow is dark, light is bright, a mirror is just this smooth, flat surface.
Exactly. But when you zoom into the actual mechanics of how light waves interact, that clean binary reality just completely blurs into this landscape of intricate overlapping ripples.
It does. And, let's start by clearing up this massive branding issue that the source material points out right away.
Oh, yeah, the terminology thing. I'd always been taught that interference and diffraction were two totally different physical phenomena.
Yeah, it's a remarkably common misconception, even in, higher-level science classrooms. But the text is completely unambiguous about this. There is zero fundamental physical difference between interference and diffraction.
None at all.
None. The underlying physics is identical. It purely comes down to, well, how many wave sources we happen to be talking about at the time.
Okay, so if you have just a few sources of waves, say, like two distinct slits letting light through, physicists conventionally call that resulting pattern interference, right?
Right. But the exact moment you scale that up to a large number of wave sources acting together, everyone suddenly switches the terminology and calls it diffraction.
So it's literally just a naming convention.
It is, yeah. I mean, whether it's 2 waves or 2 billion waves, the universe is just doing the exact same mathematical addition.
And the way this source material explains that addition is honestly incredibly visual. It kind of strips away all that heavy algebra and uses this brilliant geometric analogy.
Arrows, right.
Yes. It asks you to imagine every single wave source as an arrow, like a vector. And the length of the arrow represents the strength or the amplitude of the wave.
Right, and the direction the arrow points represents its phase, which basically just means what part of the wave cycle it happens to be in at that exact moment. Like, is it at the peak, the valley? Right. Somewhere in between.
Yeah, and adding those waves together to see what the final light looks like is simply a matter of laying those arrows tip to tail, almost like you're walking a path.
Exactly. You take a step representing the first wave. If the second wave is perfectly in sync with the first, meaning it's, perfectly in phase, your second arrow points in the exact same direction.
So you just keep walking straight. And the total distance you cover gets longer, meaning the light gets intensely bright.
But if the waves are slightly out of phase, meaning one is just a little delayed compared to the other, you have to turn slightly after that first step.
Okay, so you walk 10 paces, turn a few degrees, walk another 10 paces, turn again. You're basically tracing out the sides of a polygon.
Right. And if you have a lot of waves, all slightly increasingly delayed, you just keep turning with every step. Eventually, you turn so much that you walk yourself right back to the exact spot where you started.
The path just forms a closed circle.
Which is really the ultimate aha moment of wave mechanics. Ending up geometrically back where you started means the net result of all those arrows is just zero.
And this point is called the first minimum, right? It's a location where all these different overlapping sources of light have completely canceled each other out to absolute zero. You get total darkness.
Total darkness. Conversely, if you find a spot where all those arrows point in the exact same direction, you get this massive, towering, central spike of brilliant light. And it's surrounded by these tiny little ripples of brightness where the arrows only partially cancel.
Okay, hold on. My brain is glitching a bit here. Because if I shine a flashlight at a wall, it gets bright. If I shine 2 flashlights at the same spot, it gets brighter.
Sure.
So how can adding light to light ever mathematically or like physically result in pitch blackness? Aren't we destroying energy by doing that?
It definitely feels counterintuitive, but no energy is being destroyed.
Yeah.
You are essentially just rearranging the furniture.
Rearranging it how?
Well, when waves perfectly cancel each other out in one location to create darkness, that energy doesn't just vanish from the universe. It is physically pushed away from those dark spots and just crammed into that massive central spike of brightness we just talked about.
Oh, wow. Okay, so the total amount of energy across the entire wall is identical to what the flashlights put out.
Exactly. The wave interactions are just strictly dictating where the light is allowed to exist and where it is, forbidden.
That is wild. So if nature does this organically, how do we force waves to do this on purpose? Like, how do we build a tool that manipulates these cancellations to do something actually useful?
Well, that brings us to a brilliant piece of engineering called a diffraction grating. Picture a perfectly clear, flat piece of glass.
Okay, got it.
Now, imagine using a microscopic tool to cut thousands of incredibly fine, equally spaced parallel notches right into the surface of that glass.
Like thousands of invisible parallel scratches just side by side.
Yeah. And when a beam of incoming light hits that scratched glass, the electric field of the light literally grabs the electrons in the glass and shakes them up and down.
Because the way the notches are spaced, right?
Right, so each individual scratch acts as a completely new, independent broadcasting antenna for the light. This is called scattering. So instead of one light beam shining through, you now have thousands of tiny new beams spreading out in all directions.
And because we know different colors of light have different wavelengths, like red light is a long wave, blue light is a short wave, that arrow walking path we just described closes its circle at totally different angles depending on the color.
It's the varying wavelengths that do the trick. Because a red light wave is stretched out longer, its phase shift is different than blue light.
So when you're drawing those arrows tip to tail, the red arrows take longer to turn and close the circle. They get pushed out to a much wider angle before they finally align to create a bright spot.
Exactly. So the grating is literally weaponizing wave cancellation to physically rip white light apart.
It separates it into a spread-out rainbow because the red light waves survive the cancellation war at a wider angle than the blue light waves do.
And engineers have perfected this to an absolute art form. The source text mentions that they don't just make simple scratches anymore. They use specialized tools to cut the notches into microscopic saw-teeth shapes.
Oh, right, because that specifically biases the timing or the phase of the scattered waves.
Right. Instead of spreading the rainbow out faintly everywhere, the sawtooth shape forces almost all of the light energy into one specific, highly usable, intensely bright beam.
Okay, so as I was reading through the section on these gratings, this profound realization kind of hit me. The text explores what happens if you take those microscopic scratches and bring them closer and closer together.
Yeah, keep going.
Eventually, if the scatterers are infinitely close, you don't have a grating anymore. You just have a perfectly smooth, solid piece of glass.
A mirror.
Yes. And the math in the source proves that when you do that, the only angle where the light waves survive, the only place the arrows don't form a closed circle of darkness, is where the angle of the light coming in exactly matches the angle bouncing out.
So everyday reflection is nothing more than billions of tiny, newly scattered waves radiating in every possible direction from the atoms in the mirror, but perfectly, mathematically canceling each other out into total darkness everywhere except at that one specific angle.
Is this deep dive literally telling us that everyday reflection in a mirror is just a special case of diffraction?
It is. Reflection isn't just a Banksy ball hitting a wall.
Yeah.
It is an infinite wave cancellation machine.
That is absolutely stunning. A mirror is actively suppressing light in every direction except right back at your eyes.
Okay, so if we can use gratings to separate colors by their angle, the next logical question is about precision, right?
Precision, yeah.
If two colors of light are almost completely identical, how do we tell them apart? Well, this introduces a really critical concept called resolving power. which is governed by a rule known as Rayleigh's criterion.
Rayleigh's criterion.
Right. To visualize this, think of the brightness pattern of a color as a mountain. A massive central peak with a dark valley right next to it where the light canceled out. If you have two slightly different colors, you have two mountains side by side.
Right. And if they're too close together, the peaks just merge. They look like one big blurry plateau of light, and you can't even tell that there are actually two distinct colors there.
Exactly. So to definitively tell them apart, to, resolve them, the absolute peak summit of one color's mountain must sit perfectly inside the dark valley, the first minimum of the other color's pattern.
Oh, I see.
If they're any closer than that, the physics of the waves simply won't let you distinguish them.
And what's wild is that we can scale this exact same microscopic glass scratch math up to the size of a continent. In the source material, this directly applies to the giant radio telescopes we build out in places like the Australian outback.
Right, instead of microscopic notches cut into glass, you have a massive array of towering radio antennas spaced out over miles of desert.
But the array behaves exactly like the grating.
Exactly like it. The antennas are working together to find the precise angle where a faint radio signal from a distant galaxy is strongest. And the absolute smallest angle they can resolve their ultimate precision is elegantly simple.
It's the wavelength of the radio wave divided by the total physical length of the antenna array, right?
You got it. Theta equals lambda over L. So the longer you build the array across the desert, the smaller the angle you can pinpoint, and the sharper your resolution gets.
But there's a principle introduced here in the text that feels, totally backwards at first glance. It's called the reciprocity principle.
Ah, yes. It states that the receiving pattern of an antenna is perfectly identical to its transmitting pattern.
It is a profound symmetry built right into the laws of electromagnetism. The geometry works the exact same way forwards and backwards.
It really does.
So, just to make sure I'm wrapping my head around this analogy, if I want to know exactly how well my giant, miles-long radio telescope can hear a faint, distant star, I just have to flip the script.
Flip it how?
I imagine the telescope acting like a giant speaker, shouting radio waves out into deep space, and wherever that imaginary shout is mathematically the loudest, that is precisely the exact spot in the sky where the telescope's ear is most sensitive.
That perfectly captures the reciprocity principle. And, this exact symmetry is why we shape telescope mirrors or satellite dishes into parabolas.
Oh, because of the curve.
Yeah. A parabola is uniquely designed by geometry so that if you were broadcasting a signal from the focal point in the center, every single wave would bounce off the curved dish and shoot out into space, perfectly parallel, perfectly in sync.
Because the distance from the focus to the dish and out to a flat plane is the exact same for every single path.
Precisely. So just run that in reverse. When faint, parallel waves from a star millions of light years away arrive at that parabolic dish, the curve ensures that every single wave bounces and hits the receiver in the center at the exact same moment.
Zero time delay.
Zero. The arrows all line up tip to tail in a perfectly straight line, giving you maximum intensity.
This wave addition is dictating everything from massive deep space telescopes to highly engineered optics. But I want to bring this down to Earth for a moment.
First, let's do it.
Where can you see this chaotic wave war happening without stepping into a laboratory or driving out to a radio observatory?
Well, you honestly don't have to look any further than a parking lot after a rainstorm.
The oil slicks.
Exactly. When you see those beautiful swirling rainbow colors in a puddle of oil, or when you blow a soap bubble, you are witnessing thin film interference.
How does an oily puddle act like a highly engineered diffraction grating, though?
It all comes down to the thickness of the film. When sunlight hits that incredibly thin microscopic layer of oil floating on top of the water, some of the light reflects immediately off the top surface of the oil and hits your eye.
Okay.
But some of the light travels through the oil, hits the boundary of the water underneath, and reflects off that bottom surface, traveling back up to your eye.
So for every single beam of sunlight, you suddenly have two waves coming back at you. One from the top of the oil, one from the bottom.
And because the oil film isn't perfectly flat, it swirls and thins out at the edges, the physical distance that second bottom wave had to travel is constantly changing.
Right.
So at one specific thickness, the extra distance the bottom wave traveled might perfectly align its arrows with the top wave for, say, red light. They constructively add up, and you see a bright red swirl.
But at that exact same microscopic spot, blue light, which has a shorter wavelength, traveled just enough extra distance that its top and bottom waves are totally out of sync.
Exactly. They form a closed circle, and cancel each other out to zero. The blue is destroyed.
So as your eye scans across the varying thickness of the puddle, the physics of the wave cancellations strictly dictate which colors survive and which are plunged into darkness.
It's really beautiful to think about. And the source takes this concept from flat puddles into the 3D realm with crystals.
Oh, right, because crystals are essentially just three-dimensional diffraction gratings naturally built out of atoms.
Yeah. The atoms in a crystal, like salt or diamond, are spaced out in perfectly repeating geometric grids, exactly like the engineered notches on the glass grating we talked about earlier.
But we can't use visible light for that, can we? I mean, the wavelength of everyday light is way too large to see individual atoms.
Yeah, visible light would just wash right over the atoms like a massive ocean wave rolling over a tiny pebble. The wavelength is thousands of times too big.
So what do they use?
To see the atomic grating, scientists use X-rays, which have incredibly tight, short wavelengths that perfectly match the tiny gaps between atoms.
So they shine an X-ray beam into a crystal, place photographic film or a detector around it, and just wait to see where the bright spots emerge.
Right. And by mathematically reverse engineering the angles of those bright spots, the places where the X-ray waves constructively interfered, scientists can deduce the exact, precise layout of the atoms inside.
Which means we literally mapped the three-dimensional atomic structure of table salt and even unlocked the famous double helix shape of DNA without ever actually seeing a single atom.
It is arguably one of the greatest detective stories in the history of science.
We deduced the most fundamental building blocks of life entirely by reading the shadows and the bright spots where invisible X-ray waves perfectly canceled each other out. That's just wild.
It really is.
This idea of waves mapping the invisible is incredible, but you don't actually need X-rays or microscopic crystals to see this wave war in action. You just need to look at something that completely blocks the light, an everyday shadow.
Shadows are fascinating, mathematically speaking.
Yeah, because I think most people assume a shadow is just a clean break. You know, there is light, a sharp edge, and then darkness.
Our eyes certainly trick us into believing that.
Mm-hmm.
But the math in the source material reveals a reality that is vastly weirder. If you take a magnifying glass and look extremely closely at the edge of a shadow cast by a distant light source, the light intensity doesn't just abruptly drop off a cliff into total darkness.
It does something genuinely crazy. Just before the edge of the shadow, the intensity of the light actually rises.
Yeah, it overshoots.
It overshoots the normal brightness of the room, and then it wobbles. It oscillates up and down, brighter, darker, before finally fading out into the dark region. So why on earth does a shadow wobble?
It all comes back to the geometry of our walking arrows. When we were calculating waves coming from an infinitely distant star, the phase delay from different points changed linearly. But when you were looking closely at the edge of a nearby shadow, the geometry fundamentally shifts.
How so?
Imagine looking straight past the edge of the object blocking the light, versus looking slightly off to the side.
Right. If you look to the side, the light has to travel a slightly longer diagonal path to reach you.
And because of the Pythagorean theorem, as you move further away from that direct line of sight, the extra distance the light has to travel doesn't just grow steadily, it grows exponentially.
Oh, I see.
The phase delay increases as the square of the distance from the edge.
So when you draw the arrows to add up those waves, you aren't just turning a steady few degrees with each step. The amount you turn gets violently larger with every single wave you add.
The arrows turn faster and faster, so instead of tracing out a neat repeating circle, the arrows start to spiral inward. They wind tighter and tighter around a central point.
And this specific mathematical shape is called Cornu's spiral, right?
Yes, Cornu's spiral.
And there is an incredibly precise, specific fact hidden in the text about this spiral, right exactly at the geometrical edge of the shadow, like the precise line where your brain tells you the darkness should begin, the intensity of the light isn't 0.
Nope.
And it isn't 50% either. The math proves that right at the edge, the light intensity is exactly 1/4 of the main light source.
Because geometrically, right at that exact boundary line, you're traversing exactly half of the total mathematical spiral. When you calculate the vector length from the origin to that halfway point, square it for intensity, you get exactly 1/4.
It is a beautiful, rigid mathematical reality hiding in the blurry edge of every single shadow you cast on the pavement.
And, you know, this beautiful winding spiral math doesn't just explain wobbly shadows. It actually swoops in to solve one of the most frustrating mathematical roadblocks in the entire source text.
Oh, right. We are talking about the attempt to calculate the electrical field of the universe.
This is where the text sets up a really fascinating showdown between pure mathematics and physical reality. The problem is this: how do you calculate the electric field generated by an infinitely large, totally flat sheet of oscillating electrical charges?
Right. You have a massive plane of charges moving up and down, and you want to know the field they create at a point far away. To get the exact answer, the pure math requires you to evaluate an integral equation, summing up the contributions of all those charges all the way out to infinity.
And the math essentially tells us to look at an infinite number of waves. If you put that directly into an equation, the numbers just spin out of control to infinity, never actually landing on a usable answer.
It's a total paradox. If you try to plot the math on a graph, it just draws a circle that spins around and around forever. Because it's trying to calculate out to infinity, it never stops drawing the circle. It's like the math is stuck in a permanent roundabout, totally broken.
But physics saves the math.
How does physics save it?
We have to step back and ask, what is the actual physical reality? In our physical universe, no plane of charges is truly infinite. It might be astronomically huge, but eventually, somewhere out there, the physical material has to run out.
So because the massive sheet eventually tapers off, the contribution of the charges at those extreme distant edges gets smaller and smaller.
Exactly. Let's go back to our arrows. The arrows representing those massively distant charges start getting shorter. And because they get shorter as they turn, that endless mathematical circle finally breaks.
It turns into a spiral.
Just like the edge of the shadow, it winds tighter and tighter, zeroing in precisely on the dead center of the circle.
The physical reality forces the infinite math to collapse and land on an actual answer. And the final formula they arrive at after all that complex integration and spiraling is wonderfully simple.
It really is.
The total field from this massive plane is directly proportional to the velocity of the oscillating charges, but delayed by the exact amount of time it takes the light to travel the vast distance to you.
It embeds the ultimate speed limit of the universe right into the simplest equation. The cause happens, the wave travels across space, and only then is the effect felt.
Let's synthesize this incredible journey. We started with the remarkably simple idea of drawing little arrows to represent the strength and timing of waves.
Yeah, just walking the path.
And just by adding those arrows up, by watching them trace out polygons, circles, and tight spirals, we've unraveled the swirling colors of oil slicks, the design of giant radio telescopes listening to the cosmos, the bizarre wobbly geometry hiding in our shadows, and how the physical limits of our universe actually rescue mathematics from impossible paradoxes.
It's profound. And while we've spent this time talking about how light waves interact, interfere, and cancel each other out to create shadows and reflections, I want to leave you with a completely different thought to ponder.
Oh, what's that?
Physics tells us that matter acts like a wave, too.
Wait, matter, like physical objects.
Yes, electrons, atoms, molecules. Which means that under the right physical conditions, the very particles that make up physical objects, and maybe even the particles that make up your own body, could interfere and mathematically cancel each other out. Just like the light in a shadow or a mirror. Something to think about the next time you feel completely solid.
Wow, we might just be a collection of waves waiting for the right conditions to cancel out. Well, thank you for joining us on this deep dive. Keep looking closely, keep wondering, and keep questioning the solid reality you think you see.
Welcome to the deep dive. Today we are taking a look at something you have definitely seen a million times. You look at a glass of water, it has a straw in it, and the straw looks like bent.
Right, or like it's totally disconnected at the surface.
Exactly. And I mean, we all get that standard high school physics explanation for it, right? Light slows down when it hits the water.
Yep, the classic runner in the mud metaphor.
Yeah. The teacher tells you light is like a runner on a paved track, and suddenly they hit a muddy patch. The water is dense, it acts like mud, so the light just, bogs down and moves slower. It's a really comforting, intuitive piece of physics.
Which is a lovely metaphor, except when you actually start looking at the quantum electrodynamics of the whole situation.
Which is what we are doing today.
Right, because you realize that muddy track explanation is a complete microscopic illusion. I mean, it is the absolute definition of a simplified textbook lie that we just agree to tell ourselves to make the math easier for teenagers.
And dismantling that lie is basically our entire mission today. We are diving into Chapter 31 of the legendary Feynman Lectures on Physics.
Oh, that is such a good chapter.
It really is. Our goal is to tear apart that oversimplified concept of the index of refraction and uncover the truly, mind-bending physical machinery operating underneath everything at the atomic level.
Because Feynman simply refuses to let you get away with the easy macroscopic answer. He forces you to look at the individual gears of the universe.
Yeah, he demands the why, not just the what. So if you're the kind of person who loves finding out that everyday reality is far stranger and honestly much more elegant than you were taught, this deep dive is definitely for you.
Absolutely.
We're going to look at electrons acting like tiny springs, waves that mathematically travel faster than light.
Which sounds impossible, but we'll get there.
Right, we will get there. And we'll see how staring at a simple shadow on your wall reveals this active, miraculous feat of quantum interference. So let's start by just completely blowing up the premise.
Let's do it.
To understand how light moves through glass or water, we first have to realize that the speed of light, the fundamental speed limit of the universe, c, never actually changes.
Never.
Not in glass, not in a diamond, not anywhere.
Right. The field generated by a single moving charge always travels at that ultimate velocity, c, period.
Okay, so then why?
Well, when we say light travels at a slower speed in a material, which, physicists write as c divided by n, where n is the index of refraction.
Right.
That is strictly an apparent effect. It's what the physics looks like from a distance if you're squinting.
But if you zoom in...
If you zoom in, the original light wave is screaming through the empty space between the atoms in that glass at the exact same speed it travels through the vacuum of deep space. It never slows down.
I mean, my brain naturally rebels at that. If the light wave isn't physically slowing down, why does it look so convincingly like it is?
Well, Feynman says the trap we fall into is that we only look at the original source wave. We have to look at the total electric field.
Okay, unpack that for me, the total field.
Right, because the electric field at any point inside that glass isn't just the original wave anymore. It's this massive, chaotic mashup.
A mashup of what?
So you have the original wave from your light bulb, or the sun, and that wave is still traveling at the full speed of light. But that wave doesn't just pass through silently. It hits the atoms in the glass.
Okay.
And specifically, the electric field of the light wave exerts a force on the electrons in the glass.
It violently shakes them up and down, basically.
Exactly. It drives them. And a fundamental rule of electromagnetism is that whenever you have an accelerating electric charge light, an electron bouncing up and down, it generates its own brand new electric field.
Oh, wow. So it radiates a new wave.
Yes. So the total field you measure at the other end of the glass is the original wave, plus the billions of new fields produced by all the other moving charges inside the material.
Okay, I want to try an analogy here to get away from the runner in the mud idea, because I think this is crucial.
Go for it.
Instead of mud, let's imagine a lead singer. That represents our original source wave.
Okay, I like this.
And this singer walks briskly into a crowded room, singing a sustained, perfect note. Now, the crowd represents all the electrons in the glass.
Right.
As the singer walks through, the crowd hears the note and they start singing along. They're being driven by the source. By the time you're standing on the far side of the room, the wave of sound hitting your ears isn't just the original singer anymore.
It's the combined chorus of the entire room.
Exactly.
That paints the exact picture of the interference at play here. Because the chorus isn't just making the sound louder. The way the crowd reacts, the blended wave they produce together, it actually changes the shape of the sound.
Right, and let's follow that physical mechanism, because this is where the magic happens. How does a chorus adding their voices actually create a delay?
Well, think about your crowd.
Right. In a lot of physics classes, this gets explained with these abstract arrows on a complex number graph. But there's a physical reality to it. The crowd in our room has a physical reaction time, right?
Yeah.
There is an inertia to them.
They don't start singing the exact instant the lead singer opens their mouth.
Exactly. When the lead singer hits a note, it takes a tiny fraction of a moment for a person in the crowd to hear it, process it, and sing along.
So their added sound wave lags slightly behind the singer.
Yes. So when you blend a perfectly timed wave from the singer with a slightly delayed wave from the chorus, the sum of those two waves, like the combined peak of the sound, arrives slightly later than the singer's solo peak would have.
That is spot on. The physical addition of that new, slightly lagging field fundamentally shifts the phase of the total wave backwards.
And that's the illusion.
Yes. This is the ultimate aha moment of the whole chapter. This tiny shift in phase, created by the addition of the new fields from the shaken electrons, is mathematically indistinguishable from a wave that just took longer to travel the distance.
So you don't need physical breaks to slow a wave down.
Not at all. You just need a microscopic chorus singing slightly out of sync.
The blended sound just mimics a dragged tempo. It's an illusion born of perfect quantum interference. It's so cool. And Feynman models this behavior by treating these electrons not as little planets orbiting an atomic sun.
Which, by the way, is another terrible high school lie.
Right. But he treats them as if they were held by tiny springs.
Yes. For this specific interaction with light, wave mechanics dictates that a spring model is incredibly accurate.
Really? Just like standard springs.
Basically, yeah. The electrons have a linear restoring force. If the incoming light wave pushes the electron away from its normal resting position, the atomic spring tries to pull it back.
Good thing, get it bounce.
And just like a shock absorber on a car or, a literal weight bouncing on a spring, it has a natural resonant frequency. We call that omega 0.
So that's the specific rhythm it just naturally wants to bounce at.
Exactly. If you just plucked it and let it vibrate on its own, that's the frequency it would hit.
And by using that spring model, Feynman elegantly derives the exact formula for the index of refraction, straight from the basic properties of the atom. He just uses the number of atoms, the charge of an electron, its mass, and that natural spring frequency.
It's a beautiful piece of math, but it brings up a huge question. If the entire delay depends on how these microscopic springs react to the driving wave from the light,
Right.
what happens if we change the rhythm of the driving wave?
You mean like shining different colors of light at them?
Exactly.
Because a color is just a specific frequency of wave, right? Blue light oscillates much faster than red light.
And this brings us straight to the mechanism of dispersion. It's the reason why a simple glass prism creates a rainbow.
Oh, okay. Let's break that down.
For the atoms in typical glass, the natural frequency of those electron springs happens to sit way up in the ultraviolet range.
Which is a higher frequency than our eyes can even see, higher than visible light.
Right. So when visible light hits the glass, the blue light, which is oscillating very fast, is much closer to the natural ultraviolet frequency of the glass electrons than the slower red light is.
Okay, I see where this is going.
Because the blue light is closer to that natural resonance, it shakes the electrons more violently. It forces a much stronger response from the springs.
And a stronger physical response from the electrons means they generate a bigger secondary wave.
Yeah.
And a bigger secondary wave means a more dramatic phase shift, which translates to a higher index of refraction.
You got it. The blue light is delayed more, so it bends more than the red light.
That is amazing.
Yeah.
The prism isn't doing anything magical. It's just physically sorting the light out by how closely its frequency matches the atomic springs of the glass.
The physical mechanics are just beautiful. But, Feynman takes it a step further. He looks at the denominator of the formula he derived.
I guess this is where it gets crazy.
Yeah, because the math relies on the difference between the natural frequency of the spring and the driving frequency of the light.
So let's push that to the extreme. What if we hit the material with a frequency that is significantly higher than its natural frequency?
Right. Like what?
Like what if we take graphite, which blocks visible light entirely, and shines super high frequency X-rays at it? Or what if we beam radio waves up at the free electrons floating in the stratosphere?
The ionosphere, yeah.
Right. Those electrons aren't bound to atoms at all, so they don't have a spring pulling them back. Their natural resonant frequency is literally zero.
And when you plug that into the formula, the math does something that should make any physicist intensely uncomfortable.
It breaks.
Well, if the driving frequency is higher than the natural frequency, that denominator in the equation flips its sign. It becomes negative.
Okay.
And when you calculate the index of refraction, the result is less than 1. N is less than 1.
Okay, if you are listening to this right now and doing the mental algebra, you might be screaming at your dashboard.
They probably are.
Because we established earlier that the apparent speed of light in a material is c divided by n. So if n is a fraction, let's say 0.5, and you divide c by 0.5, your result is 2c.
Double the speed of light.
Doesn't this mean the wave is mathematically traveling faster than the speed of light? Are we just violating relativity right now?
It looks exactly like we broke physics. I mean, it really does. But this apparent violation exposes a vital, deeply misunderstood difference between two concepts.
Phase velocity and signal velocity.
Yes, we need to pull those apart,
Yeah.
because Einstein's speed limit is supposed to be absolute.
Right. It is absolute. So how does this work?
Well, the index of refraction gives us is the phase velocity. That is the speed at which the perfectly uniform, repeating crests of a steady wave travel through the material.
Okay.
And mathematically, yes, the crests of that steady wave are propagating through the X-ray graphite or the ionosphere faster than c.
Okay, my brain is breaking.
But there's a universal loophole here. You cannot use a perfectly steady, unchanging, unending wave to send a signal.
Right, because a steady hum doesn't carry any information. If I hold a continuous tone on a trumpet for an hour, I haven't communicated anything other than the fact that I have really great lungs.
Exactly. To send a message, you have to change the note. You have to start playing a melody or use Morse code or at the very least turn the sound on and off.
You have to introduce a modulation, like a notch in the wave.
Yes, a notch. And to create any sudden change or notch in a wave, Fourier analysis tells us you have to introduce a mix of different frequencies. You can't just use one perfect, steady tone.
And how do those electron springs react to a sudden, chaotic mix of frequencies?
They don't react perfectly. When you first turn the light on, or when you introduce that notch to send a signal, the electrons don't just instantly start bouncing in perfect, steady rhythm to create that faster-than-light phase shift.
There's an adjustment period.
Yes, an initial transient response. Think about pushing a child on a swing that is already swaying randomly. You have to force it into your rhythm, and those first few pushes are just messy and chaotic.
So the electrons take a microscopic fraction of a second to settle into the steady-state rhythm.
And because of that chaotic transient period at the very beginning of the wave, which is the start of your signal, the actual notch you made never propagates faster than c.
Wow.
The repeating crests inside the established steady part of the wave might be zipping along faster than light, but the information you were trying to send, the moment the light turned on, is held back by that initial settling in period of the electrons.
Oh, well, that makes so much sense. So going back to the singer analogy, the lead singer bursts through the doors of the room, and it takes the crowd a split second of confusion to figure out the song before they can start singing the weird, fast-paced chorus.
Right.
So the news of the singer's arrival, the actual signal, never beats the physical singer across the room.
Exactly. The absolute speed limit of the universe remains totally unbroken. The signal velocity never exceeds c. It is this astonishingly elegant, self-correcting mechanism in the universe.
That is genuinely profound. I mean, it really is. But it all relies on these electron springs acting like perfect little mathematical constructs. In the real physical world, nothing oscillates forever without losing energy.
True.
If I bounce a weight on a spring, eventually it stops. There has to be friction in the atomic world too, right?
There is. And introducing a damping force, basically friction into the equations, is where Feynman takes the final leap in this chapter.
Okay, what happens to the math?
Well, when you add friction, the physical math actually splits into two distinct parts.
How does it split?
One part of the math continues to describe the phase shift, the delay and the bending of the light we've been talking about. But the second part of the math describes energy being bled away.
So absorption.
Fundamentally, yes, it represents absorption. As the light wave travels through the material, it forces the electrons to move against that atomic friction, doing mechanical work. The light wave uses up its energy to push the electrons, and that energy is converted into heat.
So the wave gets attenuated, it dims.
Right, we see that everywhere. Light gets dimmer as it goes through thick glass or deep water.
But how does this connect to the resonant frequency we talked about earlier? Like, what happens if the incoming light matches the spring's favorite rhythm perfectly?
Think about the swing again. If you push the swing at the exact right moment, matching its natural rhythm perfectly, you transfer the maximum amount of energy into the swing.
It goes super high.
Yeah. In the atomic world, if the light frequency is very, very close to the natural frequency of the atoms, the electrons absorb a massive amount of energy. The absorption math completely dominates.
Wow.
The light gets swallowed up entirely and turned into heat.
So it shakes the electrons so violently and so perfectly at their favorite frequency that the friction just burns all the light energy away.
Exactly. And this specific phenomenon powers one of the most important tools in modern astrophysics. It explains the dark spectral lines we see in sunlight.
Oh, break that down for me. How does friction in an atom let us read the sun?
Well, the incredibly hot core of the sun produces a full, continuous spectrum of light, every color imaginable.
Right.
But as that white light travels outward and passes through the cooler outer atmosphere of the sun, it encounters specific atoms: hydrogen, helium, iron. Every single one of those elements has its own unique signature spring frequency.
So when the full spectrum of light hits, say, a hydrogen atom in the sun's atmosphere, the hydrogen atom ignores almost all the colors, but it absolutely devours the specific frequency that matches its internal spring.
Yes, it absorbs it entirely through that atomic friction. So when that light finally travels millions of miles to Earth and hits an astronomer's telescope, the full rainbow of the sun has these specific, sharp, black lines cut out of it.
Like barcodes.
Exactly like barcodes. By looking at which specific colors didn't survive the trip, which frequencies were absorbed by the friction, we know exactly what elements exist in the atmosphere of stars all across the universe.
That is staggering. A microscopic frictional quirk in an electron spring is the barcode we use to map the chemical makeup of the entire galaxy.
It really is. And, Feynman also points out a beautiful piece of bookkeeping here. He proves that the decrease in the light's energy intensity perfectly balances with the mechanical work done against the friction of these electrons.
So the energy isn't lost, it's perfectly conserved.
It's a wonderful bonus victory for the physics. But this concept of absorption leads to probably the most counterintuitive part of the entire chapter.
Okay, let's go there. Because if absorption happens when electrons do work against friction, what happens when a material absorbs all the light? Like, what exactly is a solid, opaque wall?
It's not what you think it is.
Well, let's say I take a thick piece of cardboard, right? And I hold it in front of a really bright flashlight. On the other side of the cardboard, there's a shadow. The light field is zero. Why?
Our brains intuitively say, well, the cardboard blocked the light. It acts like a physical barrier.
Right, it stopped the beam.
But remember, our very first principle of this deep dive. The original field from the source charge always travels at c, and it travels through everything.
Wait, I really want you to listen to this if you're tuned in.
Yeah.
Are you saying the light wave from the flashlight is still traveling right through the solid cardboard?
The original source wave is absolutely still there. It's traveling through the space on the other side.
But we don't see it. The measured field in the shadow is zero.
Right. The reason it is zero is because the original wave sets the electrons in the opaque cardboard into motion. And those moving electrons generate a new field that radiates out the back of the cardboard.
Okay.
And that new field perfectly cancels out the source field.
Oh my God. An opaque wall isn't a passive barrier at all. It's basically nature's ultimate pair of active noise-canceling headphones.
That is the perfect way to visualize it.
It's not blocking the light.
Yeah.
It's actively playing the exact anti-wave to destroy it on the other side.
Right.
The original wave is there, the new wave is there, and they just sum to zero.
Exactly.
So a shadow on your bedroom wall isn't an absence of light. It's an active roiling zone of perfect quantum cancellation. The wall has to work continuously to keep the shadow dark.
Which is miraculous when you think about it. The electrons in the material have to generate the exact right amplitude and the exact opposite phase to perfectly balance out the light of the universe.
That is crazy.
And Feynman uses this active cancellation reality to explain the bizarre physics of diffraction. He asks, what happens if you cut a small hole in that opaque wall?
Well, if I cut a hole in the cardboard, light shines through. That seems, obvious.
But how do you mathematically calculate the field of the light coming through the hole? Feynman uses this brilliant backwards-forwards argument. I want you to picture the solid wall first.
Okay, solid cardboard.
The field at a point on the other side is zero. That zero is the sum of two things: the source wave plus the field generated by the entire solid wall.
Okay, got it. Source plus solid wall equals zero. They cancel.
Now imagine a wall with a hole cut out of it. The field you measure on the other side is the source wave, plus the field generated by the wall with a hole. Now imagine the little square plug of cardboard you cut out to make the hole. If you take the field of the wall with a hole, and you add the field of the plug, what do you get?
You get the field of the complete solid wall.
Right, which we already established perfectly cancels the source.
Wait, so if the solid wall cancels the light, then the field of the wall with a hole must be the exact mathematical opposite of the field of the plug.
Yes. Through that simple, undeniable subtraction, Feynman proves something incredible. The light you see coming through an empty hole in a screen is mathematically identical, except for the sign to the light that would have been radiated only by the plug you removed from the hole.
That is deeply weird. The light coming through the empty space is mathematically equivalent to the light that the missing chunk of matter would have radiated to cancel the source.
Yes.
So the empty space is acting exactly like the missing matter.
It completely upends how we perceive empty space and solid objects. We look at a hole and we see an absence. But mathematically, you can treat that empty hole as if it is a glowing, solid source of secondary radiation. This mental gymnastics is literally the justification for the entire theory of diffraction, where physicists treat open apertures as if they are filled with millions of tiny light sources radiating outward.
This has completely broken my brain, but like in the best way possible. I think we need to recap this journey for everyone listening.
Good idea.
The next time you look at a simple glass of water with a straw in it, remember, light doesn't actually slow down. It just recruits an army of microscopic electrons that sing a slightly delayed chorus, shifting the phase of reality.
Right, and prisms sort light into rainbows because atomic springs have natural resting rhythms, and the frantic pace of blue light shakes them harder than the lazy pace of red light.
Waves can technically outpace the speed of light, but the chaotic, messy, transient state of an atom waking up means that a signal cannot. Einstein's speed limit remains completely unbroken.
And friction in those same atomic springs explains absorption, allowing us to read the missing barcodes in starlight and map the chemistry of the universe.
And finally, shadows. Shadows are not empty space or blocked light. They are active, violent zones of perfect quantum cancellation, where the matter on the wall is screaming the exact anti-wave of the light to manufacture darkness.
Feynman takes something as mundane as a window or a shadow and reveals the chaotic, elegant quantum machinery grinding away just underneath our perception.
He really does. Thank you so much for joining us on this deep dive. We've thrown a lot of heavy, counterintuitive concepts at you, but hopefully you'll never look at a sunbeam or a shadow the exact same way again.
Definitely not.
But I want to leave you with one final thought to mull over, building on what we've talked about today. If our everyday perception of a bent straw and a glass of water, our perception of slow light and solid shadows, is really just a macroscopic illusion created by trillions of tiny electrons reacting and canceling each other out at the speed of light, what other solid, undeniable facts of your everyday physical reality are just macroscopic illusions hiding a chaotic, invisible dance of quantum interference?
Oh, that's a good one.
We'll leave you to think about that. See you next time. Welcome to today's deep dive. You know, if you actually run the raw numbers on electromagnetism, the sky above you right now shouldn't just be this calm wash of blue.
Right, it really shouldn't.
I mean, it should be a chaotic, blinding mess of shifting interference patterns.
Yeah.
But because of this tiny, like 10 nanosecond delay happening inside individual atoms, you get a perfectly clear blue dome.
It is wild. And, well, we are diving into a really remarkable stack of notes today. We're looking at Chapter 32 of some legendary mid-century physics lectures.
Yeah, the Feynman lectures.
Exactly. And the overarching mission today is to uncover the hidden mechanics of light and matter. Specifically, we're looking at what happens when you grab an electron and, shake it.
Right, just physically accelerate it.
Yeah, and how that highly abstract math scales up to build the everyday phenomena you experience. So the blue sky, the white clouds, the red sunset.
And I'll tell you, by the end of this deep dive, you won't just take the color of the sky for granted. We are going to explore the exact mathematical quirk that makes light behave so wildly in our atmosphere.
Yep, the exact multiplier.
And we'll also untangle a famous misunderstanding about light interference that was, printed as undeniable fact in old textbooks for generations.
It's a great journey, but to get there, the foundational concept we need to tackle first is what happens when a charge accelerates. So whenever an electron speeds up or slows down or changes direction, it radiates energy out into the universe.
Okay, let's ground this in something physical.
Mm-hmm.
Think about a standard radio antenna.
Perfect example.
If you build an antenna out of perfectly conducting copper, logic suggests it should have zero electrical resistance.
Right. It's a perfect conductor.
But to the circuit that is actively driving it, the antenna acts exactly like a resistor. It behaves as though it is losing energy.
Yes, and the energy isn't turning into heat like it would in a normal resistor. It is leaving the system entirely, just, propagating out into space as electromagnetic waves.
Like invisible ripples.
Exactly. Physicists call this radiation resistance. If you look at figure 32:1 in the source material, it shows this really clearly. If you imagine a sphere expanding infinitely outward from that antenna, you have to integrate over the area of that spherical segment.
Okay, so the radiated power is spreading out over that surface area.
Right. The radiated power spreads thinner and thinner over the surface of that sphere, so the total energy moving through a specific patch of space drops off inversely as the square of the distance.
Okay, but I need to push back on this idea of resistance in a vacuum. Because, well, if I am pushing a kid on a swing, I feel the physical resistance of gravity. Right?
Sure, gravity and air resistance.
Yeah, the air is pushing back against us. But if an antenna is just accelerating a single solitary electron in a pure vacuum, what is actually pushing back against the electron to cause this drag?
That is such a good question. And honestly, that specific question troubled physicists for a long time. Against what force are we doing the work when we accelerate a charge?
Because there's nothing there.
Exactly. But the classical model offered this really brilliant mind-bending answer. It proposed that an electron isn't a perfect dimensionless point. It actually has a tiny bit of volume.
Okay, so treating it like a microscopic ball.
Right. And because it has some physical size, there is a minuscule time delay for the electromagnetic force to travel from one side of the electron to the other.
Wait, across the electron itself?
Yes, across its own volume. If the electron is just sitting perfectly still, all the internal forces are balanced, action equals reaction.
But the moment we accelerate it,
We disrupt that balance. The time delay becomes critical. Because the electron is moving, accelerating, while the force is still propagating across its own volume, the force acting on the front of the electron from the back is no longer perfectly equal to the force acting on the back from the front.
oh, wow.
Yeah, they don't cancel out. As a net effect, the electron literally holds itself back by its own bootstraps.
That is insane. The electron is essentially fighting its own wake. I mean, I know modern physics has evolved beyond the little ball model, but the net result is still so profound. Simply by the act of accelerating, a charge encounters a radiation resistance force and loses energy.
Which tells us that an electron cannot vibrate forever. It acts like a dying pendulum. You give an electron a shove, it radiates energy away, and its motion slowly damps down. We call this energy loss radiation damping.
Okay, so how do we actually measure the lifespan of that dying pendulum?
Well, physicists use a metric called a Q factor. The Q stands for quality.
Quality factor.
Right, it's a ratio. It represents the total energy of the oscillator divided by the energy it loses during each cycle of its vibration. So a high Q factor means the system loses very little energy per cycle and keeps vibrating for a long time.
Give me a sense of the scale here. Say we look at a sodium atom emitting yellow light. How long does it ring?
Well, the wavelength of that yellow light is roughly 6,000 angstroms. And an angstrom being, a tiny fraction of a nanometer.
Right.
When you run the math on the radiation damping for that specific atom, the Q factor is astronomical. It is around 100 million, 10 to the 8th power.
That sounds like striking a bell in a vacuum. I mean, a Q factor of 100 million implies it just wants to ring for an eternity, but the very act of emitting the light slowly drains it.
Yes, but the catch is the sheer speed of light. The frequency of that yellow light is on the order of 1,000,000 billion vibrations every single second. 10 to the 15th.
Oh, wow. So it's vibrating unbelievably fast.
Exactly. So even with a massive Q factor of 100 million, the atom burns through its energy incredibly fast. It only rings for about 10 to the negative 8 seconds.
So 10 nanoseconds.
Just 10 nanoseconds before its energy drops significantly.
10 nanoseconds. That is the entire lifespan of a single atom's freely emitting light pulse.
It's an unimaginably short window, but it leaves a permanent fingerprint on the physics of light. That 10 nanosecond lifespan is the exact reason why spectral lines have widths.
What do you mean by widths?
The light an atom emits isn't a perfectly sharp, infinitely precise single frequency. Because of the damping, the wave gets cut off, which gives it a tiny bit of spread across the spectrum.
Oh, I see. And digging into the math of that dying pulse actually reveals something fundamental about the universe, doesn't it?
It does. By calculating the rate of that energy loss, you arrive at a constant known as the classical electron radius.
Right, from the notes.
Yeah. The math spits out a length scale of about 2.82 times 10 to the negative 15th meters. It's derived entirely from the intrinsic properties of the electron's mass and charge. It emerges purely from the math of a dying light pulse.
That is beautiful. But I want to bridge this 10 nanosecond concept to the broader world because it solves a massive historical debate.
Oh, the textbook myth.
Yes. Older physics textbooks used to state definitively, like it was a law of nature, two distinct light sources never interfere. Like if you shine two separate flashlights or two distinct radio oscillators on a wall, you just get a bright spot. You don't get the complex bands of light and dark interference. So here's where it gets really interesting. Was that an actual law of physics or just a failure of our eyeballs?
It was entirely a limitation of the equipment in human biology. The textbooks were totally wrong to classify it as a fundamental rule, and the error completely stems from that 10 nanosecond lifespan.
Okay, so how does that tiny lifespan scramble the interference?
Think about two independent atoms in a normal light bulb. They are not synchronized at all. One atom fires, rings for 10 nanoseconds, and stops. Then a completely different atom randomly takes over.
Okay.
So the phase of the light, the exact timing of the wave's peaks and valleys is completely shifting and scrambling every 10 nanoseconds.
But they actually are interfering on the wall, right? They're constantly creating patterns of light and dark.
The patterns are absolutely there. But they shift their arrangement 100 million times a second. Your eye acts like a camera with a slow shutter speed. It averages out the light over roughly a tenth of a second.
So in that fraction of a second?
In that tenth of a second, the atoms have randomly shifted their phases 10 million times.
Wow. So all those millions of random bright and dark spots just average out to a flat medium brightness. We see a blur of zero interference.
Exactly. But with modern equipment, like high-speed photocells that can actually catch those 10 nanosecond windows, you absolutely can capture the interference between two independent light bulbs.
Or with lasers, right?
Yes, if you use a modern laser, which forces all the atoms to emit together and hold their phase for much longer, the interference pattern is completely visible to the naked eye.
Okay, so if our eyes are too slow to see these atoms interfering with one another in a light bulb, what happens when we look at a canvas as massive as the Earth's atmosphere? Does that chaotic scrambling help or hurt us?
It is the foundation of why the sky looks the way it does.
Okay, walk me through it.
So, when sunlight hits our atmosphere, the electric field of that incoming light drives the electrons in the air molecules up and down. Figure 32-2 in the text illustrates this beautifully.
Right.
The unpolarized beam hits the atom, shakes its electrons, and causes them to scatter radiation in all directions.
And because the air molecules are constantly moving, and because their phases are scrambling every 10 nanoseconds, we don't have to worry about calculating some impossibly complex atmospheric interference pattern.
Exactly. The random phases average out perfectly. To figure out how much light the sky is bouncing toward your eye, we can simply calculate the scattering from one individual atom and multiply it by the total number of atoms in the sky.
Which introduces a brilliant concept for measuring this, the scattering cross-section.
Right.
For anyone trying to visualize this, it isn't a physical hard target. It is an imaginary mathematical area representing how much of the incoming light beam an atom intercepts and spews back out.
Yeah, that's a good way to put it.
You're basically asking, how big of a physical net would I need to catch that exact amount of incoming sunlight?
And the size of that imaginary net depends entirely on the color of the light. The math uses the symbol omega to represent the angular frequency of the light wave.
Okay, omega.
And the critical insight is that the scattering cross-section is proportional to omega raised to the fourth power.
That exponent is the key to everything. Omega to the fourth power. Let's do the math for the listener, because it's wild. Walk us through how that plays out for the colors we actually see.
Well, blue light sits at one end of the visible spectrum and red sits at the other. Blue light waves wiggle much faster. In fact, blue light has roughly twice the frequency of red light.
Okay, so if blue has double the frequency and the scattering scales to the fourth power, we aren't just getting double the scattering.
No, not as
We take that factor of 2 and we raise it to the fourth power. So 2 times 2 is 4, times 2 is 8, times 2 is 16.
Exactly. Blue light is scattered 16 times more intensely than red light.
That is a staggering multiplier. When sunlight hits the atmosphere, the red light mostly just plows straight through the air molecules. But the blue light hits those exact same molecules and gets violently scattered in every possible direction 16 times more aggressively.
Yep.
So when you look away from the sun into the empty sky, you are staring directly at that aggressive high-frequency scattering.
It paints the entire dome of the sky. But, it immediately introduces a massive contradiction, the mystery of the clouds.
Right, because there is water vapor in the blue sky all around us right now, and you can't see it. It is completely invisible.
Exactly.
The vapor acts just like the air, scattering a tiny bit of blue. So why, when that exact same water condenses into a cloud, does it suddenly become a brilliant, blinding white?
The change has nothing to do with the water itself and everything to do with the distance between the atoms. When water is a vapor, the atoms are spread far apart, much further apart than the wavelength of the light.
Okay.
So they act as independent sources. But when water condenses, those atoms clump together into tiny liquid droplets.
So instead of a bunch of random bells ringing out of sync, if they are squished together smaller than a single wave of light, how does that change the math? Why don't they just cancel each other out?
Because they are packed into a space smaller than a single 5,000 angstrom wavelength of light, they can no longer act independently. The incoming electric field hits them all at the exact same time, forcing them to vibrate perfectly in phase with each other.
Oh, the random scrambling disappears. They are forced into a mathematical collaboration.
The amplification of that collaboration is incredible. Let's say you have n number of atoms in a tiny droplet. Their electric fields add up directly, so the total scattered electric field is n times stronger.
But wait, the actual energy of a light wave isn't just the field. The energy is the square of the electric field.
Exactly. Since the energy is the square of the field, the droplet scatters n squared times as much light.
N squared. So if you have 1,000,000 atoms in a tiny droplet, they don't scatter 1,000,000 times more light than a single atom. They scatter 1,000,000 squared times more light.
Right, 1,000,000,000,000 times.
A lump of water scatters exponentially more light than the vapor did.
That is why the cloud seemingly pops into existence out of thin air. But the n-squared trick has a strict physical limit.
What's the limit?
Well, once the water droplet keeps growing and gets bigger than the wavelength of the light itself, the atoms on the far left side of the drop are too far away from the atoms on the far right side. The waves start getting out of phase again.
So the mathematical collaboration breaks down as the droplet expands.
Exactly. This larger size removes the advantage of the high-frequency blue light. The larger droplets scatter all the colors of sunlight much more evenly. And when you mix all the colors of sunlight back together, you get white light.
Hence, white clouds.
Right. And this exact mechanism also explains the sunset. When the sun gets low on the horizon, its light has to travel through a much thicker slice of the atmosphere to reach your eye.
Oh, sure.
All along that extended path, the air molecules are violently scattering the blue light away 16 times more efficiently.
So by the time the beam finally reaches you, the blue is exhausted. It has been scattered out in every other direction. What survives the long journey? What punches straight through the atmosphere to hit your eye is the low-frequency red and yellow light.
Yes. And the notes actually mention a brilliant practical way to recreate this in a lab using sodium thiosulfate, often called hypo and sulfuric acid.
Right, the precipitation experiment.
Yeah. You mix them in a clear tank, and the chemical reaction slowly precipitates very fine grains of sulfur. At first, the sulfur particles are microscopic, acting just like air molecules.
Okay.
If you look at the tank from the side, the scattered light looks decidedly bluish. But if you look straight through the tank at a light bulb, the transmitted light looks yellow-red. It is a perfect recreation of the sky.
And as the sulfur grains grow larger and larger, acting exactly like our water vapor, condensing into large droplets, the bluish side scattering turns bright white. You literally build a sunset and a cloud in a single jar.
It's a fantastic demonstration. So we have mapped out the blue sky, the white clouds, and the red sunset. But there is one final hidden feature lurking in the scattered light of the sky.
And this is something you can only see if you know exactly where to look, right?
Exactly. It relies entirely on the geometry of how you observe the scattering.
Okay, set the stage for this geometry.
We established that the electric field of incoming sunlight is unpolarized. It is oscillating in all random directions perpendicular to the beam. As it hits the air molecules, it makes their electrons vibrate in all those same random directions across the path of the sunbeam.
Okay, imagine you are standing on the ground, looking up at the sky at a perfect 90-degree angle to the sun. Say the sun is setting exactly in the west and you are looking straight south.
Okay, visualize figure 32-3 here. You now have a perfect right angle between the sun, the air molecule you were observing, and your eye. The electrons in that air molecule are vibrating in all directions perpendicular to the sunlight.
Right.
Some are vibrating vertically, but some are vibrating directly toward you and away from you.
And here is the catch. A transverse wave vibrating directly along your line of sight doesn't send any energy to you. Like if you shake a rope side to side, you see the wave. But if you hold a rope and shake it directly toward a person's eye, they can't see the transverse motion.
Spot on. You only see the radiation from the vibrations that are moving across your field of view. Because of that perfect 90-degree geometry, half the vibrations are completely hidden from you.
Wow.
Therefore, the scattered light coming at you from that specific 90-degree patch of sky is perfectly plane polarized. It is only vibrating in one visible direction.
The light from that specific patch of sky is physically aligned. The best analogy for polarization is trying to slide a wavy piece of cardboard through a narrow mail slot.
Right.
The cardboard can only pass through the slot if the wave is perfectly aligned with the opening. If you turn the cardboard sideways, it gets blocked.
And that mail slot is exactly how polarized sunglasses work. The lenses only let light vibrating along one specific vertical axis pass through.
Which means you can test this entire phenomenon yourself. If you put on polarized sunglasses, look at the sky at a 90-degree angle to the sun, and simply tilt your head sideways.
The sky will actually get significantly darker.
Yes. By tilting your head, you are turning the mail slot. You are crossing the axis of the polarization, blocking the one direction the scattered light is vibrating. It is a direct, visual confirmation of the geometry of scattered electrons.
Testing electromagnetism with a pair of gas station sunglasses. It's incredible.
It really is. Let's take a step back and look at the path we just walked. We started with a single electron, accelerating in a vacuum, holding itself back by its own electromagnetic bootstraps to create radiation resistance.
And that resistance causes the atom to act like a dying pendulum, wringing out its energy in a microscopic 10-nanosecond pulse.
Because of those incredibly short lifespans, independent atoms are constantly scrambling their phases, making it impossible for our slow human eyes to see their interference patterns. This allows us to treat the billions of air molecules above us as individual scatterers.
And thanks to the omega to the fourth math of that scattering, the high-frequency blue light is violently scattered 16 times more intensely than red, giving us our blue dome and our red sunsets.
Right. Until the water vapor huddles close enough together to physically force a mathematical collaboration, turning N atoms into N-squared brilliant scatterers, stripping away the blue advantage and leaving us with thick, bright white clouds.
It is a flawless chain of logic, bridging the invisible world to the monumental sky above us.
It really is. So the next time you look up at a giant, fluffy white cloud drifting across a bright blue sky, don't just see the weather. Realize you are actually looking at a massive real-time mathematical equation, billions of electrons vibrating in perfect N-squared harmony, dictated entirely by the precise length of a light wave. The beauty of the sky isn't just art. It is the sheer elegance of physics. Thank you for joining this deep dive.
Imagine looking up at a star in the night sky, just staring at it, only to realize that the light hitting your eye isn't a continuous beam. It's actually this violent, stretched out optical illusion created by a particle practically chasing its own radiation.
Yeah, it completely shatters your intuition about how light works.
It really does. Welcome, by the way, to today's deep dive. We are opening up Chapter 34 of the Feynman Lectures on Physics, and we're focusing specifically on his notes concerning relativistic effects in radiation.
Right, which is a wild topic.
Oh, absolutely. The mission for today is to explore what happens to the physical rules of light when the source emitting it is hurtling through space at a significant fraction of the speed of light. Because normally we learn about light coming from stationary things.
Exactly. To understand the physics at those extreme speeds, you have to completely abandon the intuitive way you perceive the location of objects.
Because things get weird.
It's so weird. The core premise Feynman lays out involves mapping the electric field of a moving charge. When you measure the electric field of, say, an electron emitting light, the field you interact with isn't dictated by where the electron is right now in this current instant.
Wait, it's not?
No, it's not.
Yeah.
It is entirely dictated by where the electron was when the light began its journey toward you. This is it's known as the retarded position.
Okay, let's unpack this. Because the speed of light is finite, right? Which means any information about the electron's position carries this built-in time delay.
Right. It's like if a particle is moving slowly, say like a car on a highway, that delay is negligible. The car is effectively exactly where you see it.
Because the light from the car hits your eye almost instantly relative to how fast the car is moving.
Precisely. But when an electron is traveling near the speed of light, it covers a massive distance during the time it takes its emitted photons to cross the gap to your eye. So the position you perceive is essentially ghost.
A ghost? Wow. That presents a profound geometrical problem, doesn't it? If the position you observe is an illusion, how do you even map the true electric field that an observer will measure?
Well, you have to calculate the apparent path. You take the actual true physical trajectory of the charge, and mathematically, you sweep that entire path backward.
Backward.
Yeah, backward, away from the observer at the speed of light.
Okay, so wait. When you say we translate the motion backward at the speed of light, are we talking about Einstein's length contraction here, like squashing the spatial dimensions?
Ah, I'm glad you asked that. It is really easy to blur those concepts together, but no, there are no relativistic contractions occurring in this specific mapping step.
Oh, okay. So it's something else.
Yeah, it's purely a mathematical addition to account for the travel time of the light. You take the actual coordinate of the particle and simply add a vector, which is the speed of light multiplied by the time delay to find the apparent coordinate. You're just mathematically syncing up the arrival times of the light rays.
I see. So it's basically a mapping algorithm to reconstruct what the observer's instruments will physically register.
Exactly.
So let's apply this algorithm to a specific scenario from the text. What happens if we map an electron that is flying in a continuous circle, but like at near light speed?
Well, the geometry warps dramatically. If you take that circular motion and translate it backward at the speed of light, assuming you're an observer sitting up to the side, the apparent path doesn't look like a circle anymore.
What does it look like?
It looks like a series of stretched out, overlapping loops. The mathematical term for this curve is a Curtate cycloid.
A Curtate cycloid. Okay, so if the electron is moving at a massive fraction of the speed of light, the geometry of those loops distorts even further, right?
Oh, yeah. The tops of those loops, the points where the electron's apparent path is directed straight toward the observer, they narrow into these incredibly sharp points, or cusps.
Like a literal sharp point in the math.
Right. In fact, if the particle could theoretically hit the speed of light, that loop would collapse into an infinitely sharp spike.
An infinitely sharp spike. And the sharpness of that geometric cusp translates directly to the physics, right? Because the electric field generated by a moving charge is determined by the second derivative of its apparent motion.
You got it. And in physical terms, the second derivative is acceleration. So an incredibly sharp turn in the apparent path mathematically represents a colossal spike in apparent acceleration.
Whoa! So instead of a smooth, continuous sine wave of light radiating from this nice circular orbit, the electron violently whips around that sharp cusp and spits out this highly concentrated, just devastatingly intense pulse of an electric field.
It really does. The energy is bundled together, and it fires out in a narrow cone, perfectly aligned with the direction the charge is moving at that exact instant. Like a sonic boom, but
The
for...
sonic boom of light. I love
Yeah.
that. So the mathematical illusion forces the continuous motion to manifest as violent bursts.
Exactly. And, you know, we've mapped the theoretical geometry, but this exact phenomenon is heavily exploited in modern physics labs.
Right, because when we force electrons into these circular patterns at those relativistic speeds, we use massive machines, right? Synchrotrons.
Yeah, synchrotrons. We achieve this by firing electrons into a uniform magnetic field. Since a magnetic field exerts Lorentz force perpendicular to the velocity of the moving charge, it doesn't do any work to speed the electron up or slow it down.
Right, it just constantly pushes it sideways, trapping the electron in a big circular orbit.
Exactly. And the momentum of the particle in this circle is simply its charge multiplied by the magnetic field strength times the radius of the circle, which gives us that classic formula, P equals QBR.
Right, P equals QBR. So if you take a low-energy, slow-moving electron and trap it in, say, a 20-meter circular orbit using that magnetic field, the math for its radiation is pretty straightforward, right?
It is. It emits an electromagnetic wave with a wavelength equal to the circumference of its orbit. So a 20-meter wavelength, which sits deep in the shortwave radio portion of the spectrum. Yeah.
Just normal radio waves. But the electrons in a synchrotron aren't slow. I mean, they are pushed to a fraction of a percent shy of the speed of light.
Yeah, and this is where those Curtate cycloid cusps fundamentally alter the output. Because the electron is moving almost as fast as the light it emits, it stays right on the heels of its own radiation.
It's chasing its own light.
Exactly, which initiates a massive piling up effect that compresses the time scale between the pulses. And looking at the Feynman notes, this compression factor mathematically applies itself twice to the observed radiation.
Twice. Wait, why twice?
The double application is the secret to the extreme energies produced. First, the physical spatial distance between the consecutive pulses is radically compressed because the electron is physically chasing the wave front of the light it just emitted.
Okay, that makes sense. Like a Doppler squish.
Right. And second, the actual time duration of the pulse itself, the width of that sharp geometrical cusp, is incredibly brief because the apparent time scale is squeezed right in the neighborhood of the cusp.
Oh, wow. So if a synchrotron achieves a compression factor of, let's say, 8 million, applying that factor twice means you divide the original wavelength by 64 trillion.
Yeah, you're taking 20-meter low-energy radio waves and crushing them down so intensely that the effective wavelength becomes microscopic.
So the wavelength shrinks out of the radio spectrum, blasts through the infrared, past visible light, and goes deep into the realm of high-energy X-rays.
Exactly. This is synchrotron radiation. It is literally an optical illusion of timing and geometry that is so powerful it generates physical, hard X-rays that scientists use to image the atomic structure of proteins or, map complex materials.
And the beam is so intense it physically glows inside the vacuum tubes of the accelerator ring. It's crazy.
It really is.
But here's the thing for you listening. We build these massive multi-billion-dollar facilities to harness this geometric quirk. But the universe executes this exact physics natively in the vacuum of space.
Oh, yeah. On a terrifying scale, we just have to look at the remnants of the year 1054.
1054. The Chinese and Japanese astronomers of that era documented the sudden appearance of a guest star, right?
Yes, a supernova explosion so violently luminous it was visible in broad daylight for weeks. And strangely, European monks completely failed to write it down.
Which is wild. But when modern astrophysicists point radio telescopes and optical observatories at those exact coordinates today, they observe the expanding debris field we call the Crab Nebula.
The Crab Nebula. Now, if you analyze the outer filaments of the Crab Nebula, the physics are pretty standard. You see red light, which is simply atomic emissions.
Just standard thermal stuff.
Right. Nitrogen and hydrogen atoms are thermally excited. They vibrate their natural quantum frequencies and shed that energy as discrete wavelengths of light.
Yeah.
But the core of the nebula completely breaks that atomic model.
Because the dead center of the Crab Nebula glows with a hazy, continuous spectrum of light, right? It completely lacks those discrete frequency fingerprints or emission lines that atoms usually produce.
Exactly. And when observers filter this continuous light through polarizers, they find the light is highly polarized, with its electric field vectors violently aligned in specific directions.
Which is the undeniable signature of synchrotron radiation.
You got it. In a lab, when an electron whips around a magnetic field, the resulting light is strongly polarized, perpendicular to that magnetic field. So the fact that the Crab Nebula is blasting out continuous, polarized, visible, and X-ray light proves there is a sprawling, massive magnetic field woven through the center of that debris cloud.
That is just mind-blowing. It proves that countless loose electrons have been trapped in that cosmic magnetic field, spiraling continuously at nearly the speed of light for almost a millennium.
It does. But recognizing the physics immediately introduces a massive thermodynamic problem.
Right, because that star detonated over 9 centuries ago. And synchrotron radiation is an incredibly efficient way for an electron to bleed off its kinetic energy.
Yeah, those electrons are constantly vomiting X-ray radiation into the void, which means they're losing momentum.
Yeah.
Fast.
So, by any standard classical calculation, the electrons from a 900-year-old explosion should have bled away all their relativistic speed centuries ago. The nebula should be dark.
It should be completely dark. The fact that it is still glowing means there's a genuine scientific mystery here. Some hidden mechanism likely tied to the rapidly spinning pulsar at the very center is continuously pumping new kinetic energy into those electrons.
Just violently accelerating them back to light speed against the drag of their own radiation.
Exactly. It is a cosmic engine operating at an efficiency and scale we are still struggling to thoroughly understand and model mathematically.
That's incredible. So we've established that electrons spiraling through empty space yield intense pulsed radiation. But what happens when space isn't empty? Like when a relativistic electron abandons the circular orbit, travels in a straight line, and just slams into a dense physical target.
Ah, right. The geometry of the radiation shifts completely. The Feynman notes describe this interaction as Bremsstrahlung, which translates from German as breaking radiation.
Breaking radiation. So if we fire a beam of fast electrons into a solid block of a heavy metal, like tungsten, the electrons don't just gently coast to a stop, right?
No, not at all. They zip right through the empty space of the atoms, passing terrifyingly close to the heavy, dense, positively charged atomic nuclei.
And the Coulomb force of that massive positive nucleus grabs the negatively charged electron as it flies past.
Right. Now, the electron carries too much momentum to actually be captured into an orbit, but the intense attractive force yanks the electron off its straight-line trajectory. This creates a sudden, violent kink in its path before it continues on.
A tiny speed bump. But applying our retarded position mapping from earlier, any sharp geometric turn or kink translates to a massive spike in apparent acceleration.
Exactly. And because the electron is moving toward the observer at a high fraction of the speed of light when it hits this nuclear speed bump, the entire geometric picture is compressed heavily in the forward direction.
So the electron violently sheds its kinetic energy by firing a massive, concentrated spike of electromagnetic radiation straight ahead.
Boom! Gamma rays. This is the exact mechanical process used in industrial and medical particle guns to generate gamma rays.
But analyzing this single violent spike of an electric field raises a really fascinating question about what you would actually see. Like how we define the physical properties of light. Because a continuous wave of light has a wavelength, and therefore it has a color.
Right.
But a single instantaneous spike of radiation doesn't possess a wavelength.
No, it doesn't. So the concept of color breaks down entirely here. It is just a raw crack of electromagnetic energy.
But Feynman introduces this brilliant thought experiment to show how geometry can literally fabricate color out of nothing. If you take that single colorless spike of Bremsstrahlung radiation and shine it at a diffraction grating, which is just a surface etched with thousands of microscopic, evenly spaced parallel grooves, you fundamentally change the nature of the light.
You do, because as the single spike hits the grating, it violently shakes the electrons in the very first groove, scattering a pulse back toward you.
Right.
And then, a fraction of a microsecond later, the spike hits the second groove, scattering a second pulse, then the third and the fourth. And because the grooves are physically separated by a specific uniform distance, the scatter reflections must travel slightly different distances to reach your eye.
And that spatial distance translates directly into a time delay. So if you were standing at an angle to the grating, the reflections from the grooves don't hit you all at once. They arrive sequentially.
Exactly. The single spike has been shattered into a rhythmic, vibrating series of electric field pulses arriving at a perfect interval, dictated entirely by the spacing of the grooves.
The physical spacing of the grating has literally manufactured a frequency.
It has. And a rhythmic series of pulses arriving at a specific frequency is the exact mathematical definition of a continuous sine wave.
So by dictating the timing of the reflections, the diffraction grating takes a single spike of raw, colorless radiation and geometrically transforms it into a perfectly smooth wave of colored light. That is wild.
It's beautiful physics. But, we have spent this entire time analyzing the strange effects that manifest when the source of the light is moving, looping in synchrotrons, spiraling in nebulas, or crashing through tungsten.
Right.
But the foundational rule of the universe is symmetry. The laws of physics cannot prioritize one frame of reference over another. So what happens to the math when the source of the light is standing perfectly still and you, the observer, are the one moving?
The universe demands mathematical symmetry, but the classical equations immediately run into a wall of asymmetry when dealing with the Doppler effect, right?
Right. If you observe a stationary light source while rushing toward it, you are physically sweeping past the incoming wave fronts faster than they would normally arrive. The waves appear squashed together, increasing the frequency and shifting the light toward the blue end of the spectrum.
But if you write down the classical physics formula for an observer moving toward a stationary source, the math looks structurally different than the formula for a source moving toward a stationary observer.
And Einstein's relativity strictly prohibits this. If constant motion is purely relative, it should be physically impossible to tell who is actually moving, which means the formulas must match flawlessly.
So how do they fix it?
To force the math into symmetry, you have to introduce time dilation into the equations of the moving observer. Because the observer is moving, their biological and mechanical clocks are ticking at a slower rate relative to the rest frame of the universe.
So when you inject that relativistic slowing of time, the Lorentz factor, into the moving observer's frequency calculation, the asymmetry just vanishes.
Completely vanishes. The two equations resolve into the exact same formula.
Time itself has to bend to keep the geometry of light consistent. That is amazing. And that relativistic bending also applies to the physical angle at which we observe light, right? A phenomenon known as aberration.
Yes, aberration.
Imagine driving a convertible down the highway at 60 miles per hour. If a drone hovering perfectly still high above drops a baseball straight down into your car, you can't just hold your hand straight up to catch it. Because you are moving forward while the ball falls, you actually have to reach slightly behind where you think the ball is, or tilt your catching net forward to intercept the trajectory relative to your motion. Is this exactly like running in the rain and having to tilt your umbrella forward so your legs don't get wet?
That is the perfect analogy.
Yeah.
And the exact same geometric logic applies to catching light from a distant star in a telescope. The starlight is falling straight down, but because the Earth is hurtling through its orbit, the telescope is moving sideways.
So if you point the telescope straight up, the starlight will enter the top but hit the side of the tube before reaching the eyepiece at the bottom.
Exactly. You physically have to tilt the telescope forward in the direction of Earth's motion, so the photon can fall cleanly down the moving tube.
But calculating the exact angle of that tilt requires more than just basic classical vectors, doesn't it? Because of length contraction.
Yes, the relativistic twist. Because the telescope is moving, the physical length of the space it occupies is subjected to relativistic length contraction from the perspective of the incoming light. The space the telescope is traversing is literally squashed.
So to find the true exact angle of aberration, you have to apply the Lorentz transformation to account for that contracted geometry.
Exactly. You can't just use basic geometry. Now, we have dissected the electric field of light through every relativistic distortion, but Feynman's notes conclude with a critical, often overlooked physical property. One final secret.
Oh, what's that?
Light is an electromagnetic wave. We always talk about the electric field, but it possesses a magnetic field oscillating in perfect tandem with its electric field. And that magnetic component exerts a literal physical force on matter.
Wait, so light physically pushes things, but light doesn't have mass.
I know, it sounds impossible. But think about it. When a photon strikes an electron, the oscillating electric field pushes the electron violently up and down. But as we established earlier with the synchrotron, a magnetic field exerts a force perpendicular to the velocity of a moving charge.
Oh, I see. So as the electron is driven vertically by the electric field, the perpendicular magnetic field of the light crosses with that vertical motion.
Exactly. And the cross product of those vectors results in a force pushing the electron straight forward, precisely in the direction the wave is traveling.
So the light is actually physically pushing the electron. It exerts tangible radiation pressure. But classical physics defines momentum as mass times velocity. And light possesses absolutely no rest mass.
Right. And the fact that a massless wave can exert physical forward pressure on a massive object creates this incredible bridge between classical electromagnetism and the quantum mechanical nature of the universe.
The math proves that the forward momentum delivered by the light is exactly equal to the energy absorbed by the electron divided by the speed of light. The equation is P equals W over C.
And that equation forces us to acknowledge that electromagnetic waves behave as discrete streams of particles, photons. Despite lacking mass, these photons carry defined momentum and exert kinetic force.
That perfectly aligns quantum mechanics and relativity right there.
It does. Furthermore, if the light is circularly polarized, meaning its electric field vector spirals like a corkscrew as it travels, the photons carry intrinsic angular momentum.
Wait, really? Like they're spinning?
Yeah, spinning like tiny massless rifle bullets, imparting actual physical spin to the matter they strike. The classical wave equations seamlessly generate the exact momentum values required by quantum mechanics.
That is just, wow. We started by mapping the ghostly illusion of the retarded time, watching as the geometric delay of light stretched circular orbits into curtate cycloids, violently compressing radiation into the X-rays of a synchrotron. We identified that exact polarized compression lingering in the 900-year-old mystery wreckage of the Crab Nebula. We explored how a diffraction grating can geometrically shatter the colorless spike of Bremsstrahlung breaking radiation into a rainbow of frequencies.
We did all that, yeah.
We forced the universe into mathematical symmetry, using time dilation for the Doppler effect and length contraction for telescope aberration. And finally, we tracked the magnetic cross product of a wave to discover the quantum momentum of a massless photon. What a wild journey.
It really is a profound realization that light does not merely observe or illuminate the universe. We have proven that light carries physical momentum, exerting real pressure and angular spin on the matter it encounters.
So it's actively doing something.
Absolutely. Think about it for a second. Consider the state of the early universe, a dense, opaque fog of primordial plasma. The intense light of the early cosmos couldn't escape that fog. It endlessly bounced and scattered within it.
Like it was trapped.
Trapped, exactly. And that light wasn't just illuminating the void. If every photon from every exploding star and swirling galaxy is shooting through the universe carrying physical spin and pressure, is light itself subtly pushing, stirring, and physically shaping the cosmic dust of the universe.
You mean the literal physical pressure of that trapped radiation, the microscopic push of countless massless photons is what drove the primordial matter apart?
Yeah, carving out the voids and clumping the gas, physically shaping the vast structures of the galaxies we live in today. We're only just beginning to map ways in which light physically sculpts the cosmos.
That is something to seriously mull over. Light is not just a flashlight, it's a sculptor. Thank you for joining us on this deep dive into the universe's most hidden mechanics. We will see you next time.
Look around you right now. Just take a look at the room you're in. Maybe look at a colorful mug on your desk or the bright blue sky out the window. Now, what if I told you that those colors, that vibrant red or that deep ocean blue, they don't actually exist out there in the physical world?
Yeah, it is a massive shock to the system the first time you realize it. I mean, physics can measure the specific wavelength of light bouncing off that mug, sure.
Right.
But a wavelength doesn't inherently contain a color. The experience of, like, red or blue, it's completely a psychological and physiological magic trick.
It's wild.
It really is. It's a sensation manufactured entirely inside your head.
So, if that mug isn't actually red, it begs the question of what my eye is actually doing when I look at it. Like, are we just passively recording a hallucination?
Basically, yes.
Today's deep dive into our source material, which is drawn from Richard Feynman's legendary lectures, by the way, is going to completely deconstruct the mechanics of human vision. We're looking at how our eyes and brains manufacture the reality we think we see every single day.
And to do that, we have to throw out our neat little academic boundaries. Nature really doesn't care about the difference between, a physics department and a biology department.
Right, it's all connected.
Exactly. To truly understand vision, we have to look at the seamless, real-time integration of physics, biology, and psychology. They all have to work together to render your visual field.
Well, I always had this mental model of the human eye as a sort of, I don't know, organic but basically dumb camera lens.
Sure, a lot of people do.
Right. Like light comes in through the front, hits the back wall, the retina, and then that raw data just gets piped straight up an optic nerve cable to the brain's hard drive to be processed.
Yeah, but that assumes the retina is just a flat, uniform piece of biological film,
Right.
and the anatomy tells a completely different story.
Oh, so.
Well, the journey of light does start as it enters through the cornea and gets projected onto the retina at the back of the eye. But that hardware is highly specialized and unevenly distributed.
Unevenly.
Yeah. The very center of your visual field, the part you use when you stare directly at small text to read it, is called the fovea, or macula, and it's packed incredibly tightly with receptors called cones.
And the cones are they're the color ones, right?
Exactly. They are your high-definition color-sensing hardware.
Okay, but as you move away from that center point into your peripheral vision, the source says those cones thin out, and they get replaced by an entirely different kind of receptor called rods.
Right. And then, of course, all of those signals eventually have to leave the eye to reach the brain.
Through the optic nerve.
Yep. There's a physical spot on the retina where all the nerve fibers bunch together to exit, and that creates the blind spot. In that specific spot, there are absolutely no light receptors whatsoever.
Wait, so there's literally just a dead zone?
A literal hole in your vision at all times, yeah.
That is crazy.
Your brain is just seamlessly photoshopping the gap based on context.
Which reminds me of that amazing historical anecdote from the text about the blind spot. A physiologist once demonstrated this anatomical quirk to a king of France.
Oh, yeah, this is a great story.
Right, because court sessions back then were incredibly long and boring. So the king would entertain himself by carefully positioning his gaze across the room. He would line up his blind spot so it perfectly overlapped with the heads of his courtiers.
Visually cutting their heads off.
Literally visually cutting off their heads one by one without them ever knowing.
It's a slightly dark application of anatomy, sure, but it perfectly illustrates how constructed our vision is. And beyond the blind spot, that whole dumb camera model completely falls apart when you look at the actual wiring.
Oh, because the cells aren't just wired straight back to the brain.
Right. The cells in the retina are heavily interconnected with each other horizontally, so the retina is already thinking about the light before the brain ever gets involved.
I picture this kind of like a modern smartphone camera. Like when you take a picture, the phone doesn't just save the raw sensor data to your gallery. It runs automatic edge detection, it applies HDR algorithms, it pre-processes the contrast. But biologically, How is a layer of cells doing image processing without a central processor?
It uses a mechanism called lateral inhibition. When one of these horizontal cells gets hit by light, it doesn't just send a signal backward to the brain.
Okay, what does it do?
It actually sends a signal sideways to suppress its immediate neighbors.
Wait, really? So seeing light in one spot actively blinds the spots right next to it?
Temporarily, yes. By suppressing the neighboring cells, the eye artificially creates a sharper contrast at the boundary between light and dark.
Oh, wow.
It's biologically finding the edges of shapes for you. And the body does this for pure efficiency.
So the brain doesn't have to work as hard.
Exactly. By synthesizing this visual info locally, right there inside the eye, it extracts the most crucial data so the brain doesn't get overwhelmed processing redundant stuff.
That makes total sense. So we have this highly pre-processed data coming from a split hardware system, the cones tightly packed in the middle, the rods dominating the edges.
Yeah.
But this entire biological setup fundamentally changes the second the sun goes down. Like, we completely switch systems.
We do. The eye has an astonishing ability to adapt to light intensity drops of, like, over 1,000,000 to 1.
1,000,000 to 1. That's hard to even wrap your head around.
It is. And cones require a massive amount of light energy to fire. So as the environment gets dark, those color-sensing cones essentially power down. Complete control of your vision is handed over to the night shift crew, the rods.
And the rods operate under totally bizarre rules compared to the cones. Like, for starters, the text points out that rods are completely colorblind.
Yeah, in low light, your world is rendered entirely in grayscale.
Which we don't even really notice.
No, because our brains fill in the blanks.
Yeah.
But it goes deeper than that. Their sensitivity to different wavelengths of light shifts dramatically.
How so?
During the day, your cones peak in their sensitivity around the yellow spectrum. But at night, your rods peak in the green and blue spectrum. And the most extreme shift happens at the far end of the spectrum. Red light is physically invisible to the rods.
Wait, invisible. So if I'm in a dark room and a pure red light turns on, my rods just register. Pitch black.
A complete absence of light, yeah. This physiological quirk creates a phenomenon known as the Purkinje effect.
Purkinje effect, right?
Yeah. Imagine holding a bright red piece of paper and a blue piece of paper in a sunlit room. The red paper will likely look significantly brighter and more vibrant to your cones.
Makes sense.
But take those same two pieces of paper into a dimly lit room, and reality flips. Because your rods cannot see red, the red paper will appear almost black, while the blue paper will look relatively bright.
Your entire perception of the brightness scale reverses.
Exactly.
You know, I've actually experienced a glitch related to this while stargazing.
Oh, really?
Yeah. Have you ever tried to look directly at a very faint star and it just vanishes? But the second you look slightly away from it, it like pops back into your vision.
Yes. That's called averted vision.
And the anatomy we just discussed explains exactly why that happens. Because the fovea, the very center of your gaze, is packed exclusively with cones.
And cones need light.
Right, so it has zero night vision capabilities.
Yeah.
When you look directly at a faint star in the dark, you're placing that tiny point of light right onto your fovea, which basically blind at night.
So you physically have to look slightly to the side so the starlight hits the rods in your peripheral vision.
Yeah, exactly. It's such a weird feeling.
But if we view this through an evolutionary lens, it is a brilliant survival mechanism.
Oh, totally.
The periphery of the eye is highly sensitive to motion. I mean, you can't read a book out of the corner of your eye, but if a predator or even just a bug jiggles in the shadows, you notice it instantly.
Because the rods are doing their job.
Right. We are hardwired to detect faint movement on the extreme edges of our vision in low light. It functions as a low-resolution, highly sensitive early warning system.
So the rods keep us alive in the dark.
Yeah.
But let's bring the lights back up and power the cones back on. How do these tiny biological receptors synthesize the millions of distinct colors we actually perceive?
Well, to understand the mechanics of color, we have to look at physics, specifically the math of color mixing. And the first step is abandoning everything we learned in kindergarten art class about mixing physical paint.
Right, because paint absorbs light. It subtracts colors. And I always assumed mixing light worked the exact same way.
Many people do. But mixing light is about adding energy vectors together. Early scientists studying human vision realized they couldn't define what a color feels like objectively.
Because you can't measure a hallucination.
Exactly. Instead, they treated the human eye as what they call a null instrument.
Okay, what does that mean in a practical sense? Like, how do you use an eye as an instrument without measuring the feeling?
Think of it like tuning a guitar by ear.
Okay.
You don't need to know the exact mathematical frequency of the string you're tuning. You just pluck two strings at the same time and adjust the tuning peg until the sound waves stop wobbling against each other.
You tune it until the two strings sound identical.
Right. And scientists did the exact same thing with light. They projected two patches of light next to each other and simply asked the observer to turn the dials until the two patches were indistinguishable.
Purely based on matching.
Pure matching.
And the force notes that by adjusting the brightness of just 3 primary lights, say red, green, and blue projectors, they could mix them to perfectly match almost any target color of light in existence.
Which brings up a fascinating quirk about how our brains interpret those mixed lights based on context.
Oh, you're talking about the Brown illusion.
Yes.
I loved this detail so much. Because if you think about every concert or theater production you've ever been to, you have never seen a brown spotlight.
Never.
You physically can't project a beam of brown light.
Right.
Because brown is an illusion. It's born of that lateral inhibition we talked about earlier.
The edge detection stuff.
Right. If you shine a dim orange or yellow light onto a wall in an otherwise pitch black room, it just looks like dim orange.
Naturally.
But the moment you surround that dim orange light with a blindingly bright white background, your eye suppresses the signal from the orange center to enhance the contrast of the boundary.
And so your brain interprets that artificially darkened orange as brown.
Exactly. It's a context-dependent hallucination.
It only exists relative to something brighter. The text jokes about that yellowish-green color used in army uniforms. Like, by itself, the hue isn't actually that bad.
No, it's fine.
It only looks terrible because you almost always see it contrasted against a lighter background, so your brain shifts the perception of it.
That's spot on.
But I want to go back to those 3 primary projectors you mentioned. You said they could match almost any color. What was happening with the colors they couldn't match?
So the scientists hit a mathematical wall. There were a few specific, pure spectral colors that were so deeply saturated that when the scientists tried to mix their 3 primary lights to match them, the mixed light would always look a little too washed out.
It wasn't vibrant enough.
Right. Adding the projectors together caused them to lose that deep saturation. The equations simply wouldn't balance.
And the solution they came up with for this unbalanced equation sounds like straight-up science fiction. The text says they had to use negative light.
Yeah.
But you obviously can't project a beam of darkness, so how are they mathematically subtracting light using a physical projector?
Mathematically, if you have an equation where a plus b does not equal c, and you can't subtract from the left side, you can balance the equation by adding something to the right side.
Oh, I see.
So in physical terms, instead of mixing red into their green and blue projectors, they took their red projector and shined a little bit of it directly onto the target color they were trying to match.
Wait, they desaturated the target color until it matched their mixed projectors.
Exactly. Mathematically, shining it on the target functioned as a negative coefficient on the projector side of the equation.
That is a brilliant piece of lateral thinking.
Truly. And this strict vector addition, where scientists realized they could mathematically plot every single color human beings can possibly see on a 2D map called the chromaticity diagram, it proved something profound.
Because the math was so consistent.
Right, because the math of mixing light followed these incredibly rigid, predictable 3-variable equations. Physicists knew with absolute certainty that there had to be exactly 3 physical types of color receptors in the human eye.
So the math completely predicted the biology.
It demanded it.
But the biology didn't cooperate. Like for almost a century after the math was settled, nobody could actually find these 3 mythical cones in a human eye.
Well, they found the pigment for the rods way back in 1877.
The night vision ones.
Yeah, it's called visual purple. Because rods need to capture every stray photon in the dark, there is a massive amount of visual purple packed into the retina. So it was relatively easy to isolate and extract into a test tube.
My guess. Because the cones operate in bright daylight, they don't need to be nearly as sensitive, so the actual pigment chemicals inside them are microscopic.
Spot on. The cone pigments are so incredibly sparse that for decades, scientists couldn't extract enough of them to even prove they existed.
So what did they do?
They had to figure out the exact absorption curves of these invisible pigments using pure algebra.
Algebra?
Yeah. They did this by studying the intersection of color blindness and physical optics, specifically looking at individuals known as dichromats.
Right, because most of us are trichromats, meaning we need 3 primary projectors to match any color. But dichromats are individuals who are colorblind in a very specific way. They only need two primary projectors to match any color they see.
Exactly. So by finding individuals missing the red-sensitive pigment, they're called protonopes, and individuals missing the green-sensitive pigment deuterandokes, scientists essentially found biological algebra equations missing a variable.
I see. By comparing the color matching data of a dichromat against a standard trichromat, scientists just mathematically subtracted the known data to plot the exact curves of the elusive missing pigments.
Yep, it's incredibly elegant.
But at some point, math isn't enough. You need physical proof that these chemicals exist in the eye.
Of course.
And a scientist named Rushton finally got that proof, and his experiment is like one of the most ingenious workarounds I've ever encountered.
Amazing.
Since he couldn't extract the sparse pigment from a living eye to put in a test tube, he decided to use the living eye as the test tube.
Yeah, Rushton used a device called an ophthalmoscope. He essentially fired a very specific beam of light directly into a living person's eye, passing through the lens all the way to the back of the retina.
So the light passes through that incredibly sparse cone pigment, hits the back wall of the eyeball, and bounces back out toward the scientist. It travels through the pigment twice.
Exactly.
My first thought when reading this was an analogy about a stained glass window.
Oh, let's hear it.
Imagine you want to determine the exact color of a stained glass window locked inside a dark church.
Okay.
You aren't allowed to touch it or take a piece of the glass. So your workaround is to shine a powerful flashlight through the window, let the beam bounce off a mirror positioned behind the glass, and then measure the color of the beam that reflects back out to you.
That's a great way to picture it.
That is essentially what Rushton did to the human eyeball.
It is. That analogy covers the bouncing mechanism perfectly, but Rushton faced a massive complication.
What was that?
Well, that light bouncing out of the eye isn't just passing through cone pigment. It's passing through blood vessels, macular fluid, general tissue.
Oh, right.
So how do you separate the microscopic signal of the cone pigment from all that biological noise?
Yeah, if you can't touch the eye, how do you separate it?
By doing the stained glass trick twice. See, cone pigments bleach when exposed to very bright light.
Bleach, like they lose their color.
Exactly. The intense light physically alters the pigment molecule, temporarily rendering it transparent. It's actually the same reason you see a lingering afterimage when a camera flash goes off in your face.
Oh, that makes sense.
So Rushton measured the faint reflection once. Then he blasted the eye with a bright, bleaching light, temporarily erasing the cone pigment's color, and measured the reflection a second time.
Oh, by subtracting the second measurement from the first, the only difference between the two is the bleached pigment.
You got it.
All the blood vessels and tissue stayed exactly the same. He isolated the cone pigment mathematically without ever cutting into the eye.
He physically measured the missing red pigment curve in a living colorblind eye versus a normal eye. It provided the biological proof that finally matched the century-old physics equations.
That is unbelievable. All of this effort, all of this staggering complexity were in both physics and biology just to generate a sensation. What does this all mean for us, the people walking around using these eyeballs every day?
Well, it brings us back to our overarching theme. Color is fundamentally a sensation based on comparison. The text details a beautiful, simple experiment that proves the eye is not a passive camera.
Okay.
Imagine casting two shadows of a single object on a wall. You illuminate the object with two distinct light sources. One light source is purely white. The other light source is purely red.
Okay, so I'm picturing a white shadow and a red shadow on the wall.
But an observer looking at that wall won't see a white shadow. If you ask them, they will inevitably insist the shadow illuminated by the white light looks undeniably blue.
Even though there is zero blue light anywhere in the room.
Zero.
Yeah.
Because the retina is looking at the intense red light surrounding that white shadow, making a rapid, unconscious mathematical comparison, and literally hallucinating the opposite color blue to maximize the visual contrast.
Wow.
It is an active interpreter of reality.
To recap this incredible journey we've been on, your retinas are doing intense edge-detecting math right now before your brain even gets involved.
Yep.
Your colorblind rods are waiting for the lights to dim so they can shift your entire perception of brightness and render the color red completely invisible.
True.
And your microscopic cone pigments are performing strict vector addition to paint the world around you, relying on pigments so elusive we had to bounce light off the inside of a living eyeball just to prove they were there.
I want to leave you with a final implication to ponder based on all of this.
Please do.
As you look around your room right now, you must accept that you are not seeing an objective physical reality. You are experiencing a highly curated, custom-rendered hallucination.
A hallucination.
Yes, it is generated by the quirky, specific biological wiring of your human retinas. So imagine if you were born with a fourth type of cone. What invisible colors are hiding in the light bouncing around you right now, completely imperceptible to you simply because you lack the biological hardware to translate them?
I will definitely be staring at the walls thinking about that later. Thank you for joining us on this deep dive into the source material.
My pleasure.
Never look at a shadow, a faint star, or a brown shirt the same way again. We'll catch you next time.
I want you to picture a flat disc, like an old vinyl record, but painted with nothing but stark black and white geometric patterns.
Right, just black and white ink, no other pigments at all.
Exactly. There is absolutely no color on it whatsoever. Now imagine you put that disc on a turntable and spin it really fast. As the patterns blur together, something seemingly impossible happens. Inside those dark, spinning rings, you suddenly start seeing distinct, real colors.
Which is wild because the color obviously isn't on the paper, right?
Mm-hmm.
And it doesn't exist in the light bouncing off the paper either. It is entirely an invention of your visual system.
It just makes it up.
Completely. And we see this happen in other classic experiments too.
Yeah.
I mean, for example, if you shine only red and white light onto a pink background and then an object casts a shadow, your visual system will actually fill that shadow in with a distinct blue color.
Wow. Even though there's no blue light shining anywhere in the room.
Exactly. The blue isn't physically there. Your brain is taking the content, the background colors, the pattern of the spin, and making these active corrections. It combines information at a very elementary level to literally invent color and contrast where there isn't any, just to make sense of the scene.
Today, we are taking a deep dive into the underlying mechanics of seeing. We are drawing our source material directly from Chapter 36 of the legendary Feynman Lectures on Physics. And our mission for this discussion is pretty simple. We want to prove to you that your eyes are not just, dumb little cameras passively recording the world.
Not at all.
Right. They are actively calculating, interpreting, and even outright guessing at reality long before you consciously realize you're looking at something.
It really completely reframes how we think about perception. Because we tend to view the eye as a purely optical instrument, right? Like it just funnels a raw video feed down a wire to the brain where all the actual heavy lifting and processing happens.
Yeah, that's definitely the standard assumption.
But anatomically, we know that's just not the case. If you trace the embryological development of a human being in the womb, the retina, which is that light-sensitive layer at the very back of the eye, it doesn't just connect to the brain, it actually originates as part of the brain.
Wait, really?
Yeah. During development, a piece of the central nervous system physically grows outward toward the surface of the face. So the tissue in the retina is organized remarkably similarly to brain tissue.
Now, I want you to think about that the next time you look in the mirror. You are literally looking directly at an exposed piece of your own brain that has grown outward to touch the light.
It is a totally fascinating biological reality.
Yeah.
And the hardware surrounding that exposed brain tissue is it's incredibly sophisticated. Take the cornea, for instance, the clear front dome of your eye. It handles most of the heavy lifting when it comes to focusing light. It actually has a refractive index of 1.37.
Okay, and just for context, water has a refractive index of about 1.33, right?
Correct.
So is that tiny difference why everything becomes a blurry, unreadable mess when you open your eyes underwater?
That is the exact reason. Because the density of the water is so close to the density of your cornea, the light barely bends at all when it passes from the water into your eye. You essentially lose almost all your focusing power.
Oh, that makes so much sense.
Right. But when you're in the air, the cornea bends the light sharply, and then right behind it sits the lens, which acts as a fine tuner. And the lens isn't just, a uniform bead of biological glass. It's actually built in microscopic layers, very much like an onion.
Like an onion?
Yeah, the refractive index is 1.40 in the solid center, and it gradually drops layer by layer until it reaches 1.38 at the outer edges.
But why go through the trouble of building it and changing layers like that? I mean, why not just make it a clear, uniform sphere? Wouldn't that be easier to grow?
You'd think so, but a uniform sphere is actually terrible at focusing light cleanly. It suffers from something physicists call spherical aberration.
Right, I've heard of that with camera lenses.
Exactly. If you shine light through a perfect glass marble, the light rays hitting the outer edges of the marble will bend much more sharply than the rays passing through the dead center. so they don't meet at a single focal point, which creates this blurry, weird halo effect.
So by making it less dense at the edges?
By layering the lens so it's less dense at the edges, the eye actually slows down the light in the center more than the light at the rim. It artificially brings all those rays into a single razor-sharp pinpoint focus. It corrects for the physics flaw of a curved surface way better than a uniform piece of glass ever could.
That is just brilliant biological engineering. But in the middle of all that perfection, there is a structural feature of the retina that feels like a massive mistake. The retina is literally built inside out.
It is a profound structural quirk, yes. The actual light-sensitive receptor cells are pushed all the way to the very back of the retina, pointing entirely away from the incoming light.
Which means the light has to travel through layers of other cells, blood vessels, and nerve fibers just to reach the receptors. It's like building a smartphone camera, but installing the digital sensor backward, expecting the light to pass through the internal microchips in the battery to somehow take a picture.
It is deeply counterintuitive.
And the wiring for the iris is just as convoluted. The nerves that control the radial muscles, the ones that open your pupil wide, they don't just run a few millimeters from the brain straight to the eye. They take this massive detour all the way down your spinal cord, out into your upper chest, up through your neck, and finally back into your head.
It's a really great example of evolutionary baggage. Those nerves are part of the sympathetic nervous system. So, in our deep evolutionary past, the rudimentary structures that eventually became our head and our eyes, they developed in tandem with segments of the neural tube that ended up in the upper spine and neck.
Oh, so as we evolved necks.
Exactly. As organisms grew more complex and the head extended forward, those nerve connections simply stretched along with it. Nature generally doesn't scrap a working system to build a more efficient one from scratch. It just modifies what's already there.
It sounds incredibly messy, to be honest.
It does seem inefficient, but even these bizarre structural quirks are woven into a masterfully integrated processing system. Like, let's look at the wiring heading from those inside-out retinas back to the brain. The optic nerves don't just go straight back. They meet at a junction called the optic chiasma, where the wiring is deliberately split.
Split how?
Well, the left visual field from both of your eyes is routed entirely to the right hemisphere of your brain, and the right visual field from both eyes is routed to the left hemisphere.
Wait, so the brain takes the physical image from the eyeball and just chops it right down the middle?
It cleanly divides the visual field, yes. And this forces the two hemispheres of the brain to constantly communicate and compare notes. By overlapping the slightly different perspectives from each eye, the brain can mathematically calculate depth and distance. It turns a flat 2D projection into a real 3-dimensional understanding of the world.
That's amazing. But with all this incredibly complex cross-wiring and processing, how does an animal know how to use it? Do we have to learn how to see through trial and error? Like, does a newborn reach for something, miss, and then have to sort of update its visual software to correct the math?
It's a great question. And to answer that, biologists conducted some pretty groundbreaking experiments on amphibians, specifically salamanders.
Salamanders?
Yeah, because salamanders have a simpler visual system. They don't have that optic chiasma crossover we just talked about. Their eyes map directly to the corresponding side of the brain. So researchers wanted to see what would happen if they disrupted that mapping. If you actually cut the optic nerve of a salamander, you sever thousands of individual microscopic nerve fibers into a totally scrambled mess.
Oh, wow.
But salamanders have incredible regenerative abilities, and those fibers will actually grow back.
Okay, but do they just grow back randomly, or do they somehow find where they're supposed to go?
They find their exact, precise, original connections in the brain. Out of thousands of possibilities, each fiber reconnects flawlessly, and the salamander regains perfect vision.
That alone is mind-blowing. But I know they took the experiment a step further. Did they test what happens if they mess with the physical orientation of the eye itself?
They did. They cut the optic nerve again, but before it could heal, they physically popped the eyeball out of the socket, rotated it 180 degrees, and placed it back in upside down.
Ouch.
Yeah, and then they let the nerve heal. Now, the eye is physically seeing the world completely inverted. So when a fly buzzes above the salamander, the upside-down eye tells the brain the fly's down below.
Right. So does the salamander eventually figure it out and adjust its aim after a few misses? I mean, surely hunger drives it to correct the error, right?
It never learns. It will continuously strike downward at a fly that is above it for the rest of its life. You will literally starve rather than correct the aim.
Wow.
This experiment definitively proves that much of our visual processing is completely hardwired. It is not something the animal figures out through experience.
But if they aren't learning, how do thousands of severed microscopic cables know exactly where to plug back in? It's not like there are little labels on the nerve ending.
The mechanism is actually chemical gradients. As the tip of a severed nerve fiber grows back, it essentially smells its way through the brain tissue. The brain sets up these overlapping chemical fields. Think of them as distinct scents. One chemical gets stronger as you move up, another gets stronger as you move left.
Oh, like a coordinate system.
Exactly. Each individual nerve fiber has a unique combination of receptors on its tip. It grows, testing the chemical environment, following the specific concentration it is programmed to seek, until it reaches the exact coordinate where the chemicals perfectly match its programming. It's pre-programmed geometry.
So the hardware is rigidly set up before the animal even opens its eyes.
Yes. And we see this even more clearly when we look at the frog. A frog's visual center in the brain, which is called the tectum, is built in physical layers. Researchers discovered that the optic nerve of a frog isn't just sending a generic video feed of the world. It sends specific, pre-calculated alerts.
What kind of alerts?
Well, they found 4 distinct types of visual nerve fibers coming from the eye. One type specifically fires only when it detects a convex edge moving into the field of view. Another type is a dimming detector that fires when the overall light level drops.
It's like the eye is doing the sorting before the brain even gets the memo.
And those fibers sort themselves automatically into 4 distinct physical layers in the brain, guided by those exact same chemical gradients. The hardware is programmed to break the visual world down into specific mathematical features without any conscious thought involved whatsoever.
We're talking about all these cables sending signals and calculating edges, which is amazing. But let's zoom in on the physics for a moment. How does a particle of light, just a single photon, actually pull the trigger to start an electrical signal in that cable?
The trigger mechanism happens deep in the retina, inside the rod cells, which are responsible for our low-light vision. Inside these cells is a pigment protein called rhodopsin, sometimes referred to as visual purple. And attached to this protein is the active ingredient, a tiny molecule called retinine.
And just for anyone taking notes at home, retin is essentially vitamin A, right?
That's right.
This is exactly why we're always told to eat our carrots. Our bodies can't manufacture vitamin A from scratch. So if your diet lacks it, you run out of retinine, and your rod cells literally lose their chemical triggers, which leads to night blindness.
That is exactly the mechanism behind night blindness. Now, to understand how a photon triggers this molecule, we really have to look at the chemical structure of retin. It is built as a long chain of carbon atoms connected by what chemists call alternating double bonds.
Let me use an analogy here to visualize this, because alternating double bonds sound a bit complicated. Think of those double bonds as a long, straight row of dominoes stood on end.
I like that.
In an ordinary molecule, if light hits an electron, the electron might wiggle a bit, but the energy mostly stays localized. But in this alternating chain, the electrons are loosely bound and highly interconnected. When a photon of light strikes one end of the retinine molecule, it shifts one electron out of place. That electron instantly bumps the next one, which bumps the next, causing this massive cascade. It shifts an electron all the way down the chain to the other side of the molecule in just a fraction of a second.
Right, and that domino cascade changes the physical shape of the entire molecule, which is what actually kicks off the electrical nerve signal. It's an incredibly sensitive and efficient mechanism for capturing light energy. And what is truly profound is how universal this design is. Nature didn't just invent this domino trick for human eyes. No. If you examine chlorophyll, the molecule that plants use to capture sunlight to make sugar, you'll find it relies on the exact same structure of alternating double bonds. The hemoglobin that makes your blood red uses it too. Early in evolutionary history, biology found one highly effective physical trick for interacting with light, and it basically deployed it across the entire natural world.
That's incredible. But if the underlying chemistry of catching light is identical across the natural world, why do eyes themselves look so radically different? I mean, why aren't we walking around with compound eyes like a fly?
Because the physical structure of the eye is largely dictated by the environment and the scale of the animal. A bee is a really great example of an alternative evolutionary solution. Instead of a single large lens focusing light onto a single retina, their compound eye is made of thousands of tiny individual tubes called ommatidia, all arranged in a big dome.
Which gives them a completely alien visual experience. We see colors from red to violet. Bees can't see red at all. A red rose just looks black to them. But their vision extends deep into the ultraviolet spectrum. A flower that looks plain yellow to us might have brilliant, glowing UV patterns acting like a landing strip, pointing the bee right to the nectar. And they process time differently too, don't they?
They do. Their temporal resolution is much higher. Humans perceive smooth motion at around 24 to 30 frames per second. A bee can distinguish flickers of light up to 200 times per second.
Wow.
Yeah, so if a bee watched a human movie, it would just look like a painfully slow slideshow. They can also detect the polarization of light. This means they can look at a small patch of blue sky and instantly calculate the exact geometric position of the sun, even if the sun itself is completely hidden behind clouds.
But let's talk about the physical construction of that compound eye, because it presents a really fascinating physics problem. You have these thousands of little tubes, the ommatidia. Logically, if you want a sharper image with higher resolution, you need to pack as many of those tubes into the eye as possible, which means making them smaller and smaller. It's like trying to cram more megapixels onto a digital camera sensor. So why can't a bee's ommatidia just be microscopic?
Because light acts as a wave, and that introduces a strict physical limitation known as diffraction. Imagine ocean waves rolling through a narrow gap in a breakwater. If the gap is wide, the waves pass straight through, mostly undisturbed. But if you make the gap very narrow, the waves bend as they pass through and spread out in all directions on the other side.
Right, they splash out.
Light does the exact same thing. If the opening of the bee's ommatidia is too narrow, the light waves bend and splash all over the inside of the tube, turning the image into a blurry mess.
So evolution faces this really tight compromise. If you make the tubes too large to avoid diffraction, you can't fit very many on the bee's head, and the image is heavily pixelated. But if you make them too small to get more pixels, the physics of diffraction blurs the whole image anyway.
It is a pure optimization problem, balancing geometry against wave mechanics. Using physics equations, you can calculate the exact mathematical optimum, the specific size of an opening that provides the best possible balance between pixel density and diffraction blur for the wavelength of light a bee actually sees.
And what's the number?
That mathematical optimum is approximately 35 micrometers. And when biologists put a real bee's ommatidia under a microscope and measure them, they're roughly 30 to 35 micrometers across.
No way.
Yes. The biological reality perfectly matches the theoretical physics calculation.
Nature literally solved the calculus problem. But if the compound eye is so perfectly optimized, why didn't nature scale it up for bigger animals, like us?
Well, because of the geometry of those tubes, the compound eye scales terribly. If a bee wanted human-level visual sharpness using a compound eye, the eye would have to be the size of a beach ball.
Okay, that would be terrifying.
Yeah, highly impractical. To get high resolution in a compact space, larger animals required the camera-style eye, a single lens focusing light onto a dense retina. But mammals aren't the only ones who ended up with this design. The octopus has one too.
I love the octopus example.
It's so good. The octopus is a cephalopod, an invertebrate. Its evolutionary lineage split from ours hundreds of millions of years ago, long before anything resembling an eye existed. Yet, the octopus somehow evolved a cornea, a lens, an iris, and a retina that are functionally identical to ours. It is one of biology's greatest examples of convergent evolution.
And if you're listening to this and wearing glasses, you can blame evolution for putting your camera sensor in backward, while the octopus in the ocean got the premium upgrade. Because the octopus doesn't have our inside-out retina flaw. Their light-sensitive cells face outward, directly toward the light, with all the messy wiring neatly tucked behind. They independently engineered the exact same eye, but they just organized the parts more logically.
It's a very humbling comparison, honestly. But whether you have the optimized compound eye of a bee, the perfectly logical camera eye of an octopus, or our weird inside-out mammalian eye, the optic nerves still have to take all those electrical domino chain signals and mathematically calculate an image.
Right, and earlier we talked about the frog having those hardwired edge detectors. How does the eye actually calculate what an edge is before the brain even gets involved?
Well, to understand the physical mechanism behind that, we have to look at an animal with a much simpler visual system, the horseshoe crab. They have a very rudimentary compound eye with only about 1,000 large ommatidia.
So it's easy to study.
Exactly. Because the system is so simple, scientists can insert microscopic electrodes directly into single optic nerve fibers and literally listen to the signals being sent to the brain.
And they hear those electrical spikes. And just to be clear, nerves don't communicate by sending a larger or smaller voltage spike. The spikes are always the exact same size. Intensity is communicated by the rate of the spikes, right? Like a dim light might cause a slow pop, 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 while a bright light causes a rapid pop, 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 pop.
That is the basic language of the nervous system, yeah. So researchers shone a light on one specific ommatidium on the crab's eye, and they heard the nerve fire rapidly. Then, they did something that changed our entire understanding of vision. While keeping the light perfectly steady on that first ommatidium, they shone a second light on its immediate neighbor.
Logically, you'd expect the first one to just keep firing at the exact same rate because the light hitting it hasn't changed at all.
Right. But the moment the neighbor was illuminated, the firing rate of the first nerve slowed down. The researchers discovered a phenomenon called lateral inhibition. When a visual cell receives light, it doesn't just send a signal to the brain, it also sends a horizontal signal to its immediate neighbors, telling them to suppress their own firing. They actively inhibit each other.
But why on earth would the eye deliberately suppress its own signals? It sounds like it's just artificially dimming the image for no reason.
It definitely seems counterintuitive until you apply it to a boundary between light and dark. This is the mechanical explanation for those frog edge detectors we discussed.
Okay, walk me through it.
Imagine looking at a scene where a bright white wall meets a dark black shadow. The visual cells looking at the middle of the bright white wall are getting flooded with light. But because all of their neighbors are also getting flooded with light, they are all mutually inhibiting each other. The whole group turns their signal volume down.
So they're basically communicating, we all see bright white, keep it quiet, there's no changing information here.
Exactly. Now consider the cells right at the boundary, the ones looking at the very last sliver of white before the black shadow begins. They are getting bright light, but half of their neighbors are in the dark shadow, and those dark neighbors aren't firing, which means they aren't sending any inhibition signals.
Oh, I see it. The cells right on the edge of the light don't get suppressed by the dark side.
Yes, they're freed from the inhibition. So they fire extra strong, much stronger than the cells just a few millimeters over in the solid white area. The dark side of the boundary experiences a similar math trick in reverse. The result is that the eye artificially exaggerates the contrast right at the boundary. It is mathematically calculating the difference between light and dark, creating this enhanced spike in the signal right at the edge.
This perfectly explains something I've always wondered about visual art. If our eyes are just taking in fields of light and shadow, why do humans naturally draw objects using outlines? If you look at a coffee cup sitting on a desk, there is no actual black line floating in the air around the rim of the cup.
This is the ultimate realization of lateral inhibition. Outlines do not exist in the physical world. They are a biological illusion. We draw outlines because that is the literal mathematical shortcut our optic nerves use to tell our brain where one object ends and another begins. Your eye manufactures a line of exaggerated contrast to make the edges of objects pop. So when an artist draws a simple line drawing, they are bypassing physical reality and directly mimicking the mathematical processing of the retina.
We draw outlines because our eyes are wired to hallucinate them. That is incredible. We've covered so much ground today. We've seen that the eye isn't a passive window at all. It is a highly opinionated data processing center. From the physics of domino chain molecules catching photons, to the perfect mathematical constraints of a bee's eye, to a horseshoe crab using lateral inhibition to literally invent the concept of an outline. Your eyes are constantly calculating, filtering, and actively constructing the reality you think you're just passively watching.
It is a continuous dynamic negotiation with the light around us. And if we return to that frog experiment from earlier, there's one detail we saved for the end that perfectly encapsulates how active this construction really is.
All the darkness detectors. Let's explain this because it challenges everything we assume about closing our eyes.
When researchers mapped the frog's different nerve fibers, they found a specialized set of fibers that behave entirely backward to what you'd expect. These fibers do not fire when there is light. If the environment is brightly lit, they are completely silent. They only begin to fire when the light goes away.
Wait, so darkness isn't just a lack of an electrical signal?
No. Plunging the frog into absolute pitch darkness causes these specific nerve fibers to start firing furiously. They send a massive continuous wave of electrical signals to the brain. They are energetically, actively screaming, "It's dark! It's dark!"
I want you to take that thought with you. When you turn off the lights tonight, get your room as pitch black as you can and just close your eyes. And while you're lying there in the dark, remember the spinning disc from the beginning of this deep dive where your mind invented colors. And wonder to yourself, when you are looking at absolute pitch black, are your eyes truly resting? Or is an entire specialized network of nerves inside your skull firing furiously right now, burning energy, actively working to create the sensation of blackness for you?
It completely reframes what nothingness actually looks like. The brain is still painting, even without the light. Usually when we talk about a physics experiment in this deep dive, there's this expectation of precision.
Right, like a beautifully engineered piece of clockwork.
Yeah, exactly. Like you roll a billiard ball across the table, the high-speed camera catches that clean, straight line, and the physicist just points to the math and says, well, there it is. X marks the spot.
It's totally deterministic. You know the starting conditions, so you know exactly what the end result will be.
Because we're wired to understand a universe where objects have, defined positions, clear trajectories, and they just follow the basic rules of cause and effect.
Right, but then you step into the world of atomic particles.
Oh boy, yeah.
You shrink down to the quantum level, and suddenly that camera is completely useless.
Yeah.
We're looking at a physical landscape that is, well, honestly, it's just murky.
And nobody mapped that murky water better than Richard Feynman.
Oh, absolutely.
In chapter 37 of his famous physics lectures, which is just titled Quantum Behavior. By the way, he zeroes in on one specific phenomenon.
Yeah. He calls it a phenomenon which is impossible, like absolute impossible to explain in any classical way.
Agreed.
And he says it has in it the absolute heart of quantum mechanics.
And what's really interesting is he doesn't try to explain why nature behaves this way.
Because nobody truly knows why.
Right, exactly. So the mission here, and what we want you, the listener, to walk away with today, is a deep structural understanding of how it behaves.
Not why, but how.
Exactly. And to do that, we need to walk through a series of thought experiments, step by step.
Ground ourselves in the familiar first, right?
Yeah, because to really grasp the bizarre nature of the atomic world, you have to start with what you know. So imagine a machine gun.
Okay, a machine gun.
But it's a bit of a wobbly machine gun. It's spraying bullets randomly over a wide angle. And right in front of the gun, there's an armor plate with two small holes in it.
Just big enough to let a single bullet through.
Right. We can call them hole 1 and hole 2. And behind that armor plate, you have a backstop.
Like a thick wooden wall.
Yeah, or maybe a sandbox, acting as a movable detector that slides back and forth to count where the bullets actually land.
Okay. And just to keep the physics clean here, let's say these are perfectly indestructible bullets. They don't splinter or shatter when they hit the armor plate.
Which means they arrive in distinct lumps.
Right.
You never sweep that sandbox and find half a bullet. You find 0 bullets, or 1 or 20.
So what we are doing is measuring the probability of a lump arriving at a certain point on the backstop.
Right. So if we cover up hole 2 and just shoot through hole 1 for an hour, we count the bullets and get a nice predictable cluster right behind hole 1.
A probability curve.
Exactly. A curve we'll call P1. It peaks at the center and kind of tapers off at the edges.
And logically, if we cover hole 1 and open hole 2, we get the exact same thing, just shifted over.
Right.
A cluster behind hole 2, which is our probability curve P2.
So the critical baseline here is what happens when we open both holes at the same time.
The total probability of a bullet landing anywhere on that backstop is mathematically simple. It is literally just the sum of the two curves.
T12 equals P1 plus P2.
The probabilities simply add up. I mean, if a certain spot on the backstop gets 10 bullets an hour from hole 1 and 10 from hole 2, opening both doors means it gets 20 bullets an hour.
Makes sense. The physical world makes sense.
Yeah.
We are safe and sound in classical physics.
For now, yeah, that is our classical particle baseline. But physics gives us a second classical baseline, which is waves.
Okay, let's unpack this one.
Imagine replacing the machine gun with a shallow trough of water.
Okay, so we've got a pool of water now.
Right. And a motor is jiggling a wave source in the water, sending these circular ripples toward that exact same wall with the two holes.
And behind the wall.
Instead of a sandbox, we have an array of detectors measuring the intensity of the water waves.
Which is the energy, right?
Exactly. The energy, which is mathematically proportional to the amplitude or the height of the wave squared.
Okay, so if bullets are like throwing tennis balls through a fence, water waves are like overlapping ripples in a pond.
That's a great way to picture it. And the fundamental difference here is that waves don't arrive in these indivisible lumps. Water is continuous.
Right. You can have a massive swell or just a microscopic ripple.
And because it's continuous, when you open both holes, the waves from hole 1 and the waves from hole 2 spread out, they overlap and they actually interfere with each other.
Which gives us an interference pattern.
Exactly. When the peak of a wave from hole 1 arrives at the same point as the peak from hole 2, they amplify each other.
That's constructive interference.
Right. But if a peak from hole 1 hits a trough, a valley from hole 2, They cancel each other out perfectly. You just get dead flat water.
Destructive interference.
Yes. And mathematically, this is where the classical models totally diverge.
Because for waves, the combined intensity when both holes are open is not just the sum of the individual intensities.
It is not I1 plus I2. Not at all.
The equation requires a completely new mathematical component, right? An interference term.
Which is exactly why the physical result looks so drastically different. When you map out the wave intensity on the backstop, you don't get a smooth curve like with the bullets.
No, you get a dramatic oscillation. Huge peaks of intense waving, separated by these deep valleys of total calm.
So we have our two distinct frameworks. We have particles, which are lumpy and don't interfere.
Probabilities just add up.
Right. And we have waves, which are continuous and do interfere.
Which finally brings us to the atomic scale. This forces us to look at the star of the show, the electron.
Ah, the electron.
It has mass, it has an electrical charge.
Yeah.
Classically, it should behave exactly like the machine gun bullet.
So to test that, we swap out the machine gun for a heated tungsten wire.
Okay.
This wire emits a stream of electrons toward our plate with the two holes, and our detector is now a highly sensitive electron multiplier.
Which is essentially a Geiger counter connected to a loudspeaker.
Exactly. And when we run the machine, the very first thing we notice is the sound.
It clicks. Sharp, distinct clicks. Like click, 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 click.
There are absolutely no half clicks, no muffled partial signals at all. You can turn the tungsten wire's heat down so low that electrons are emitted like once every few seconds.
And every single click is completely identical.
Which means electrons are definitively lumpy. They arrive at the detector one by one, fully intact, exactly like our indestructible machine gun bullets.
So our intuition immediately jumps to the logical conclusion, right? If they arrive in discrete lumps like bullets, they must travel like bullets.
You'd think so. But here's where it gets really interesting. When we open both holes and map out the probability of where these individual electron lumps actually land over time...
The curve doesn't look like the bullets at all.
No, it doesn't.
It looks exactly like the rippling interference pattern of the water waves.
It's wild.
P12 does not equal P1 plus P2. You get these dramatic peaks where thousands of electrons land, and right next to them, valleys where almost zero electrons land.
It is entirely counterintuitive. I mean, they are arriving as indivisible particles, as individual lumps, but distributing themselves as if they were a continuous wave that somehow passed through both holes simultaneously.
Okay, if I'm looking at this data, my brain is just desperately trying to find a mechanical workaround to save classical physics.
Naturally.
Because this feels like a paradox. So wait, are we absolutely sure the electrons aren't just splitting in half at the plate, going through both holes, and then magically recombining right before they hit the detector?
It's a fair question, but the physics completely rules it out. We established that the clicks from the detector never change in intensity.
Right, no half clicks.
If you move the detector right up to the holes, you catch whole electrons at hole 1 or whole electrons at hole 2. You never, ever measure a fraction of a charge anywhere in the system. They remain whole.
Fine, fine. What if they were taking, like, wildly complicated paths?
What do you mean?
Like an electron goes through hole 1, loops back around, bumps into an electron coming out of hole 2, and they ricochet off each other to form this wavy pattern on the backstop, like a massive quantum traffic jam.
Feynman actually dismantles that exact idea using the data itself.
Yeah.
Look closely at the valleys in the interference pattern.
Okay, the spots on the backstop where almost zero electrons land when both holes are open.
Right. If you close hole 2, suddenly more electrons start landing in that spot.
Oh, right, because closing a hole shouldn't magically summon more particles to a specific area if they're just bumping into each other.
Exactly.
If I close the door in a busy hallway, I don't increase the foot traffic in the next room.
Yeah.
I decrease it.
Precisely. So the interference pattern requires the possibility of both paths to exist. To predict where these electrons will land, physicists had to adopt a completely new mathematical framework.
Right.
We don't add the probabilities directly. We add what are called probability amplitudes.
Which are often represented by complex numbers.
Yeah. We add the amplitude of path 1 and the amplitude of path 2, and then we square the absolute value of that combined amplitude to get the final probability.
And it's that squaring process that generates the mathematical interference term.
And that math is absolutely identical to the math used for the continuous water waves. Yet, we are talking about singular, indivisible lumps of matter.
This is where any curious scientist says, enough with the math, I want to see it.
Oh, yeah.
If the equation says the electron's probability amplitude goes through both holes,
Yeah.
but the electron itself is a single lump, Let's catch it in the act. We need an observation.
Which leads perfectly to the next logical step, the watching experiment.
Okay, how do we watch an electron?
Well, since electrons have a negative electric charge, they scatter light. So if we place a strong light source directly between hole 1 and hole 2, we can illuminate the space just behind the wall.
The logic is airtight. The electron goes through a hole, it scatters the light, and we see a tiny flash. Every time we hear a click at the detector on the backstop, we just look to see where the flash happened. Did it happen at hole 1, hole 2, or both?
So we turn the light on, the electrons are fired, we hear a click, and we see a flash at hole 1.
Okay.
Another click, a flash at hole 2.
Wait, do we ever see a flash at both holes simultaneously?
Never. The electron definitively picks a single door. It goes through hole 1 or hole 2.
So we solved it. The electron acts like a bullet. It takes a single path.
But then we look at the backstop.
Oh, no.
We map out where the electrons are actually landing while the light is turned on. The interference pattern, the dramatic, wavy peaks and valleys has completely vanished.
The distribution curve flattens back out into the simple, boring machine gun bullet curve.
Exactly. P12 is suddenly equal to P1 plus P2 again.
So the moment we actually look to see which path it takes, the wave behavior is destroyed.
Completely destroyed.
Okay, obviously we are just being too clumsy here. Light isn't just a passive observer.
Yeah.
It exerts physical momentum.
It does, yes.
When that light scatters off the electron to create the flash, it's physically kicking the electron. We're bumping these delicate little particles off course and smearing out the precision required to build the wave pattern.
That's a very logical assumption.
So the solution is simple. We outsmart the experiment. Let's just turn down the brightness of the light. Make it a tiny, dim, barely there glow. A gentle whisper of a light so we don't disturb the electron's path.
It's the most intuitive next step. Everyone thinks of this, but it fails completely.
Why?
Because it bumps into another mind-bending truth about reality. Light is also lumpy.
Photons.
Right. Light doesn't flow as a perfectly smooth, infinitely divisible stream of energy. It travels in these discrete packets, photons. When you turn down the brightness of the light bulb, you aren't making the individual photons weaker.
Oh, I see. You're just spitting out fewer of them.
Exactly.
It's like switching from a fire hose of tennis balls to just tossing one tennis ball every few seconds.
Precisely. The momentum of each individual photon remains exactly the same. So what happens in our dim light experiment? Because there are fewer photons flying around the holes, a lot of the time, an electron passes through without hitting a photon at all.
So we hear the click at the backstop, but we don't see a flash. The electron kind of snuck by in the dark.
Right. So now we have two distinct sets of data. We have the electrons we successfully caught with a flash of light, and we have the electrons that pass through unseen.
Okay, let me guess. The ones we saw act like bullets. No interference pattern.
And the ones that snuck by unseen?
The interference pattern is perfectly intact.
It's perfectly intact.
That is staggering. I mean, it means this isn't just a mechanical flaw in our setup. It's almost a bifurcation of reality.
Yes.
The particles we have information about act one way, and the identical particles we lack information about act another way.
Observation itself, the mere extraction of path information from the system, fundamentally alters the physical behavior of the universe.
All right, I'm not giving up on classical physics that easily.
I didn't think you would.
If dimming the light just reduces the number of photons, let's change the type of photons.
Okay, how so?
The energy of a photon is tied to its color, right? Its frequency. Blue light has short, highly energetic waves. Red light has longer, gentler waves. What if we use infrared? Or, even better, radio waves.
Going for the low energy.
Exactly. We use a wavelength so incredibly long and a frequency so incredibly low that the photon's momentum is barely a whisper. We give the electron the tiniest, gentlest little microscopic nudge. Not enough to knock it off course.
It's a valiant, brilliant attempt, truly. But physics lays a trap for us here regarding how waves resolve images.
The trap.
There is a fundamental limitation. You cannot resolve the precise location of an object if you are using a wave that is significantly larger than the object itself.
Okay, that makes sense. Like if you're trying to find a tiny pebble on the ground, and you're probing the ground by rolling a giant 6-foot inflatable yoga ball across it,
Yes.
the ball might bounce off something, telling you a pebble is generally in that area. But the ball is too wide to tell you exactly where the pebble is.
Exactly. So back to our experiment. As you lower the frequency of the light to make it gentler, the wavelength gets longer. And as the wavelength gets longer, the flash of light you see when it hits the electron gets optically fuzzier.
The resolution drops.
It drops drastically. It becomes this blurry blob. By the time the wavelength is long enough and the momentum is gentle enough that it doesn't disturb the electron's delicate path.
On you guess. The flash is so impossibly wide that it illuminates both hole 1 and hole 2 at the same time.
Bingo. We see a flash, but it's too blurry to tell which hole the electron actually went through.
So we preserve the interference pattern on the backstop, but we completely lost the information about the path.
You can have the interference pattern, or you can know which path the electron took. You can never, ever have both at the same time.
And this brings us face to face with Heisenberg's uncertainty principle.
It really does. It's not just a clumsy observer effect. It's a hard limit on reality.
Wow.
The uncertainty principle basically states that it is fundamentally impossible to design any apparatus using any mechanism to determine which path the electron takes without disturbing the system enough to destroy the interference pattern.
But Feynman, being Feynman, pushes the thought experiment even further in the text. He proposes a setup to try and beat Heisenberg without using light at all.
Oh, the roller wall, figure 37-6.
Right, we completely get rid of the photons. Instead, we look at the armor plate with the 2 holes, we detach it from the wall, and we mount it on tiny, frictionless rollers so it can slide freely up and down.
Because we want to measure the physical recoil of the wall itself.
Exactly. Because physics dictates conservation of momentum. If an electron comes from the tungsten wire, goes through the top hole, and then angles sharply downward to hit a detector near the bottom of our backstop, it had to push off something.
It must have given the roller wall a tiny upward kick.
Conversely, if it goes through the bottom hole and angles up, it gives the wall a downward kick.
So we just measure the momentum of the wall before the electron arrives and then measure it again after. We look at the change in momentum to deduce the path.
No light, no photons, no direct interference with the electron. It sounds totally foolproof. We cheat the system.
It does sound foolproof, but Heisenberg's principle applies to all matter. Not just tiny electrons, but the massive macroscopic roller wall as well.
Okay.
To measure the microscopic change in the wall's momentum caused by a single electron, what is the prerequisite?
Well, we have to know the wall's initial momentum with absolute perfect precision. We need to know that the wall is perfectly stationary down to the quantum level.
And if you require the uncertainty in the wall's momentum to be virtually zero, Heisenberg dictates that the uncertainty in the wall's position must approach infinity.
Okay, wait, explain the mechanism there, because that's the part that breaks people's brains. Why does knowing how fast it's going make its location disappear?
Well, to have a perfectly defined momentum in quantum mechanics, the object, even a macroscopic wall, must be described mathematically as a pure wave with a single unvarying frequency.
Okay.
But a pure single-frequency wave is a continuous sine wave that oscillates perfectly forever. It has no beginning and no end.
Meaning it has no single defined location in space. It is literally smeared out across the universe.
Exactly. To build a wave packet that has a localized, precise position, something that actually looks like a solid wall in a specific spot, you have to add together dozens of different waves with different frequencies.
But the moment you mix different frequencies together, you are mixing different momentums.
Right, so if we demand to know the wall's momentum perfectly, so we can measure that tiny recoil, its position becomes inherently uncertain. The wall is essentially smeared out and vibrating randomly on its rollers.
And if the wall is vibrating randomly, the 2 holes are vibrating randomly.
Which means the distance from the holes to the backstop is constantly changing while the electrons are flying through.
Oh, which means the center of your delicate interference pattern is shifting randomly up and down with every single electron.
And when you add up millions of those randomly shifted peaks and valleys on the backstop,
They average out. The peaks fill in the valleys. It smears into one big, smooth lump.
P12 equals P1 plus P2.
We destroyed the interference again. We just can't win. Nature is structurally designed to prevent us from knowing the path and keeping the wave.
It fundamentally refuses.
Okay, but this brings up a massive lingering question for me.
What's that?
If quantum mechanics says everything is governed by probability amplitudes and wave mechanics, even large objects like our roller wall, why didn't the machine gun bullets show an interference pattern in our very first experiment? Why don't billiard balls or tennis balls act wavy?
It's an essential question, and Feynman actually addresses it directly with figure 37-5 in the text, and the short answer is, they do.
Wait, really? Machine gun bullets have an interference pattern.
They absolutely do.
But the wavelength of an object is inversely proportional to its momentum, which is tied to its mass.
Exactly.
An electron has incredibly tiny mass, so its quantum wiggles are wide enough for us to spread out and measure with a Geiger counter.
And a massive lead machine gun bullet.
A bullet has a wavelength that is infinitesimally small. The peaks and valleys of its interference pattern are crammed so impossibly tight together that no physical detector in the universe is precise enough to measure the difference between them.
Because even, like, a single grain of sand in our detector is billions of times wider than the quantum wiggles of a bullet. It straddles millions of peaks and valleys simultaneously.
Exactly. So what your macroscopic detector measures is just the classical average. It averages out the quantum oscillations, and it looks to us like a smooth, predictable, purely classical curve.
But underneath that average, at the deepest level of reality, it's all quantum.
It's all waving.
That is just phenomenal. So we've run the absolute gauntlet here. We tried classical logic, we tried lights, we tried frictionless rollers, and nature outsmarted us at every turn.
Every single turn.
So what is the ultimate takeaway from Chapter 37? What is the philosophical fallout of this deep dive into the double-slit experiment?
The fallout is what physicists call the ultimate retrenchment of science.
The retrenchment.
Yeah. For centuries, since Isaac Newton, the grand goal of physics was determinism. The belief that the universe was a giant clockwork mechanism. If you knew the precise starting position and momentum of every gear, every particle, you could perfectly calculate the future.
But quantum mechanics forces us to abandon that dream completely.
Science has officially given up on predicting exactly what will happen to a single electron in a given circumstance.
We only have the odds. We only have the probability amplitude.
That's it. And people try desperately to hold on to comfort. They say, well, maybe our math is just incomplete. Maybe the electron has some hidden internal machinery.
A tiny microscopic steering wheel inside that predetermines its path.
Right. But the math, the experiments, and the logic of the interference pattern prove that is impossible.
Because if it had internal machinery, if the electron left the tungsten wire having already decided to go through hole 1, then closing hole 2 later shouldn't alter its behavior.
But it does.
Yeah.
There is no hidden mechanism. This is simply how nature is. It is inherently, unavoidably probabilistic.
Wow. We've officially traded our precise, predictable billiard balls for the murky, rippling waters of probability.
We have.
But before we leave you today, I want to offer you one final provocative thought to mull over, building on the profound weirdness of the watching experiment.
The observation problem.
Yes. We've established that watching the electron with a photon of light, or physically measuring a wall's recoil, extracts information and forces the electron to pick a path. It collapses the wave.
Right.
But what exactly counts as an observer? Does it require a conscious human scientist in a lab coat writing notes on a clipboard to collapse the wave?
Or does a stray, mindless speck of dust randomly bumping into the electron in the dark count as a measurement?
It's the ultimate boundary problem. If a tree falls in a completely isolated quantum forest, and absolutely no other particles interact with it to record the event, does it fall in every possible direction at once?
Where does the boundary between the wavy, probabilistic quantum world and our hard, rigid, real, macroscopic world actually lie?
Is there even a boundary at all?
It's a question that has kept the greatest minds in physics awake at night for a century.
And hopefully it gives you something fascinating to ponder today as well, because out there, underneath the clean, mechanical, predictable lines of our everyday lives, those murky quantum waters are always rippling. Welcome to today's deep dive. So today we are looking at the profound physical connection between the microscopic madness of atoms and the everyday reliable properties of matter that you actually experience.
Right, the things you interact with constantly, like pressure, volume, and temperature.
Exactly. And to do this, we are drawing from some truly legendary source material today. We're diving into Chapter 39 of the Feynman Lectures on Physics.
Yes, specifically the chapter titled The Kinetic Theory of Gases. And alongside the text itself, we have 4 foundational diagrams provided by the source that we'll be breaking down and visualizing for you.
And our mission for this deep dive is pretty clear. We're going to bypass the intimidating complex math that usually surrounds this topic.
Which is a relief, honestly.
Right, because instead we want to use pure physical intuition to understand the mechanics of the universe. We really want to know why things behave the way they do. Now, to get us started, I want you, the listener, to consider a genuinely mind-bending fact from our source.
This one is wild.
It really is. If your ears were just slightly more sensitive, like just a tiny bit more attuned to the environment around you, you wouldn't hear the quiet hum of your room or the gentle breeze outside. You would hear a perpetual, deafening racket.
Yeah, an irregular, terrifying, just boom, boom, boom tattoo right against your eardrums.
It sounds like the absolute definition of a sensory nightmare. But evolution, thankfully, purposefully tuned our hearing just below that threshold so we wouldn't, lose our minds.
Right, but just because you can't hear it doesn't mean it isn't happening. Right now, as you sit there listening to this, billions upon billions of atoms are furiously bombarding your eardrums.
That concept is just wild to me. When I picture this atomic bombardment, I kind of think of standing under a tin roof during a torrential rainstorm. You have all these individual chaotic drops violently hitting the metal. But if that is what the air around us actually is, just billions of tiny, random, violent collisions, why does the air feel like a steady, continuous fluid? Like, why doesn't it feel like a chaotic hailstorm?
Well, answering that requires us to step into the realm of probability and statistics. Now, our source notes right out of the gate, that classical physics, where we treat atoms like tiny little billiard balls bouncing around, is technically an incomplete picture.
Because quantum mechanics is the real boss of the microscopic world.
Exactly. Quantum mechanics is the true boss. However, when you're dealing with billions upon billions of atoms and you're just trying to find their average behavior, classical mechanics gives us a brilliantly accurate approximation for our everyday lives.
So it comes down to the law of large numbers.
Yeah, precisely. The individual raindrop hitting your tin roof is entirely unpredictable, but the overall roar of the storm and the weight of the water on the roof is incredibly steady and predictable.
Okay, so if we're looking at the average behavior, let's look at the first model our source gives us to actually quantify this hailstorm. This is figure 39:1 in our materials. We are asked to imagine a volume of gas, so just a bunch of atoms trapped inside a box.
Right.
And one end of this box is a movable, frictionless piston.
And if you just left that setup alone, and let's assume there's a perfect vacuum on the outside of the piston, you would see the continuous bombardment of those trapped atoms hitting the inside of the piston.
Wow.
Yeah, they are transferring their momentum to it, which would gradually push the piston outward. They're literally hammering it out of the box.
So to keep that piston completely still, you have to actively push back.
Exactly. You have to apply a physical force to the outside of the piston.
So the force I'm applying to hold the piston in place is balancing out the invisible hammers. Does that mean pressure is literally just the measurement of that bouncing force spread out over the surface of the piston?
That is the exact anatomical breakdown of pressure. It's the total force applied divided by the area of the piston. Think about the mechanics of a single bounce. When an atom flies through the box and hits that piston, it goes in with a certain amount of momentum. Then it bounces off and flies back the other way with an equal amount of momentum. Because the atom completely reverses its direction, the total momentum it delivers to the piston is actually double its incoming momentum along that specific axis.
Oh, I see.
So if you tally up the total momentum delivered every single second by all the atoms hitting that wall, you get the total force.
Which means we don't necessarily need to read out the raw equations here to understand what is happening. The pressure pushing against the walls of the box, combined with the volume of the box itself, is directly tied to the internal kinetic energy of all those atoms bouncing around.
Yes, it's a direct relationship, and tying it to everyday experience makes it even more tangible, I think. The text uses a brilliant example regarding your own body. Imagine you have a severe cold, and you ride a fast elevator up to the top of a very tall building.
Oh man, that is a terrible feeling. Your ears get completely blocked and start aching.
It's awful, but the underlying mechanism causing that pain is entirely about this atomic bombardment. Because of the inflammation from your cold, the eustachian tube gets swollen shut.
That's the tiny tube that connects your inner ear to the outside ear through your throat, right?
Yep, that's the one. So as you ride the elevator up, the air density in the elevator cabin drops. There are simply fewer atoms bombarding the outside of your eardrum.
But trapped inside my inner ear, behind the eardrum, I still have the dense hailstorm of atoms that I brought with me from the ground floor.
You do. Those systems fail to equalize because the tube is swollen. So the atoms on the inside of your ear are hitting the eardrum much harder and much more frequently than the atoms on the outside.
Yikes.
The pressure imbalance forces your eardrum to physically bow outward, causing that sharp pain.
It makes perfect sense when you visualize it as billions of tiny hammers. But wait, I want to unpack this a bit and push back on one assumption the source makes here.
Sure, go for it.
We are talking about these atomic collisions being perfectly elastic. Are we really saying that the pressure keeping my car tires inflated is just the combined force of microscopic ping-pong balls hitting the rubber and they bounce off without losing a single drop of energy? Because if I throw a ping-pong ball at a wall, it eventually loses energy and drops to the floor. How is perfect elasticity possible in the real world?
That is a fantastic point of skepticism. If you look at any single physical wall on an individual atomic level, it is not perfectly elastic. When one atom hits the wall of your car tire, it absolutely might lose a little bit of energy, and that tiny transfer of energy makes the wall slightly warmer.
Okay, that tracks.
But the crucial concept we have to introduce here is equilibrium. At the exact same time that one atom loses energy, the wall itself is vibrating with its own thermal energy. It might swing out and smack a completely different atom much harder than it was hit, giving energy back to the gas.
Oh, wow.
So when the system reaches equilibrium, the net energy exchange balances out to zero. On a macroscopic level, the gas appears to lose no energy to the walls at all.
Okay, so if the gas naturally exerts this steady pressure by bouncing off the walls, what happens if I refuse to just hold the piston still? What if I actively force the piston inward and compress the gas?
Yeah.
Am I physically fighting the momentum of those atoms?
You are. And this leads us to the concept of adiabatic compression. Imagine you push that frictionless piston inward, but the container is perfectly insulated. No heat is allowed to leak in or out through the walls. As you physically push that piston inward, you're expending energy. You're doing work.
And that physical effort has to go somewhere, right?
Yeah.
The energy can't just vanish.
It goes directly into the internal energy of the gas. Picture the atoms bouncing toward the piston. If the piston is stationary, they bounce off at the same speed. But if the piston is moving toward them when they hit it, it acts like a tennis racket swinging at a ball.
Oh, I like that analogy.
The atoms bounce off much faster than they came in. You are actively speeding them up, which means the gas gets hotter. For a simple gas where the molecules are just single atoms, like helium, the relationship between the pressure and volume during this compression involves a specific fraction, which is 5/3.
Yeah, I noticed that fraction in the text, and since we promised to explain the why behind the math, where does 5/3 actually come from? It seems like such a random number to dictate how a gas heats up.
It seems random, but it's entirely based on the geometry of our universe. The atoms are flying around in 3 dimensions of space. Up, down, left, right, forward, backward.
Right.
The 3 in the denominator of that fraction directly represents those 3 physical dimensions where the kinetic energy is distributed. Because you are only compressing the gas along one dimension, just pushing the piston in one direction, the math perfectly reflects how that localized energy redistributes across all 3 spatial dimensions.
That is deeply elegant. And speaking of the geometry of the universe, this is the point in the source material where we get a stunning pivot. We go from talking about gas in a box straight out into the cosmos.
Yes. The exact same bouncy ball kinetic theory we're using for pistons and car tires applies to the most extreme, unfathomable environments in the universe.
Like what?
The cores of supermassive stars.
See, I was trying to wrap my head around this. In a star that hot, atoms are stripped apart. It's mostly just a chaotic soup. But the text focuses on the light itself, the photons.
Exactly. In a star that incredibly hot, the radiation is so intense that we can effectively ignore the matter for a moment and treat the photons, the particles of light, exactly like a gas trapped in a box.
Here's where it gets really interesting, though. Photons don't have mass. Are you saying that light actually exerts a physical push, and we can use the exact same logic we use for a bicycle pump to calculate the crushing forces inside the core of a star?
I am. While it's true that photons have no mass, they do possess momentum. It's a fundamental property of light. When a photon hits a boundary or interacts with matter inside the star, it delivers a microscopic physical kick. It exerts what we call radiation pressure. And because there are so many photons in a stellar core, that collective kick is powerful enough to hold up the entire weight of the star against the crushing force of its own gravity. The underlying mechanism is identical to our helium atoms hitting the piston.
So the universe scales up from the mechanics of a party balloon to the core of a star using the same invisible logic. That is incredible. But this brings up a glaring question. We have been throwing the word hotter around. We know that compressing a gas speeds up the atoms and makes it hotter, but what actually is temperature? We talk about it like it's a substance, like heat is a fluid that pours from one object to another.
Right, and overcoming that idea is a massive conceptual hurdle. To figure out what temperature actually is at a microscopic level, we have to look at what happens when two different systems try to agree on a single temperature.
And this brings us to figure 39-2. Imagine that box again, but this time, the movable piston is locked right in the middle. On the left side, you have one type of gas, let's say helium. On the right side, you have a totally different, heavier gas, like neon.
If we just let them sit there, we know from everyday experience that they will eventually reach the same temperature. A hot cup of coffee eventually cools down to match the room. That final condition, when things interact long enough to reach a steady state, is called equilibrium. But the real puzzle is the mechanism.
Right, how do they do it?
Exactly. How do the helium atoms on the left communicate their temperature to the neon atoms on the right if they can't cross the piston?
Oh, it goes back to that invisible chaotic tattoo, the bombardment against the piston itself.
Yes, exactly. The piston is not receiving a perfectly smooth, uniform push from either side. Because the atomic impacts are statistically irregular, the piston jiggles. It vibrates rapidly back and forth in a microscopic dance.
So let's visualize this. Say the left side has just a few helium atoms, but they are incredibly energetic. They are moving at blinding speeds. And the right side has a massive crowd of heavy neon atoms, but they are sluggish and cold.
When one of those lightning-fast helium atoms on the left smacks the piston, it drives the piston hard to the right. The piston moves quickly, and in doing so, it acts exactly like a baseball bat swinging into the slow-moving neon atoms on the right. It smacks them and speeds them up.
It physically transfers the kinetic energy across the boundary.
And that jiggling continues infinitely. It transfers energy from the fast side to the slow side, back and forth, until a very specific balance is reached. The transfer only levels out when the rate of energy going from left to right perfectly equals the rate of energy going from right to left.
So what does this all mean for you, the listener? If I am understanding this analogy, temperature isn't actually a thing or a substance. It's more like a chaotic dance floor speed limit.
The speed limit, yeah.
And everything in the room eventually agrees on the same speed limit by constantly elbowing each other via this jiggling piston. It's like a mosh pit. You have highly energetic people bouncing off the walls, and they eventually bump into the tired, slow-moving people. The collisions continue until the entire crowd is moving at the exact same moderate intensity.
That is a brilliant way to picture it. What's fascinating here is that the specific condition they reach at equilibrium, that moderate intensity of the mosh pit, is that both sides have the exact same average kinetic energy. That is all temperature is. It's a direct measurement of average kinetic energy.
Which is a combination of mass and speed. So if the light helium atoms and the heavy neon atoms have the exact same average kinetic energy, they can't be moving at the same speed.
They absolutely are not. To maintain the same energy ledger, the heavy neon atoms will always be moving significantly slower on average than the light helium atoms. A heavy object moving slowly packs the same punch as a light object moving very fast.
To really drive this home, the source provides two more diagrams that prove this energy distribution. Figure 39-3 asks us to picture a direct collision between a heavy atom and a light atom. When we look at the center of mass system, which just means observing the collision from a perspective that moves along with their combined momentum, we see something fascinating.
Think of it like a semi-truck colliding with a small bicycle. It is not a clean, predictable bounce. The math of these asymmetrical collisions shows that they essentially spray the particles randomly in all directions.
This is total chaos.
Right. Any initial organization or unequal energy distribution is completely scrambled by these collisions. The energy gets perfectly equally distributed among all the particles over time.
And figure 39-4 provides another elegant thought experiment. Imagine a container separated by a semi-permeable membrane, a wall with holes so tiny that only the small atoms can leak through, while the heavy atoms are trapped on one side.
Even in this scenario, where the small atoms can wander freely back and forth, the physics demand that the mixed gas on one side and the pure gas on the other must reach the exact same average kinetic energy per molecule. The microscopic interactions always force the system into this perfect statistical balance.
Knowing this finally allows us to construct the grand mathematical rules of chemistry and physics. The rules you might have memorized and probably quickly forgot in high school chemistry class. Because once we establish that temperature is literally just the average kinetic energy of molecules, we can scale it to understand any gas.
To do that, scientists use the Kelvin scale and a specific universal exchange rate called Boltzmann's constant. You don't need to worry about the letters or the raw numbers. Just know that Boltzmann's constant is the bridge that converts the microscopic energy of a single atom into the macroscopic temperature that you can read on a thermometer.
And if you take that concept and plug it all the way back into our very first idea about the pressure on the piston, you arrive at the ideal gas law. It states that the pressure multiplied by the volume is directly equal to the total number of molecules multiplied by that exchange rate multiplied by the temperature.
Which reveals an absolute miracle of nature, often called Avogadro's law. The math tells us something staggering. If you have equal volumes of any gas at the same pressure and the same temperature, they must contain the exact same number of molecules.
Okay, I am going to challenge that because it feels like it violates common sense.
Yeah.
You're telling me that a box filled with heavy, massive bowling balls representing a heavy gas, and an identical box filled with tiny, fast ping pong balls representing a light gas will take up the exact same volume if their pressure and temperature are identical.
Yes.
But the bowling balls are huge. How do they not take up more space?
It feels incredibly counterintuitive, I know, but reality obeys this law perfectly. Remember our definition of equal temperature. They must have the same average kinetic energy. The heavy atoms, your bowling balls, are moving much, much slower. Because they are slow, they hit the walls of the box far less frequently. But because they're heavy, when they do finally hit, they hit with massive force.
Okay, I see where this is going.
The ping pong balls are very light. They hit the walls with almost no force at all, but because they are moving incredibly fast, they hit the walls constantly. 1 billion tiny taps versus 100 heavy thuds. When you average out the total force per unit of area, the ledger balances perfectly.
The pressure is identical, so the volume remains identical, regardless of the size of the individual atoms.
That is stunning. And because the total number of atoms in any normal volume of gas is a hilariously large, unmanageable number, chemists decided to package them into convenient units called moles. It is just a massive grouping of molecules to make the math easier for human brains, giving us the classic high school formula where pressure and volume relate to the number of moles and the temperature.
Exactly.
But wait, everything we've talked about so far involves monatomic gases, single atoms acting like tiny billiard balls. What about complex molecules, like oxygen, which is a diatomic molecule? It's 2 oxygen atoms bonded together, shaped like a tiny dumbbell. Do these beautiful rules break down when the shapes get complicated?
The rules do not break down, but complex molecules do hide some fascinating secrets. The law states that the entire object, the whole dumbbell flying through space, still has the exact same center of mass kinetic energy tied to its temperature. That translational motion, just moving from point A to point B, dictates the pressure we measure.
But a dumbbell is different than a billiard ball. A dumbbell can spin through the air. It can tumble end over end. The 2 atoms can even vibrate back and forth on their chemical bond like they are connected by a spring.
Exactly. In physics, we call these extra movements degrees of freedom. Think of them as hidden energy lockers inside the molecule. Those internal vibrations and tumbling rotations take up energy, too.
How does that change how the gas behaves when we heat it up?
Well, it means you have to work harder to raise its temperature. If you pump heat into a simple gas like helium, all the energy goes directly into making the atoms fly across the room faster so the temperature spikes quickly. But if you pump heat into a diatomic gas like oxygen, some of that energy gets distracted.
Distracted how?
It goes into making the dumbbells spin faster or vibrate harder rather than just moving them across the room. You have to supply significantly more energy to achieve the same rise in temperature. But the core truth of the physical laws remains intact.
That brings us to the end of a truly incredible journey through our source material today. We started at the localized microscopic scale, an imperceptible, chaotic bombardment of individual atoms drumming violently against your own eardrum.
We discovered how the mathematical averages of those countless collisions create the steady macroscopic force we call pressure. We use the jiggling of a frictionless piston to understand that temperature is nothing more than the physical equalization of kinetic energy, the balancing of the mosh pit.
And we finally saw how all of this invisible, furious chaos perfectly averages out into the elegant, ideal gas law. A singular law that governs everything from the expanding helium balloons at a birthday party to the crushing, photon-filled gravitational cores of distant stars.
The knowledge buried in the source material is so valuable because it completely reframes reality. The next time you check the tire pressure on your car, or watch a pot of water boil on the stove, or simply take a deep breath of the air around you, remember the furious, invisible machinery at work. You are experiencing the reliable result of trillions upon trillions of tiny, violent collisions, all obeying beautiful, unyielding mathematical rules.
Which leaves you with something pretty profound to ponder as you go about your day. If the solid, reliable macro world we interact with every single day, our concepts of temperature, pressure, and volume, is actually just a statistical illusion created by the average behavior of microscopic chaos, what other solid facts of our human experience might just be an illusion of scale? If we can just tune our senses a little differently and look just a little deeper into the fabric of reality, what other deafening rackets are we currently missing? Imagine for a second that you're just, studying the air around you.
Okay.
You are tracking the chaotic bouncing of microscopic air molecules, and you're completely confident that you have the mechanical rules of the universe totally figured out.
Right, because everything seems smooth, continuous, and perfectly logical.
Exactly. And then suddenly, your classical math just drives you straight into a brick wall.
A very hard brick wall.
Yeah, a wall so unexplainable, so frustrating, that it actually forces the invention of an entirely new branch of physics. Like, quantum mechanics had to be born just to save reality from falling apart.
It really is one of the most dramatic plot twists in the entire history of science. I mean, you start with the simple mechanics of bouncing balls, and you end up tearing down the entire 19th century understanding of physics.
And that is exactly the journey we are taking you on today. In this deep dive, we are pulling directly from the legendary Feynman lectures on physics.
Chapter 40, to be specific.
Yes, Chapter 40. We are exploring the original charts, the diagrams, the theories, and we're translating them into the physical reality you experience every single day. Your mission today is to understand the grand principles of statistical mechanics.
Which sounds intimidating, but it's really just seeing how the random, unpredictable motion of a billion tiny parts dictates the completely predictable behavior of the whole.
Right. And, perhaps more importantly, we will see what happens when those classical rules spectacularly fail.
It's a beautiful progression, really. We're going to look at how molecules behave under gravity, how they interact with each other, how fast they move, and then, well, the ultimate test. What happens when we try to heat them up?
So whether you are just brushing up on your physics or you're insanely curious about the hidden machinery of the universe, you are about to see the empty space around you in a completely different light. Okay, let's unpack this.
Let's do it.
To understand how molecules behave, I think we have to start with the most ever-present force in our everyday lives, gravity.
Yeah, we tend to think of gas as weightless, but it is absolutely not. Every single molecule in the air has mass.
And gravity is pulling it down.
Exactly. So if you picture a tall, invisible column of gas stretching from the ground straight up into the sky, the pressure at the very bottom of that column has to be incredibly strong.
Because it's supporting the weight of all the gas stacked up above it.
Right.
I always picture this like a giant human pyramid of cheerleaders.
Mm-mm.
The people at the very bottom are bearing the most weight. Because they have the entire structure pressing down on their shoulders, they're packed together the tightest.
That's a great way to visualize it.
And as you go higher up the pyramid, there's less weight to support, so the pressure decreases. Translated into physics, the math shows us this massive exponential battle. The density of the gas drops off exponentially as you go up.
Because it's basically a tug of war, gravity is pulling the molecules down, while the ambient heat, the thermal energy that keeps the molecules buzzing, is pushing them outward.
It's a perfect physical balancing act.
It really is. The gravitational potential energy is trying to compress everything into a dense layer at the bottom, and the thermal energy is just trying to scatter everything evenly across the sky. And because it's an exponential relationship, I mean, even a small change in height or temperature creates a massive shift in how the gas is distributed.
But wait, I have to push back on this a little bit.
Sure.
If this is just a battle between heat and gravity relies on mass, heavier molecules should drop off much faster than light ones, right?
Yes, theoretically.
So if oxygen is heavier than nitrogen, why aren't we suffocating in a pure, dense swamp of heavy oxygen right down here at sea level? Like, shouldn't the heavy stuff just pool at our feet?
Well, the reason you aren't wading through knee-high oxygen right now is that our actual atmosphere is incredibly chaotic. We have winds, constant thermal currents, weather patterns just violently mixing everything up.
Oh, so it's not a closed system.
Right, our planet is not in a state of perfect, undisturbed thermal equilibrium, but if you could somehow create a perfectly still atmosphere inside a giant sealed tube,
The heavy gases actually would sink.
they absolutely would. In a perfectly still environment, lighter materials dominate at great heights. Hydrogen, for example, which is incredibly light, easily survives at altitudes where the heavier oxygen has essentially dropped to zero. What's fascinating here is that for this exponential distribution to remain stable, the temperature must perfectly equalize at all heights.
Wait, why couldn't it be colder at the top? High altitudes are usually freezing.
Think about the physical mechanics of what would happen if the temperatures were different in a perfect equilibrium. Imagine placing a solid metal rod inside that tall column of gas.
Okay, a metal rod.
The bottom of the rod touches a warm pocket of gas at the ground, and the top of the rod reaches up into a cold pocket at the top. The molecules at the bottom are hot, meaning they're moving fast.
Right, bouncing around.
Yeah, they would crash into the bottom of the rod, transferring their high thermal energy into the metal. The rod would begin to vibrate, carrying that heat all the way up to the top.
Where it would shake and heat up the sluggish molecules in the cold pocket.
Ex-
So you would be transferring energy continuously from the bottom to the top without doing any actual work.
Which means you would have created a perpetual motion machine. And the fundamental laws of thermodynamics tell us that is strictly impossible in a state of equilibrium.
Oh, wow.
Yeah, therefore, the temperature must ultimately become identical everywhere in that closed system. Otherwise, energy would just keep flowing forever.
Okay, so gravity handles the macro scale, squishing the entire atmosphere down toward the Earth. But if you zoom in, gravity isn't the only thing dictating where these molecules sit. They aren't just reacting to the planet, they're reacting to each other.
Yes, this is where we introduce Boltzmann's law.
Right.
In a real gas or liquid, molecules are constantly pulling and pushing on their neighbors. If you track the potential energy between two molecules based on how far apart they are, you find a very specific curve.
How so?
Well, at a distance, molecules actually attract each other. As they drift closer, their potential energy decreases. But if they get too close, their electron clouds overlap.
And then what happens?
The energy spikes sharply upward, and they repel each other violently.
I love thinking about this like a crowded dance floor. You know, everyone on the floor has a preferred personal space.
Right, exactly.
It's that perfect distance where you aren't standing completely alone in a corner, but you also aren't getting elbowed in the ribs by the person next to you.
That sweet spot of comfort is the potential energy minimum.
Yeah. And the temperature of the room is the music.
Oh, that's a perfect analogy.
Right. If the temperature is low, the music on the dance floor is slow and calm. People gently cluster together right at that preferred personal space distance. But if the temperature is high, if the music is crazy, energetic, and loud, people are bouncing all over the place.
Yeah, that high thermal energy bumps people out of their preferred spots, and the entire crowd just spreads out into a chaotic mess.
Exactly.
And Boltzmann's law turns that dance floor into an exact mathematical probability. It shows that the likelihood of finding molecules clustering together in any specific arrangement drops exponentially based on a simple ratio.
Which is?
Their potential energy divided by their thermal energy. If the thermal energy is huge compared to the potential energy, the molecules are spread out, flying past each other almost completely independent.
But as the temperature drops, the thermal energy shrinks.
Yes. And suddenly, the probability of them locking together at that minimum energy distance skyrockets. If we connect this to the bigger picture, this single relationship is the master key for understanding why matter changes state.
It completely explains the mechanics, like why heating a liquid gives the molecules enough chaotic energy to break their mutual attraction and evaporate into a gas.
Exactly, and why cooling it down robs them of that energy, forcing them to clump together into a solid.
Right.
It is the ultimate many-body problem in physics. Writing down Boltzmann's law conceptually is elegant and straightforward.
But solving it.
Oh, actually solving it to predict the exact behavior of a gas. That is monstrously complex. You aren't just tracking the personal space of two people on a dance floor, you are calculating the personal space of 1 billion molecules, all shifting, attracting, and repelling each other simultaneously.
Okay, so now that we have a grasp on the probability of where the molecules are,
Yeah.
we really need to figure out the mechanics of how fast they're moving.
Let's return to our tall, invisible column of gas.
Sounds good.
We already established there are fewer molecules at the high altitude than at the low altitude. The molecules at the bottom are buzzing around in every possible direction.
Right.
For a molecule at the bottom to travel to the top, it needs a massive amount of upward velocity just to climb the gravitational hill.
Here's where it gets really interesting. This entire system functions exactly like a grueling obstacle course with a massive wall at the end.
I like where this is going.
You have a huge crowd of runners at the starting line. They all have different fitness levels. They're running at different speeds. When they hit the wall, only the absolute fastest, most energetic runners have enough momentum to vault over it.
Everyone else runs out of steam halfway up and slides back down.
Exactly. So by pure logic, you're going to find far fewer people on the other side of the wall.
And classical physics provides the exact fraction of molecules that have enough kinetic energy to make that climb. Just like the atmospheric pressure, the distribution of molecular speeds drops off exponentially.
So as you demand higher and higher speeds, the number of molecules capable of reaching those speeds just plummets.
Precisely.
But wait, I have to push back on the physics text here.
Uh-oh.
Well, to calculate this beautiful exponential curve, we're assuming these molecules are just flying straight up the wall. But we know they are constantly slamming into each other, millions of times a second.
Right, they are.
So if a superfast molecule is sprinting up the wall, and it gets sideswiped by a slow, sluggish molecule, it loses its momentum. Doesn't that constant crashing completely ruin this perfect mathematical distribution?
It absolutely feels like it should, doesn't it? But the reality of those collisions is what makes statistical mechanics so incredibly robust. When two molecules collide, they do not destroy energy. They just swap it.
Oh, I see.
Yeah, if a fast molecule hits a slow molecule, the fast one slows down, but the slow one speeds up by the exact same amount. The kinetic energy is just, well, wearing a different jersey.
So the overall pool of speeds across the entire gas remains exactly the same.
Yes. The total distribution remains mathematically identical at every single height in the gas. To visualize why collisions don't ruin the curve, physicists use this classic thought experiment. Imagine a sealed pipe full of gas, and you drill a microscopic hole in the side.
Okay.
A hole so unfathomably tiny that as molecules leak out of it, they almost never collide with each other on the way through.
A perfect interference-free leak.
Exactly. When you measure the particles leaking out of that tiny hole, their speeds perfectly demonstrate the exponential distribution of kinetic energy. The fraction of particles exiting the pipe with a velocity greater than a certain amount perfectly traces the mathematical curve predicted by the classical equations.
Okay, so up to this point, the 19th century mechanics seem flawless. I mean, we've got exponential atmospheres, Boltzmann's dance floor, velocity filters. It all clicks together perfectly on paper to explain the macro world.
It does.
But physics isn't just about elegant thought experiments. It requires rigorous experimental proof.
Which brings us to the specific heat disaster.
The disaster.
Yes. To verify that this entire classical theory of gases was actually true, scientists needed to measure a property called specific heat. Put simply, specific heat is the exact amount of energy required to raise the temperature of a gas by a certain amount.
So what does this all mean for our classical rules? Like, how do you actually test that in a lab?
Well, you take a sample of gas, compress it, and meticulously measure how its pressure and volume change in relation to each other. This gives you a very specific ratio.
Okay.
According to the classical mechanics we just outlined, the internal energy of a gas is directly tied to the physical ways its molecules can move. We call these degrees of freedom.
Degrees of freedom.
Right. For a very simple monatomic gas, a gas where the molecules are just individual, single atoms bouncing around like helium or argon, an atom can only really move in three directions, up and down, left and right, or forward and backward.
Three directions, meaning three shares of the thermal energy.
Exactly. When you plug those three shares into the classical formulas, the math predicts that the specific heat ratio for a monatomic gas should be roughly 1.66.
And what happened in the lab?
When scientists ran the physical experiments on helium and argon, the results came back at 1.66 and 1.668.
Wow, so a spectacular match.
Yes, the classical theory was working flawlessly.
But then they decided to test diatomic gases. You know, gases like oxygen and hydrogen, where the molecule isn't a single atom, but two atoms chemically bound together.
Right. In classical mechanics, you can picture a diatomic molecule like a tiny dumbbell or two heavy metal balls connected by a flexible spring.
And because it's shaped like a dumbbell, it'd have completely new ways to move. I mean, it can still travel in the three straight directions, but now it can also tumble and rotate through space.
Exactly.
And because that connection is a spring, the two atoms can vibrate, bouncing closer and farther apart.
And here's the kicker. Every single one of those new motions, the translating, the rotating, the vibrating, demands its own share of the ambient thermal energy.
Okay.
When physicists added up all those required shares, the classical math gave a very firm prediction. The specific heat ratio for a diatomic gas must be roughly 1.28.
But then they ran the actual experiment, and the real-world ratio for hydrogen was 1.40.
Yep.
For oxygen, it was almost exactly the same. They were completely off from the predicted 1.28.
It was a massive, unignorable discrepancy. The physical reality of the universe was suddenly refusing to obey the math.
It's like engineering a perfectly flawless car engine on paper. You have calculated the friction of every gear, the combustion of every drop of fuel. But when you physically build the engine and turn the key, it revs completely differently depending on the weather outside.
It defies all logic.
But physicists are stubborn. They tried to tweak the engine. Like, what if they assumed that the connection between the two atoms wasn't a flexible sprung at all? What if it was a completely rigid rod that physically couldn't vibrate?
It was a desperate mathematical fix. If you assume the connection is infinitely rigid and just strip away the shares of energy dedicated to vibration, the classical math suddenly predicts a ratio of 1.40.
Which neatly matches the room temperature experiments for hydrogen and oxygen. So it sounds like they solved it. Just assume the atoms are on a stiff rod.
The problem is, you can't just delete the vibration because it is inconvenient. Classical mechanics strictly dictates that even an infinitely stiff spring must still contain vibrational energy relative to the heat of the room.
Oh, I see.
But the crisis gets much worse than that. When physicists measured the ratio for hydrogen at drastically different temperatures, it wasn't a flat line at 1.40.
It wasn't.
No, it wildly fluctuated. At negative 185 degrees Celsius, the ratio spiked up to 1.6. At an incredibly hot 2,000 degrees, it plummeted down to 1.3.
So the fundamental behavior of the gas was physically transforming based entirely on how hot the room was.
Exactly. And this raises an important question. What about the internal structure of the atoms themselves?
What do you mean?
Well, by the late 19th century, scientists knew there were electrons orbiting inside every atom. Classically, those electrons are moving mass. They should be absorbing kinetic energy just like the tumbling dumbbell.
Yeah.
If you factor the energy of the electrons into the classical equations, the predicted ratio drops even smaller, pushing the math even further away from reality. The classical model wasn't just slightly inaccurate, it was fundamentally broken.
That realization must have been terrifying for the scientific community. I mean, the equations that James Clerk Maxwell proved in the mid-1800s, the elegant theories that completely defined thermodynamics, they were airtight on paper. But they couldn't explain why certain molecular motions, like vibration, seemed to mysteriously freeze out and disappear at low temperatures.
Yeah, tweaking the old math wasn't going to work. We needed a completely new set of rules.
We needed a quantum rescue.
Exactly. The resolution to this entire specific heat crisis couldn't be found in the continuous, smooth mechanics of the 19th century. It required an entirely new paradigm, quantum mechanics.
And the core of that quantum resolution completely shatters our everyday intuition. We think of energy as a smooth, continuous ramp. You can push a little harder or a little softer, but in reality, energy is a discrete staircase.
That's right. For a vibrating molecule, the energy levels are spaced out by very specific, rigid amounts. In classical physics, you can give a molecule any tiny microscopic fraction of energy you want, and it will vibrate just a tiny bit.
But in quantum physics,
energy only comes in specific chunks. You have to give the molecule an exact minimum chunk of energy, or it will refuse to accept it entirely.
I love thinking about this like an incredibly stubborn vending machine. Imagine a vending machine that only accepts crisp $1 bills.
Okay, a dollar bill only machine.
The coin slot is jammed. It will not take pennies, nickels, or dimes. Now imagine the ambient thermal heat in a cold room is just a massive pile of pennies.
Right.
The hydrogen molecule wants to vibrate. It wants to buy that snack from the vending machine. But because it only has pennies, and the first step of vibration costs a full indivisible dollar, it literally cannot buy the vibration.
And that lack of currency is what completely baffled the 19th century physicists. The molecule is entirely locked in its lowest possible energy state, its ground state.
So because it cannot vibrate, it absorbs absolutely none of the ambient heat for vibration.
Exactly. It contributes exactly 0 to the specific heat of the gas.
Which perfectly explains the freezing out effect. At low temperatures, the ambient thermal heat is just pennies. The cost of the quantum step is $1. So the molecules simply do not vibrate.
But as you heat the gas up to extreme temperatures, the thermal currency increases. You start handing out dollar bills.
Suddenly, the higher energy states unlock, the molecules finally start vibrating, and the gas begins to behave closer to the old classical predictions.
That is exactly how the quantum staircase explains the wild temperature fluctuations. And physical evidence perfectly backs this up.
Oh, really?
Yeah. If you look at a gas made of iodine, the atoms are massive and incredibly heavy compared to hydrogen. Because of their sheer mass, their quantum steps, their dollar bills are actually much smaller. They're more like quarters.
Okay, so the cost is lower.
Right. Because the steps are smaller, the ambient pile of thermal pennies at room temperature is actually enough to trigger the vibrations. So iodine acts classically and vibrates even in a mild room, while hydrogen remains completely frozen out until it is superheated.
That is amazing. It completely flips everything we thought we knew.
And there is a wonderful irony to all of this.
What's that?
Because energy exists in these discrete locked steps, calculating statistical mechanics actually becomes far easier in quantum theory than it ever was in classical theory.
Wait, really?
Yeah, the math cleans up. You aren't dealing with an infinite continuum of tiny fractions. You are just counting discrete steps.
So by introducing this mind-bending concept of a quantum staircase, physics actually brought order to the chaos. What an incredible journey.
It really is.
We started today with a simple observation about why the atmosphere gets thinner high up in the sky, and that led us to tracking the exponential tug-of-war of gravity and mapping the personal space of a billion chaotic molecules on Boltzmann's dance floor.
Yep, from the macro to the micro.
We watched the fastest molecules filter over the velocity wall, only to watch classical physics completely collapse when it tried to explain the simple act of heating up a hydrogen dumbbell.
It took the profound realization that energy is dealt out in rigid, discrete chunks to save the math and accurately describe the reality we observe every day.
So the next time you boil a pot of water on the stove or feel your ears pop from the air pressure changing on a flight, I want you to remember the invisible mechanics at play.
It's all happening right in front of you.
You are witnessing a billions of years old battle between thermal chaos pushing outward and potential energy pulling inward.
All of it governed by quantum rules that operate on levels we can't even see.
And I want to leave you with a final thing to chew on today. Think back to those 19th century scientists tracking the chaotic bouncing of microscopic air molecules, completely convinced that reality was a smooth, continuous ramp, only to crash headfirst into a quantum brick wall.
A very humbling moment for science.
Absolutely. So if our understanding of the physical world was so completely upended by discovering that molecular energy is actually made of a hidden staircase, what other seemingly smooth, continuous things in your everyday life, like the steady flow of time or the invisible pull of gravity itself, might actually be made of hidden, discrete steps just waiting to be discovered? I want you to imagine for just a second that you are peering through a brass 19th century microscope.
Like one of those really heavy, clunky ones.
Yeah, exactly. You're a botanist, perhaps, adjusting those heavy lenses, and you finally get the focus just right on a single drop of water.
And inside that water, you see these tiny microscopic pieces of plant pollen.
Right? But they aren't just floating peacefully, They're violently jiggling around, twitching, never stopping, never resting.
Instinctively, almost anyone looking through that lens would assume they were watching something alive.
Because that frantic twitching looks exactly like the erratic swimming of a tiny living organism.
Exactly. And, you sent us this incredible set of notes summarizing Richard Feynman's physics lectures, specifically focusing on this bizarre phenomenon, the Brownian movement.
Yeah, but we aren't just here to talk about a botany experiment today. We are going to take that simple observation of jiggling dirt and, well, follow it down a rabbit hole for this deep dive.
We're going to show you how staring at a twitching speck of dust completely broke classical physics.
Literally forced the invention of quantum mechanics.
Right, and ultimately gave scientists the tools to literally count the invisible atoms that make up our universe.
It really is one of the most profound intellectual journeys in the history of science.
You start with something entirely mundane, dirty water.
Right. And by simply refusing to stop asking the fundamental question of why it's happening, you end up having to rewrite the foundational laws of nature.
So the year is 1827. A botanist named Robert Brown is the guy squinting through that microscope.
He sees the pollen jiggling, but rather than just publishing a paper claiming he found microscopic bugs, he actually questions his own assumptions.
Which is the mark of a great scientist.
Exactly. He asks himself whether this is biological life or if it's just a physical property of matter itself.
So to test it, he completely abandons the pollen.
He hunts down ancient quartz crystals that have had tiny pockets of water trapped inside them for millions and millions of years.
Oh, wow. That is dedication.
Yeah, and he puts that ancient water under the lens, and he looks at the microscopic dust suspended inside it.
And he sees the exact same motion. I mean, dust that has been entombed in solid rock since the time of the dinosaurs is jiggling with the exact same frantic energy as the fresh plant pollen.
That observation is the critical pivot. He proves beyond a shadow of a doubt that it has nothing to do with biology.
It is a purely physical phenomenon. The microscopic world is inherently restless.
But the actual mechanism, like the cause of that restlessness, remained a complete mystery to the scientific community for decades.
Right.
Okay, let's unpack this. Feynman's notes use a brilliant visual to help us understand what is actually happening to that dirt.
A push-ball analogy, right?
Yeah, picture yourself sitting in the nosebleed section of a massive sports stadium, looking down at the playing field from miles away.
Down in the middle of the field is a giant push-ball.
Right, and you are way too far away to see the individual people standing underneath the ball.
But you can see the ball itself violently jerking around.
Exactly. Drifting left, lunging right, popping up and down. Because it's moving so erratically, you instinctively know there are unseen forces pushing it.
And in the case of the pollen in the water, those unseen pushers are the water molecules themselves.
Because the pollen particle is a behemoth compared to a single water molecule, right?
Oh, absolutely. Millions of times heavier. But it is being bombarded on all sides continuously by these incredibly fast-moving, entirely invisible molecules of water.
And that brings us to a fundamental concept in thermodynamics.
Right, the equipartition of energy.
The notes throw around some heavy math here, specifically claiming the energy is 3/2 K times T.
Yeah, that formula pops up a lot.
I don't want to lose our listener in textbook formulas right out of the gate.
Yeah.
Can we ground that in physical reality? What is equipartition actually doing?
Let's break it down. Equipartition just means that if a system is in thermal equilibrium, meaning everything in the glass of water is at the exact same temperature, the available energy is shared equally among all the ways a particle can move.
Okay, so we live in a three-dimensional universe.
Right. A particle can move up and down, it can move left and right, and it can move forward and backward.
And the laws of thermodynamics dictate that the microscopic jiggling energy is split perfectly evenly across those three dimensions.
Exactly. Each dimension gets an equal slice of the temperature pie.
That's a great way to put it. So each of those three directions gets an average kinetic energy of 1/2 times K, which is a fundamental constant times T, the temperature.
Yes. And if you add up the up, down, left, right, and forward, back dimensions, you get 3/2 K times T.
So the jiggling water molecules smash into the speck of dirt, transferring their kinetic energy until the dirt is jiggling with that exact mathematically perfect amount of energy.
Precisely.
But I noticed the physicists in these notes don't actually try to calculate the chaotic math for a complex liquid like water to prove this.
No, they cheat a little bit with a thought experiment.
Right, because water is incredibly messy mathematically.
Yeah, the molecules interact with each other in really complex ways. So physicists substitute water with an imaginary ideal gas.
Imagine a gas made of tiny, perfectly hard, artificial pellets bouncing around.
We understand the physics of those imaginary pellets perfectly. Now, imagine putting the dirt particle in the complex water and putting another dirt particle in the imaginary gas, both at the exact same temperature.
If the dirt particle somehow jiggled faster when hit by the water than when hit by the imaginary gas, we'd have a massive problem.
We would have a perpetual motion machine.
Wait, really? How does that work?
Well, if the water made the dirt move faster, the dirt would then transfer that extra kinetic energy into the gas, heating the gas up spontaneously.
Oh, which violates the laws of thermodynamics. Things don't just spontaneously heat up out of nowhere.
Thermodynamics absolutely forbids it. Equilibrium is universal across the cosmos.
So if the particle has a predictable energy of 3/2 kT when bombarded by our imaginary gas pellets, it must have that exact same energy when bombarded by the messy water molecules.
Exactly. The math holds firm regardless of the substance.
And this universal jiggle isn't confined to a botanist Petri dish.
Far from it. It plagues the most sophisticated laboratories on Earth.
Like delicate equipment. Say you build an incredibly delicate piece of equipment, let's say a galvanometer.
Right, which uses a tiny, supersensitive mirror hanging on a microscopic quartz fiber to measure faint electrical currents.
You build it perfectly. You seal it in a vacuum. You bounce a laser off that mirror to take a measurement, expecting it to sit dead still.
But it won't. It wobbles.
Just because the room is warm.
Because the ambient temperature of the room means the mirror is in thermal equilibrium with its environment.
So it has that same fundamental kinetic energy.
Yes. It is constantly being kicked around by the residual air molecules or even by the microscopic thermal vibrations inside the quartz fiber itself.
That's wild. There is a literal, inescapable physical limit to how perfect an instrument can be, simply because the universe is warm.
And the notes mention this extends into electrical circuits, too. We were talking about Johnson noise.
Oh yeah, if you build a highly sensitive radio receiver, you get random voltage fluctuations. That static you hear on an old radio is that literally just the heat of the electronics causing the electrons to bounce around.
That is the direct acoustic translation of the universal jiggle.
That is amazing.
The electrons inside the resistor of the radio are in thermal equilibrium with the material around them. They are jiggling.
And because electrons carry an electric charge, their random jiggling creates tiny, chaotic electrical fields that drive the circuit.
The heat causes the jiggle, and the jiggle causes the static noise.
Which brings us to a really dangerous historical question.
Dangerous how?
Well, if our listener is following the logic here, absolutely everything at a given temperature jiggles with a predictable amount of energy, even electrons.
Right.
But electrons have an electric charge. What happens when a charged particle jiggles?
What's fascinating here is that specific question triggered the collapse of classical physics.
Wow. Because we know from electromagnetism that when an electric charge jiggles or oscillates, it acts like a miniature antenna.
It radiates light. It emits electromagnetic energy. So imagine a charged oscillator floating in a thin, warm gas.
The gas molecules collide with it, giving it that thermal jiggle.
But the moment it jiggles, it radiates some of that energy away as light.
Because it's shooting out energy, it's losing energy, it's cooling down.
Yes, it acts like a thermal parasite.
A thermal parasite, I like that.
It steals heat from the gas through collisions, radiates that heat away as light, and eventually the entire system would freeze solid.
Unless you trap that light. The notes talk about building a black-body furnace to reach equilibrium.
Right, but let's drop the jargon for a second. We are basically talking about putting this jiggling electron inside a perfectly sealed, perfectly mirrored oven, right?
A mirrored oven is the perfect way to visualize it. The electron jiggles and shoots out a photon of light.
But that light hits the mirrored wall of the oven and bounces right back.
It hits the electron again, getting absorbed, then scattered, then re-emitted.
Eventually, the oven reaches a perfect equilibrium where the amount of light the electron radiates perfectly matches the amount of light it absorbs.
From the glowing space bouncing around inside the box.
Right, and physicists in the late 19th century were thrilled about this mirrored oven.
They assumed they had the classical math to calculate exactly how much light and at what specific frequencies or colors should be bouncing around inside that oven at any given temperature.
It was called Rayleigh's law, and it was derived using the absolute best, most rigorously tested classical physics available at the time.
Here's where it gets really interesting. Rayleigh's law predicted something genuinely terrifying.
Oh, absolutely terrifying.
The classical math dictated that the amount of light intensity goes up as the square of the frequency.
Well,
Meaning as the frequency of the light goes up, the amount of that light goes up exponentially and never tapers off.
which is a fatal flaw for the universe.
Let's put this in perspective for our listener. If you are sitting in your kitchen right now next to a warm stove, classical physics says that the intensity of the light coming off that stove should just keep climbing with frequency.
There should be a huge amount of high-frequency visible light.
There should be an even more massive amount of ultraviolet light.
And there should be an infinite amount of X-rays.
If Rayleigh's law were true, the moment you open the door of an oven set to 350 degrees, you wouldn't feel a warm breeze of air.
You would be instantly vaporized by a lethal, infinite blast of X-ray radiation.
Physicists called it the ultraviolet catastrophe.
Yeah, the mathematics of classical mechanics. The same formulas that successfully built suspension bridges, predicted the orbits of planets, powered the entire Industrial Revolution, confidently predicted that every warm object in the universe should be an infinite source of blinding radiation.
Since we aren't vaporized every time we look at a hot cup of coffee, something was profoundly, fundamentally wrong with the most basic laws of physics. I just love the visual of the universe's math, essentially outputting an error code that says, hey guys, existence is impossible.
Yeah, it's pretty wild. So how did they stop the infinite X-rays?
They needed entirely new rules.
Enter Max Planck. Planck ignored the classical theories and looked at the actual experimental data of what light comes out of a hot furnace.
Because in reality, the curve doesn't shoot up to infinity.
No, the light intensity increases at first, peaks at a certain color depending on the temperature, and then drops back down to 0 for the really high frequencies like UV and X-rays.
So Planck found a brilliant mathematical formula that perfectly matched that real-world curve.
But to justify his formula, to make the math physically possible, he had to make an incredibly radical assumption about reality itself.
He had to break the continuous nature of the universe.
He shattered it. Classical mechanics assumed that an oscillator could take on any amount of energy. Energy was a smooth, continuous spectrum.
You could have 1 unit of energy, or 1.5, or 1.0001.
Exactly. But Planck hypothesized that the oscillators inside the material could only absorb or emit energy in specific, rigid, discrete chunks.
The energy had to be a multiple of a certain value, which we now write as h bar omega, or a quantum step. You couldn't have half a chunk, only whole chunks.
Right.
Let me try to visualize this. Classical physics viewed energy like a smooth wheelchair ramp.
Okay, I like where this is going.
If you have an electron sitting at the bottom of the ramp, even the tiniest microscopic bump of ambient heat from the room could push it slightly up the ramp.
It could always absorb some tiny fraction of energy.
Exactly. But Planck's universe is not a ramp, it's a staircase.
A staircase where the height of the steps changes depending on the frequency of the light.
Right. For low-frequency radio waves, the steps are microscopic. A tiny bit of room temperature heat can easily bump the electron up a few of those tiny steps, so it absorbs energy and radiates radio waves.
But for high-frequency X-rays, the very first step on that quantum staircase is a massive, towering cliff.
And at normal room temperatures, a random thermal collision just doesn't carry enough force to push the oscillator up that massive first step.
It's like a ping-pong ball colliding with a bowling ball. The thermal ping-pong ball bounces off, and the bowling ball doesn't move a millimeter up the stairs.
Because it doesn't have enough energy to reach that massive first step, it absorbs absolutely nothing, and it emits absolutely nothing.
The high-frequency X-ray motions are effectively frozen out by the sheer height of the quantum step.
The universe is saved from vaporizing itself simply because room temperature doesn't have the muscle to climb the X-ray stairs.
When you do the math using Planck's staircase, the discrete energy levels, you get a formula with an exponential function in the denominator.
And as the frequency gets larger and larger, the step height grows, and that exponential term grows massively.
Right, pulling the total intensity of the radiation down to 0. The curve naturally comes back down.
The X-ray catastrophe is entirely neutralized.
And if we connect this to the bigger picture, this derivation by Max Planck was the very first quantum mechanical formula ever discovered.
By solving the problem of why a hot oven doesn't kill you, Planck discovered the fundamental granularity of nature. It was the death of classical mechanics.
It really was.
It's staggering to realize we went from a botanist staring at dirty water to literally inventing quantum mechanics.
It is incredible.
But let's zoom back out to that original speck of dirt that Robert Brown was looking at.
Right, the pollen.
Quantum mechanics saved the universe by redefining how things jiggle at the subatomic level. But what about the dirt itself? With all this random quantum-regulated jiggling from the water molecules, how far does the pollen actually travel through the water over time?
That is the exact problem that Albert Einstein and Marian Smolchowski decided to tackle.
To understand their solution, you first have to grasp the sheer scale of the chaos happening in that drop of water.
A single water molecule hits that microscopic speck of dirt 10 to the 14th times a second.
That is 100 trillion collisions.
Every single second.
It's incomprehensible.
After just 100th of a second, the particle has been hit 1 trillion times. It has completely forgotten whatever trajectory it was on previously.
The collisions are entirely random in every direction.
Einstein approached this using a mathematical concept known as the random walk problem.
It's famously compared to a drunken sailor stumbling out of a bar, right?
Exactly. He takes a step, spins around completely randomly, takes another step in a random direction, spins again, and so on.
So what does this all mean? Like, the question is, after a long time, how far away from the bar is the sailor?
Yes.
If I think about this logically, if every single step is totally random, he's just as likely to stumble left as he is to stumble right.
True.
He's just as likely to go forward as backward.
Yeah.
Shouldn't all those random steps eventually just cancel each other out? Shouldn't his average distance from the bar remain exactly 0? How does it make any headway?
It's a very intuitive objection, and mathematically you are half right.
Only half?
Yeah, if you tracked millions of drunken sailors, the mean or average location of the entire group would indeed be right back at the bar door.
Because every left step by one sailor is eventually canceled by a right step from another.
Exactly. But if you want to know how far the dirt particle actually travels from its starting point, you don't look at the mean distance. You have to look at the mean square of the distance.
Okay, the notes dive into vector geometry and angles to explain the mean square. Let's skip the textbook geometry. Give me a visual our listener can actually picture while they are driving or making dinner. What is actually happening to the dirt?
Think of it like a single drop of dark ink hitting a wet paper towel.
Okay, I can picture that.
The center of the ink drop, the mean location, stays exactly where it landed. It doesn't move.
But as the random microscopic collisions push the ink particles around, the stain spreads out.
Right. The perimeter of the stain pushes further and further outward into the white paper. The mean square is essentially measuring how the area of that expanding stain grows over time.
So the center doesn't move, but the boundaries of the chaos expand steadily.
Exactly. And Einstein mathematically proved that the mean square of the distance increases directly proportionally to time.
Represented by alpha t. The longer you wait, the further the boundary of the random walk expands.
But to figure out exactly how fast that boundary spreads, Einstein had to confront a completely counterintuitive truth about the water itself.
Which is?
For these random thermal fluctuations to even exist, there must be resistance in the fluid, there must be drag or viscosity.
Wait, how does the water slowing the dirt down relate to the water pushing the dirt forward?
They are the exact same mechanism.
I'm not following.
Imagine you are standing still in a crowded, chaotic room where everyone is walking around randomly. People bump into you equally from all sides.
Okay.
Now, try to run forward through that chaotic crowd. Suddenly, you are slamming into far more people on the front of your body than on your back.
Because I'm moving into them.
Right. That increased bombardment on your front feels like resistance. It feels like drag.
Oh, wow. So viscosity isn't a magical opposing force. It is literally just the thermal jiggling acting unevenly against you because you're trying to move through it in one direction.
The mechanism that causes the resistance is the exact same mechanism that causes the jiggling.
That makes so much sense. And this realization leads to the ultimate payoff of the entire deep dive. How did this let them count atoms?
Einstein realized that you could run a completely separate, simple experiment on that piece of dirt. You could apply a steady force to it, like dropping it through the water and letting gravity pull it down, and measure exactly how fast it drifts.
That drift speed tells you the exact coefficient of drag.
It gives you the viscosity of the fluid acting on that specific particle.
Okay, so I measured the drag first.
Yes. And once you know the drag, you plug that number into Einstein's equation for the random walk.
So by patiently watching a piece of dirt jiggle under a microscope and measuring how fast that ink stain spreads out, scientists could solve for the underlying thermodynamic variables.
Specifically, they used this experiment to calculate Boltzmann's constant.
Which is the K in the equipartition energy we talked about at the very beginning.
Yeah.
The link between temperature and kinetic energy.
Exactly.
But how does having Boltzmann's constant tungsten let us count atoms?
To count atoms, we need to introduce one more number. The macroscopic gas constant, known as R.
Okay.
Chemists had known the value of R for a long time just from observing how large volumes of gases behave under pressure.
But theoretically, physicists knew that R was simply Boltzmann's constant K multiplied by the number of atoms in a mole of substance.
Which is Avogadro's number.
Let me make sure I have this sequence right. Chemists already knew the big number, R.
Oh.
By watching the dirt jiggle and calculating the drag, Einstein and Smoluchowski finally found the microscopic number, K.
Yes, and because R equals K times Avogadro's number, all you have to do is divide R by K.
And the result is the exact number of atoms in a mole of materia.
Humanity literally counted the invisible atoms making up our world simply by analyzing the mathematical spread of a speck of dust twitching in dirty water.
That is just a masterpiece of scientific deduction. Let's just summarize this incredible intellectual journey.
Yeah, it's a lot to take in.
We start with Robert Brown in 1827, staring at ancient quartz water, proving that the microscopic world is boiling with an unseen, non-biological motion, the universal thermal jiggle.
Right.
But when scientists tried to apply the classical rules of that 3D jiggling to an electric charge, the math predicted household ovens that shoot infinite X-rays. The universe broke.
The ultraviolet catastrophe.
Exactly. To stop the catastrophe, Max Planck invented the quantum staircase, proving energy comes in rigid chunks, birthing quantum mechanics.
And finally, Einstein takes all of this newly revealed chaos, looks back at the dirty water, figures out the expanding stain of the random walk, equates the jiggling to drag, and uses it to count the atoms in the universe.
It perfectly demonstrates how in physics there are absolutely no isolated phenomena.
Everything is intimately connected. This raises an important question.
Oh.
Something for you, the listener, to think about long after we finish our deep dive today. Think about the electronic device you are using to listen to this right now. It has a temperature, it's warm in your hand, or radiating heat in your pocket.
Yeah, inevitably.
That means deep inside its microscopic circuitry, at this very second, countless electrons are performing the exact same random walk as that ancient piece of pollen.
Wow.
They are generating that chaotic Johnson noise through the precise quantum rules we just discussed. True stillness doesn't exist anywhere in the cosmos. Everything around you is locked in a perpetual, mathematically perfect dance.
That's incredible.
What else is hiding in the noise of your daily life, just waiting for you to look at it closely?
So the next time you happen to look through a microscope or even just hear the static hiss on a speaker, remember, you're not just looking at dirt or hearing bad reception. You are witnessing the engine of the universe.
If you take a glass of water and just leave it on the sidewalk on a sunny day, eventually, well, it disappears.
Right, it evaporates.
Yeah. But if you look at the underlying mathematics of exactly how that water vanishes, you'll actually find the precise equation that engineers used to build, like the laser scanner at your local grocery store.
It's crazy to think about.
It really is. Welcome to the deep dive. Today, our mission is to decode one of the most legendary pieces of scientific literature. We are talking about chapter 42 of the Feynman lectures on physics.
Oh, an absolute classic.
Yeah, we're exploring the kinetic theory of matter, basically looking for a single hidden mathematical rule that connects the steam rising off your coffee, the absolute emptiness of deep space, and, the invention of the laser.
It is honestly an incredible piece of synthesis by Feynman. I mean, the beauty of this specific lecture is that it takes these seemingly completely unrelated, highly complex phenomena and just strips them down to one universal behavioral trait of matter. The foundational premise of kinetic theory is that at a microscopic level, absolutely everything is jiggling.
Just constantly moving.
Exactly. Atoms and molecules are in a constant state of chaotic motion. They're endlessly colliding with each other. And the magic happens because occasionally, purely by statistical chance, an atom or molecule will, borrow enough energy from its neighbors during a sequence of collisions to do something extraordinary.
Okay, let's unpack this, because that concept of borrowing energy is really the engine driving this entire deep dive.
Yeah, it really is.
If we want to understand how a laser works, we have to start by understanding the dice being rolled behind the scenes of everyday objects. So let's go back to that puddle of water evaporating. What is the physical mechanism allowing those molecules to just float away?
Well, to understand the escape, we really have to look at the trap. In a liquid, the molecules are bound together by strong intermolecular attractive forces. They basically sit in a potential energy web.
Like they're stuck in a pit.
Yeah, exactly. For a single molecule to break free and escape into the air as vapor, it has to perform physical work. It must overcome that attractive force holding it down. Let's think of the specific amount of energy required to break those bonds as a threshold like an escape energy.
So they aren't just drifting apart casually. There's a strict energy toll they have to pay to cross the border from liquid to gas.
Precisely. And this is where the chaotic jiggling, the thermal energy, comes into play. If you look at the energy of the molecules in that puddle, they don't all have the same amount.
Right.
They follow a statistical distribution, a bell curve. The vast majority of molecules are just vibrating near the average energy, which is honestly nowhere near enough to cross that threshold.
They're just kind of bumping shoulders.
Yeah, but because they are constantly smashing into each other trillions of times a second, energy is constantly being exchanged.
So it's almost like a microscopic lottery, or maybe like a chaotic mosh pit. Most people in the pit are just getting jostled around.
Right.
But occasionally, by pure random chance, one person gets shoved by 3 or 4 people simultaneously, all pushing in the exact same direction. They win the energy jackpot. They suddenly have enough kinetic energy to leap completely out of the mosh pit.
That is a brilliant way to visualize it. Feynman breaks down the mathematics of this lottery. The probability of a molecule accumulating that massive excess of energy is an exponential function.
Okay.
Specifically, it depends entirely on the ratio between the required escape energy and the ambient temperature. It's a compounding relationship. The big takeaway from the math is that this probability is intensely exponentially sensitive to temperature.
So heating it up changes the odds completely.
Exactly. If you increase the temperature of the water even a tiny bit, you don't just get a few more molecules escaping. You create this exponential explosion in the number of molecules residing in that high-energy tail of the bell curve.
Now hold on, because there's a logical trap here that I really want to push back on. If we follow this mechanism, that only the absolute fastest, most energetic jackpot winners are escaping the liquid, shouldn't the vapor floating above the puddle be incredibly hot compared to the liquid left behind?
Oh, I see where you're going.
Because, temperature is just a measure of average kinetic energy. If only the speed demons are getting out, the gas should be boiling hot, right?
It's a completely logical assumption, and it's actually a misconception that Feynman specifically addresses, because the truth is so counterintuitive. You have to remember the potential energy, well, the trap.
Right.
The molecule that won the lottery has a tremendous amount of kinetic energy right at the surface, yes. But the moment it breaks the surface and starts to pull away, it has to fight the attractive forces of all the molecules it's leaving behind.
Ah. So it's like a rocket trying to escape Earth's gravity. It might be going incredibly fast when the engine's cut off, but gravity is constantly pulling it backward, bleeding off its speed the higher it goes.
Precisely. That's exactly it. The molecule pays the toll with its own velocity. It loses that excess kinetic energy fighting its way out of the potential well.
Wow.
By the time it is completely free and floating as vapor, it is slowed down significantly. Astonishingly, the mathematics dictate that the evaporating molecules end up with the exact same energy distribution, the exact same average temperature as the liquid they just left.
That is wild. So the vapor isn't a collection of speed demons at all. It's a collection of speed demons who exhausted themselves just getting out the door.
Exactly.
The fastest ones slow down to average speed, and the slow ones never even made it out of the liquid.
Right. And the consequence of those high-energy molecules leaving is that the average energy of the liquid that remains drops.
Yeah.
That is the physical mechanism of why evaporation cools things down.
Okay, so we've established that molecules can escape a puddle by basically rolling the microscopic dice. What happens if we push this to the absolute extreme? Like, what if the puddle isn't water, but a solid block of metal, and the things trying to escape aren't water molecules, but electrons?
Then you are dealing with thermonic emission. The underlying exponential probability law is totally identical, but the stakes are much higher. Inside a piece of metal, say a tungsten filament, the electrons are trapped in an incredibly deep potential well by the positive charge of the atomic nuclei.
Like a much deeper pit.
Way deeper. Pulling an electron completely off the surface of the metal takes a massive amount of work, typically measured in a unit called electron volts.
And reading through the sources, the sheer scale of an electron volt is kind of staggering. The text points out that to get an electron to naturally vibrate with just 1 electron volt of thermal energy, the ambient temperature would have to be around 11,600 degrees Kelvin.
It's insane heat.
Yeah. That's twice as hot as the surface of the sun, just to get 1 electron volt.
Yeah.
And tungsten requires several electron volts to give up an electron.
It is an immense barrier. But again, we are dealing with the extreme tail end of a statistical bell curve. Because of the law of large numbers, even if that tungsten filament is only glowing at, say, 2,000 degrees inside an old radio vacuum tube, a minuscule fraction of electrons will still hit the jackpot.
Even at that low temperature.
Right. They will randomly accumulate that massive energy, overcome the barrier, which we call the work function, and just boil right off the surface of the metal into the vacuum.
Which brings up a massive contradiction in the material that I really want you to clarify. The text transitions from thermonic emission to the Saha ionization equation.
Oh, yes.
This is the math of how entire atoms break apart into positive ions and free electrons when they smash together. But if it takes temperatures in the tens of thousands of degrees to rip an electron off an atom, why do physicists confidently state that there are vast clouds of ionized gas floating in the freezing dark void of deep space?
It's a great question.
The space between stars is just a few degrees above absolute zero. There's no thermal lottery happening out there. How can atoms be ionized without the heat to power the collisions?
What's fascinating here is that you have to rethink the kinetic reality when you change the spatial scale. You are absolutely right that in the freezing void of deep space, the thermal energy is practically non-existent.
Right.
The chance of an atom getting struck with enough energy to eject an electron is astronomically low. But space is constantly bombarded by high-energy cosmic rays, which can occasionally act as that massive energy spike.
Okay, so a rogue cosmic ray acts like a cue ball, hits an atom, and knocks an electron away.
But shouldn't that free electron immediately feel the positive pull of the ion, snap right back, and neutralize the atom again?
Under normal density, yes. In a gas cloud here on Earth, recombination happens in fractions of a microsecond. But space is a vacuum. The mean free path, which is the distance a particle travels before hitting something else, is immense.
Because it's so empty.
Exactly. Imagine that rare cosmic ray event happens. The electron goes flying off. You now have a free electron and a positive ion. Because the density of deep space is so absurdly low that electron might wander through the interstellar void for hundreds or thousands of years before it ever crosses paths with another ion to recombine with.
Because the sheer volume stretches the probability of a collision practically down to zero.
Exactly. The Saha equation balances the rate of ionization against the rate of recombination. In deep space, the rate of ionization is incredibly slow because of the cold.
Right.
But the rate of recombination is even slower, practically zero, because of the sheer emptiness. Over millions of years, those rare cosmic ray hits accumulate. The ions just pile up. It's a beautiful example of how that exact same kinetic equation dictates behavior differently when you stretch the volume out to galactic proportions.
So the mechanism isn't that space is hot enough to create ions, it's that space is too empty to let them fix themselves once they break. I love that.
It's the ultimate isolation.
All right, so we've talked a lot about things breaking apart. You know, water molecules escaping, electrons boiling off tungsten, atoms shattering into ions. But if kinetic theory governs everything, we really need to talk about things coming together, specifically chemical reactions.
Yes.
The very chemistry that keeps our bodies alive. These atoms have to obey this exact same law of kinetic probability to form bonds, don't they?
They absolutely do. This is the domain of chemical kinetics. Let's say you have two atoms, A and B. When they combine to form a molecule, AB, they drop into a more stable energy state, which means the reaction releases energy. The universe naturally prefers them to be joined.
Right. So if it releases energy and the universe prefers it, why don't they just instantly snap together like magnets the moment they get near each other? I mean, why isn't the wooden desk I'm sitting at spontaneously combusting into the oxygen in this room? Both the wood and the oxygen want to react.
Well, it doesn't happen spontaneously because of the electron clouds surrounding those atoms. Before the nuclei can get close enough to share electrons and form a stable chemical bond, their outer electron shells, which are both negatively charged, strongly repel each other.
Like repelling magnets.
Exactly. It's like trying to push the north poles of two really strong magnets together.
So they can't just casually bump into each other, they'll just bounce off.
Precisely. To get close enough to bond, they have to hit each other incredibly hard. A soft collision just won't breach the repulsive barrier. They need a minimum amount of extreme kinetic energy just to force their way through that initial repulsion. In chemistry, we call this the activation energy.
Feynman visualized this with a pretty brilliant analogy. He described it as a landscape where you have a ball resting on a high plateau, and it wants to roll down into a deep, stable valley. The deep valley is the chemical bond.
Right.
But between the plateau and the valley, there is a steep hill. The ball can't just slide into the valley. You have to physically push it up and over the hill first.
And that push is the activation energy. Just like the molecules escaping the puddle, the reacting atoms rely entirely on the microscopic lottery to crest that hill.
Yeah.
They need to randomly collide with enough force to overcome the electron repulsion.
So if it's too cold?
If the ambient temperature is too low, the probability of a high-energy collision is effectively zero. The wood on your desk is constantly being bombarded by oxygen molecules, but the collisions are just too weak. The hill is too high.
Which is incredibly lucky for us, otherwise biology wouldn't exist. Everything would just burn up instantly.
Very true.
But wait, what if I actually want that reaction to happen quickly, but I can't just set it on fire? Like inside the human body, for instance, we need complex chemical reactions to happen constantly, but our internal temperature is only 98.6 degrees. We can't boil our cells to get over the activation energy hill. So how does biology bypass the math?
By introducing catalysts. A catalyst is a chemical structural scaffold that participates in the reaction without being consumed by it.
You know, I always thought catalysts just somehow made the atoms move faster to create harder collisions.
No, increasing speed is just adding heat. A catalyst works by physically changing the landscape itself. Instead of forcing the atoms to smash through the intense repulsion of a head-on collision, a catalyst molecule physically binds to the reactants. It twists them, stresses their existing bonds, and holds them in the exact perfect geometric orientation so that the repulsion is minimized.
So it's not just lowering the hill, it's almost like digging a highly specific tunnel straight through the mountain.
Exactly. By holding the atoms in the perfect alignment, the catalyst drastically lowers the required activation energy. And remember that exponential mathematical relationship we talked about with evaporation.
Temperature and energy ratio, yeah.
Right. Because the probability is an exponential function of the barrier height, even a modest drop in that activation energy hill causes an exponential explosive increase in the reaction rate. At 98.6 degrees, a reaction that might naturally take thousands of years can happen in milliseconds, entirely because the catalyst lowered the threshold.
It's incredible. The exact same statistical math governing a puddle drying up is dictating the speed of the enzymes digesting my breakfast.
Exactly.
Okay, let's pivot, because we've covered physical collisions, heat, chemistry, basically matter bumping into matter. But what happens when the energy being transferred doesn't come from another atom, but from pure light?
Now we cross the boundary into quantum mechanics. The source material takes us to a brilliant deduction made by Albert Einstein in 1916. He applied this exact same statistical reasoning to the energy levels inside an atom.
Right, because atoms don't just have random amounts of internal energy. They have rigid, specific quantum levels, like rungs on a ladder.
Correct. And physicists already knew about a process called spontaneous emission. If an atom absorbs energy and jumps up to a high-energy rung on the ladder, an excited state, it is inherently unstable.
It wants to drop back down?
Yes, eventually, purely randomly, it will naturally drop back down to a lower stable state. When it drops, it sheds that excess energy by spitting out a photon, a particle of light.
It basically just falls like a ball rolling off a table and emits a flash of light.
Exactly. But Einstein, looking at the thermal equilibrium of gases, realized the math didn't balance if spontaneous emission was the only way atoms release light. He proposed that there must be a second, completely different kind of emission. He called it induced emission, or stimulated emission.
What's the physical mechanism there?
Well, he theorized that if an atom is already in that high-energy excited state, and a photon of the exact right frequency comes flying by and hits it, the atom doesn't absorb the photon. Instead, the passing photon acts like a trigger. It shakes the atom, forcing it to instantly drop to the lower level and emit its own photon.
Wait, so one photon comes in, strikes the loaded atom, and now two identical photons go flying out perfectly together?
Yes. And if we connect this to the bigger picture of kinetic theory, Einstein proved a profound statistical symmetry. He deduced that the probability of an atom absorbing a photon to climb up the ladder must be perfectly equal to the probability of a passing photon inducing an excited atom to fall down the ladder. In a normal environment, absorption and induced emission are perfectly identically balanced.
Here's where it gets really interesting. Because if you have a physical mechanism where one photon can basically clone itself by triggering an atom, creating two photons, well, you have the recipe for a microscopic avalanche.
You certainly do.
How do we take Einstein's math from 1916 and weaponize this induced emission to create a laser?
Well, to weaponize it, you have to break the rules of statistical mechanics. In a normal gas at thermal equilibrium, the Boltzmann distribution, that bell curve we keep talking about, dictates that the vast majority of atoms will always be sitting in the lowest energy state, the ground state.
Right, because high energy is rare. The lottery winners are few.
Exactly. So if you shine a light through a normal gas, almost every photon will just be absorbed by an atom sitting at the bottom rung. There aren't enough excited atoms waiting around to trigger that avalanche. To get a laser, you have to engineer an entirely unnatural state of matter. You have to create what is known as a population inversion.
Meaning you force the math backward. You need more atoms at the top of the ladder than at the bottom. How do you physically force that?
You pump the system. You flood the gas with a massive, intense burst of external energy, like a high-frequency flash lamp. This brute forces trillions of atoms to absorb photons and jump to a highly excited state.
Okay, they're all at the top.
But you don't want them to drop back down immediately. The trick Feynman describes involves utilizing a specific atomic structure that has a metastable state.
Metastable. So they fall partway down the ladder and then they get stuck on a specific rung.
Yes, precisely. They trickle down and get trapped on a rung where spontaneous emission is physically suppressed. They are loaded with energy, but they can't easily drop on their own.
Yeah.
By continuously pumping the gas, you hoard all these atoms in that metastable state. You have successfully inverted the population.
I can picture it perfectly. You have this massive chamber of atoms all cocked and loaded, trapped at high energy, just waiting for a catalyst.
Waiting for a trigger.
And then the inevitable happens. One single atom randomly overcomes the metastabile barrier and spontaneously drops. It emits a single photon. That photon flies into the next loaded atom and induces it to drop. Now you have 2 photons moving in perfect lockstep.
And then it builds.
Those 2 fly into 2 more atoms, making 4, then 8, 16, a million. It's an exponential chain reaction. They all dump their trapped energy simultaneously in a massive burst of identical light.
That avalanche of photons is the core of the laser. But there is one final crucial piece of engineering. If you just trigger a population inversion in a glass tube, that avalanche happens in every possible direction. It's an incredibly bright flash, but it's scattered. It isn't a beam.
Oh, right. To make it a beam, you need to organize the avalanche.
Precisely. You build an optical cavity by placing nearly perfect mirrors at both ends of the tube. When the chain reaction starts, most of the light shoots out the sides and is lost. But the photons that happen to be traveling perfectly parallel to the tube hit the mirror, bounce back through the energized gas, and induce more atoms to emit light on the return trip.
So it's just sweeping back and forth.
Yeah. The light bounces back and forth between the mirrors, amplifying itself exponentially with every pass, perfectly synchronized in frequency and direction.
And you make one of those mirrors just slightly transparent, maybe 1%.
Exactly. And that tiny fraction of light that leaks out of the mirror with every bounce is a perfectly uniform, completely unidirectional, highly concentrated beam of pure optical power. Light amplification by stimulated emission of radiation. A laser.
We just built a laser by exploiting the exact same kinetic probability laws that dictate how a puddle dries up on the sidewalk. So what does this all mean?
It means that nature is deeply, profoundly interconnected by probability. The steam rising off your teacup, the electrons glowing inside an old radio, the ancient ions drifting through the interstellar void, and the laser reading the barcode on your groceries. They are all just different physical manifestations of the exact same underlying mathematics.
The lottery.
Mathematics of atoms continuously colliding, rolling the dice, and occasionally borrowing just enough energy to leap over the barriers that nature sets up.
You know, tracing it all back, like this leaves you with something highly unsettling to think about. We navigate our daily lives viewing the physical world as solid, certain, and completely predictable. My desk feels solid. I know water boils at 100 degrees. It feels like an absolute macroscopic law.
It feels certain.
But when you look at the mechanisms, if every chemical reaction keeping your cells alive and every piece of technology we rely on fundamentally operates on the microscopic random chance of an atom winning a kinetic lottery, is the certainty of our everyday existence just a grand illusion? Are the laws of physics that we trust just the ultimate manifestation of the law of large numbers, smoothing out trillions of chaotic, random coin flips? Think about that next time you boil a pot of water. Thank you for joining us on this deep dive.
Imagine a world where you can't move even a fraction of a millimeter without, like, slamming into a brick wall at the speed of sound.
Yeah, which is basically the violent, chaotic reality of the exact air you are breathing right now.
Right. It is just a relentless, high-speed game of microscopic bumper cars. And it's happening constantly all around us, inside us.
But the wild part is that out of all that staggering microscopic violence, we get the perfect, predictable calm of our everyday macroscopic world.
Exactly. Welcome to today's deep dive. You know, we usually think of physics in terms of perfect balance, right? Like thermal equilibrium, a still pond, or a hot cup of coffee cooling down perfectly evenly on your desk.
Right, the clean, smooth stuff.
Yeah, but today our mission is to dive headfirst into the underlying chaos of a gas. We're looking closely at Chapter 43 of the Feynman Lectures on Physics. We are going to explore the classic mechanics of molecular collisions.
Because we really need to understand how completely erratic, unpredictable atom-by-atom crashes actually construct the ironclad physical laws we rely on. I mean, things that run our entire society.
Electrical currents, heat transfer, all of it. So we are going to shrink down, track the completely unpredictable life of a single molecule, and watch how the tiniest directional nudge creates a steady drift.
And we'll eventually uncover a really mind-bending paradox about how heat travels that just defies all everyday logic.
Totally. But before we can figure out how our molecule gets anywhere useful, we have to grasp just how rough the terrain actually is. These molecules aren't taking leisurely flights across the room.
Far from it. They are perpetually crashing into one another. And to make any sense of this environment, physicists rely on a critical baseline measurement. It's the average time between collisions.
Which they call tau, right? The Greek letter tau.
Exactly, tau. It is a beautifully simple concept, just a mean time, but it leads to some incredibly counterintuitive realities about probability.
Well, because molecules don't have memories. Like, they have no internal stopwatch tracking when their last collision was.
Oh, no, not at all.
So if you pick any arbitrary instant in time, say you just snap your fingers and ask, how long on average until this specific molecule hits something else?
The answer is always exactly tau.
Which is so weird.
Yeah,
Because our human brains deeply struggle with that lack of memory.
we really do. We tend to think, well, if the average wait time for a crash is a minute, and the molecule has already been flying freely for 30 seconds, the next crash must be, due in 30 seconds.
Right, like it's owed a crash.
Yeah.
Yeah.
But the universe doesn't run a train schedule for particles.
Mhm.
Every microsecond is a fresh roll of the dice. Your probability of surviving the next tiny fraction of a second, let's call that dt, without crashing, is exactly dt over tau.
Wow, okay.
So it's the same whether you just suffered a massive collision or you've been flying unimpeded for a while.
It's basically the gambler's fallacy applied to thermodynamics.
Exactly that.
It's like standing at a roulette wheel and assuming a red number is due just because it's landed on black 5 times in a row.
Yeah.
The wheel doesn't remember previous spins. The molecule doesn't remember previous flights.
Right. And as time stretches on, the probability of surviving without a crash drops off exponentially. Mathematically, it's e to the negative t over tau, meaning the longer you wait, the drastically fewer molecules remain crash-free.
But the underlying average wait time from whatever moment you choose to start the clock remains completely constant.
Always tau. But because that internal clock is constantly resetting, the actual physical distance these molecules manage to travel is wildly unpredictable. So to figure out how far they get, we need to shift our perspective from time to space.
We need to look at the mean free path,
Right.
which is just that average time, tau, multiplied by the molecule's average speed.
Hmm.
Let's visualize what actually dictates that physical distance. Imagine you put on a blindfold and start sprinting at top speed through a forest.
That sounds dangerous.
Very. But your mean free path is just how far you manage to run before you inevitably slam into a tree.
And the distance you survive depends entirely on two specific properties of that forest.
First, how wide are the tree trunks? Like, if you're running through an ancient grove of massive redwoods, your run is going to be incredibly short.
Yeah, you're hitting wood almost immediately.
But if it's a field of incredibly thin bamboo stalks, you've got significantly better odds. In our gas, the thickness of those trees is the actual target area of the background molecules.
Which physicists call the collision cross-section. We use sigma for that. And the second property of the forest is how tightly packed it is, so the density of the gas.
Right.
If you have just a few trees spread out over a square mile, you can run all day blindfolded. But a dense, overgrown thicket guarantees almost immediate impact.
So you put those two factors together, and you have a perfect geometric limit.
Yep. You will crash exactly when you've run far enough that the effective width of the trees you've passed finally adds up to completely block your forward view. The background molecules essentially form a solid, overlapping wall of targets, and your mean free path abruptly ends.
That gives us our baseline reality. A violent, completely random dance governed entirely by probability, target size, and gas density. In this state, nothing is going anywhere in particular. It's just pure, undirected thermal jiggling.
Exactly.
So how do we actually extract useful work out of this mess? Like, what happens if we introduce a gentle, directional push to this system?
Well, we need to single out a few special molecules to receive that push. Let's call them S molecules. Imagine a handful of these S molecules mixed into our gas that carry an electric charge. Because they are charged, we can turn on a background electric field to basically pull them in a specific direction.
Okay, my immediate instinct here says that if you apply a constant force to an object, it is going to accelerate. Like, it should just go faster and faster and faster in the direction you're pulling it.
In a perfect vacuum, absolutely. But remember, our charged molecule is stuck in the bumper car forest, so it starts to accelerate, picking up forward speed, and then
Smack, it hits a tree.
it hits a background neutral molecule. That collision violently scatters its forward momentum. It bounces off in some random direction and has to start the entire acceleration process all over again from scratch.
Oh, I see. It is microscopic stop-and-go traffic. You slam on the gas, slam on the brakes, hit the gas, hit the brakes.
Yeah, and that unending cycle creates what we call drift velocity. It is a slow, agonizingly steady forward progress layered entirely on top of the chaotic high-speed bouncing.
So the molecule is still mostly darting around randomly at hundreds of meters per second.
Oh, totally. But over time, it creeps forward along the electric field at just a tiny fraction of that speed.
And the ratio of that steady forward creep to the strength of the force we're applying is a property called mobility, right?
Yes, mobility. Moo.
So a higher mobility simply means the molecule responds more efficiently to the push. You naturally get higher mobility if the molecule is lighter and easier to accelerate, or if the average time between crashes, or tau, is longer.
Because that gives it more breathing room to build up speed?
Right. But we have to tread very carefully here, because calculating that exact drift velocity based on the applied force and the crash time traps almost everyone who attempts it.
Oh, it's a notorious pitfall. Even seasoned textbook authors have stumbled into this one.
Okay, I'm going to attempt to walk through the derivation right now because I genuinely want to see if my own high school physics logic leads me into the trap.
Go for it. Let's hear it.
All right, so we apply a constant force to our charged molecule. It accelerates from a dead stop immediately after a crash. It accelerates for an average time of tau. Basic kinematics dictates the final speed is just the acceleration multiplied by the time, force times tau divided by mass.
Your logic is perfectly sound so far.
Okay, so if the molecule starts at 0 forward speed and ends at that calculated final speed, the average speed of that entire trip should logically just be exactly half of the final speed. Like if you graph it, it's a simple triangle into the curve, base times height over 2. So the final equation for drift velocity must have a factor of 1/2 sitting right at the front of it.
And boom, the trap snaps shut.
Really? I fell for it.
You fell for it perfectly. The logic feels incredibly solid, but that 1/2 is the trap. The true drift velocity equation does not contain a 1/2. It's just force times tau over mass. The factor vanishes entirely when you perform the true microscopic statistics.
Wait, how is that geometrically possible? A triangle always has half the area of a rectangle. How can the average not be half?
Because your mental model is imagining every single collision behaving like a perfectly regular metronome. Crash. Wait, exactly time tau. Crash. Wait, exactly time tau.
Right.
In that perfectly rhythmic universe, your 1/2 factor is entirely correct.
Oh, but we just spent the entire opening establishing that the universe does not run a train schedule. The times between crashes drop off exponentially.
Exactly. Think deeply about what that exponential distribution actually means for our stop-and-go traffic. You are going to have a massive number of really short flights, little instantaneous double taps where the molecule barely moves before hitting something else.
Right, the early part of the probability curve.
Yes. And you'll also have a small handful of very rare, very long flights.
Okay, but if there are vastly more short trips than long trips, why does that systematically erase my 1/2 factor? Wouldn't that bring the average down even further?
You'd think so, but no. During those incredibly frequent short trips, the molecule barely has a chance to accelerate. It doesn't build up any meaningful forward speed at all, so those trips contribute practically nothing to the overall forward drift.
Oh, wow.
The rare long flights disproportionately dominate the actual forward progress because the molecule finally gets a sustained window to really get going. Since distance scales with the square of time when you're accelerating, a trip that lasts twice as long gets you 4 times as far.
Ah.
When you take the mathematical integral of that wildly skewed, lopsided probability curve of flight times, the outsized statistical weight of those rare long flights perfectly and entirely cancels out your 1/2 factor.
That is genuinely wild. The inherent lopsided randomness of the collision schedule fundamentally alters the final macroscopic math. You cannot just take an average time, plug it into a clean kinematic equation, and expect the right answer.
No, you have to deeply respect the chaos of the distribution.
Okay, so respecting that chaos is exactly what allows us to bridge the gap between abstract gas mechanics and, well, the physical technology running the very devices people are using to listen to us right now. Let's visualize this forced drift in a physical space.
Let's do it.
Picture a clear, sealed rectangular box filled with this chaotic gas. Mixed in with the standard neutral gas molecules are our special charged particles, the ions. Now, we cap the two opposite ends of the box with solid metal plates and wire them up to a battery.
So we are essentially engineering a controlled lightning storm inside this container.
Exactly. And that battery projects an electric field straight through the gas, from one metal plate all the way to the other. The field grabs hold of those charged ions and starts a relentless tug of war.
And our ions are now experiencing that exact stop-and-go drift we just mapped out. They are tumbling violently through the dense forest of background molecules, constantly scattering, but slowly, inevitably creeping toward the opposite metal plate.
Right. And every time one of those drifting ions finally manages to crash into the destination plate, it deposits its electrical charge. If we set up a meter to count how much total charge hits that plate every single second, what physical phenomenon are we measuring?
We are measuring an electric current, amperage. And if we piece together the microscopic mechanism we just constructed, the amount of current arriving at that plate depends entirely on the drift velocity. Faster drift means more charge arrives per second.
And what ultimately drives that drift velocity? The strength of the electric field, which is directly dictated by the voltage of the battery.
Yes.
If you swap in a battery with double the voltage, you double the physical pull on the ions, which precisely doubles their drift velocity, which perfectly doubles the resulting electrical current.
Yep. The current is perfectly proportional to the voltage.
And every other variable inside that box, how dense the gas is, the physical length of the box, the mass of the specific ions, the collision cross-sections of the forest, all of that chaotic geometric mess just clumps together into one massive, unchanging mathematical roadblock.
Resistance.
Yes. So V equals I times R isn't just some empirical rule we notice while soldering circuit boards together. Ohm's law is the inevitable mathematical shadow of microscopic bumper cars.
It really is. The macro rule emerges purely because trillions of jagged, random little paths average out into a perfectly straight mathematical line.
It fundamentally shifts how you view the world. When you take a multimeter and measure the resistance of a copper wire, you aren't just measuring a superficial property, you are actively measuring the specific texture of the microscopic collisions happening deep inside that material.
Yeah, that covers what happens when we actively bully the molecules with an outside force like a battery. But what happens if we leave them completely alone? Let's say we have a high concentration of our special molecules tightly clumped on one side of the box, and we just sit back and watch.
Well, even entirely devoid of a battery, they will not stay clumped. They will spontaneously spread out through a process called molecular diffusion. But we must be incredibly precise here to separate this from everyday macroscopic assumptions.
Right. We're not talking about a fan blowing smoke across a room, or hot air rising due to gravity and creating a draft.
No drafts, no convection currents, just the pure, unrelenting thermal jiggling of the molecules in a sealed environment, like a drop of heavy dye slowly, inevitably dispersing in a completely still glass of water.
And because the molecules are constantly bouncing and scattering off whatever is near them, they will naturally migrate away from the densely crowded areas simply because there are more of them available to bounce outward. It is a statistical inevitability, not a directed force.
And this migration creates a diffusion current, a steady flow from high concentration to low concentration.
The speed of that natural spreading is governed by a diffusion coefficient, d. If you calculate the complex math of molecules randomly crossing an imaginary boundary plane in the gas, that coefficient turns out to be directly tied to our old friend, the mean free path.
Because how far they can physically jump between crashes dictates exactly how fast the clump can spread.
Exactly. So we now have two entirely distinct, seemingly unrelated phenomena on the table. We have mobility, which measures how obediently a particle responds to being shoved by an external force field. And we have diffusion, which measures how particles naturally randomly spread out in a vacuum of external forces.
They feel conceptually opposed. Like one is a force-directed march, the other is a leisurely, completely undirected wander. But they both share the exact same underlying frictions the bumper car forced.
Right.
So do they share the same roots, or are they mathematically linked?
Oh, they are. And uncovering that link requires one of the most elegant thought experiments in statistical mechanics. Imagine our box of gas again. We have a dense cloud of special molecules on the left side, naturally diffusing toward the empty space on the right.
Okay, visualizing it.
Now we turn on an electric field pushing from right to left. We perfectly tune the dial on our battery, adjusting the voltage until the force drift backwards precisely cancels out the natural diffusion forwards.
So the net flow of molecules stops completely. For every single molecule that randomly wanders to the right due to diffusion, the electric field actively shoves one back to the left.
Yes. We have artificially engineered a state of perfect thermal equilibrium.
And because the system is deadlocked and stationary, we can finally unleash the heavy fundamental equations of thermodynamics that govern probability and energy states.
Exactly. When you mathematically balance the equation for the force drift against the equation for natural diffusion and filter that balance through the thermodynamics of the system, almost all the messy, specific variables cancel themselves out.
Just disappear.
Yep. And you are left with a profoundly simple, universal truth known as the Einstein relation.
Ah, I love this part. The diffusion coefficient is exactly equal to the mobility multiplied by the Boltzmann constant and multiplied by the temperature.
D equals ma kT.
The innate ability of a molecule to be pushed around by a battery is mathematically permanently locked to its innate desire to spread out into empty space.
And the only thing mediating that profound relationship is the physical temperature of the room. It is a breathtaking unification of concepts. It proves that whether a molecule is reacting to an applied voltage or simply wandering down a concentration gradient, it is fighting the exact same microscopic battle.
Temperature is the universal bridge connecting external forces to internal spreading.
It really is.
Man, I am thoroughly strapped in at this point. We've watched these molecules physically carry electrical charge, and we've watched them carry themselves via diffusion. What happens if one side of our room is freezing cold and the other side is boiling hot?
Well, nature absolutely abhors a gradient. So thermal energy has to flow from the hot side to the cold side to equalize the room. And the vehicles actively carrying that thermal energy are the molecules themselves.
Right, so the hot molecules, the ones vibrating with massive amounts of kinetic energy, diffuse downward into the cold area, while the slow, sluggish cold molecules diffuse upward into the hot area. They are physically ferrying the heat across the room in tiny invisible packets.
We measure the efficiency of this specific ferrying process with a property called thermal conductivity, kappa.
Right.
If you meticulously derive the formula for this conductivity based on the collision mechanics we've established, you find it relies heavily on the average speed of molecules, the specific heat capacity of the gas, and the physical size of the collision cross-section.
Okay, I want you to mentally review those ingredients for how heat travels and try to spot what is glaringly absent from that list. We have molecular speed, heat capacity, and the target size of the molecules. What physical property of the gas is entirely missing?
The density of the gas.
Yes. The density of the gas isn't in the equation anywhere. It has absolutely zero mathematical impact on the final rate of thermal conductivity.
It is a massive paradox that completely defies our everyday intuition about how insulation and heat transfer should work.
It really does. Like, think about the physical implications here. If I take a perfectly sealed box of gas and I use an industrial vacuum pump to suck out 99% of the air, I have physically removed 99% of the molecules.
Right.
So I only have a tiny fraction of the vehicles available to ferry the heat across the box. Fewer trucks on the road absolutely must mean less cargo delivered.
Right.
How can a nearly empty box conduct heat just as fast as a highly pressurized, densely packed one?
Your logic makes perfect sense until you factor in the obstacles. When you lower the density by pumping out the air, you do indeed dramatically reduce the raw number of molecules available to carry the thermal energy, but you also simultaneously thinned out the forest.
Oh, the mean free path.
Exactly. The remaining molecules now have massive, wide-open spaces to fly through. The incredibly rare carriers that are left can transport their heat packets exceptionally far distances before they finally crash and scatter their energy.
Wow, it is a brilliant self-correcting mechanism. You have 100 times fewer trucks available, but every single truck can drive 100 times further down the highway without hitting a roadblock.
The math proves that these two competing effects, having significantly fewer carriers but proportionally much longer travel distances, perfectly and flawlessly cancel each other out. The thermal conductivity remains absolutely constant, regardless of how much gas you pump out.
Okay, I have to push back just a little on this because there clearly has to be a physical breaking point.
Sure.
Like, if I leave the vacuum pump running until I pump absolutely all the gas out, leaving a pure, perfect vacuum, the box cannot conduct heat via the gas because there is no gas left.
Okay, yes. You have zeroed in on the critical boundary condition of this entire statistical framework. The mechanics we've been unraveling only hold true under one strict geometric assumption.
Which is?
The mean free path of the molecules must remain significantly smaller than the physical box they are trapped inside.
Ah, so they have to actually be bouncing off each other, not just ricocheting off the walls of the container.
Right. The exact moment you pump out so much gas that a single molecule can fly from the hot wall, traverse the entire empty width of the container, and smack directly into the cold wall without ever colliding with another gas molecule. the game of bumper cars is completely over.
The statistical averages of the fluid break down entirely because there are no collisions left to average out. You just have individual ballistic projectiles.
Exactly. At that extreme threshold, you have to throw out the statistical fluid mechanics we've discussed today and use entirely different ballistic math. But anywhere within the realm of a normal, internally interacting gas, that bizarre, counterintuitive independence from density is a very real, mathematically ironclad fact of nature.
What an incredible arc we've traced today. We plunged into a violently chaotic, invisible world where molecules are blindly careening into each other millions of times a second. We watched how a wildly lopsided distribution of flight times mathematically erases our simplest, most logical assumptions about average speeds.
And we witnessed Ohm's law emerge not as some fundamental magical commandment of the universe, but simply as the smoothed-out aggregate of microscopic stop-and-go traffic.
We saw temperature act as the great unifier, perfectly balancing a particle's innate urge to diffuse with its forced reaction to an electric field. And we uncovered the beautiful paradox of a thinning gas conducting heat just as efficiently as a dense one, purely because the open road effortlessly compensates for the missing trucks.
I think the most valuable takeaway is realizing that our pristine, predictable macro world is built entirely on the back of overwhelming micro-chaos. The rules aren't magic, they are just the inevitable, staggering power of incredibly large numbers.
And that leaves me with one final thought for you to chew on today. We just proved that rigid, dependable physical laws, the very things we use to wire our homes and engineer our engines, are actually just the smoothed-out averages of trillions of random, erratic accidents. It makes you wonder, what other ironclad rules or predictable patterns in your own life or in human behavior or even the economy are actually just the illusion of massive numbers masking total chaos underneath? Next time you see something in perfect, serene balance, just remember, it's probably just a really big game of bumper cars.
You know, if you happen to have a rubber band nearby, just grab it. Seriously.
Yeah, if there's one right on your desk, pick it up.
Right. Now hold it right up to your lips, but, don't snap yourself.
That would be bad.
Just quickly stretch it out. If you pay really close attention, you'll feel something totally unexpected.
The rubber band actually gets warm.
It does. It almost feels like a magic trick.
It's one of those tiny, everyday phenomena that just completely defies our mechanical intuition.
Because we're so used to friction generating heat, right? Like rubbing your hands together.
Exactly. We don't expect a simple, clean, mechanical action like stretching a piece of elastic to just instantly generate a temperature spike.
But of course, it's not magic. It is a perfect, tangible example of the hidden rules that govern, well, almost everything around us.
It really is.
Which is why today we are taking a deep dive into those exact rules.
We are looking at Chapter 45 of the legendary Feynman lectures on physics.
Right, titled Illustrations of Thermodynamics. And our mission for this deep dive isn't to get completely lost in dense calculus.
Thankfully.
Yeah, thankfully. The mission is to decode this universal macroscopic rulebook, the one that dictates how that rubber band behaves, how the battery in your phone actually works, and even how stars radiate light into the void.
Which is quite an ambitious mission, honestly.
You think so?
I mean, considering thermodynamics can be notoriously difficult to navigate, yes.
Oh, fair.
The fundamental challenge of this field is just the sheer volume of ways you can describe the exact same physical system.
Like a jungle of variables.
A totally jungle. If you want to analyze, say, a gas trapped in a cylinder, you have this massive toolkit at your disposal.
Right, you could track its pressure or its total volume or its temperature.
You could calculate its internal energy or, measure its entropy.
And if you change just one of those, like 5 other things, immediately shift and respond.
A complete information overload.
So to survive that overload without getting hopelessly lost in a sea of equations, the text makes a really brilliant tactical choice right at the start.
Feynman decides to keep things strictly disciplined.
Yes, he limits the independent variables to just 2 things, temperature and volume.
Everything else we observe in this deep dive, we're going to understand purely through the lens of how temperature and volume interact.
Okay, let's unpack this. If we are filtering the entire physical universe strictly through temperature and volume, where do we even begin to look for a baseline rule?
Well, we really have to start with the foundational engine of all thermodynamics. I'm talking about the Carnot cycle.
Right, the classic Carnot cycle.
To truly understand how temperature and volume interact, taking a static snapshot of a system just isn't enough.
You have to put the system through a complete cycle of work.
Exactly. You add heat, let the gas expand, take heat away, and then compress it back to its original state.
But how does the text suggest we visualize a process like that, without immediately relying on the math, I mean?
Oh, Feynman gives us a remarkably elegant mental image for this.
Okay, lay it on me.
Imagine a graph where the vertical axis represents pressure and the horizontal axis represents volume.
The classic PV diagram.
Right. Now, if you plot the physical journey of a gas going through that Carnot cycle we just described, you end up drawing a series of intersecting curves.
So you draw isothermal curves first, where the system is expanding but the temperature stays perfectly constant.
Then you draw adiabatic curves, where the system is completely isolated.
Meaning no heat enters or leaves, but the volume is still changing.
Exactly. So by alternating between adding heat and isolating the system, those intersecting curves end up forming a closed loop on the graph.
It looks a bit like a curved parallelogram.
It does. And the geometry of that shape reveals something incredible.
The area inside it.
Yes. If you calculate the physical area inside that closed loop, that shaded region mathematically equals the actual physical work done by the gas.
It's just the change in volume multiplied by the change in pressure over the course of the cycle.
Seeing the work visually represented as an area is super helpful.
It is, but the text uses that geometry to derive a core equation that looks, frankly, incredibly intimidating on the page.
Oh, it's a total tangle of partial derivatives.
Yeah, relating internal energy, volume, temperature, and pressure. And reading calculus aloud is a quick way to lose anyone's attention.
For sure.
So how do we conceptualize what that equation is actually telling us?
Let's completely avoid reading the raw calculus. Conceptually, Feynman derives an equation that balances three distinct physical actions.
Okay, what are the three actions?
It balances how the internal energy of the system changes when you stretch the volume, how the pressure changes when you turn up the heat, and then just the baseline pressure of the system itself.
So mathematically, the partial derivatives are just a tool for isolating those specific relationships.
Exactly.
Let me try an analogy here to make those isolated relationships click for the listener.
I'd love to hear it.
Imagine you are sitting at a massive sound mixing board in a recording studio.
Okay, I like the sound mixing board concept.
You've got sliders for all sorts of things. Let's say one slider controls the temperature, another controls the volume, and the master output meter at the top of the board is your pressure.
Right.
A partial derivative in this scenario is basically asking a highly specific question about how that mixing board is wired.
It's asking, how much does the master output meter the pressure change if I slide the temperature up?
Yes, but strictly only if I take a piece of duct tape and tape the volume slider firmly in place so it physically cannot move.
You are forcing one variable to freeze so you can witness the pure, unadulterated relationship between the others.
You're isolating the variables perfectly.
And when Feynman applies that logic to the Carnot cycle, the resulting equation links two very different physical actions that you wouldn't intuitively connect.
It inextricably links the amount of heat you need to inject into a gas to keep its temperature constant while it expands, directly to how much the pressure spikes when you heat it while keeping the volume locked down.
Knowing one of those behaviors automatically tells you the other.
What is truly profound here, though, is the why.
Oh, absolutely. We can deduce this unbreakable physical relationship without knowing absolutely anything about the internal mechanism of the gas.
We don't need to know that the gas is made of tiny atoms.
We don't need to model how those atoms are bouncing around or colliding with the walls of the container.
Because this relationship relies entirely on the macroscopic laws of thermodynamics.
It is a fundamental rule of the universe that operates completely above the messy, invisible microscopic details.
But wait, if this framework is completely independent of atoms bouncing around in a cylinder, it shouldn't just apply to steam engines, right?
Right. It should apply to entirely different physical material.
Which brings us right back to your rubber band.
It does. The text points out that if this is truly a macroscopic law, we should be able to apply it to other systems simply by swapping out the variables to match the physical reality.
So for a gas in a cylinder, the physical work done is the pressure pushing outward multiplied by the change in volume.
But for a rubber band, the work done is the mechanical force you apply with your hands multiplied by the change in its length.
So we take that core thermodynamic equation, literally erase pressure and volume, and write in force and length.
The mathematical logic shouldn't care about the labels. And it doesn't.
The math holds up perfectly.
It does. And when you run those equations for an elastic material, it reveals the thermodynamic reality that explains the heat you felt on your lip earlier.
The math dictates that stretching a rubber band must raise its temperature to balance the thermodynamic cycle.
But the equation also proves the bizarre reverse scenario.
Yeah, this part is crazy. If you take a stretched rubber band, hold it taut, and blast it with a hairdryer to apply heat,
It doesn't sag or stretch further.
it physically pulls itself inward. It actually shrinks.
It shrinks because thermodynamics demands symmetry.
Right.
If mechanical stretching produces a release of heat, then injecting heat into a stretched state forces the system to perform the reverse mechanical work to maintain thermodynamic equilibrium.
It has to pull inward.
It is a beautiful example of how macroscopic thermodynamics predicts bizarre physical behaviors that microscopic kinetic theory would struggle immensely to guess.
Because kinetic theory would just be trying to imagine the molecular chains and the rubber tangling up.
Which is way too complicated.
We can push this abstraction even further, moving from mechanical elasticity to electricity.
Let's do it. Let's talk about the battery inside the phone or computer the listener is using right now.
Okay, swapping variables again. What replaces pressure and volume this time?
Instead of pressure and volume, or force and length, we substitute the electrical driving force.
Which is voltage,
Yeah.
denoted as E in the text, right?
Yes, and the amount of electrical charge moving through the system.
Wait, let me push back on this for a second.
Yeah, go ahead.
Why do we need a complex thermodynamic equation for a battery? Isn't the energy of a battery just its voltage?
You would think so.
Like, if I buy a 9-volt battery, doesn't that number tell the whole story of its internal energy?
It seems logical that the voltage tells the whole story. But thermodynamics reveals a hidden layer of complexity here.
So what's the hidden layer?
The equation shows that the change in the internal energy of a battery isn't just a simple product of voltage and charge. A real battery gets warm when charge actually moves through it.
Oh, right. Because its internal energy is changing for two distinct reasons simultaneously.
First, the chemical reaction is doing actual work on the outside circuit, pushing the charge along.
But second, the battery is physically generating heat through internal resistance and chemical inefficiencies.
Exactly. The thermodynamic equation captures that hidden heat.
It relates the thermal energy of the battery directly to the way its voltage fluctuates depending on the ambient temperature.
And the text points out a remarkably practical trick that stems from this relationship.
Right. Imagine you are a chemist tasked with measuring the exact total energy required to produce a highly specific, complex chemical reaction.
Measuring raw heat output from a chaotic chemical reaction sounds like a laboratory nightmare.
Oh, it is incredibly messy. Heat escapes into the room, the glass beakers get warm, it's just super inefficient.
But thermodynamics gives the chemist a brilliant hack.
Tell them the hack.
Instead of measuring the heat directly, you just build an electrical battery cell that runs on that specific chemical reaction.
You wire it up, but you don't even draw any charge from it.
Nope, you just attach a voltmeter. Then you simply observe how that baseline voltage changes as you slowly alter the temperature of the room.
So by just watching how the resting voltage reacts to the room temperature without the battery actually powering anything, the math allows you to calculate the precise internal energy of the chaotic chemical reaction happening inside.
Because the macroscopic laws demand it.
The equations relating temperature, voltage, and internal energy hold absolutely true regardless of the messy microscopic chemistry happening in the acid bath.
But that actually brings up an interesting contradiction in the text.
Oh, what's that?
Well, we have been praising this strict temperature and volume framework as the ultimate foolproof way to decode the world.
Yeah, we have.
But the text makes a rather funny admission at this point. Chemists, by and large, completely refuse to use these specific equations.
Wait, really? Why?
They use a completely different set of thermodynamic variables.
But if Feynman's method is so mathematically perfect, why do the chemists reject it?
It comes down to the dangerous reality of physical laboratories versus the clean safety of theoretical physics.
Ah!
Remember, our entire framework relies on holding volume strictly constant. In a theoretical thought experiment, keeping a gas at a constant volume is trivial.
You just imagine an infinitely strong, rigid metal box.
Right. But in a real chemistry lab, experiments are happening in glass beakers.
Uh-oh.
Yeah. If a chemist initiates a vigorous reaction that produces gas, and they seal the glass beaker to force the volume to stay mathematically constant.
The pressure builds up rapidly, and the glass beaker just explodes into shrapnel.
Exactly. It is technically difficult and highly dangerous to force volume to stay constant during a volatile physical reaction.
What is much safer and infinitely easier for chemists is to keep the pressure constant.
Because most chemistry happens in beakers open to the air.
The pressure on the reaction is simply the constant, unyielding weight of the Earth's atmosphere pushing down on the laboratory.
So how do chemists fix the math to account for an open beaker without breaking the universal laws we just established?
Well, they employ a very clever mathematical and conceptual trick. The text shows how you take the core equation for internal energy and you just add the product of pressure and volume to it.
And this isn't just abstract math, right? There is a physical reason for it.
Definitely. When a chemical reaction in an open beaker creates a gas, that gas has to expand.
To expand, it literally has to push the entire Earth's atmosphere up and out of the way to make room for itself.
And pushing the atmosphere out of the way requires physical work. It costs energy.
Exactly the point. By adding pressure times volume to the internal energy, the chemists are creating an accounting trick.
It perfectly tracks the mechanical work done pushing against the atmosphere.
And they give this new hacked variable a name.
Enthalpy.
Enthalpy, yes.
So when chemists talk about enthalpy, they are basically using a customized version of internal energy that automatically pays the atmospheric push tax so their glassware doesn't explode.
That is a highly practical way to look at it, yes. It shifts the independent variables from temperature and volume, which physicists love, to temperature and pressure, which keeps chemists alive.
Fair enough. But regardless of whether you are a physicist locking down volume or a chemist relying on pressure, the text points out that eventually both disciplines have to confront the concept of the ideal gas.
The theoretical perfect gas is the ultimate testing ground for these equations.
Because from the microscopic perspective of kinetic theory, we know that for a perfect ideal gas, its internal energy depends only on the motion of its molecules.
It only depends on temperature.
Right. So if you change the volume of an ideal gas, say you expand the box but somehow keep the temperature perfectly the same, the internal energy of the gas doesn't change by a single joule.
Which means that entire partial derivative from our intimidating equation, the one tracking the change in internal energy with respect to volume, simply collapses to zero.
And when you plug a zero into our core macroscopic equation, it simplifies beautifully.
It mathematically proves that for an ideal gas, pressure is strictly and linearly proportional to temperature.
Which leads to what might be the biggest mind-bender of the entire chapter.
Oh, the two temperatures.
Yes. The text stops everything to ask a monumental question. When we say pressure is proportional to temperature, which temperature are we actually talking about?
It sounds like a trick question, but it exposes a massive historical and scientific coincidence.
We actually have two completely different independent definitions of temperature running in parallel in physics.
We have the microscopic definition, which the text calls the kinetic temperature.
This assumes temperature is nothing more than a direct measurement of the kinetic energy of atoms bouncing around in space.
But on the other side, we have the temperature we derive from the Carnot cycle and the PV diagrams.
The text calls this the grand thermodynamic absolute temperature.
Right, and this definition relies entirely on the macroscopic laws of heat engines and efficiency. It has absolutely nothing to do with atoms or molecules.
Humanity arrived at two independent temperature scales from two completely different directions.
But when Feynman simplifies that core equation with the ideal gas, it proves mathematically that the pressure of a gas is directly proportional to both definitions.
The kinetic scale and the macroscopic scale are perfectly proportional to each other.
It is a stunning alignment of physical reality. The microscopic chaos of atoms and the macroscopic laws of heat engines perfectly agree.
And as the text jokes, humanity actually did something scientifically sensible for once.
Shocking, I know.
When setting up our standard units, we chose the proportionality constant to be exactly 1, ensuring the two distinct temperature scales perfectly coincide forever.
We could have easily ended up with two completely separate temperature scales that required messy conversions.
But the universe allowed us to make them the same. It's a really satisfying resolution.
It is.
So we've seen how this framework conquers perfect ideal gases, the mechanical elasticity of rubber bands, and the hidden heat of batteries.
But the physical world gets much messier than that.
Let's look at phase changes. What happens to our equations when a liquid literally boils and turns into a gas?
To handle phase changes, the text introduces us to the Clausius-Clapeyron equation.
Imagine you have a cylinder with a piston, but instead of a perfect ideal gas inside, you have a condensable vapor.
Think of steam hovering over a puddle of liquid water.
Okay, returning to our mental PV diagram. Pressure on the vertical axis, volume on the horizontal.
If we push the piston down to squeeze the pure liquid water, the volume barely budges, but the pressure shoots straight up like a rocket.
Because liquids are incredibly stubborn and hard to compress.
Exactly. But if we reverse course and pull the piston out, expanding the volume, the pressure drops rapidly until it hits a very specific critical point.
The boiling point. The liquid begins to boil, and vapor starts rapidly forming in the newly created space.
And the graph does something very strange at this exact boiling point.
The curve goes completely flat. It forms a perfectly horizontal line.
That flat horizontal line represents physical equilibrium.
Meaning, at that specific pressure and temperature, you have liquid molecules escaping into vapor, and vapor molecules crashing back into the liquid at the exact same rate.
It's a molecular tug-of-war, perfectly balanced.
If you pull the piston out further to increase the volume, you just create more empty space, so a little more liquid evaporates to fill the void.
But the pressure inside the cylinder, it doesn't drop. It stays absolutely rock solid.
The pressure holds constant on that flat line until every last drop of the liquid has vaporized into steam.
Only then does the pressure start to drop again as the volume expands.
So that flat horizontal line becomes the perfect testing ground for our Carnot cycle.
We can take a tiny trip along that flat line, looking at the heat required to boil the liquid, the latent heat, and the mechanical work done as the expanding vapor pushes the piston.
Applying the Carnot cycle to that flat line yields the Clausius-Clapeyron equation.
It creates a direct, infallible mathematical link between the rate at which vapor pressure changes with temperature and the amount of latent heat required to evaporate the substance.
And Feynman uses this equation to demonstrate the ultimate superpower of macroscopic thermodynamics over microscopic kinetic theory.
If you try to use kinetic theory to calculate how a liquid boils into a gas, you are forced to guess at the insanely complex interactions of trillions of molecules tugging at each other.
You have to make massive approximations about their internal energy states.
Kinetic theory, at best, gives you an approximate, messy answer.
But the Clausius-Clapeyron equation doesn't care about the trillions of molecules.
Not at all. Derived entirely from the macroscopic behavior of heat and volume, it is exact.
You don't need to model the molecular tug-of-war to know the macroscopic relationship holds perfectly true.
And the exact same logic applies to melting a solid block of ice into water.
The molecular lattice dynamics of ice melting might take a supercomputer to model accurately, but the thermodynamic equation linking pressure, temperature, and latent heat gives you the exact parameters instantly.
We have one final scenario from the text to cover, though.
Right. A situation that pushes thermodynamics to its absolute limit, dealing with something that isn't solid, liquid, or gas.
We need to talk about blackbody radiation.
Blackbody radiation involves analyzing light itself as a thermodynamic substance.
Imagine a completely sealed, perfectly insulated box. We pump out all the air, all the liquid. The box contains absolutely nothing but electromagnetic radiation.
Trapped photons bouncing endlessly off the walls.
But how can we apply equations built for steam engines and volume changes to a box of trapped light?
We have to acknowledge that light exerts a physical force.
Think of a room entirely coated in mirrors, filled with millions of bouncy balls moving at the speed of light.
Every time a ball ricochets off a mirror, it imparts a tiny mechanical push.
Photons do the exact same thing. They exert radiation pressure on the walls of the box.
And the text provides the known physics formula for that pressure.
The radiation pressure multiplied by the volume equals exactly 1/3 of the total electromagnetic energy trapped in the box.
Armed with that formula for pressure, we simply plug it directly into our trusty universal thermodynamic equation.
The exact same equation we use to calculate the shrinkage of the rubber band and the voltage of the battery.
We look at the physical work required to expand the mirrored box against the outward push of the light pressure and how that relates to the internal energy.
Taking that relationship and integrating the differential equation it spits out reveals something monumental about the shape of the universe.
The math proves that the total energy density of the trapped radiation varies as the fourth power of the temperature.
It scales as T to the fourth, which is an exponentially massive realization.
It dictates that if you merely double the temperature of a glowing object like a star, the total energy it radiates out into space doesn't just double.
It increases by a factor of 16.
But the text is very clear about the limitation of our thermodynamic toolkit here.
Oh yes, the macroscopic math proves, without a shadow of a doubt, that the relationship is an exponential curve of T to the fourth.
But thermodynamics is fundamentally incapable of telling us the actual numerical constant that goes in front of that t.
It gives us the precise shape of the curve, but not the starting point.
To find the exact specific number, the Stefan-Boltzmann constant, which is 5.67 times 10 to the negative eighth, we must finally abandon the macro and dive deep into the microscopic.
We have to use quantum mechanics to integrate the actual discrete frequencies of light using Planck's constant.
Thermodynamics maps out the overarching architecture of the universe's rules.
But quantum mechanics has to step in at the very end to fill in the exact numerical values.
It is the ultimate scientific partnership.
It truly is.
So what does this deep dive mean for you?
It means you don't need a degree in theoretical physics to appreciate the hidden architecture of the physical world.
We started in a jungle of confusing variables surrounding steam engines, and we discovered a single, elegant core concept.
A macroscopic relationship between temperature, volume, pressure, and internal energy that simply cannot be broken.
The next time you stretch a rubber band and feel it warm up against your skin, or you notice the back of your laptop getting hot while it processes data, you aren't just experiencing random thermal noise.
You are experiencing the exact same infallible universal rulebook that dictates the flatline equilibrium of boiling water.
And the exponential T to the fourth radiant glow of a distant star.
Which leaves us with a fascinating thought to consider.
If thermodynamics is so incredibly powerful, if it can give us exact, unbreakable mathematical rules for complex systems like boiling liquids and trapped light, without requiring us to know anything about the invisible microscopic mechanisms driving them.
What other incredibly complex, chaotic systems in our world might be secretly governed by these exact same macroscopic laws?
What wildly complex biological ecosystems, or even global economic markets, are just waiting for us to discover the right abstract pressure and volume variables to completely decode their behavior?
It's definitely something to mull over the next time you stretch a rubber band.
It really is. Thanks for taking the deep dive with us.
Imagine you're trying to lift a tiny flea. Like you've got this microscopic string, and you're trying to lift it using literally nothing but the random, invisible jiggling of warm air around it.
Which sounds completely ridiculous, right?
Yeah, it sounds like some kind of weird cartoon setup. But
Yeah.
what if figuring out why that exact, cartoonish machine fails actually holds the absolute secret to the arrow of time? And, the literal birth of our entire universe.
It really does. It's wild.
Welcome to a brand new deep dive. Today we are exploring a really famous concept. We're looking at notes and diagrams from chapter 46 of the legendary Feynman lectures on physics.
Oh, such a great source text.
Right, and we're going to focus on this deceptively simple little gadget called a ratchet and pawl. Our mission today is to figure out how this tiny imaginary mechanical gadget holds the key to, well, the biggest mysteries of reality.
Yeah, and to really get our heads around this, we need to picture the setup. So imagine a tiny microscopic box filled with gas. And this gas is just at a specific temperature. Inside this box, there is an axle. And attached to that axle are these little flat vanes. They're almost like the paddles on an old school riverboat.
I can picture that.
And that axle extends out through a hole in the box and connects to a ratchet. Now, if you're looking at figure 46:1 in the text, a ratchet is just a gear wheel, but with asymmetrical jagged teeth.
Right, they're slanted.
Exactly. And resting against those teeth is a pawl. It's basically a little spring-loaded lever that clicks down into the grooves, mechanically forcing the wheel to turn in only one direction.
Okay, let's unpack this, because at first glance, this setup looks like a literal cheat code for infinite free energy.
It really does seem like a loophole.
Because, the gas molecules inside the box are warm, and heat at a microscopic level is literally just movement. So you have all these molecules zipping around in total chaos.
Brownian motion.
Right, Brownian motion.
Yeah.
They're just constantly battering into the paddles.
Yeah.
And they are trying to spin that axle in both directions at the same time. But because the ratchet and the pawl on the outside only allow the wheel to turn forward.
They block the reverse movement.
Exactly. All the backwards bumps just hit a wall. But all the forward bumps actively push the wheel ahead. So slowly but surely, click by click, the wheel turns.
Yeah.
And then we tie our little flea to the string on the axle, and up it goes. We are extracting usable directed work out of ambient heat, which is supposed to be completely illegal according to the second law of thermodynamics.
Oh, it directly violates the foundational rule of thermodynamics.
Yeah.
You just cannot generate useful work from a heat source if everything in your entire system is resting at the exact same temperature.
But setting it up the way we just described makes it seem completely foolproof.
It does.
So I really want to push back on the physics here. If the gas is providing the chaotic pushing and the mechanical ratchet is providing the structural stopping, why doesn't this perpetual motion machine work?
Well, like, think about a subway turnstile that only spins one way. If you pack a station with a massive, completely chaotic crowd of people just surging randomly back and forth, their random collisions against the turnstile will eventually push it forward.
Sure.
Because they physically cannot push it backward. The mechanics of the turnstile force order out of the chaos. So why doesn't the microscopic version work?
Okay, so that works perfectly for a human-sized turnstile because, well, a turnstile is massive, right?
Right.
It's rigid
Yeah.
and it's physically cold compared to the kinetic energy of a crowd of humans.
Right. The metal isn't jiggling around on its own.
Exactly. But scale that logic down to the microscopic level of our gas box. The ratchet, the wheel, the pawl, they're all microscopic. And more importantly, they're sitting in the exact same thermal environment as the gas.
Oh.
They are completely bathed in that ambient heat.
Wait, meaning the metal of the gear isn't some cold, rigid object. It's hot, too.
Yes. It has its own Brownian motion.
Yeah.
At the microscopic scale, heat means everything is violently vibrating.
The pawl isn't just sitting there patiently waiting for a gear tooth to slide by. It is shaking and jiggling and bouncing up and down uncontrollably because it's being relentlessly bombarded by the surrounding heat energy.
That makes so much sense.
And to make the pawl work, you have to add a spring to push it down, right? And a way to dampen its bouncing so it doesn't just flap wildly in the breeze. But damping mechanisms absorb kinetic energy and turn it into, you guessed it, more heat.
So the entire locking mechanism is basically just vibrating wildly, essentially trying to shake itself apart.
Exactly. And that vibration creates a fascinating balance of probabilities.
How so?
Well, it takes a very specific, measurable amount of energy to lift the pawl up and over a gear tooth against the pressure of its spring. The text calls that energy threshold epsilon.
Okay, epsilon.
Right. And the probability that the gas molecules randomly hit the paddles hard enough to generate epsilon and push the wheel forward, that probability is exactly matched by the probability that the pawl itself, just through its own random thermal shaking, accidentally bounces up with that exact same epsilon amount of energy.
Wait, really? So at the exact moment, the gas molecules randomly swarm the paddles, trying to push the wheel backward. The locking lever just happens to be randomly floating up in the air.
The math breaks it down beautifully. The number of times the pawl accidentally bounces up, allowing the gear to slip freely backward, perfectly equals the number of times the paddles get enough coordinated energy to turn it forward.
That is incredible.
It takes a step forward, the pawl bounces, it slips a step backward, forward, backward. The net movement over time is absolute zero. The flea just dangles there.
So the mechanics are completely defeated by their own temperature.
Exactly.
But, I mean, that naturally leads to the next question.
Mm-hmm.
If equality is what kills the machine, what happens if we introduce inequality? Like, what if we rig the system so the temperatures are different?
Well, now we are talking about creating a heat engine.
Let's set the scene for the listener. Imagine we keep the paddles inside a box of boiling hot gas, but we build the axle extremely long so the ratchet wheel and the pawl sit far away in an entirely different box filled with freezing cold gas.
What's fascinating here is that the machine suddenly springs to life.
Really?
Yeah. The hot gas is violently bombarding the paddles, easily gathering enough collective energy to push the wheel forward. Meanwhile, the pawl is freezing cold.
So it's not jiggling anymore.
Right. Its thermal fluctuations are totally suppressed. It's rigid. It rarely ever bounces up by accident.
So the ratchet clicks forward smoothly, doing exactly the work it was designed to do.
It does. It officially extracts work by transferring heat from the hot side to the cold side. Every time the cold pawl snaps down against a tooth, it clatters, generating a tiny bit of heat, which is then absorbed by the cold gas. The thermodynamics perfectly align with Carnot's equations.
Okay, so it works. But here's where it gets really interesting, because I want to flip this around, as this is the part of Feynman's logic that just totally bends the mind.
Oh, this is the best part.
What if we reverse the environments? What if the paddles are sitting in freezing cold gas, but the mechanical ratchet and pawl are sitting in a furnace? Wait, If the wheel is hotter, does it just stop working entirely?
You would assume the heat just breaks it, right? But no, a hot ratchet actually runs backwards.
Backwards. Hold on. The physical teeth of a ratchet are literally slanted to prevent that.
Yeah.
It is mechanically shaped to be a one-way street. Are you saying the heat literally overpowers the physical geometry of the gears?
It actively rebels against its own geometry. Just think about what that intense heat is doing to the pawl. It is bouncing up and down violently.
Because of the Brownian motion again?
Exactly. Every single time it comes crashing down, it hits the slanted, inclined plane of the gear tooth. It's essentially a microscopic hammer pounding down on a slide.
Oh, I see where this is going.
And since the paddles on the other side are in freezing gas, they offer almost zero resistance. So the violent, frantic bouncing of the hot pawl, constantly pushing against those slanted teeth, actually drives the wheel in the exact opposite direction it was designed for.
That is wild. I mean, think about trying to push a heavy door the wrong way against its hinges. You just can't do it. But imagine the door getting so hot that the hinges just give up and the door swings backward under the pressure. The machine is actively defying its own engineering.
The text mentions figure 46.2 to show how unsymmetrical the system is. If you physically grabbed that axle and tried to pull it backward by force against the pawl, you could hang a massive weight on it and it would barely turn.
Right, the mechanical resistance is huge.
But if you just let the temperature difference do the work, heating up the gear and cooling the paddles, it glides backward effortlessly.
It's crazy.
It's like an electrical rectifier in a circuit, allowing current to rush one way but completely blocking it the other, purely based on where the heat is.
So dumb metal, gears, and springs are ultimately useless if they get too hot. They either freeze up or they run in reverse. But what if we outsmart the metal?
What do you mean?
Well, if the problem is dumb mechanics absorbing heat, could we replace the gears with something intelligent? Like, could some kind of tiny brain sort the hot from the cold without doing physical work?
This brings us right to the doorstep of Maxwell's demon.
Right. The physicist James Clerk Maxwell came up with this famous thought experiment. Imagine a tiny, intelligent demon sitting at a microscopic hole between two separate boxes of gas.
And he's just watching the molecule.
Exactly. This demon just watches the molecules flying around. I always joke that he'd need eyes in the back of his head to watch both sides at once. But anyway, whenever a fast, hot molecule approaches from the left, the demon opens a tiny door and lets it slip into the right box.
Yeah.
And when a slow, cold molecule approaches, the demon keeps the door closed. Over time, without the demon doing any real physical pushing, all the fast, hot molecules are collected on one side and all the cold ones on the other.
Which would, again, allow us to spontaneously create a temperature difference out of nowhere, shattering the laws of physics.
But a demon is magical. We don't have magical demons. So what if we just build a microscopic, spring-loaded mechanical trapdoor instead?
Like a physical flap.
Yeah. We design it so that only a fast-moving molecule hits it hard enough to blast the door open and slip through. The slow molecules hit it weakly, and the door stays shut, bouncing them back. Doesn't that beat the system without needing a brain or a demon?
It really looks like a brilliant loophole, but the mechanical trapdoor is just the ratchet and pawl wearing a different hat.
Oh, really?
Yeah, it suffers from the exact same microscopic reality.
How so? The door doesn't have a brain to get confused.
Because the door is made of matter. It has a finite heat capacity. As those fast, hot molecules smash into your trap door to push it open, they transfer some of their kinetic energy into the door itself.
Ah, right. The door absorbs the impacts. The hinge absorbs the impact.
It starts to heat up.
Rapidly, I'm guessing.
Exactly. And because it cannot endlessly dissipate this heat into a vacuum, the mechanical parts start vibrating from Brownian motion. The spring gets hot and loses its strict tension. The hinge starts jiggling.
So it's basically falling apart again.
Soon, the trapdoor is flapping open and closed completely on its own, violently vibrating.
So a slow molecule just casually drifts by, and the door happens to be vibrating wide open, so it just wanders right through.
Precisely that. The door becomes thermally blinded. It shakes so violently that it can no longer distinguish between a fast molecule purposefully pushing it open or its own thermal jiggling randomly throwing it open.
Wow.
It begins letting fast and slow molecules through indiscriminately in both directions. The sorting completely stops, the system reaches equilibrium, and the second law remains undefeated.
The trapdoor essentially gets too hot to think. It's a profound realization when you step back. The demon, the ratchet, the trapdoor, they all fail for the exact same reason.
Heat always wins.
It does. Heat ultimately mixes everything up. It ruins any attempt to separate things. And this leads us to a massive, glaring contradiction in how we understand the world. If every microscopic collision between molecules is perfectly reversible, why is the macroscopic world you and I live in irreversible?
This is the reversibility paradox. It sits at the absolute core of physics.
Think about your morning routine. Imagine you drop an egg on the floor or you pour a splash of milk into your black coffee. If you film that and play the video backward, it looks hilarious. It's obviously impossible.
Right, a scrambled egg doesn't magically levitate off the tile, unscramble itself, and seal back into a perfect shell.
And the milk doesn't separate out of the coffee and leap back into the carton.
No, the irreversibility of our daily reality is incredibly obvious to us.
If you zoom way, way in down to a single collision between two individual molecules of that egg, or two molecules of that coffee, and you film just that one microscopic collision, playing that film backward looks completely normal.
It does.
Two billiard balls bouncing off each other look exactly the same, whether time is moving forward or backward. Newton's laws of motion don't care about the direction of time.
They really don't.
So how do trillions of perfectly reversible microscopic events somehow add up to an irreversible one-way macroscopic event?
Feynman illustrates this beautifully with a classic thought experiment. Imagine a box divided straight down the middle by a barrier. On the left side, you have neon gas. Let's just visualize them as black molecules. On the right side, you have argon gas white molecules.
Okay, a perfectly orderly system. Black on the left, white on the right.
Highly ordered. Now you pull the barrier out. We all know what happens next. The gases mix. The white molecules bounce their way into the black side. The blacks bounce into the whites. And eventually, you are left with a uniform gray mixture of gas filling the entire box.
Right.
Now, this mixing process is made entirely of those perfectly reversible microscopic collisions you just mentioned.
Meaning, if you could somehow hit a cosmic pause button and magically reverse the velocity and direction of every single molecule at the exact same instant, they would all bounce backward, retrace their exact paths, and flawlessly unmix themselves back into the separated black and white halves.
Exactly. It would look like absolute magic, but structurally, it obeys every single law of physics.
So why don't we ever see coffee unmix or gas unmix naturally?
Well, this brings us to the true nature of entropy. People often use entropy as a vague, poetic synonym for messiness or decay, but it's actually a strict mathematical measure of probability.
Break that down for me. How does probability prevent my coffee from unmixing?
Think of it like shuffling a brand new deck of cards. When you open the box, the deck is perfectly ordered by suit and number. There is exactly one way to arrange the cards to achieve that specific perfect order.
Just one.
But once you start shuffling, there are billions, trillions of ways to arrange those cards where they just look like a randomized, jumbled mess.
So entropy isn't a physical force pushing the cards around, it's just the math.
Yes. There are relatively few ways to arrange the gas molecules so all the black ones stay on the left and white on the right. But there are nearly infinite ways to arrange them where they overlap and look like a gray mixture.
Wow.
Irreversibility is simply the inevitable statistical slide from a highly restricted state, which we call order, to a highly probable state, which we call disorder.
Right.
So every individual molecule's path could technically be reversed, but the sheer mind-bending mathematics of probability dictate that returning to that one specific separated state is statically impossible, even if you waited 1 trillion lifetimes of the universe.
Exactly. It's just a numbers game.
So what does this all mean for you, the listener? If the natural flow of reality is to constantly slide from ordered states into disordered, probable states, why did we ever have an egg to drop in the first place?
That is the million-dollar question.
Why did we have unmixed coffee or cold ratchets?
Right.
If everything wants to be a mixed-up gray soup, is the order we see around us right now just a lucky, random fluctuation in a mostly chaotic universe? Physicists wrestled with that exact idea for a long time. The fluctuation theory suggests that maybe the universe is, generally speaking, just a high-entropy, chaotic gray soup. But given infinite time, probability says that eventually, randomly, things will bounce into an ordered state.
Like the infinite monkey theorem. If 1,000 monkeys mash on typewriters for eternity, eventually one of them accidentally types out Shakespeare.
Right.
So maybe our entire solar system, our planet, our perfectly ordered biology is just the universe accidentally typing Shakespeare for a brief moment before it decays again.
It's an incredibly tempting theory, but if we connect this to the bigger picture, it completely falls apart.
Why? If time is infinite, wouldn't every possible fluctuation happen eventually?
Yes, but it's about what that theory predicts we should see today. If our world is just a localized random bubble of lucky order, we shouldn't expect to find order anywhere else.
Oh, because random fluctuations are incredibly rare.
Exactly. If you look out your window and see a neatly organized city block, and you assume it's just a random, lucky fluctuation of atoms, you would safely bet that the next town over is back to total chaos. You wouldn't expect the luck to hold.
Right.
But what happens when astronomers look through telescopes? They point them at new stars, new galaxies, billions of light years away.
And they see the exact same ordered physics. They see galaxies spinning, stars burning, planets forming. They don't see the chaotic gray soup.
They see immense, staggering order everywhere we look in the cosmos. Therefore, our universe cannot possibly be a random, localized fluctuation. The order we see today in the stars, in the trees, in the cells of your body is a memory.
A memory.
It is a lingering echo of a time when the entire universe began in a state of unimaginably low entropy.
The Big Bang.
Yes. The universe was born in a state of extreme, tightly wound order. And the entire history of existence since that spark has been the slow, irreversible unwinding of that cosmic clock.
That is profoundly beautiful. And, brings us right back to our tiny Ratchet and pawl.
It really does.
Because the whole reason our little machine works as a heat engine is because it can dump its waste heat into a cold environment. It requires a temperature difference.
Exactly.
The Ratchet's ability to tick in one direction is fundamentally, inextricably tied to the entire universe's one-way unwinding. The machine only works because the universe provides a cold, expanding vacuum to absorb its heat.
The one-way nature of the tiny gadget is a direct mirror of the one-way nature of the cosmos. If you put that ratchet in a perfectly sealed box and waited 1,000,000 years, it would eventually heat the box until everything was the exact same temperature and the machine would die.
Wow.
It only functions because we open the shades, let the heat escape, and cool off into the vastness of space. And Feynman points out that you can see this cosmic history in practically any everyday object.
Right. He uses the example of a glass of wine, doesn't he?
He does. If you look closely enough at a glass of wine, the complex biology of the grapes, the fermentation process, the glass itself, the light refracting through the liquid, you are looking at a direct, unbroken chain of events cascading down from the universe's initial low-entropy state.
What an absolute trip. I mean, we started out trying to cheat nature by lifting a tiny flea using the random jiggling of gas molecules.
And we went everywhere from there.
We realized that hot machines don't just break, they aggressively rebel and run backward. We learned why microscopic trapdoors get too hot and blind to do their jobs. And ultimately, we discovered that every one-way street in our lives, every shattered glass, every scrambled egg, every ticking clock is powered by the lingering, cooling echoes of the Big Bang.
It's just incredible. And I want you, the listener, to carry this perspective with you today. Look around at everything that decays, mixes, or cools down. When you pour milk into your coffee and watch it swirl, or watch a piece of fruit ripen on the counter, recognize it as more than just a mundane morning routine. You are watching a microscopic manifestation of the universe's grand timeline. You are watching the arrow of time in real time.
I love that. The universe unwinding in your coffee cup. And it leaves me with one final, deeply unsettling thought for you to ponder.
Oh, lay it on me.
If our entire perception of time moving forward is just our physical brains experiencing this transition from order to disorder, what happens trillions of years from now?
Oh, wow.
When the universe finally reaches maximum entropy, when it is nothing but a uniform, tepid, gray soup with no more order left to lose and our cosmic ratchet finally stops turning for good, will time itself simply cease to exist? Something to think about the next time you try to lift a flea. We'll catch you on the next deep dive.
You know, usually when we talk about hearing a sound, there's this expectation of instant magic, like sending a text message, right?
Yeah, it feels totally binary. It's either silent or there's noise filling the room.
Exactly. A speaker vibrates somewhere in the room, and your brain just instantly registers a melody or a voice. We tend to picture this direct, unbroken line from the source straight to your ear.
Well, step into the world of fluid mechanics and kinetic theory, and that simple, clean line is just completely shattered.
Oh, completely. Because we're looking at a space between a speaker and your ear that is filled with absolute microscopic chaos. I mean, trillions of air molecules just colliding with each other at hundreds of miles an hour.
Right. It is the absolute definition of invisible mechanical turbulence.
Which makes the physics of what you are listening to right now so incredibly beautiful. So welcome to today's custom deep dive. Today we are looking at chapter 47 of the truly iconic Feynman lectures on physics, volume 1.
And the topic on the table today is sound and the wave equation.
Yes, and our mission here is, well, we aren't just going to list facts about sound. We are going to rebuild the phenomenon of sound from absolute scratch.
We really are. We're going to decipher the secret life of those moving air molecules, explore how invisible waves survive that chaos to travel through space, and uncover a rather famous mistake made by none other than Sir Isaac Newton.
I can't wait for that part. And we're going to do all of this using nothing but the fundamental laws of mechanics.
Yeah.
For me, the real hook here is how incredible physics is at connecting the dots.
Oh, definitely.
Like the exact same mathematical rules we're going to discuss today for sound, they also govern massive ocean swells and even the quantum matter waves of subatomic particles. It's just a universal language.
It really is. But before we can actually build a sound wave from the ground up, we really have to define what a wave fundamentally is, both in space and in time.
Right, getting our definition straight.
Exactly. The Feynman text takes care to categorize the different types of waves to give us a solid foundation. Sound, for instance, is a compressional wave.
Meaning what, physically?
It means the air particles are oscillating back and forth along the exact same direction that the wave itself is traveling.
So pushing and pulling in a straight line rather than waving up and down like a plucked guitar string.
Precisely. That up and down motion is a transverse wave.
Mm-hmm.
And then you have those quantum matter waves you mentioned earlier, which are entirely different. They deal with waves of probability, showing where a particle might be found.
Wow, okay. But across all these types, the defining characteristic is the same, right?
Yes. A wave is an oscillation that propagates, it travels.
Okay, let's unpack this a bit, because oscillations that propagate still sounds a little, textbook to me.
Oh, enough.
How do we visualize this mathematically without getting totally bogged down in jargon? Is a wave just a moving picture, like a flip book?
Actually, that is a brilliant way to think about it. If we look at figure 47.1, figure 47.2 in the source material, Feynman introduces this deceptively simple mathematical function to describe a one-dimensional wave.
Okay, I promise we wouldn't throw raw equations without explaining them, so walk me through it.
So the function is f of x minus ct.
Okay.
Imagine taking a snapshot of a zone of high air pressure in the room. You just freeze time. That physical shape of the pressure zone, plotting how pressure rises and falls across the distance, is our function f of x.
I have my snapshot. It looks like a little hill on a graph.
Perfect. Now unfreeze time. As time passes, it's the t variable, that exact same hill shape shifts perfectly intact over a distance.
Okay, and that distance is what?
It's determined by the speed of the wave, c, multiplied by the time, t. So the expression x minus ct is just the mathematical way of saying our snapshot is sliding to the right, completely unchanged in its shape.
Oh, I see. It's just panning the camera across the screen. The hill doesn't flatten out or get spiky. It just moves.
Exactly.
Ah.
And understanding that sliding shape leads us to a crucial mathematical property of waves, which is the principle of superposition.
Superposition. Okay, what does that mean in plain English?
It means if you have two different moving shapes, say F1 and F2, and they happen to cross paths, they can occupy the exact same physical space at the exact same time.
They just cram into the same spot.
Basically, yeah. They just
Right.
add their values together. They don't bounce off each other or destroy each other. They pass right through one another, temporarily combining, and then keep going as if nothing happened.
Okay, wait. Does this explain why I can hear, the high notes of a piccolo and the booming low notes of a tuba at the exact same time at a symphony?
It explains it perfectly.
I've always wondered how the air handles all those different noises at once without just turning into mush.
Well, because of superposition, and because sound waves travel at the same speed, regardless of their frequency, all those different pressure shapes from the orchestra just stack on top of each other.
They just literally add up.
Right. They merge into one incredibly complex, jagged shape in the air, travel across the concert hall, and arrive at your ear perfectly intact.
That is wild, because if high and low frequencies traveled at different speeds,
Oh, it would be a mess.
Yeah. A short, sharp clap would stretch out and reach me as this bizarre sequence of drawn-out musical notes.
It would be complete auditory chaos. Imagine if red light and blue light separated in the air like that. A flash of white light would reach you as a slow rainbow over time.
This sounds kind of beautiful, but terrible for trying to see anything.
Exactly. The fact that wave speed in these mediums is independent of frequency is what allows our senses to process the world with complete fidelity.
Right. Now, we also have to mention what happens when these waves interact over time, not just in space. because the text brings up a really cool phenomenon called beats.
Ah, yes. Figure 47:1 illustrates this concept of interference in time. Usually we think of waves interfering in space, like two distinct ripples on a pond crashing into each other.
Sure.
But imagine you have two tuning forks side by side, and one is vibrating just slightly faster than the other.
So they have slightly different frequencies.
Right. When you listen to both of them simultaneously, their sound waves will temporarily align crest to crest, making the sound louder.
Okay, because of that superposition we just talked about.
Exactly. But because one is slightly faster, they will gradually drift out of sync until a crest aligns with a trough, which cancels the sound out entirely.
Oh, so the volume literally pulses up and down like, what?
You got it.
Hmm.
That rising and falling is called a beat. It is a direct result of two mathematical shapes, adding and subtracting from each other purely as a function of time.
Which is mind-blowing, but, it brings up a massive physical problem for me.
What's that?
If sound behaves like this elegant, unbreakable, mathematical moving shape, how does a chaotic jumble of air molecules actually pull this off?
It does seem contradictory.
Right. Because air molecules are bouncing around randomly, they are constantly colliding. If there's a pocket of high pressure in one spot, our mathematical hill, wouldn't the molecules just instantly rush out in all directions and smear the shape into nothing?
You would think so.
So how does the wave survive the chaos?
The secret is entirely about scale. You really have to zoom out. The text introduces a critical concept to bridge this gap, called the mean free path.
Mean free path, what exactly does that measure?
It is the average distance an individual molecule travels before it smacks into another molecule.
Okay.
Imagine a crowded room where everyone is walking around blindfolded. You won't get far before bumping into someone. That short, chaotic distance is the mean free path.
Huh. Okay, I am definitely picturing the blindfolded room.
Now, for a sound wave to exist and maintain its shape, the distance between the wave's crests and troughs, its wavelength, must be vastly larger than this mean free path.
So wait, the sound wave is like a giant stadium wave rolling through the stands, and the mean free path is just the tiny distance individual people are shifting in their seats.
That is a phenomenal analogy.
Us.
Because the wavelength of the stadium wave is so huge, we aren't tracking individual blindfolded people.
We don't care about a single molecule bouncing around.
Exactly. We are tracking the center of mass of small blocks of air. As long as the pressure changes happen over a large enough distance, the molecules can't just freely escape and smear the wave.
Oh, because they hit someone else first?
Right, they bump into their neighbors almost instantly and transfer their momentum forward.
Okay, so we are looking at the forest, not the bouncy ball trees. That sets the stage beautifully. We are dealing with blocks of air.
Yes, blocks.
So how do these blocks, physically, mechanics-wise, generate a sound wave?
Feynman breaks this down into three interconnected physical features. Let's trace the chain reaction, starting with displacement.
Okay, step one.
Referencing figure 47-3, imagine our imaginary block of air. If we push it, the block is displaced. The text uses the Greek letter chi to represent this movement.
Okay, I push the block. But how does moving a block create a wave? Doesn't that just create wind?
If the entire room of air moved perfectly together, yes, that's just wind. But what if the displacement varies with distance? What if you push the front of the block, but the back of the block hasn't started moving yet?
Ooh, the block gets squished. The front is catching up to the back.
Yes. The air inside is compressed. And because you are cramming the exact same number of air molecules into a smaller volume, the density of that block goes up.
Except
That is the first fundamental link. A change in displacement leads directly to a change in density.
which naturally leads to the second link.
Mm-hmm.
If we have more molecules packed into a smaller space, they're going to hit the imaginary walls of our block much more frequently.
Exactly.
That has to mean the pressure spikes.
It does. Step 2 is that a change in density corresponds to a change in pressure. But we really need to look at the numbers Feynman provides here, because they challenge our intuition about what a sound wave actually is.
Yeah, I always thought of sound waves as these forceful, violent things pushing against my eardrums. Especially something loud, like a rock concert.
Well, we live under a constant, heavy blanket of atmospheric pressure, which is about 1 bar. When you were listening to a fairly loud conversation, maybe around 60 decibels, how much do you think that sound wave shifts the baseline pressure of the room?
I don't know, I would guess maybe a few percent, like a noticeable fraction.
A 60 decibel sound only shifts the air pressure by 2 times 10 to the negative 7th bar.
Wait, 2/10 millionths of a standard atmosphere.
It is an unimaginably microscopic ripple riding on top of the massive crushing weight of the static atmosphere.
How do our ears even survive that kind of sensitivity? We are picking up changes that are fractions of a millionth of the baseline pressure.
The biological engineering of the human ear is staggering, really. But for our physics derivation, these incredibly tiny numbers are a massive gift.
Why is that?
Because the changes are so microscopic, the math stays incredibly clean. The excess pressure is directly proportional to the excess density. It forms a perfect straight-line relationship.
Okay, so let me recap. Step 1, we push the air, which changes the displacement. That squishes the block, which increases the density. Step 2, the higher density increases the pressure.
Right.
So what's step 3? How does that pressure keep the wave moving forward?
This is where Isaac Newton enters the chat with his second law of motion. Force equals mass times acceleration. Look at figure 47-4.
Okay, looking at it.
We have our squished block of air. Because it was squished from the left, the pressure is now slightly higher on the left side of the block than on the right side.
And high pressure naturally wants to push toward low pressure.
Exactly. It creates a net force pushing to the right.
Mm.
And according to Newton, applying a net force to a mass causes that mass to accelerate. So our little block of air accelerates forward, pushing into the next block of air.
Which squishes that next block, increasing its density, which spikes its pressure, which creates a new force that accelerates it into the next block.
It's a continuous chain reaction. The wave propagates.
The mathematical shape moves forward, even though the air molecules themselves are basically just wiggling back and forth in place.
You've just fully derived the mechanics of a compressional sound wave.
Wow. It is so satisfying to break it down like that without needing a PhD in fluid dynamics. But now we need to see how fast this wave actually moves. We have all these interlocking pieces: displacement, density, pressure, acceleration.
Feynman performs a grand mathematical synthesis here. By combining those physical links we just discussed, he shows how we can substitute the variables to eliminate pressure and density from the equations entirely.
Oh, because they are just middlemen.
Exactly. We are left with an elegant equation tying the acceleration of the air, how it moves in time, directly to how the displacement changes in space.
And that's the wave equation.
That is the wave equation. It proves, purely from Newton's mechanical laws, that a sound pulse will move through a gas at a constant, predictable speed, which we label c sub s.
Okay, but what dictates that speed limit? Why does sound travel at roughly 343 meters per second in the room I'm sitting in right now and not, say, 1,000,000 miles an hour?
Well, this specific question actually tripped up Sir Isaac Newton, one of the greatest mathematical minds in history. He made a famous blunder when trying to calculate the absolute speed of sound.
I genuinely love when the historical geniuses get things wrong. It just humanizes the whole process of science. What was his mistake?
Newton calculated the speed using the exact chain reaction we just built. But he had to make an assumption about how the temperature of the air behaved when the wave passed through.
Okay.
He assumed that when the sound wave squished the air, the temperature remained perfectly constant.
But wait, compressing a gas heats it up? I mean, anyone who has ever used a manual bicycle pump knows the bottom of the middle cylinder gets hot when you cram the air in.
Oh, Newton absolutely knew that compressing a gas generates heat.
So why did he assume it stayed constant?
Because he assumed that the heat generated by the squished air was instantly conducted away to the surrounding uncompressed air. He pictured the hot, high-pressure zone sitting right next to the cooler, low-pressure zone and figured the heat would just immediately flow out and equalize. He called it an isothermal process.
So he thought the heat leaked out before it could actually affect the wave.
He did. And based on that, he published his calculated speed of sound. But when experimentalists actually went out and measured the speed of sound in the real world, Newton's number was significantly too slow.
Ouch. So what was he missing? Why doesn't the heat just leak away?
It took over a century for the French mathematician Laplace to spot the error. Laplace realized Newton ignored the concept of scale that we talked about earlier.
The blindfolded room, the mean free path.
Exactly. The distance molecules travel between collisions is microscopic. But the wavelength of a sound wave is huge, and the wave is moving incredibly fast.
Ah, I see. So the heat simply doesn't have time to travel from the crest of the wave all the way to the trough.
Right. The wave is long gone before the heat can conduct across that vast molecular distance. Laplace proved that sound is an adiabatic process.
Adiabatic.
That's the physics term for a process where no heat is exchanged with the surrounding environment.
The sound wave traps its own heat. It squishes the air physically heats up, and that heat stays in the crest of the wave.
Exactly.
But why does a slight temperature bump make the sound wave travel faster than Newton predicted. What is the physical mechanism there?
Think about what heat actually is on a kinetic level. Heat means the molecules are moving faster.
Right, more kinetic energy.
So when our imaginary block of air gets squished, not only are there more molecules packed into the space, creating pressure, but those molecules are now hotter. They're zipping around faster, hitting the imaginary walls of our block with even more energy.
So you get a double whammy of pressure. You get pressure from the density plus extra pressure from the heat energy.
That extra pressure makes the gas act stiffer. It pushes back against the compression harder than Newton initially accounted for, and the stiffer spring snaps back faster.
Which accelerates the wave forward at a higher speed.
Exactly.
That is incredible.
Yeah.
So when you factor in Laplace's adiabatic correction, what does the final formula for the speed of sound actually look like?
Well, without reading out the raw algebra, the final formula boils down to a very elegant relationship. The speed of sound in an ideal gas depends on only two main things:
What are they?
the mass of the individual molecules making up the gas and the temperature of the gas. There is also a constant in there that accounts for how different types of gases handle heat. But the crucial variable is temperature.
So it doesn't depend on the heavy baseline atmospheric pressure at all, or how dense the room is overall.
Not at all. If you are in a room with a specific gas, the only thing that will change the speed of sound is turning the thermostat up or down.
That's fascinating. But Feynman doesn't just leave us with the formula, though, right? He connects this math back to the kinetic chaos we started with.
He does.
Because temperature isn't just a number on a dial, it's a measurement of how fast those individual air molecules are zipping around the room.
This is exactly where we bring the macro world and the micro world together.
Yeah, because when you run the numbers in Feynman's formula, the speed of the sound wave mathematically works out to be roughly 1 over the square root of 3 of the average speed of the chaotic air molecules themselves.
Which is roughly 0.58, just over half.
This means the sound wave carrying my voice to you right now travels at roughly half the speed of the messengers, the chaotic, bouncing air molecules doing the actual carrying.
It is a deeply satisfying realization. The overall wave can never travel faster than the kinetic speed of molecules carrying it.
Right.
But because those molecules are frantically bouncing in every possible direction, zigzagging constantly, the net forward movement of the organized wave is a bit slower.
It is the ultimate team effort of physics. So let's trace the full journey we took today. We started with the abstract idea of a wave as a mathematical shape sliding across space and time.
Right, f of x minus ct.
Then we zoomed way in to understand the mean free path, proving that a giant wave can survive the chaotic collisions of tiny molecules.
And then we walked through the mechanical engine, how displacement squishes the air to create density, how density generates pressure, and how pressure creates the force that accelerates the wave forward.
And finally, we uncovered Newton's thermal blind spot, learning from Laplace that sound waves trap their own heat, making the air stiffer, and proving that temperature is the ultimate speed limit for sound.
It's a brilliant sequence. And, if we pull back to the absolute biggest picture of physics, the derivation we walk through today isn't strictly limited to hearing.
What do you mean?
The mathematical architecture of the wave equation is a universal truth. Just as Newton's laws of mechanics lead us inevitably to the wave equation for sound, Maxwell's equations of electrodynamics will eventually lead us to the exact same mathematical wave equation for light.
Oh, wow. It's the exact same sliding shape, just using completely different physical messenger.
Exactly. Instead of blocks at air pressure, it's electric and magnetic fields oscillating through space.
It's the fundamental architecture of reality expressing itself in different mediums. That is so cool.
It really is. But before we wrap up, exploring this kinetic world raises a fascinating boundary question. Something for you to mull over.
I am always ready for a good thought experiment to close us out. Lay it on me.
Well, we spent a lot of time discussing the mean free path. We established that sound only works, the mathematical shape only survives, because its wavelength is vastly larger than the tiny distance those molecules travel between collisions.
Right. The stadium wave requires a massive stadium to exist.
Right. But what if you could engineer a sound wave with a frequency so incredibly high, and therefore a wavelength so microscopic, that the wavelength actually becomes smaller than the mean free path between the molecules?
Oh, wow. So the wave is trying to compress and stretch the air on a physical scale that is actually smaller than the distance the molecules naturally travel anyway.
Exactly. What happens to the sound in that extreme scenario? Does the wave just shatter?
Does
Or does the mathematical shape instantly dissipate into pure, unorganized heat energy. It is the exact threshold where the macroscopic world of smooth waves crashes head-on into the microscopic world of kinetic chaos.
That is a phenomenal puzzle, and it brings us right back to staring into the space between the speaker and your ear. It is not a clean delivery system. It is a vibrating, colliding, heat-trapping sea of invisible mechanics. Something to think about the next time you sit in a perfectly quiet room. Keep diving.
You know, if you've ever, sat at a piano
Mm.
and you just strike two keys that are right next to each other at the exact same time, you've definitely heard it.
Oh, yeah. That sound.
Right. It's not just a messy chord.
Yeah.
There's this very distinct wobbling, pulsating sound, like a whoop, whoop, whoop.
Yeah, exactly.
It almost feels like an acoustic mistake.
Yeah.
You know, like the instrument itself is just struggling to process the noise.
It creates this really intense sense of instability in the air. I mean, for a musician, that pulsing sensation is usually the telltale sign of an instrument being out of tune.
Right. Time to call the piano tuner.
Exactly. But for a physicist, that simple little auditory wobble is actually the gateway to understanding how the universe fundamentally operates.
Which is just wild to me.
Mm.
And welcome to today's deep dive, by the way. Our mission today is to explore how this simple act of adding two waves together, that wobbling sound, explains, well, everything.
Yeah, it really scales up.
It totally does. We're talking about the detuned piano, the way AM radio stations broadcast across the globe, and even, and this is the crazy part, the fundamental nature of quantum mechanics.
It's quite the journey.
It is, and we are drawing our map today from a truly legendary source.
Mm-hmm.
We're looking at Chapter 48 of the Feynman Lectures on Physics. It's titled simply Beats.
And the beauty of this text is how it takes a concept you can hear with your own ears right now in your living room, and it scales it up to explain the cosmos.
Yeah.
It perfectly bridges the gap between everyday acoustics and really high-level theoretical physics.
And trust me, you are going to want to picture this journey with us. Because what starts as a basic acoustic trick very quickly escalates.
Oh, it escalates big time.
Right. I mean, we are going to run into a situation
Mm-hmm.
where a golden rule of relativity appears to be completely broken.
Which is always fun.
Seriously.
Okay.
And then we'll uncover this massive revelation about the speed of light itself. So, okay, let's unpack this.
Sounds good. So the anatomy of that wub-wub sound.
Yeah, what's actually happening there?
Well, physicists call that a beat. So imagine you have two wave sources. Let's say you set up two loudspeakers sitting side by side in a room.
Okay, come with speakers.
Now, if both speakers play a tone at the exact same frequency, say 440 oscillations per second, which is an A note, the sound you hear is totally steady.
Right, the volume just stays flat.
Exactly. The intensity doesn't change at all. But if you detune one of those speakers just a tiny bit, maybe bump it up to 442 oscillations per second, the sound suddenly starts to swell and fall.
It gets loud, then quiet, then loud again.
Precisely.
To picture what's physically happening in the air, you kind of have to imagine plotting those two sound waves over time as like rolling hills and valleys.
That's a great visual.
Thanks. So because their frequencies are slightly different, they don't perfectly align. At certain moments, the crest of the wave from speaker A lines up perfectly with the crest of the wave from speaker B.
Right, and that is what we call constructive interference.
Constructive because they add up.
Exactly. When a crest meets a crest, the high pressure of both of those sound waves adds together, so you get a very strong, very loud sound.
Okay, makes sense.
But because one wave is moving just a little bit faster than the other, they obviously can't stay synced up forever.
Right, the faster one's going to pull ahead.
Exactly. The faster wave starts to drift.
And eventually, the crest of that faster wave aligns with the trough, like the valley of the slower wave. So the high pressure from one speaker meets the low pressure from the other.
And what happens?
They completely cancel each other out, right?
Yeah.
And the room goes virtually silent.
Yep. The result is that you hear this high-frequency pitch that is trapped inside a larger, slowly pulsating envelope.
An envelope, I like that word for it.
Yeah, the underlying sound waves are rippling hundreds of times a second, but that envelope, the swelling and falling volume, might only pulse once or twice a second, and that is the beat.
So the text has a lot of pretty elegant trigonometry to prove this.
Yeah.
But let's step away from the math formulas for a second to really lock in a visual for you.
Good idea. The math can get heavy.
Yeah, let's keep it grounded. Imagine two runners on a circular track, and they're going at slightly different speeds.
Okay.
When the starting gun goes off, they are side by side, but as they keep running, the faster runner slowly pulls ahead. And because it's a circular track, Eventually, the faster runner is going to completely lap the slower one.
Right.
And for just a brief second, they are side by side again.
That analogy actually aligns beautifully with how the text visualizes this mathematical relationship. It uses these things called complex vectors.
Which sounds incredibly intimidating.
It does. But it's really just a way of mapping a wave to a circle, exactly like your runners. So imagine drawing two arrows originating from the same center point.
Like hands on a clock.
Yes, exactly like clock hands rotating around. Each spinning arrow represents one of the sound waves.
Okay, so the length of the arrow represents the volume of the sound. And how fast the arrow spins around the clock face represents the frequency.
Spot on. And as the arrow spins, you basically just track its height relative to the center.
Height meaning where it's pointing.
Yeah, so when the arrow points straight up at 12 o'clock, the wave is at its peak crest. When it points straight down at 6 o'clock, the wave is at its lowest trough.
Oh, okay. That
Yeah.
totally makes sense. So if the two sound frequencies match exactly, those two clock hands are basically glued together.
Right, they rotate at the exact same speed.
And their combined height is always consistent. You just get a steady tone.
But introduce a detuned speaker, and one hand starts moving slightly faster than the other.
It slowly pulls away.
Exactly. When both hands pass 12 o'clock at the same time, they combine for a massive crest, a super loud sound. But as the faster hand laps the slower one, you get this moment where the fast hand is at 12 o'clock and the slow hand is stuck at 6 o'clock.
Oh, they point in complete opposite directions.
Yes, the crest meets the trough.
Hmm.
The arrows cancel each other out entirely, bringing the combined height to 0.
Absolute silence.
Yep. It's the exact same phenomenon as your runners lapping each other on the track, just translated into geometry.
That is so cool.
It really is. It's a fundamental property of how waves superimpose or, stack on top of each other.
Right.
But here's the thing. This pulsating envelope isn't just some acoustic quirk isolated to a piano or a pair of speakers. It is actually the core mechanism we use to transmit information across the globe.
Okay, which brings us to amplitude modulation.
Mm-hmm.
Or, as we all know it, AM radio.
Exactly.
I always assumed AM radio was just magically beaming voices through the air, but it's entirely built on this concept of the envelope.
It is. Think of a radio transmitter tower. When the station is turned on, but nobody is actually speaking into the microphone, the tower just emits this carrier signal.
Like a blank canvas.
Yeah, a pure, uniform wave oscillating at a really high frequency, let's say 800,000 times a second, which is 800 kilocycles.
But 800,000 uniform waves a second doesn't tell you the traffic or play a song.
No, it doesn't.
In fact, the text literally calls a perfectly uniform wave useless information. Right. To actually send information, say, a soprano sings into a microphone in the studio, her voice creates an audio frequency wave.
Right, a much slower, much messier wave.
Exactly. The transmitter takes that relatively slow audio wave and uses it to change or modulate the amplitude of that super fast carrier wave.
It essentially squeezes and expands the height of that 800 kilocycle wave to perfectly mirror the shape of the soprano's voice.
Wow.
So the carrier wave becomes the high-frequency ripple trapped inside the slower envelope of the music.
So it's basically making a beat.
Exactly. And when the radio in your living room receives this tangled signal, the electronics just strip away that 800,000 cycle carrier wave entirely.
It just tosses it out.
Yep. It ignores the fast ripples, traces the shape of the slow envelope, and pushes your speaker cone to match it. And out comes the soprano.
Okay, wait, let me push back on this a little bit because I think there's a really common misunderstanding here.
Sure, go for it.
If a radio station announces they are broadcasting precisely at 800 on the AM dial, and they're just changing the height of that wave to match the music,
Right.
they're still just sitting there at that one single frequency of 800 kilocycles, right? I mean, they're just making it taller and shorter.
What's fascinating here is they aren't.
What?
The very moment that station begins broadcasting the soprano's voice, they are no longer transmitting purely at 800 kilocycles.
How is that possible? If my dial says 800, shouldn't the wave be exactly 800?
You have to look at what physically happens when you force a wave to change its shape. A pure 800 kilocycle wave is a perfect, uninterrupted rhythm.
Okay.
To change its amplitude, to squeeze it down or stretch it up, you have to introduce interference. You are fundamentally disrupting that perfect rhythm.
Oh, I see. It's like trying to shake a jump rope at a perfectly steady pace, but someone keeps grabbing your arm to make your swings wider and narrower.
That's a perfect way to look at it.
You can't maintain the pure original rhythm. The forced changes inevitably introduce messy secondary rhythms.
That is exactly it. In the mathematics of waves, when you multiply the function of the carrier wave by the function of the audio wave, the resulting signal mathematically splits.
It splits.
Yeah. You don't just have an 800 kilocycle wave changing height. You actually produce the original carrier frequency plus 2 brand new separate waves called sidebands.
Okay, let's break those sidebands down because this completely shifts how I visualize a radio signal in my head.
It's pretty wild. So one sideband is the carrier frequency plus the frequency of the soprano's voice.
Okay.
And the other sideband is the carrier frequency minus the voice frequency.
Oh, wow.
So if our soprano hits a high note that oscillates at, let's say, 10,000 cycles per second, the radio station is still broadcasting the 800 kilocycle carrier.
But they're also sending out more waves.
Yes. It is simultaneously broadcasting a new wave at 810 kilocycles and another one at 790 kilocycles.
So the transmitter is basically leading over a whole range of frequencies.
Exactly.
It's not a single sharp point on the dial, it's a smear.
It's a total smear. And the real-world consequence of this frequency smearing is massive. I mean, this is exactly why the government has to heavily regulate the radio dial and space stations far apart.
Right, because if they didn't,
if another station tried to broadcast at 795 kilocycles, its signal would crash right into the lower sideband of our soprano. You'd just get terrible, garbled interference.
the text actually brings up television to show just how extreme this sideband problem gets.
Oh, TV is a whole different beast.
Yeah, because for a television broadcast, you aren't just sending an audio track. You are sending a grid of light and dark spots scanning across a screen like 30 times a second.
It's a massive amount of data.
The text calculates you need to transmit about 4 million pieces of information per second just to get a coherent picture.
Which is mind-boggling for an analog signal.
It really is.
Yeah.
Because visual information requires so much more data per second than a simple voice. Modulating a PV signal creates massive sidebands.
Oh, yeah.
A single TV channel requires a sprawling 6 megacycles of bandwidth.
That's huge.
You could even put a television signal on the AM radio dial, because the sidebands of just one channel would be wider than the entire AM spectrum.
Yeah, it requires an enormous amount of real estate on the electromagnetic spectrum.
Wow.
Now, everything we've discussed so far, from the detuned piano to the radio towers, has focused on waves oscillating over time in a fixed location.
Right.
But this raises a really important question. What happens when these waves are physically traveling through space?
Right, because radio waves actually travel from the tower to your car antenna. Light waves travel from the sun to the earth.
Exactly.
If you drop a pebble in a pond, you can watch the ripples physically move outward. The speed at which those actual wave crests move through space is called the phase velocity.
Yes. Keep that term in mind, everyone. Phase velocity.
Okay.
But remember our beats. When you add two waves of slightly different frequencies as they travel through space, they create that pulsating envelope we talked about.
Right, the wub-wub.
Here is the critical distinction the text makes. That envelope, the modulation, the lump of the wave containing the actual information, travels at an entirely different speed than the underlying ripples themselves.
Wait, really?
Yes. And we call the speed of the envelope the group velocity.
To picture this, I like to imagine a caterpillar moving across a leaf.
Okay, I like where this is going.
The ripple of its little legs moving across its body might be traveling backward, as it steps.
Right.
But the caterpillar itself, the overall shape is moving forward. The underlying movement and the overall package are operating at totally different speeds.
That's a super helpful way to visualize the disconnect between those two velocities.
Well, here's where it gets really interesting. Because this difference between phase velocity and group velocity sets up a massive paradox in the text.
Oh, it's a huge problem.
We all know the ultimate cosmic speed limit of relativity, right? Nothing can travel faster than the speed of light in a vacuum, period.
Right. It is the absolute bedrock of modern physics.
Yet the text looks at X-rays passing through a solid block of carbon. Now, X-rays are electromagnetic waves, just like visible light, just at a higher frequency.
Correct.
And because of how the carbon atoms interact with those specific frequencies, the math proves unequivocally that the phase velocity of those X-rays, the physical speed of the underlying wave crests, is moving faster than the speed of light in a vacuum.
The crests of the wave are literally outrunning the cosmic speed limit.
It sounds like physics is just breaking its own foundational laws. I remember reading that and thinking, wait, how does the universe not just implode? How can anything outrun light?
It's a brilliant paradox, but relativity is actually saved by the beats.
Really? How?
We have to go back to that idea of useless information we mentioned earlier.
Oh, right, the blank canvas wave.
Exactly, a perfectly uniform, endless wave, even one with crests zipping along faster than light, carries no signal. It cannot cause an effect, it cannot trigger a switch, it cannot send a message.
Right, it's just repeating into infinity.
Right. To transmit information, you have to create a change. You have to modulate the wave.
You have to make a beat. You have to create an envelope.
Exactly. And any signal, any actual physical consequence you try to encode is entirely bound by the group velocity, the speed of that envelope.
Okay, so the envelope is what matters.
Yes. The text calculates this group velocity by looking at the mathematical relationship between the wave's frequency and its spatial squishiness, which we call the wave number.
The wave number, right.
And when you measure how the oscillation speed shifts in response to the wave getting squeezed together by the block of carbon, the resulting speed of the envelope is strictly slower than the speed of light.
Oh, wow. So the underlying ripples are zooming along at impossible speeds, literally phasing through the carbon faster than light.
Right.
But the actual package of information, the envelope that could actually affect reality, is lagging behind, perfectly obeying the speed limit.
Exactly. Relativity holds firm. The universe doesn't break.
Thank goodness.
Right, because the modulation is what actually interacts with reality, and the modulation always respects the speed of light.
Okay, that is just an incredible save by group velocity. It almost feels like a mathematical loophole that protects the laws of physics.
It does feel like a cheat code, honestly.
It totally does. But it makes me wonder, if the math of beats governs how light and information travel, does it govern the physical stuff carrying that information? Like, a block of carbon is made of atoms. Does this apply to matter itself?
Well, that takes us into the strangest territory of all, quantum mechanics.
Oh boy, here we go.
In the quantum realm, a physical particle like an electron isn't treated as a tiny, solid billiard ball.
Right.
It is entirely represented by a wave of probability.
Meaning, the wave doesn't tell you exactly where the electron is right now, but rather the likelihood of finding the electron in a specific spot if you were to look for it.
Yes, exactly. But if you know roughly where an electron is, its probability wave isn't just an endless uniform ripple spread across the entire universe.
Right, because that would mean it could be anywhere.
Exactly. To describe an electron that is localized in one spot, physicists mathematically add several waves of slightly different frequencies together, just like we did to make an acoustic beat.
So they use constructive interference to make a huge peak in one location, and destructive interference to cancel out the probability everywhere else.
You've got it.
So you end up with a localized wave train. The text actually calls it a lump of probability.
A lump, yeah. And this raises the ultimate question. If this probability lump represents a physical particle moving through space, how fast does the lump move?
Well, the lump is the envelope, right? It's the beat. So the lump has to move at the group velocity.
Yes. And when you sit down and calculate the group velocity of this quantum probability wave using the fundamental quantum equations where a wave's frequency relates to its energy and its wavelength relates to its momentum, the math spits out a miraculous result.
What is it?
The group velocity of the probability wave perfectly, exactly equals the classical velocity of the physical particle.
No way.
Yes. The speed v you would calculate if you just treated the electron like a regular moving object, like a thrown baseball.
That is the ultimate aha moment for me. The abstract math of overlapping ripples the exact same trigonometric principles that explain the wobble of a detuned piano.
Yeah.
It directly predicts how physical matter moves through space and time.
Yeah.
It links the weird wave-like nature of the quantum realm to the physical motion we see in the macroscopic world. The electron literally is the beat.
It is profound. I mean, the particle isn't a solid thing riding on top of a wave. The particle's physical behavior, its momentum, its location, is entirely described by the interference pattern of these overlapping waves.
Okay, my brain needs a breather.
It's a lot to take in.
We've gone from speakers to X-rays to the quantum probability of electrons. Let's bring this grand sweeping physics back down to Earth for a second.
Sure, let's ground it.
Let's look at something you could literally build in your garage this afternoon to see this in action.
The final example Feynman offers is wonderfully tangible for exactly that reason. It involves two simple pendulums.
Okay.
So imagine hanging two heavy balls on strings, side by side from the ceiling.
Got it.
Now, connect the two hanging strings with a very weak, flimsy spring.
Okay, I can totally picture that. Two pendulums lightly tethered together.
Now, you pull one pendulum aside and let it go while leaving the other one hanging straight down.
Okay.
The first pendulum swings back and forth, but because of that weak spring connecting them, the moving pendulum slowly tugs on the stationary one.
Oh, I see.
Gradually, the first pendulum transfers its kinetic energy through the spring to the second one. The second pendulum starts swinging wider and wider, while the first one swings less and less.
Until eventually, the first pendulum stops completely, hanging dead still, and the second pendulum is swinging wildly, holding all the energy.
And then the process runs in reverse.
It bounces back.
The second pendulum begins giving the energy back to the first. It's this endless, mesmerizing dance of trading energy back and forth until friction eventually stops them both.
It sounds like a magic trick.
It looks like one, too.
And the text says there are actually two ways to understand this mechanical transfer. You can view it through the lens of resonance, where one pendulum acts as a driving force physically pushing the other.
Right.
Or you can view it through the lens of beats.
And viewing it as beats is far more illuminating because it reveals the hidden mathematical reality of the system.
How so?
We have to look at what are called the normal modes. A normal mode is basically a way the coupled system can oscillate where the amplitude never changes.
Where no energy is traded at all.
Exactly. For these two connected pendulums, there are two distinct normal modes.
Okay, so mode 1 is the symmetrical swing. You pull both pendulums back together in the exact same direction and let go. They swing side by side in perfect sync. Because they move together, the spring connecting them never stretches or compresses. It's as if the spring isn't even there.
Exactly. They just swing forever at a constant frequency determined by gravity.
Now consider mode 2, the asymmetrical swing. You pull the pendulums in exactly opposite directions and let go. They swing toward each other, almost touch, and then swing away from each other. Perfectly mirrored.
And in this mode, the spring is stretching and compressing constantly.
Right.
Because the spring adds its own mechanical pulling force on top of gravity, it yanks the pendulums back toward the center just a fraction of a second faster.
So this opposite swinging mode happens at a very slightly higher frequency than the side-by-side mode.
Precisely. We now have two constant amplitude motions occurring at two slightly different frequencies.
So what does this all mean? How does this explain the magic energy trading trick?
Think about it. What happens when you mathematically add those two distinct motions together? What is a superposition of these two modes?
Oh, I see the matrix now.
Tell us.
If you superimpose those two modes, at the exact moment you let go, the starting positions add up for the first pendulum, giving it a big swing.
Right.
But for the second pendulum, the swing left of mode 1 is perfectly mathematically canceled out by the swing right of mode 2.
Yes. So the second pendulum stays perfectly still.
It does. But because the two underlying modes have slightly different frequencies, their relative phases slowly drift over time.
Just like the clock hands.
Exactly like the clock hands. The motion that was adding up starts to fall out of phase and cancel out. The pendulum stops.
And the motion that was canceling out drifts into phase and adds up. The other pendulum swings.
You've got it.
The energy trading dance isn't really energy being passed back and forth like a baton in a relay race.
No, it's not.
It is literally just the acoustic beat we heard at the very beginning of the show, played out in physical motion. The amplitude of one pendulum is the swelling volume of the beat, and the other is the fading volume. It's just the superposition of two constant frequencies drifting in and out of phase. It perfectly unites the mechanical motion of physical objects with the abstract mathematics of waves.
That is just incredible. To recap this massive journey.
It's been a big one.
Yeah, we started by simply listening to two slightly different frequencies playing at the same time. That creates beats.
Right.
That pulsating envelope is the exact mechanism that allows us to modulate a carrier wave and broadcast AM radio across the globe.
Which is wild.
Then it resolves an apparent paradox about X-rays moving faster than the speed of light by proving that information always travels at the group velocity.
Yep.
It explains the physical momentum of quantum particles. And finally, it decodes the secret energy trading dance of two pendulums swinging in a garage.
It really is a testament to how universal these physical principles are. Feynman masterfully shows that the exact same math applies at every single scale.
It's amazing.
And I'll actually leave you with a final thought to mull over, building on that quantum lump we discussed earlier.
Ours too.
The text shows us that any physical particle is just a localized lump made of overlapping quantum waves. So if every single electron, proton, and atom in your body is essentially a packet of wave superpositions,
Right.
then you aren't just solid matter. You, and everything you see around you, are quite literally composed of an infinitely complex symphony of oscillating beats.
An infinitely complex symphony of oscillating beats.
Wow.
Next time you hear that wub 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 of a detuned piano, realize you aren't just hearing a mistake, you are literally listening to the very fabric of the universe. Thank you for joining us on this deep dive. Keep questioning, keep exploring, and listen closely to the world around you. Have you ever, inhaled helium from a balloon at a party
Yeah.
and just completely cracked up at how ridiculous your voice sounds?
Oh, yeah. I mean, everyone has done that at some point. It's a classic.
Right. And you probably thought that the helium was doing something physical to your vocal cords.
Yeah.
You know, like maybe making them vibrate faster or tightening them up somehow.
Which makes intuitive sense, right? Because the pitch goes way up.
Exactly. But it isn't doing that at all. Your vocal cords are doing the exact same thing they always do. What actually changed is the invisible mathematical architecture of the air inside your mouth.
Yeah, that is such a wild realization when you first learn it.
It really is. So, welcome to the deep dive. Today we're taking material from the legendary Feynman lectures to explore a hidden physical law. A law that explains that helium balloon, how a guitar works, and honestly, literally why your body is made of solid matter. We are digging into the really profound concept of confined waves and the hidden patterns they create, which physicists call modes.
And the beauty of this concept, is just how universal it is. We spend so much time putting different areas of science into distinct boxes.
Oh, for sure. Like acoustics over here, mechanical engineering over there.
Right, and quantum physics in its own weird esoteric corner. But the mathematics that dictate how a plucked string vibrates are the exact same mathematics governing the behavior of electrons in the atoms of your own body. I mean, it all comes down to what happens when you trap a wave inside a boundary.
That is just mind-blowing. So to set the stage for you listening right now, I want you to imagine the universe not as a collection of solid static objects, but as this massive invisible symphony of overlapping vibrations.
I love that analogy.
Thanks. I mean, every object is just humming with these hidden patterns. But to understand how that symphony actually plays, we really have to start incredibly small, with the simplest possible form of confinement.
Right, the absolute basics.
Yeah. So imagine a single long string.
Yeah.
And one end of it is tied to a perfectly solid, immovable brick wall.
Okay, so that boundary condition right there, that is the engine for everything that follows. Because the wall is infinitely solid, the end of the string attached to it simply cannot move. It's impossible.
Right. It's completely stuck.
Exactly. It must always have exactly zero displacement. And in the language of physics, that specific point of zero motion is called a node.
A node. Okay, so if I'm holding the free end of that string, right, and I give it a sharp, quick flick, I send a wave pulse rippling down toward the wall.
You do, yeah.
And when it hits the wall, that kinetic energy doesn't just, disappear. It has to reflect back.
Right, energy has to go somewhere.
But mathematically, something really specific has to happen to keep that exact attachment point perfectly still while all this energy is crashing into it. And I want to unpack this because Feynman uses this brilliant mental trick to visualize it. He asks you to imagine a hypothetical upside-down wave.
Yes. It is such a profound way to understand the mechanics of reflection. You essentially picture this mirror universe behind the solid wall.
Right. So coming from behind the wall is the exact same wave pulse you just sent, but it's flipped upside down.
Exactly.
And you time it so that both waves, the real one traveling forward and the imaginary upside-down one traveling backward, meet at the wall at the exact same moment.
Right. They converge right at that boundary.
So the upward pull of your real wave is perfectly canceled out by the downward pull of the imaginary wave as it passes through into our reality. That cancellation is what keeps the knot on the wall completely motionless.
It's just brilliant. And things become truly fascinating when we stop talking about a single flick of the wrist and start looking at a continuous rhythmic wave, like a continuous sine wave.
Okay, so I'm not just flicking it once, I'm just shaking it up and down constantly.
Right, at a steady rhythm, sending a continuous wave toward the wall. That continuous wave reflects back on itself, constantly undergoing that upside-down change in sign we just talked about.
Oh, I see. So the incoming wave and the reflected wave are constantly crossing paths.
Exactly, they interfere with each other. And because of that perfect mathematical cancellation happening over and over again, you don't just get one single node at the wall anymore. you generate a whole series of nodes spaced out along the entire length of the string.
Wait, really? So you get these distinct spots on the string that just sit completely still, even though the whole rest of the string is vibrating furiously?
Yeah, that's exactly it. Between those stationary nodes, the string is whipping up and down. But the pattern itself, the specific locations of the dead spots and the peaks, stays completely fixed in space.
Yeah.
The wave is oscillating in time, but its shape is stationary. And that stationary pattern of vibration, that is the fundamental definition of a mode.
It's so strange to visualize, honestly. I mean, the material is moving constantly, but the shape of the movement is totally frozen.
Right, it's a standing wave.
That makes perfect sense for a string with one wall. But let's be real, almost nothing in the real world is infinitely long.
Mm-hmm.
What happens if we introduce a second wall? Like, let's pin down both ends of the string.
Okay.
We've essentially just built a basic guitar string, right?
So we have. And adding that second boundary completely changes the rules of the system.
How so?
Well, with just one wall, you could shake your hand at any frequency you wanted, and a wave would travel down the string. But with two walls, the physical confinement dictates the allowed and natural frequencies.
Ah, because both ends have to be nodes now.
Exactly. You are mathematically demanding that the wave has a node at the beginning, and it absolutely must also have a node at the end.
You know, it makes me think of, like, two people holding a jump rope.
Oh, that's a perfect analogy.
Yeah, like if you want to swing a jump rope smoothly, you can't just flail your arms at any random speed. You have to find that specific rhythm where the rope bows up in the middle and comes down in one big perfect arc.
Right.
The two people holding the ends are the nodes. That one big loop is the simplest possible way a wave can fit between those two boundaries.
Yeah. And that single loop is the first mode, or the fundamental frequency. Now, what happens if the two people holding the jump rope swing it twice as fast?
Well, they'd hit the next rhythm. The rope forms two arcs with a new stationary dead spot right in the middle of the rope.
Exactly. The wavelength is exactly half of the first one, which means the frequency is exactly double.
Oh, so it's a perfect multiple.
Right. The next possible way it can fit is with 3 loops, taking 3 times the frequency, then 4 loops, and so on. The allowed frequencies for this confined string are simply perfect integer multiples of that lowest natural frequency, 1, 2, 3, 4.
It's incredibly clean, but I actually have to push back on this a little bit.
Oh, okay. Go for it.
Because this pristine mathematical model, it just feels totally detached from reality. I mean, if I actually pluck a real guitar string, I don't see a perfect, elegant jump rope sine wave.
True. You really don't.
I just pull the string back into a sharp, messy triangle shape with my finger, I let go, and it's just this jagged bump violently traveling back and forth. So how does this beautiful theory of nodes and modes actually apply to the messy reality of a physical instrument?
Okay. This is exactly where we need to introduce one of the most powerful concepts in all of mathematical physics, the principle of superposition for linear systems.
Whoa, hold on. Superposition for linear systems. That sounds like we're about to write a graduate thesis. Let's break that down. What does that actually mean for our messy triangular guitar string?
Fair enough. Let's unpack it. It basically means that any complex motion, no matter how messy or jagged it looks to your eye, is really just an infinite number of those simple, perfect modes operating simultaneously.
Wait, simultaneously?
Yeah. When you pluck that string into a triangle and let it go, you aren't just exciting the first mode, the big single loop. You are exciting the first mode, the second mode, the third mode, the 1000th mode, all at the exact same time.
That is wild.
They are all vibrating at their own specific integer frequencies, completely independent of one another, but physically layered on top of each other.
So a messy shape is really just a stack of pure shapes. But I'm trying to picture how adding stationary vibrating loops together can create the illusion of a single bump sliding left and right along the string. Like, how does that work?
Okay, imagine just 2 of those modes combining to start. You take the first mode, the single big loop vibrating up and down.
Got it.
Now layer the second mode on top of it, the 2 loops with the node in the middle. But, and this is key, you stagger their timing. In physics terms, we make them 90 degrees out of phase.
Okay, let's visualize that out of phase part. It's kind of like 2 people doing the wave in a sports stadium, but one person is a quarter beat behind the other.
That's a great way to picture it. When the first mode is at its absolute peak height, the second mode is perfectly flat, but it's moving really fast through the center.
Oh, I see. So when you add those 2 specific motions together, at one moment, the left side of the string bulges up because both modes happen to be moving up on that side.
Yes. And a moment later, as the modes continue their stationary oscillation, the sum of their positions makes the right side bulge up.
So the individual modes aren't actually traveling left or right.
Not at all. They are just standing there, vibrating in place. But their layered, staggering rhythm creates the illusion of a bump physically traveling from one end to the other.
Wait, so the movement of the wave on the string is essentially a mathematical illusion. It's
Yeah.
just a bunch of stationary standing waves doing a highly coordinated dance.
That is the profound truth of superposition, yes.
That is incredible.
And this isn't just a neat mathematical trick for musical instruments. This exact principle applies to incredibly complex engineering structures. Think about an airplane wing flying through severe turbulence.
Oh, man. The way it bends, twists, and whips around looks completely chaotic. And terrifying, honestly.
Right. It definitely looks like the physics are just randomly breaking down.
Yeah.
But aerospace engineers analyze it exactly the same way we just analyze the guitar string. The airplane wing has its own fundamental modes, the simplest, pure ways it can twist and bend based on where it's attached to the fuselage.
Oh, wow. So that chaotic whipping in the turbulence is just a superposition of those simple stationary modes vibrating at different intensities.
Exactly. If you know the underlying pure modes, you completely understand the total messy reality.
Okay, that makes perfect sense for a one-dimensional line like a string or, long, thin airplane wing.
Yeah,
But almost nothing else in the real world is a one-dimensional line.
true.
So if I tap on a drum, the wave isn't just traveling left to right, it's spreading out in all directions across a surface. Does this whole perfect mathematical integer thing fall apart when we look at a two-dimensional surface?
It definitely gets more complicated.
Let's take a rectangular rubber drum head. Now, we aren't just bouncing waves back and forth between 2 points. We're bouncing them around 4 solid edges.
And you're right, the confinement becomes significantly more complex, and the resulting patterns change dramatically. On the 1D string, the nodes were just single points. But on a two-dimensional drumhead, the nodes are entire lines where the rubber simply doesn't move.
Entire nodal lines. Wow.
Yeah. You get these really intricate checkerboard patterns of standing waves across the surface. Whole sections of the rubber are bulging up while neighboring sections bulge down, and they are separated by stationary nodal lines that cross the entire drumhead.
What fascinates me here is what happens to the frequencies, actually. Because on the string, we saw that all the higher frequencies were just clean, simple multiples of the lowest one, 1, 2, 3, 4. It was perfectly harmonic.
Right.
But for a 2D rectangular drum, that beautiful harmonic ladder goes completely out the window. The natural frequencies are determined by this incredibly messy equation involving the square roots of the sums of the squares of different integers based on the length and width of the rectangle. I mean, the mathematical point is they're absolutely not simple multiples of one another.
And this forces us to reevaluate how we view the physical world, honestly. We are so used to the harmonic perfection of strings and pipes and music that we implicitly assume it's the natural order of things.
Yeah, we assume the universe is naturally harmonic.
But harmonically related frequencies are actually a rare, isolated exception in physics. They are a special case. The moment you move to a two-dimensional system like a rectangular drumhead, the frequencies become highly complex and inherently inharmonic.
Well, if 2D gets that messy, we absolutely have to talk about 3D. Because the Feynman lectures take this concept straight into the human mouth, which is basically a 3D cavern of squishy, weirdly shaped boundaries.
Oh, the mouth is a terribly complicated cavity resonator, but the principle of confined waves still applies flawlessly. When you speak, your vocal cords create a raw, complicated buzzing tone.
Right.
But that tone doesn't just shoot straight out of your mouth into the air, it bounces around inside that 3D cavity.
It's trapped. The sound wave is confined by your cheeks, your palate, your tongue.
Yes. And just like the 2D drumhead, that 3D cavity has its own resonant frequencies, its own 3D modes. As you move your tongue and lips, you are actively changing the physical boundaries of the cavity.
Which inherently changes the frequencies of those allowed modes, right?
Precisely. The frequencies from your vocal cord buzz that happen to match the cavity's active modes get amplified. The frequencies that don't fit the boundary conditions get suppressed. That selective amplification is the filter that allows you to shape a raw buzz into distinct vowels like or ooh.
Which brings us right back to the helium balloon from the beginning of our deep dive. We've seen it or done it. You inhale from a balloon and suddenly you sound like a cartoon character.
Yeah.
But as we established earlier, your vocal cords aren't changing.
Not at all.
And helium is much less dense than regular air. Because it's less dense, sound waves travel significantly faster through it.
The speed of sound is the crucial variable here. The frequencies of your cavity modes are directly tied to how fast the waves can bounce back and forth between the fleshy boundaries of your mouth.
Oh, I get it. So you inhale the helium, you are buzzing your vocal cords at the exact same pitch as before.
Yeah.
But because the sound waves are suddenly moving faster through the helium gas, they bounce around the cavity faster.
Right.
This drastically raises all the resonant frequencies of the modes in your mouth. The invisible filter sitting on top of your vocal cords basically shifts upward. Even though the input buzz is exactly the same, the amplified modes change entirely, and your vowels get completely warped.
It's a perfect physical demonstration of how the medium itself, combined with the boundaries, dictates the modes of the system.
It is so cool. Okay, so we've talked about continuous things so far. Strings, rubber drum heads, 3D air cavities, they're continuous fields, meaning they technically have an infinite number of possible modes if you just keep driving the frequency higher and higher.
Right, theoretically infinite.
But what about discrete, simple mechanical systems? Do they have modes too?
They absolutely do. You don't need a continuous medium to have a mode. You just need a system of connected parts where the motion of one part intrinsically affects the others.
Let's visualize a really simple mechanical system for you listening. Imagine two identical playground swings hanging side by side. But there is a metal spring connecting the two swing seats together. This is a system of coupled pendulums.
Okay, great example.
Unlike the guitar string that has an infinite number of places along its length where it can vibrate, this system only requires two pieces of information to describe its entire state. Where is swing A and where is swing B?
And in physics, we say that system has 2 degrees of freedom, and a beautiful mathematical rule emerges for discrete systems. The number of degrees of freedom exactly equals the number of modes.
Oh, wow.
Yeah, because it has 2 moving parts, it possesses exactly 2 fundamental modes of vibration. No more, no less.
Let's reason out what those two modes actually look like. If I walk up to those two connected swings and I pull them both back the exact same distance and let them go simultaneously.
They swing forward and backward exactly together. They're perfectly in phase.
Right. In that scenario, the spring connecting them isn't actually doing anything, is it? It's just coming along for the ride.
Exactly. Because they are moving together at the exact same speed, the distance between them never changes. The spring never stretches or compresses. It's as if the spring isn't even there. The frequency of this first mode is dictated entirely by gravity pulling on the swings, just like a normal pendulum.
But then there's the second mode. For the second mode, I pull one swing back toward me, and I push the other swing forward away from me by the exact same amount. When I let go, they swing exactly opposite to each other. They rush toward each other in the middle and then fly apart.
And now the spring is the defining feature of the motion. When they swing apart, the spring is violently stretched, pulling them back. When they swim together, the spring is compressed, pushing them apart.
So this spring adds a strong, new restoring force to the system, working on top of gravity.
Exactly. Because there is more overall force pulling the swings back to their center point, they oscillate faster. The frequency of this second mode is mathematically, predictably higher than the first mode.
And just like the guitar string, if a couple of kids just grab those swings and shove them randomly, the resulting messy, chaotic dance is mathematically just a combination of those two simple modes happening at the exact same time.
Yeah, the math truly doesn't care if it's an infinite continuous string or 2 discrete playground swings. The underlying rules of confinement and superposition are exactly the same.
Which perfectly prepares us for the most profound transition in physics, I think. We've traced these rules through tangible macroscopic things, right? Guitar strings, drum heads, swings, balloons. But these exact same rules of confined waves are the foundational architecture of quantum mechanics.
They really are. And this is the massive leap. In classical mechanics, we are looking at something physical waving. A stretched nylon string, a rubber sheet, air pressure inside a mouth.
Right, stuff we can touch.
But when we transition to quantum mechanics, what is actually waving?
Yeah, the textbooks always say it's the probability amplitude function of a particle, like an electron. But what does that even mean? The electron isn't a tiny solid planet orbiting a sun, right?
It is not a solid ball, no. At the quantum scale, an electron is much better understood as a smeared-out cloud of probability. It is literally a wave that dictates where the electron is likely to be found.
Okay.
And when an electron is bound to a proton in an atom, it does not have enough energy to escape the proton's electromagnetic pull. It is trapped.
So the electromagnetic pull of the proton Acts exactly like the two physical walls trapping the guitar string.
Yeah.
The electron wave wants to fly away, but the boundary says, no, you must have a node here. You cannot pass this point.
That's exactly it. An electron bound to a proton is quite literally a confined wave.
That is wild.
And because it is a confined wave, it is subjected to the exact same mathematical demands as our jump rope. The electron's probability wave cannot just vibrate any way it wants. It has to fit the boundary conditions perfectly.
Right, the zero displacement rule.
Yeah. If the wave doesn't fit perfectly into a whole number of loops, it mathematically cancels itself out and cannot exist. Therefore, the electron's wave can only exist at definite specific frequencies, the first mode, the second mode, and so on.
Okay, and here is the crucial bridge between classical physics and quantum reality. In our everyday world, if I shake a jump rope faster, I'm just changing the frequency, right? It just takes a little more effort. But in quantum mechanics, there is a fundamental law. Frequency translates directly into energy.
Right. Because the confined electron must vibrate in perfect whole number loops, it can only possess perfect whole number frequencies. And because frequency is energy, the electron can only exist at strict specific energy levels.
It can't exist between the levels because a wave with like 1.5 loops would cancel itself out at the boundary. It has to be step 1, step 2, step 3.
Exactly.
This is the exact origin of the fixed energy levels of atoms that we all had to memorize in high school chemistry. It's why an atom absorbs or emits very specific, precise colors of light. The atom is essentially a three-dimensional quantum drumhead.
That's a beautiful way to put it.
When it absorbs energy, the electron jumps from a simpler confined mode to a more complex confined mode. When it releases energy, it drops back down a step.
The entire structure of the periodic table, the specific ways that molecules bond together, the complex chemistry that allows your body to function, it is all dictated by the allowed integer modes of these confined quantum waves.
So the physical world exists the way it does because of boundary conditions.
It really does.
It completely changes how you look at yourself and the space around you. I mean, we started by noticing how solid a table or an airplane wing feels. But the solidity is an illusion. You are just looking at the invisible mathematical music of confined waves, which really leaves us with a staggering question to mull over.
What's that?
If everything, from the vibration of a rubber drumhead to the foundational probability waves of electrons operating inside your own body, follows the exact same mathematical rules of confinement, might the entire material universe simply be an infinitely complex, overlapping symphony of standing waves waiting to be understood? It's definitely something to think about the next time you hear a guitar string ring out.
What if I told you that the next time you go to a really loud concert, you are actually going to be hearing music that literally does not exist?
I mean, it's a pretty unsettling thought, right?
Right, because we just assume we're hearing what's there.
Exactly. We tend to trust our senses implicitly. Like, we just assume that a sound happens out in the physical world, it travels through the air, and our ears simply act as, these perfectly objective microphones.
Just recording the reality of the room.
Yeah, but the truth of what is actually happening inside your head is far stranger, and, well, mathematically, it's much more complex.
So today, we are going to completely change how you hear the world. Welcome to this custom-tailored deep dive. We've got a really fascinating stack of sources today.
We really do.
Yeah, specifically, we're looking at notes and excerpts from Richard Feynman's legendary physics lectures.
Focusing specifically on his chapter about harmonics.
Right. And whether you're a musician or like a total math nerd or just someone who is insanely curious about how the universe actually operates behind the scenes, we're going to uncover the hidden architectural machinery behind everything.
Everything from the noise of a stomping foot to human speech, AM radio, and
even lasers, which is just wild to me.
It's a really profound shift in perspective when you realize that the physics of a plucked guitar string and the physics of a color-shifting laser are, well, they're governed by the exact same underlying rules.
It's crazy.
It is. You really start to see the hidden scaffolding of reality.
Okay, so let's unpack this, because I think the best place to start is just the most basic distinction our ears have to make every single day.
Right, the difference between noise and music.
Yeah. If you were to somehow, pause time and look at the actual air molecules hitting your eardrum when someone aggressively stomps their foot on a hardwood floor, what does that actually look like?
Well, if you charted it out, it would just be a jagged, unpredictable mess.
Just chaos.
Totally. The physical definition of noise is an irregular vibration.
Okay.
So the pressure changes in the air. They have no pattern whatsoever.
They just sort of violently jump around.
Exactly. They push and pull the eardrum erratically, and then they just die out.
Right. So think of noise like a messy, completely random splatter paint canvas.
That's a good way to put it.
But a musical tone is a completely different story, right?
Yeah.
If you chart out the air pressure of, say, a sustained note on a cello, it has this specific repeating shape.
It does.
The air pressure goes up and down in this uneven but perfectly consistent pattern over and over and over again. So it's less like splatter paint and more like an intricately patterned, perfectly repeating geometric tile floor.
I like that analogy.
Yeah.
And that repeating tile pattern has three main characteristics that our ears automatically decode.
Okay, what are
First is loudness, which is just the amplitude, basically, how extreme the pressure changes are.
how hard the air is hitting you?
Yeah. Second is pitch, which is the period, meaning how fast that tile pattern repeats itself. High notes repeat very quickly, and low notes take longer to complete a full cycle.
Got it. And the third characteristic is the one I find, honestly, the most fascinating: quality.
Yes, quality is huge.
Because this is the thing that explains why a middle C played on a piano sounds entirely different from that exact same middle C played on an oboe or, sung by a soprano.
Right.
The pitch is the same, the loudness is the same, but the internal structure of that repeating tile pattern, the specific shape of the wave itself, is completely different.
Which naturally brings us to perhaps one of the most significant intellectual milestones in human history.
Oh, yeah. Discovered by Pythagoras thousands of years ago in ancient Greece.
The very same.
We usually just know him as, the triangle geometry guy from high school math.
Right, the a squared plus b squared guy. But his work with sound is arguably way more profound. Well, Pythagoras was experimenting with strings under tension. He noticed that if you take two similar strings and you pluck them, they sound incredibly pleasant together, what musicians call consonant.
Yeah, they just sound nice.
Exactly. But they only sound pleasant together if their lengths are in the ratio of small integers.
So if one string is exactly half the length of the other, like a 1-to-2 ratio, you get an octave.
Right.
They sound like the same note, just higher and lower. And if the ratio is 2-to-3, you get a perfect fifth, which is that majestic, stable interval you hear right at the start of the Star Wars theme.
Yes. And what's really fascinating here is the historical context of that discovery.
Yeah.
I mean, this wasn't just a neat little musical trick for tuning a lyre.
It was bigger than that.
Much bigger. This is the very first time in human history that a numerical mathematical relationship was discovered in nature, totally outside of pure geometry.
Because before this, arithmetic was just sort of a utilitarian tool, right?
Exactly. You use math for counting sheep, measuring land, calculating your taxes, stuff like that.
And suddenly, Pythagoras proves that invisible aesthetic experiences, like whether two notes sound pretty or ugly together, are secretly governed by strict mathematical fractions.
It's incredible.
That had to be an absolute paradigm shift for how humanity viewed the universe.
Oh, it definitely was. But here is the grand irony that Feynman actually points out in his lectures.
All right, this is funny.
Yeah. Pythagoras had this massive epiphany, but he entirely missed the importance of how he found it, which was through physical experiment.
He didn't realize what he'd actually stumbled onto.
Right. Instead of realizing he had just laid the foundation for the scientific method, testing physical reality to find governing laws, he went in the exact opposite direction.
He basically started a mystic cult.
He essentially did, yes.
Yeah.
The Pythagoreans became completely obsessed with the mystical power of the numbers themselves.
Like they thought the numbers were magic.
Exactly. They assumed the planets must also, sing in perfect ratios as they orbited, the whole music of the spheres concept.
Right.
They got so caught up in the aesthetics and the mysticism of the math that they completely overlooked the power of physical experimentation that was just staring them in the face.
Wow.
I mean, experimental physics could have had a centuries-long head start if he had just kept plucking strings instead of starting a religion.
That is wild to think about. But okay, let's bring it back to the sound itself. Pythagoras figures out that simple ratios make pretty chords.
Right.
But if music is that, perfectly repeating patterned tile floor we talked about earlier, how do we determine exactly which mathematical tiles are being used to make the pattern?
That's the big question.
Yeah, how do we map these pure, clean ratios to the messy, actual shape of a real sound wave?
Well, that specific problem actually went unsolved for a very long time, until a French mathematician named Fourier came along and introduced what we now call the Fourier series.
And here's where it gets really interesting. Because Fourier figured out that any periodic wave, no matter how jagged, weird, or complex that repeating pattern is actually just a combination of simple, perfectly smooth sine waves stacked on top of each other.
Precisely. Every repeating sound has a lowest frequency, which we call the fundamental.
Okay.
Let's say that fundamental wave repeats every 1/100th of a second. Fourier proved that the overall complex wave is basically made of that fundamental, plus a wave vibrating exactly twice as fast,
Right.
plus one vibrating exactly 3 times as fast, and so on.
Right.
And these higher integer multiple frequencies are called harmonics.
I just love thinking about this as the unbaking a cake analogy.
And that's a great way to look at it.
Because, it's incredibly easy to bake a cake if you have the recipe. You put in the flour, the sugar, the eggs, mix it up, bake it. You put simple ingredients in and you get a complex thing out.
Sure.
But Fourier figured out how to take a fully baked cake, taste it, and mathematically extract the exact recipe used to make it.
That's exactly what he did.
He can take this chaotic-looking violin waveform and tell you exactly how much of the fundamental pitch, the second harmonic, and the fifth harmonic were used to bake that specific sound.
And the mathematical mechanism he invented to do this is it's nothing short of elegant. It essentially functions like a mathematical sieve.
Okay, how does that work?
Let's say you have this complex sound wave, and you want to know exactly how much of the 7th harmonic is hiding inside it.
How much of that specific ingredient is in the cake?
Exactly. Fourier showed that if you take the mathematical equation for the whole complex wave and multiply it by the equation for a pure 7th harmonic, and then average the result out over a period of time, something magical happens.
What happens?
All the other harmonics,
Yeah.
the fundamental, the second, the third, the eighth, they all average out to absolute zero.
They just completely vanish from the map.
They completely vanish.
Yeah.
The only thing that doesn't average to zero is the 7th harmonic interacting with itself.
What?
So whatever number you are left with after that averaging process is completed, well, that is the exact amount of the 7th harmonic present in your original wave.
That's brilliant.
You just run that sieve for every integer, and boom, you have your complete recipe.
It's so elegant. Now, the source notes do mention that Fourier's math hits, like a tiny glitch, when dealing with shapes that exist in theory but are physically impossible in the real world.
Yes, that's right.
Like a square wave, which is a wave that stays perfectly flat at a high pressure and then instantly drops to a low pressure.
Right. In a pure mathematical model, a square wave jumps instantaneously from a positive value to a negative value. There's no slope, there's no smooth transition, it's just a vertical drop.
Right, but if we ground that in physical reality, think about what a speaker cone would have to do to physically produce a perfect square wave.
It would be impossible.
Yeah. The speaker would have to be pushed all the way out and then instantaneously teleport to being pulled all the way in literally 0 seconds.
Right. And because teleportation is impossible, Fourier's math has to compromise.
How does it do that?
If you calculate the sum right at the exact breaking point of that drop, it doesn't give you the top value or the bottom value. It splits the difference and gives you the exact halfway point.
Which is a perfectly reasonable compromise for a situation that violates the laws of physics, right?
Absolutely. But if we connect this to the bigger picture, Fourier's recipe leads us to something called the energy theorem.
Okay, what's that?
It tells us that the total physical energy of that baked cake, the entire complex sound wave pushing through the air, is simply the sum of the energies of all its individual Fourier component ingredients.
Oh, wow.
Yeah, so energy is perfectly conserved.
Okay, so we know how to unbake the sonic cake. We know that any repeating tone is just a stack of simple harmonics.
Right.
And this finally explains what we were talking about earlier. Quality. Why a piano, an oboe, and a violin all sound totally distinct even when they're playing the exact same note.
Exactly. Because when you play a middle A on a violin, you aren't just hearing a 440 hertz fundamental pitch.
Right, there's more to it.
The wood of the violin body, the friction of the bow, the tension of the strings, all of those physical properties naturally emphasize certain harmonics and dampen others.
An oboe has a completely different shape.
Right, an oboe playing that same note has a completely different physical structure. It's a wooden tube with a double reed, so it physically emphasizes a totally different recipe of those upper harmonics.
And because we know the recipe, we can build our own cake from scratch. Like, this is how electronic synthesizers work, isn't it?
It is. It's pure application of the math.
You take basic oscillators that only generate pure, smooth sine waves. You tune them to the fundamental, the second harmonic, the third.
And then you just turn the volume knobs up or down on each one to match the Fourier recipe.
Right.
And if you get the proportions right, you can force an electric speaker to sound exactly like a flute.
It's amazing.
Yeah.
But, you don't even need a synthesizer to do this. You do this yourself continuously every time you speak.
Yes. This part of the source material was amazing to me. The physics of vowel sounds.
It's fascinating. The human mouth is just an incredibly sophisticated acoustic filter.
Because when your vocal cords vibrate, they create a really rich, complex tone packed with harmonics, right?
Right.
But your mouth acts as a resonant cavity. By changing the shape of your lips, your tongue, and your throat, you are actively choosing to amplify specific frequency zones and suppress others.
Exactly. So when you shape your mouth to say E, you are physically boosting one specific band of frequencies.
But the wild part is, if I sing a really high E or a deep low E, the listeners still recognize it as an E sound.
Even though the pitch is totally different.
Yeah, even though my fundamental pitch completely changed and the specific individual harmonics shifted, my mouth is still emphasizing the same overall frequency envelope.
And that tells us something really profound about human hearing.
Which,
We aren't just blindly registering raw pitch.
Yeah.
Our brains are constantly, subconsciously analyzing the overall harmonic structure, the quality to decode language and meaning.
which brings us right back to our buddy Pythagoras.
Ah, yes.
Because now that we understand harmonics, we can finally explain why his small integer ratios sound so pleasant.
Let's look at that perfect fifth again.
Right, the ratio of 2 to 3, like playing a C and the G right above it.
So if you use Fourier's math to look at the harmonic recipe for the C, its third harmonic is vibrating at a specific frequency.
Okay.
Now look at the recipe for the G. Its second harmonic is vibrating at that exact same frequency.
They literally physically overlap.
They do. The upper harmonics of the two different notes fall into perfect mathematical unison, so there's no physical clashing in the air.
Okay, but this raises an issue for instruments like the piano, doesn't it?
How do you mean?
Well, a violinist can slide their finger on the string to make that mathematical 3 to 2 ratio absolutely perfect, right? Depending on what key they're playing in. But a piano has fixed strings. You can't just retune a piano mid-song.
That is a brilliant point, and it's the exact reason we use something called tempered tuning.
Tempered tuning?
Yeah. See, if you tune a piano so that C major is mathematically perfectly aligned to Pythagorean ratios, it will sound angelic.
Okay.
But if you try to play a song in F sharp on that same piano, the fixed strings will be misaligned for that key, and it will sound horribly sour.
Ah, so we use the piano fudge.
Yes, the fudge. To allow musicians to play in any key on a fixed keyboard, we basically divide the octave into 12 mathematically equal intervals.
So they aren't perfect ratios anymore.
Exactly. The ratio between notes isn't a clean integer fraction anymore. It relies on the 12th root of 2.
Oh, wow.
It means every single key on a piano is actually slightly mathematically out of tune. The harmonics never overlap perfectly.
But it's close enough that our ears just accept the compromise.
Right.
I do want to push back on this a little bit, though. This whole math is beauty idea. When I hear a beautiful consonant chord and I get chills, am I experiencing that pleasure because the physical sound waves are literally fitting together cleanly in the air without clashing?
Right.
Or is my brain just secretly doing arithmetic behind my back and giving me a shot of dopamine for recognizing a simple math pattern?
I mean, that is the million-dollar question.
Yeah.
And Feynman is remarkably humble about it in the text.
Yeah, he doesn't claim to know for sure.
Not at all. He admits that physics has advanced light years since Pythagoras, but our understanding of aesthetics, of why we prefer what we prefer, hasn't really evolved much at all.
So we really don't know.
The jury is entirely still out on whether it's physical acoustics or mental arithmetic.
Well, I have a theory on this.
Oh, let's hear it.
If the brain is basically a prediction engine, right? It constantly wants to know what happens next.
Okay. Yeah.
A simple mathematical ratio like 2 to 3 is incredibly predictable. The pattern resolves quickly. So maybe we evolved to find consonant chords beautiful because our brains reward us for successfully predicting the pattern. Predictability equals safety.
You know, that is a really compelling psychological argument.
But there's a physical one too.
There is an equally strong physical argument. When two notes have harmonics that are very close to each other but don't perfectly overlap, they create physical beats.
Like a rhythm?
Sort of rapid pulses of loud and soft air pressure. And some acoustic biologists argue that those beats physically cause turbulence in the fluid of our inner ear, which actually irritates the tiny hair cells in the cochlea.
Oh.
So a dissonant chord might literally physically stress out our ear mechanics, whereas a perfect ratio is physically smooth to process.
Wow, that makes so much sense. But it also perfectly tees up the next big pivot in our deep dive.
Right.
Because up to now, we've been living in this like perfect mathematical utopia, sines, cosines, predictable ratios. If I push a string twice as hard, it moves twice as far. But the real physical universe doesn't play by perfect rules, does it?
It does not.
At some point, if you push a system too hard, it buckles. The real world is crooked. And that crookedness is called nonlinearity.
This is a crucial shift in understanding physics. Everything we've discussed so far assumes a linear response.
Like a spring.
Exactly. Imagine a physical spring. You push it with 1 pound of force, it compresses 1 inch. You push it with 2 pounds, it compresses 2 inches. The output is strictly proportional to the input.
But what happens when I push that physical system too far and it just can't respond perfectly anymore?
Then you enter a nonlinear system. Maybe you push the spring so hard that the metal binds up.
Okay.
You push with 2 pounds of force, but the spring only compresses 1.5 inches. The math is no longer a straight proportional line, it curves. The output might become proportional to the square of the input.
And when you force our beautiful, perfectly symmetrical sound waves through a crooked, nonlinear system, things get weird.
They get very weird.
Let's say you blast a pure, smooth sine wave into a cheap speaker. The speaker cone gets pushed to its physical limit and can't travel any further.
Right.
So the smooth peak of the wave gets squashed and flattened out. The output wave is fundamentally distorted.
And remember the rule Fourier taught us.
Unbaking the cake.
Exactly. If a wave is no longer a perfectly smooth sine wave, it must be made of multiple harmonics.
Oh.
So, by simply passing a pure fundamental tone through a nonlinear device that squashes the wave, the device physically creates new harmonics that were never in the original signal.
It's literally baking new ingredients into the cake that weren't in the recipe.
That's exactly what it's doing.
And this distortion causes two massive effects, right? The first is rectification.
Yes.
Because the top of the wave got squished flat, but the bottom maybe didn't, the whole average baseline of the wave actually shifts. The 0 point moves.
And the second effect is even more consequential.
Yeah.
Modulation.
Modulation. Okay, break that down.
Okay. If you play 2 different frequencies simultaneously into a nonlinear system, they don't just stay separate and stack nicely.
Like they do in a linear system.
Right. Because the crooked math of the system often involves squaring the input. The 2 frequencies are forced to multiply against each other. They cross-pollinate.
And when they multiply, they spawn totally new frequencies.
They do.
They generate a tone that is the exact mathematical sum of the 2 original notes and another tone that is the exact difference between them.
And I really want to emphasize a critical law governing this. These nonlinear effects are proportional to the product of the amplitudes. Meaning, the louder or stronger the original signals are, the more extreme the multiplication gets. The distortion grows exponentially as the volume increases.
Okay, but usually when we talk about distortion or like blown out speakers, it's a bad thing. We want clear sound.
Usually, yes.
But here is where the science takes a massive left turn. These crooked, nonlinear flaws aren't just annoyances. They are the secret foundation of human biology and modern technology.
They really are.
Which brings us back to my promise at the very beginning of the show about hallucinating music. You'd think human ears would be highly evolved, perfectly linear instruments.
But they aren't.
They aren't.
Far from it. The human ear is inherently nonlinear. The eardrum, the tiny bones in the middle ear, the fluid dynamics in the cochlea, they all have physical limits.
So when we hear 2 very loud sounds in a room, our own physical ear mechanics get pushed past their linear limits.
And they start squaring the input.
Our eardrums physically generate those sum and difference frequencies, ghost harmonics. We're literally hearing mathematical tones that do not exist in the physical air around us.
Our ears are fabricating the sound.
It's crazy.
It's a fascinating paradox, really. Audio engineers spend fortunes building hi-fi amplifiers high fidelity that are perfectly linear.
Right, so there's no distortion.
They work obsessively to ensure the amplifier doesn't add any distortion to the recording. But ironically, we don't mind our own ears' distortion.
The text actually jokingly asks why we find loudspeaker distortion so objectionable when our own biology is doing it to us constantly.
It's a great point.
But we don't just tolerate nonlinearity, we harness it to build the modern world. Like AM radio completely relies on it.
Precisely. AM stands for amplitude modulation.
Right. And I like to visualize this with water.
Oh, let's hear it.
Imagine dropping a tiny pebble into a huge lake. The little ripple it makes doesn't go very far before dying out. That tiny ripple is a human voice.
Okay.
Now imagine a massive speedboat tearing across the lake, creating a huge, powerful, repeating wake that travels for miles. That is the radio carrier wave.
Good analogy.
So what AM radio does is use a highly nonlinear circuit called a modulator. It forces that massive speedboat weight to physically carry the shape of your tiny pebble ripple for miles and miles.
And because the circuit is nonlinear, the two frequencies multiply.
Right.
The high-frequency carrier wave becomes modulated by the shape of the low-frequency voice. It travels through the air to your car antenna, where another nonlinear circuit in your dashboard catches it.
And it essentially unbakes it.
Exactly. It subtracts the big carrier wave out and leaves you with just the voice. The radio is just executing the math of sum and difference frequencies.
It's just so cool. But the implications go even further than sound or radio waves, because the exact same math applies to light.
It does, because the physics of waves is universal.
Right.
For a long time, scientists assumed the transmission of light through glass was perfectly linear. You shine a light in, the same light comes out.
Makes sense.
But modern lasers are capable of producing light that is so incredibly intense. And remember, nonlinear effects multiply exponentially with strong signals.
Wait, hold on. You're telling me that if I shine a laser pointer into a piece of glass hard enough, the physical glass distorts the light wave exactly like a chip guitar amp distorts a power cord?
That is exactly what happens.
No way.
Yes. The sheer intensity of the laser triggers a nonlinear response in the glass itself. The glass squares the input wave, which mathematically generates a second harmonic.
And a second harmonic of a red light wave is literally a different color.
It shifts the frequency right up into the blue spectrum. You shoot a massively intense pure red laser into a piece of glass, and a little bit of blue light actually comes out the other side.
It's the visual equivalent of playing a low note on a piano and hearing the octave ring out above it.
Yes.
It's an overtone of light.
It is the exact same fundamental math, echoing across entirely different physical domains.
That is incredible. Okay, let's do a quick recap here because we have covered some serious conceptual ground today.
We really have.
We started with Pythagoras realizing that pleasant musical chords aren't magic, they're just simple integer ratios.
Right.
Then Fourier proved that every repeating sound in the world is just a cake baked out of those simple harmonic ingredients, and he gave us the mathematical sieve to extract the recipe.
And we explored how the physical shape of our mouth filters those ingredients to create language.
Right. But then we learned the universe is fundamentally crooked. Pushing physical systems too hard causes nonlinear distortion.
Which creates ghost frequencies.
Exactly, which allows us to broadcast AM radio and literally bend red lasers into blue light.
It's just a perfect illustration of how scientific understanding builds on itself. From a plucked string in ancient Greece to the quantum nature of light, all connected by the hidden scaffolding of mathematics.
Which leaves me with a final, slightly mind-bending thought for you, the listener, to chew on.
Oh boy.
We talked about how the human ear is inherently nonlinear. It constantly invents ghost harmonics and beats that aren't actually in the air when things get loud.
Right.
So if our own biology is physically distorting the data before it even hits our brain, does objective, perfect, hi-fi reality even matter?
Wow.
Or is your brain always actively remixing the universe before you even have a chance to perceive it? Are we ever really hearing the world exactly as it is?
That is a profound question. I mean, if the instrument of perception is inherently flawed, the reality it perceives is inevitably customized just for you.
Definitely something to think about next time you put on your headphones. Thank you for taking this plunge with us today. Keep your ears open, keep questioning the hidden machinery of the world around you, and remember, even the simplest noise is hiding a masterpiece of math. Until next time. Welcome to another deep dive. If you're listening to this right now, I want you to just picture a chalkboard.
Yeah.
You pick up a piece of chalk and you draw a perfect smooth wave right across it. Up, down, it's symmetrical, it's clean.
And if you've ever taken like a high school physics class, it's incredibly familiar.
Exactly.
It's the classic sine wave, it's comforting, it's predictable. And as a representation of how the universe actually works in real life, it's entirely inadequate.
Yeah, nature just isn't a chalkboard. The real world is super messy, and our mission today is basically to shatter that simple image. We're going to explore the mind-bending reality of complex wave phenomena.
Yes, we are.
And our source material today is just an absolute treasure trove. It's chapter 51 of the legendary Feynman lectures on physics. So we are moving way past those introductory textbook sine waves to look at the advanced, chaotic, and honestly sometimes downright weird behaviors of waves.
Right, and I think the goal here isn't just to talk about the math either.
No, definitely not.
We really want to translate these dense physics concepts, the equations, the diagrams, into vivid, real-world phenomena. We're going to unpack everything from the terrifying silence of an atomic shock wave to the hidden reasons why ocean waves actually physically break at the beach.
Which I'm really looking forward to, because we are going to explore things that you see every single day, but probably never really understood on a mechanical level.
Right.
But before we get totally lost in the chaos, though, we should probably establish that there are still rules here.
Without a doubt, yeah. No matter how wild these phenomena seem, they are all governed by strict mathematical laws, laws of conservation and geometry. Chaos in physics is really just complexity that still follows the rules.
Right, right. So let's start with the source of the wave itself. Before a wave can change shape, something has to create it.
Exactly.
So what happens when the object making the waves decides to outrun the wave it's creating? Like, we're talking about breaking the local speed limit.
Okay, to visualize this, you have to think about expanding geometry. Imagine a bug sitting perfectly still on the surface of a pond, just bobbing up and down.
Okay.
It sends out spherical waves, like expanding rings. Now imagine that bug starts swimming forward.
All right.
It emits a ring, moves forward, emits another ring, moves forward. If the bug swims faster than the ripples can travel across the water, those circular rings start to overlap.
Because it's literally outswimming its own ripples.
Exactly. They pile up on each other, and all those individual circles form a distinct cone shape trailing behind the bug. If you look at it from above, in 2 dimensions, it looks like a giant V.
So does that V shape change depending on how fast the bug or, the object is moving, or is it always just the exact same angle?
Oh, it changes. It's based on a very strict mathematical ratio. The half angle of that cone is directly tied to the speed of the wave divided by the speed of the moving object.
Okay.
So the faster the object goes compared to the wave, the narrower the V becomes. It's a strict geometric relationship called a bow wave.
Okay, that makes sense. And what really stood out to me in the Feynman lectures is how this applies to sound. Because I always assumed that to make a sound, an object had to physically vibrate.
Right, yeah.
Like, it had to have some sort of inherent tone, like a guitar string or a vocal cord or something.
Yeah, that is a really common misconception. An object doesn't need to vibrate at all.
Really?
Yeah, simply by moving through a medium faster than the local speed of sound, the object physically forces the air to generate these conical pressure waves.
Wow.
The sheer motion of shoving the air out of the way faster than the air can naturally transmit pressure. That is what creates the sound. It's a sonic boom.
So wait, does this only happen with mechanical things like water and sound? Could a bow wave happen with something like, I don't know, light?
It absolutely can.
Really?
Now, we have to be careful here because, we all know the fundamental rule of physics. Nothing goes faster than the speed of light in a vacuum.
Right. The ultimate speed limit.
Exactly.
Yeah.
But light actually slows down when it enters a physical medium, like a block of glass or a pool of water.
Oh, because it's hitting things.
Right. Because the photons are interacting with the atoms in that material.
So the local speed limit drops.
Yes. The local speed of light in glass is significantly slower than it is in a vacuum. So if you have a high-energy subatomic particle, say, from a nuclear reactor, and you shoot it through that glass, that particle doesn't interact with the atoms in the same way.
Okay.
It can actually travel through the glass faster than the light around it can travel.
Wait, so it's literally a glowing sonic boom.
Essentially, yeah.
It's like a speedboat tearing through a lake, but instead of water, it's a subatomic particle tearing through glass and leaving a wake of pure light.
The mathematics of the speedboat wake and this glowing cone of light are remarkably similar.
Yeah.
In physics, this is called Cherenkov radiation.
Cherenkov radiation.
Okay, it usually emits this really eerie blue glow. And what's brilliant is that scientists use that exact geometric ratio we just talked about.
The V shape.
Exactly. By looking at the angle of that cone of blue light, they can calculate the exact speed and therefore the energy of those invisible high-speed particles.
Oh, that is so clever.
Right. That simple geometric insight won Cherenkov, Frank, and Tam a Nobel Prize.
That is amazing. Okay, so we've been talking about what happens when a source moves too fast. Let's flip it around for a second. What happens when the wave itself starts changing its own speed as it moves?
Oh, this takes us into the realm of shock waves.
Okay.
To understand how a wave changes its own speed, we have to look at how the speed of a sound wave is affected by its amplitude, or, its strength.
Right. So let's break down the mechanism there. Why would a louder or stronger wave travel faster?
Well, think about a massive high-pressure wave moving through the air. As it moves, it has to violently push the air out of the way.
Yeah.
It compresses the gas ahead of it. And when you compress a gas quickly, you are doing physical work on those molecules.
You're cramming them together.
Exactly. You are cramming them into a smaller space, which makes them bounce off each other with more kinetic energy. And higher kinetic energy in a gas just means higher temperature.
Okay.
This process is called adiabatic compression.
Let me make sure I'm following this. The compressed air is now hotter, right? And sound naturally travels faster through a hot gas than a cold gas.
That's the key mechanism.
Yeah.
Because the molecules in hot air are already moving faster, they can transmit the wave's energy to their neighbors much quicker.
Okay, say.
So the back of this big pressure wave is sitting in a zone of air that is just heated up. Because it's in hot air, the back of the wave actually moves faster than the front of the wave, which is, still pushing into normal cool air.
It's like the back of the wave is running on a moving walkway at the airport,
Yes.
while the front of the wave is stuck walking on the normal floor, so eventually the back is going to catch up to the front.
It catches up and the slope of the wave begins to steepen. It goes from a gentle rolling hill of pressure to a sheer vertical cliff.
Wow.
And that vertical cliff is a shock wave.
The Feynman lectures use the atomic bomb as an example to visualize this, and it is pretty chilling.
Yeah, it really is. The pressure bump from an atomic explosion is so massive that it heats the air tremendously.
Right.
So because the back of the wave is in such superheated air, the shock wave steepens and travels vastly faster than the normal speed of sound in the surrounding atmosphere.
So if you are standing miles away, you don't hear a rumble building up like thunder.
No. You hear absolutely nothing beforehand. Because the shock wave is traveling faster than the ambient sound ahead of it, there is literally no acoustic signal warning you that it's coming.
That is terrifying.
It outruns its own warning.
Yeah.
The very first thing you experience is the shock wave hitting you.
Wow. Okay, so let's translate the steepening effect to water, because the same principle applies, but you can actually see it with your own eyes.
Right.
Imagine you have a long, straight channel of water, and you push a large, flat piston down at one end.
Okay, so pushing that piston piles up the water into a bump. Now, a known hydrodynamic property of water is that long waves travel faster in deep water than they do in shallow water.
Okay.
As you push that bump of water forward, the water trailing immediately behind the bump is physically deeper than the undisturbed water in front of it.
Oh, so the trailing waves are moving through a deeper water column,
Exactly.
which means they travel faster and they run right up the back of the leading wave.
Yes, they pile up into this sharp, chaotic wall of water moving down the channel. Hydrodynamics calls this a bore.
A bore. It sounds a bit like driving a snowplow.
That's a great analogy.
If you drive a plow, the snow keeps piling up higher and higher in front of the blade. But here's where my intuition gets kind of stuck. If these trailing waves keep catching up and piling onto the front infinitely, shouldn't the wave eventually become a perfectly straight, geometrically vertical wall of water?
Well, the math certainly pushes it toward infinite steepness. The wave desperately wants to be a perfect vertical line. But if you push a snowplow too fast, the snow doesn't just form an infinitely tall, thin wall. Eventually, gravity and friction take over, and the snow collapses over itself or spills violently off the sides.
Oh, I see.
Nature just doesn't allow physical things to happen infinitely fast or be infinitely steep. There's always an energy loss to consider.
So what forces the wave to spill over then? Like, what is the physical limit?
It depends on the medium.
Yeah.
In the gas of a sonic boom, the energy goes into physically heating the air.
Okay.
But geometrically, a shock wave in the air cannot be thinner than the physical distance between the individual gas molecules bumping into each other.
Oh, wow.
Yeah, that tiny distance is called the mean free path.
The mean free path.
Right. And in the water channel, that spilling over you mentioned is the violent frothing white water you see at the front of a bore.
Oh, so that's what the white water is.
Yeah, the physical structure of the medium essentially fights back against the infinite math, dissipating the energy through heat or turbulence.
Okay, so we've been talking about air and water, where molecules basically just get pushed out of the way. But what if the medium can't be pushed out of the way easily? Like, what happens when a wave hits solid rock?
This requires a fundamental shift in how we think about the medium. Fluids, like a gas or a liquid, they don't have shear strength.
Meaning what, exactly?
If you push them sideways, they just flow. Solids, on the other hand, try to snap back.
Okay.
If you push sideways on a block of Jell-O, it resists your hand and wobbles back to its original shape.
Right.
Because solids have this internal structure, they can carry two distinct types of waves simultaneously.
Oh, I didn't know that.
Yeah, they carry longitudinal waves, which are compression waves where the material squishes back and forth, just like sound in the air.
Okay.
But they also carry transverse waves, or shear waves, where the material moves up and down, perpendicular to the direction the wave is actually traveling.
Does one of those travel faster than the other?
Your compression waves always travel fast.
Always.
Always. The material can transmit a straight squish much quicker than it can transmit a sideways wobble.
That makes intuitive sense.
Right. And the ultimate real-world laboratory for these solid waves is the Earth itself.
Okay, yeah.
An earthquake is essentially just a giant acoustic event. Two massive plates of rock slide past each other, creating an immense sound source inside the planet.
But the Earth isn't just one uniform block of solid rock. I mean, the density and the pressure must change dramatically as you go from the crust down toward the center.
They absolutely do.
Yeah.
Because the density of the medium changes. The seismic waves don't travel in straight lines through the planet. They refract. They curve and bend through the Earth's layers, very similar to how light bends when it passes through a curved glass lens.
And this leads to one of the most fascinating deductions in the source material, because this bending and traveling of waves is literally how humanity figured out what the center of our planet is made of.
Yes. It is an elegant piece of detective work.
I love this part.
Remember that transverse shear waves, the wobbly ones,
Right.
they require a solid medium with structure to snap back.
Right, like the Jell-O.
Exactly. They
Yep.
simply cannot travel through a liquid. So scientists looking at delicate seismographs on the exact opposite side of the globe from a major earthquake noticed a glaring anomaly.
Okay.
They received the fast compression waves, which traveled right through the center, but the slower transverse waves never arrived.
Never arrived at all.
Never. There was a massive shadow zone on the opposite side of the planet.
Wait, so we basically use the entire planet as a giant ultrasound machine.
That's a great way to think about it.
Yeah.
Yeah, by mapping out where those shear waves didn't arrive, scientists deduced that they must have hit a liquid roadblock.
Because that's the only thing that would stop them.
It was the only mechanical explanation for the shadow zone. We discover the Earth's liquid core by listening to the shadows of sound waves.
That is wild. But the deep dive gets even more intense when we look at the 1960 Chilean earthquake.
Oh, absolutely. That earthquake was so unbelievably powerful, so loud in acoustic terms, that the sheer energy of the waves traveled around the entire globe multiple times.
Wow.
It physically rang the planet Earth like a massive bell.
And because seismographs had become sensitive enough by the 1960s, scientists actually recorded this global ringing.
Right, and they took that massive data set and applied a mathematical tool called Fourier analysis.
Okay, so if you're listening to this and trying to visualize Fourier analysis, think about trying to unbake a cake.
Unbake a cake, I like that.
Yeah, you have the final cake, the incredibly messy, jagged earthquake data, and this tool lets you mathematically pull out the individual eggs, the flour, the sugar, or actually maybe a better analogy, it's like isolating the bass guitar track from a really dense, loud rock song.
The rock song analogy is perfect. The earth ringing is a very complex, messy chord. Fourier analysis separated that chord out into individual clean sine waves to find the dominant notes. They found the Earth's natural resonant frequencies, the exact acoustic pitches at which the entire planet naturally wants to vibrate.
But when they isolated that lowest note, they found a mystery buried in the data, right? The split mode.
The split mode, yeah. When they look closely at the fundamental frequency, the absolute lowest pitch of the Earth stretching and squishing, they expected to see one clean peak. One single frequency.
Sure.
Instead, the data showed a doublet. Two distinct frequencies right next to each other. One at 54.7 minutes and one at 53.1 minutes.
Why would the Earth have two slightly different fundamental pitches for the exact same physical movement?
The explanation comes down to the fact that the Earth is spinning,
Oh.
right? Imagine these massive seismic waves traveling all the way around the globe, radiating out from Chile. Some waves travel east, some travel west.
Okay.
Because the Earth is rotating, the waves traveling in one direction are experiencing the Coriolis force differently than the waves traveling in the opposite direction.
Nice.
It's like two trains running around the equator. One is fighting the rotation of the track beneath it, and the other is riding with it.
So the rotation of the planet itself physically alters the speed of the wave depending on which way it's going.
Exactly. The mechanics of the moving system split the frequency. We are literally measuring the rotation of the Earth using subterranean sound waves.
That is just incredible. Okay, so we've been talking about waves the size of a planet.
Yeah.
But if we go the completely opposite direction, like if we shrink a solid wave down, how short can the wavelength possibly get? Is there an absolute limit?
There's a hard limit. You cannot have a wave that is shorter than the spacing between the individual atoms of the solid material.
Because the atoms are the things actually doing the waving. You can't have like half an atom wave.
Precisely. The ultimate shortest possible solid wave is one where every single atom is moving in the exact opposite direction of its immediate neighbor. You can visualize the atoms in a solid lattice, like an endless series of heavy pendulums connected by stiff springs. The wave is just the kinetic energy passing between them. So you can't have a solid wave smaller than the atomic lattice itself.
Okay, so we've gone from the Earth's liquid core down to the atomic lattice. You would naturally assume that the solid Earth is the most mathematically complex medium we could look at.
You would assume that, yes.
But ironically, the Feynman lectures point out that the most confusing, messy waves are the ones you interact with at the beach or in your bathtub.
Oh yeah. Water waves are the ultimate mess of physics.
Which is funny because they are everywhere.
Right. They're often used as a simple introductory example in high school, which is almost a cruel joke because their underlying mechanics are incredibly complicated.
Why is water so much worse than a solid or a gas?
The key is that water is essentially incompressible.
Okay.
If you push down on a column of air, the air squishes. If you push down on the surface of a water wave, the water can't squish. It physically has to go somewhere else. It gets squeezed sideways, which pushes the water next to it upward. So a water wave isn't a pure longitudinal compression, and it isn't a pure transverse wobble. It is a messy combination of both.
So what are the individual water molecules actually doing as a wave passes by?
They're moving in circles.
Circles.
Yeah, circles. When a wave crest passes over, the water particles are traveling forward at the very top of a circle. They ride down into the trough, move backwards at the bottom of the trough, and then ride back up.
So if you're floating in an inner tube on the ocean, you aren't just bobbing straight up and down.
No, if you track your literal motion from the side, you are tracing a vertical circle in the air.
Yeah.
You physically move forward with the crest, and you get pulled backward in the trough.
This circular motion, it leads to a massive source of confusion about how water waves actually travel over distance. This is the concept of phase velocity versus group velocity.
Yes, and this is notoriously tricky to wrap your head around. Let's look at standard gravity waves. Normal ocean swells where gravity is the primary restoring force pulling the raised water back down. Okay, for these gravity waves, the phase velocity, which is the speed of a single individual wave crest, depends on its length. Long waves travel much faster than short waves.
Which explains why, if a big storm happens far out in the middle of the ocean, the long, gentle swells hit the beach days before the choppy, short storm waves arrive. The long ones won the race.
Exactly. They literally outrun the small ones. But here's the catch.
Okay.
The group velocity, which is the speed at which the entire cluster of waves travels together and carries the storm's energy, is only half the phase velocity.
Wait, so if you're trying to visualize this, the whole group is moving at half the speed of the individual waves inside it.
Yeah.
How does that actually work visually?
The best way to see this in real life is to look at the wake of a boat.
Okay.
If you watch a boat moving through a lake, it produces a distinct V-shaped group of waves. If you stop looking at the whole V and lock your eyes onto one specific ripple at the back of the group, you will see that individual ripple move forward through the group. It moves faster than the pattern itself.
So the ripple starts at the back, moves to the middle, gets to the very front, and then what happens to it?
It dies out.
It just disappears.
It shrinks and vanishes at the front edge of the group. And mystically, at the exact same moment, a brand new, weak wave appears at the back of the group to replace it.
Wow.
The waves are constantly flowing through the pattern, being born at the back and dying at the front.
That is mesmerizing to watch once you know what's actually happening. And that complex math just applies to normal gravity waves, right?
Correct.
What happens when the waves get really, really tiny?
Oh, when waves shrink down to tiny ripples, gravity is no longer the primary force pulling them flat. The main physical force changes to surface tension.
Okay, surface tension.
These are called capillary waves. Think of the surface of the water like a stretched rubber trampoline. The sharper you bend a tight membrane, the harder and faster it snaps back.
Okay.
Because of this, the rules entirely flip,
Why would tiny ripples act completely backward?
because surface tension dominates. For capillary waves, shorter waves actually travel faster than longer waves. The math goes in the exact opposite direction of gravity. Ocean swells.
So if I throw a jagged rock into a still pond, creating a sharp splash, I'm definitely not making one clean, simple wave.
Not at all. That sharp splash creates a chaotic spectrum of many different wavelengths. And because of a phenomenon called dispersion, they all instantly sort themselves by speed.
Oh, I see.
The tiny, fast capillary ripples shoot out ahead of the main splash, while the slower, longer waves lag behind.
Does this dispersion explain why ocean waves dramatically crash and break at the beach?
It does. Remember earlier with the water channel bore, how the speed of water waves depends on depth?
Yes, deep is faster.
Right. So as an ocean swell approaches the shore, the shallow water physically slows the front of the wave down.
But the back of the wave is still in slightly deeper water than the front.
Exactly. So the back is moving faster. It steepens into a contorted shock wave, it overcurves, and because the water molecules are moving in those forward circles we talked about earlier, the top violently breaks and crashes over the front.
Everything is connected. To bring all of this together, let's look at one final everyday example.
Okay.
If I am sitting by a stream and I am watching a duck paddling against the current, just trying to stay in one place,
Yeah.
the pattern of water around that duck isn't just a simple ripple, is it?
No, it is a highly specific stationary pattern of multiple wave types balancing against each other.
How so?
The duck is creating a continuous disturbance, and the water is flowing past it. Because capillary waves, those short, tiny ripples, have a group velocity that is actually faster than their phase velocity. They can push upstream ahead of the duck, fighting the river's current.
Oh, so you see a tight pattern of fine little ripples sitting right in front of the duck's chest.
Exactly.
And what about the water trailing behind the duck?
Behind the duck, you have the gravity waves. Their group velocity is much slower, so they get immediately swept backward by the river's current, creating those long trailing slurps in a V shape behind the duck.
So the entire system, the ripples pushing forward in front, the slurps dragging in back, is a stationary pattern perfectly mathematically balanced against the speed of the stream.
That's it. It's a perfect balance.
Well, we started this deep dive looking at the invisible bow waves of sonic booms and, glowing subatomic particles tearing through glass. We explored the thermodynamic cliffs of atomic shock waves and the churning bores of water channels. We mapped the liquid center of the Earth using seismic shadows. And we finally deciphered the dizzying circular math of a duck sitting in a river.
And the main takeaway here is that understanding these advanced wave mechanics isn't just an academic exercise. It explains the fundamental mechanisms of how energy travels through our universe. It shows us that beneath the chaotic, violent surface of a breaking ocean wave or the devastating unpredictability of an earthquake, there's a beautiful, decipherable set of rules at play.
It really fundamentally changes the way you look at your daily environment. And to prove that, I want to leave you with a final thought experiment you can try yourself.
Okay.
The next time you are pouring milk out of a jug into your cereal bowl, pour it just a little bit fast and look closely at the stream of milk hanging in the air.
Oh, that's a good one.
You won't just see a smooth white cylinder. If you look closely, you will see a distinct crisscross pattern of lines, like a tiny braided net sitting perfectly still on the surface of the falling milk.
Yeah.
Those lines aren't just random splashes, they are stationary capillary waves. They are governed by the exact same complex rules of surface tension, phase velocity, and group velocity that dictate a boat's wake or a duck fighting a stream. It is a tiny liquid symphony of advanced physics happening right over your breakfast. So the next time you picture a wave, don't think of that smooth, simple line drawn on a chalkboard. Think of the complex, chaotic reality pushing the universe forward.
Imagine you are standing in front of, like, a really large mirror.
Okay, picture it.
You look in, and everything is exactly as it should be, Your right hand is the reflection's left hand.
Right.
The room behind you is inverted. It is a completely predictable, totally symmetrical image. But then you wink your right eye.
And your reflection winks its left eye.
Exactly. It just does the wrong thing.
That is deeply unsettling.
Right. It's just this incredible fundamental breakage of the rules. And welcome to the deep dive, by the way.
Right.
Today, for all of you out there who just love to learn and experience those, massive aha moments, We are looking into the mirror of the universe.
We are talking about the day physics actually winked back with the wrong eye.
Yeah, we are unpacking a true masterclass today.
Yeah.
We're looking at Richard Feynman's legendary lectures, specifically Chapter 52, which is called Symmetry in Physical Laws.
It is a phenomenal piece of work.
It really is.
Right.
And our mission today isn't just to skim this stuff. We really want to decode the profound, sometimes super bizarre connection between the symmetries of the universe and the fundamental rules of reality.
We're basically asking one massive question. Is the universe perfectly symmetrical?
Right. So to even approach that, we kind of have to define the rules of the game. What do physicists even mean when they throw around the word symmetry?
Well, Feynman uses this beautifully elegant definition from the physicist Hermann Weyl.
Okay.
Weyl basically said that a thing is symmetrical if you can do something to it, and then after you've done that thing, it looks exactly the same as it did before.
Okay, so taking that and applying to physical laws like translation in space is a symmetry.
Exactly.
Meaning, if I build, I don't know, a complex chemistry experiment in my office, and then I build the exact same setup across town, it's going to react the exact same way.
Right. The universe doesn't care about your specific coordinates.
And that works for time, too, right? Like, running the experiment on a Thursday gives you the exact same results as running it 3 days later on a Sunday.
Yeah, the underlying physical laws are invariant under those translations, and this applies to rotation, too.
Meaning, if I just spin my chemistry set around.
Yeah, turning your apparatus 90 degrees doesn't suddenly change gravity or electromagnetism. And it also applies to uniform velocity, which is the principle behind Lorentz transformations.
Oh, like the train car example.
Exactly. If your experiment is inside a train car and it's moving at a smooth, constant speed in a straight line, everything inside behave as if the car were standing entirely still.
I follow that. But sure that not every single translation or transformation leaves the physics perfectly unchanged.
Well, what do you mean?
Take scale, for instance.
Right.
If I build a working machine and then I build an exact, perfectly proportioned replica of it, but I scale every single part up to be like 100 times bigger, my intuition says the physics should remain identical. It's the same machine, just way larger.
It's an incredibly common intuition, but the laws of physics are absolutely not symmetrical under a change of scale.
Wait, really?
Yeah. Galileo was actually one of the first people to articulate this mathematically.
How did he figure that out?
He was analyzing the bone structure of a dog, actually. He imagined this hypothetical superdog scaled up 10 or 100 times.
Okay.
And he realized that if you just scaled the bone up proportionally, the animal's massive new weight would just instantly shatter its own legs.
Oh, wow. Yeah, Feynman uses the example of a retired guy who builds these incredibly intricate, beautiful cathedrals out of little matchsticks.
Right, and they hold together perfectly at that scale.
But if you took those matchsticks and scaled them up to the size of massive timber logs to build a life-size cathedral, the whole thing would just completely collapse under its own weight.
Exactly.
It's like, building a towering skyscraper out of regular Legos.
That's a great way to think about it.
Right. Like, you can build a small tower just fine, but if you try to build a life-size skyscraper with standard Lego bricks, eventually the weight of the structure is just going to crush the bricks at the very bottom into dust.
That is exactly it. It's the square cube law in action. The structural strength of a pillar or a matchstick or a Lego or a bone scales with its cross-sectional area, which is squared.
Okay.
But the mass of the structure scales with its volume, which is cubed.
Oh, I see.
So as you scale up, the weight increases drastically faster than the strength of the materials holding it up.
Because matter is fundamentally atomic.
Right. There is an absolute scale to the universe. You can't just zoom in and out arbitrarily without fundamentally altering how physical forces interact with the matter.
Okay, so changing scale definitely breaks symmetry. What about the direction of time?
That's a fascinating one.
Because we established that the laws of physics don't change from Thursday to Sunday. But running time in reverse, that feels like a totally different story.
In what sense?
Well, in the macroscopic world, time has a really clear arrow. If I have like a sealed glass chamber with a divider gas on one side, vacuum on the other, and I yank that divider out, the gas expands to fill the whole chamber.
Right. Entropy increases.
Yeah, and I'm never going to see those gas molecules just spontaneously reorganize themselves back into one half of the box. An egg splatters, it doesn't unsplatter.
That is true in our everyday experience, absolutely. But that irreversibility you're describing, it's actually a statistical illusion.
An illusion? How so?
It's created by the sheer massive number of particles involved.
If you were to zoom all the way in, right down to the atomic level, and track the trajectory of just a single gas molecule bouncing off the walls, the fundamental laws of physics governing that specific collision are perfectly reversible.
Wait, so the physics itself doesn't care which way time is moving?
Exactly. If you could somehow instantly reverse the velocity of every single atom in that glass box, the gas would actually contract right back into the corner.
That is wild.
It doesn't violate any fundamental law of mechanics at all. The statistical probability of it happening randomly is just infinitesimally small. But the underlying microscopic laws possess perfect time reversal symmetry.
Okay, let's follow that thread. Because Feynman takes these symmetrical rules, space, time, rotation, and he connects them directly to quantum mechanics.
Yes, this is where it gets really beautiful.
He claims that for every single rule of symmetry, there is a corresponding, inescapable conservation law.
This is Noether's theorem. It was developed by Emmy Noether, and it is arguably the bedrock of modern physics. It dictates that continuous symmetries in nature are directly responsible for the conservation laws we observe.
I really want to understand the actual mechanics of that connection, though. Like, how exactly does moving an experiment across town translate into a conservation law?
Let's break it down. We said the universe doesn't care where your experiment is located, right?
Right, spatial translation symmetry.
Exactly. Because the laws of physics do not change from point A to point B, the mathematics of quantum mechanics strictly dictate that the momentum of a closed system has to remain constant. Space symmetry literally creates the conservation of momentum.
Okay, and what about the time symmetry we just discussed? The fact that the physical rules are the exact same on Thursday and Sunday.
That time symmetry is the exact reason why energy is conserved in our universe.
Really?
Yes. Energy cannot be created or destroyed entirely because the laws of physics are invariant across time.
Wow. And similarly, the fact that the universe doesn't care if you rotate your experiment.
That rotational symmetry mathematically guarantees the conservation of angular momentum.
I have to play devil's advocate here for a second.
Go for it.
I'm struggling a bit to see how an abstract mathematical symmetry actually enforces a physical reality. Like, it sounds almost like a neat accounting trick on a chalkboard. Does nature actually physically care about these mathematical symmetries?
It absolutely does. And to illustrate just how deep this goes, Feynman introduces a purely quantum mechanical symmetry.
Okay.
In quantum mechanics, particles are described by a wave function. You can kind of think of a wave function as having a magnitude, which gives you the probability of finding the particle, and a mathematical phase.
A phase, like phases of the moon.
More like a geometric angle. You can visualize it as the angle of a hand on a clock.
Okay, so a probability and a phase angle. Got it.
Right. Now, the rules of quantum mechanics state that if you shift the phase of that wave function universally, say, you just rotate that clock hand by 20 degrees for every particle everywhere, absolutely nothing changes physically.
Interesting.
All the probabilities, all the interactions, they remain completely identical. This is called a phase symmetry.
Okay, I follow.
But here is the really profound part. To maintain that symmetry locally, to allow the math to actually work out so that physics doesn't just break down when phases shift, the universe requires the existence of an electromagnetic field.
Wait, seriously?
Yes. And this specific, highly abstract phase symmetry directly enforces the conservation of electrical charge. Because the universe allows this invisible phase shift, the total electrical charge in reality can never, ever change.
So you're saying the invisible geometric architecture of the math is literally generating the physical guardrails of reality.
That is exactly what is happening.
That is incredible. But I want to pivot a bit to the symmetry of reflections. The mirror.
The winky mirror.
Yes, the winking mirror. We've established that space, time, and rotation preserve the laws of physics. So what happens if we build a really complex mechanical clock and then we build its exact physical mirror image?
Okay, a left-handed clock.
Yeah, we use left-hand screws instead of right-hand screws. We wind the springs in the opposite direction.
Sure.
If we start them under identical conditions, will they tick at the exact same rate?
For a very long time, physicists believed the answer was an unequivocal yes. This was known as reflection symmetry, or the conservation of parity.
The conservation of parity.
Right. The assumption was that if you perfectly mirror the entire physical system, the fundamental laws governing the gears, the springs, the friction, they all operate identically. Nature shouldn't care about left versus right.
But looking at the chemistry of living things,
Mm-hmm.
there seems to be a glaring exception to this. Life clearly prefers one side of the mirror.
Yes, biology is definitely biased.
We know that if you shine polarized light through sugar water, The sugar molecules rotate the light in a specific direction. And Feynman brings up alanine, which is an amino acid that is fundamental to biological life.
Right. There is L-alanine and D-alanine.
Yeah.
The L stands for levo, or left, and the D stands for dextro, or right.
Yeah.
They are perfect chemical mirror images of each other. Same exact atoms, same bonds, just a mirrored 3D structure.
Right. And if a chemist synthesizes alanine from scratch in a lab, they end up with a perfect 50-50 mix of the left-handed and right-handed versions.
Because the chemistry is symmetrical?
But living biology only uses the left-handed alanine. If you feed bacteria a 50-50 mix of lab-made sugar, they will entirely consume the left-handed molecules and completely ignore the right-handed ones.
It's true.
So if nature is completely symmetrical, why is biology so heavily biased toward the left?
It is a brilliant observation, but we really have to separate biology from fundamental physics here. The chemical rules governing those molecules are perfectly symmetrical. The left-handed and right-handed molecules contain the exact same energy, and they react identically to basic physical forces.
So why the bias?
The biological bias is not a fundamental asymmetry in the laws of physics. It is just a historical accident. Feynman illustrates this with the analogy of Cinderella's slipper.
How does Cinderella's slipper explain picky bacteria?
Well, a biological enzyme is a highly complex 3D structure. It acts like a mold or, a glass slipper designed to fit a very specific chemical foot.
Okay.
Billions of years ago, the very first self-replicating molecules just happened, by pure random chance, to be left-handed. It was a coin flip.
Oh.
Once that first molecular machinery was in place, everything that evolved from it had to use the same lopsided building blocks just to interface with the existing enzymes.
Right.
It's exactly like a left foot requiring a left shoe.
So it just got locked in.
Right. If you were to construct a completely mirrored frog with perfectly mirrored enzymes and mirrored DNA, its internal biology would function perfectly.
What?
But the moment it tried to eat a normal left-handed fly, it would starve. The enzymes just wouldn't fit the food. The physics of the frog remains entirely symmetrical. The biology is just locked into a billions of years old coin flip.
Okay, so biology's left-handedness is just a frozen accident of history. But that leaves us with a real problem, doesn't it?
What's that?
If life is just an accident, how do we fundamentally define left and right? Feynman introduces this great thought experiment for this. Imagine we establish communication with a Martian.
Or any alien intelligence on the far side of the galaxy.
Right. We can communicate purely through a radio signal, but we can't send them any physical objects.
So we can't just mail them a left-handed glove.
Exactly. We can't say, hey, look at the Big Dipper to orient yourself, because their night sky is totally different.
Sure.
We can easily explain our physical size. We say, hey, we are 17 billion hydrogen atoms tall. Hydrogen atoms are identical everywhere, so they can build a perfect ruler.
And we can explain our mass using atomic weights, sure.
But how do we tell them which side of our chest our heart is on? How do we explain left versus right over the phone, relying strictly on the fundamental laws of physics?
This is where it gets tricky. It requires us to look very closely at how physics handles directions. Specifically, the difference between what physicists call polar vectors and axial vectors.
Let's define those, because the distinction is subtle but really important for this Martian dilemma.
Absolutely.
A polar vector is just a straight translation in space, like an arrow pointing from my nose directly to the wall.
Right.
If you look at that arrow in a mirror, the head of the arrow reverses direction relative to the room. It flips.
Exactly. But an axial vector deals with rotation. Imagine a spinning wheel. If you look at a spinning wheel in a mirror, it appears to spin in the opposite direction. But the mathematical vector we use to represent that rotation, which is an imaginary axle pointing straight out from the center of the wheel, that vector does not reverse its direction relative to space in the mirror.
That feels a bit abstract.
Yeah.
How does that apply to us trying to talk to the Martian?
It applies directly to magnetism. A magnetic field is created by spinning electrical charges, so magnetism relies on axial vectors. If you build an electromagnet by winding a coil of wire, it creates a north pole and a south pole.
Right, and Feynman points out that if I put that electromagnet in front of a mirror, the reflection shows the wire winding in the opposite direction.
Yes.
And because the wire winds the other way in the mirror, the physics of electromagnetism dictates that the north pole in the mirror actually becomes a south pole.
It flips, yeah.
That feels like a massive asymmetry. The mirror physically swapped the magnetic poles. Doesn't that break symmetry?
It seems that way, but you have to look at the actual physical effect on another particle, not our human labels of north and south.
What do you mean?
If you fire an electron past that real-world magnet, the magnetic field will deflect the electron in a very specific direction. If you look at the mirror image, where the coil is reversed and the poles are supposedly swapped, and you fire an electron past that mirrored magnet, the electron gets deflected in the exact perfectly mirrored direction.
Oh.
The overall physical phenomenon remains flawlessly symmetrical. The reflection perfectly obeys the laws of physics. So, our Martian friend on the radio,
They're still completely clueless.
entirely clueless about what we mean by left and right. Magnetism doesn't break the mirror.
So parity is completely conserved. The universe just doesn't care about left and right.
Or so we thought.
Right, because this is the exact moment the story takes a massive, massive turn. Because parity conservation wasn't just a theory, right? It was basically an absolute article of faith in physics.
Oh, absolutely. Gravity, electromagnetism, the strong nuclear force holding atoms together, they all behave identically in a mirror.
But then physicists ran into a brick wall when they started studying the weak nuclear force.
Yes. The weak nuclear force is responsible for radioactive decay. And in the mid-1950s, researchers who were observing particle collisions from cosmic rays and early accelerators noticed a really serious anomaly.
The theta and tau puzzle.
Exactly. They discovered two short-lived subatomic particles, which they called the tau meson and the theta meson.
And the data on these two particles was just maddening. They had the exact same mass. They lived for the exact same incredibly brief fraction of a second before decaying. They were produced in particle accelerators in the exact same ratios. By every single measurable metric, the tau and the theta were the exact same particle.
But there was a glaring contradiction in how they died. The tau meson decayed into three smaller particles called pions. The theta meson decayed into two pions. Now, under the strict mathematical rules of parity conservation, it was believed to be utterly impossible for the exact same particle to decay in both of those ways.
Because the symmetries were different.
Right. The spatial symmetries of the 2-pion decay and the 3-pion decay were entirely different. One decay pathway conserved parity, the other flipped it.
So physicists were just stuck. They had to either believe nature, coincidentally, created two identical twin particles that just happened to decay differently, which makes no sense.
No sense at all.
Or the other option was that it was the exact same particle, and parity, the perfect mirror of the universe, was fundamentally broken.
Which was heresy at the time.
Complete heresy.
Yeah.
So to prove that, they needed an experiment. And in 1956, a physicist at Columbia University named Chien-Hsiung Wu, Madam Wu, devised a genuinely brilliant way to test it.
It's one of the great experiments in physics. Madame Wu focused on cobalt-60, which is a radioactive isotope that undergoes beta decay. It emits electrons via the weak nuclear force.
Okay.
She cooled the cobalt atoms down to near absolute zero
Wait, why so cold?
to stop the thermal jiggling. At room temperature, atoms are vibrating chaotically. By freezing them to near absolute zero, she could quiet the atoms down enough to actually manipulate them. She then placed them in a tremendously powerful magnetic field.
Okay, so they're frozen and magnetized.
Right. This field forced the spin of all the cobalt atoms to align perfectly in the same direction, parallel to the magnetic field.
Okay, I follow. So all the cobalt atoms are spinning the exact same way. Now, if the universe is symmetrical, when these cobalt atoms decay and shoot out their electrons, they should shoot them out symmetrically.
Right. Half up, half down relative to their spin.
But that is not what Madame Wu found.
No, she did not.
The cobalt atoms spat the vast majority of their electrons preferentially downward in a specific direction relative to their spin.
It was a truly paradigm-shattering moment. Let's think about the mirror again. If you were to build a mirror image version of Madame Wu's experiment, the spinning cobalt atoms in the mirror would appear to spin the opposite way.
Right.
In a perfectly symmetrical universe, that mirrored setup should shoot its electrons upward. But physics doesn't work that way. The weak nuclear force actually prefers a direction. The action is fundamentally, undeniably unsymmetrical.
Feynman captures the shock of this beautifully. He says, "The magnet has grown hairs."
It's a great line.
For the very first time, humanity found a fundamental physical phenomenon that distinguishes a preferred direction in space, which means we can finally get back on the radio with the Martian.
Yes, the communication problem is finally solved.
We can call him up and say, "Hey, Martian, gather some cobalt-60, cool it down to absolute zero, put a wire coil around it to create a magnetic field and align the spins. When the cobalt decays, watch which way the majority of the electrons shoot out."
The direction those electrons travel, that is definitively down.
Yes. And based on how the current is flowing in your coil relative to that down, we can mathematically define what left and right are. We can finally tell them which side of our chest the heart goes on.
It is a massive triumph of experimental physics. But, of course, this revelation immediately raised a terrifying theoretical problem.
Because of Noether's theorem.
Exactly. Symmetries are intimately tied to conservation laws. If reflection symmetry is broken, if the universe fundamentally treats left and right differently, does that mean the entire foundation of physics is flawed?
So to fix the foundation, physicists had to look at another completely radical concept.
Yeah.
Antimatter.
Right. Paul Dirac had predicted mathematically that for every fundamental particle in the universe, there must be a corresponding antiparticle.
And it is crucial to understand what antimatter actually is. It isn't just normal matter with an opposite electrical charge, right?
No, it's much more profound than that. Yes, an antiproton has a negative charge while a proton is positive. But an antiparticle possesses an entirely opposite set of quantum numbers across the board.
So they're true opposites.
Completely. If a particle of matter and a particle of antimatter collide, they don't just bounce off each other, they completely annihilate, converting their mass instantly into pure energy.
Okay, so let's revisit our mirrored clock problem with this new knowledge.
Let's do it.
We established that because of Madame Wu's discovery with the weak force, if you build a clock and then build its exact physical mirror image out of normal matter, they actually won't run identically.
Right. The weak nuclear interactions decaying inside the atoms of the gears have a slight lopsidedness to them.
So the left-handed clock ticks very, very slightly differently than the right-handed clock. Spatial symmetry is just broken.
However, theoretical physicists realize something astonishing that actually restores the balance.
What's that?
If you build your right-handed clock out of normal matter, and then you build your left-handed mirror clock out of entirely antimatter.
Oh, wow.
They run exactly, flawlessly, identically. Nature didn't abandon symmetry. She just combined two separate rules into one grander reality.
This is known as CP symmetry, right?
Yeah. Exactly. Reversing the space, the parity breaks the rules. Reversing the charge-switching matter to antimatter also breaks the rules.
But if you do both...
If you reverse the space and swap matter for antimatter at the exact same time, the universe behaves perfectly. Right-handed matter is perfectly symmetrical to left-handed antimatter.
It's just an incredibly elegant solution.
Right.
But Feynman includes a very serious, very practical warning regarding our Martian friends based on this.
Oh, the handshake warning.
Yes. Let's say our radio calls go so well that we decide to meet up in deep space. We build our rocket, they build theirs, we meet in the middle, we open the airlocks, and we walk toward each other. The Martian reaches out their hand for a friendly handshake.
Okay.
If they reach out with their left hand, do not touch them.
Definitely do not touch them.
Yeah.
Because if they reach out with their left hand, it means they followed our cobalt instructions for defining right, but their reality naturally produced the mirror image result.
And the only way their physics would produce the mirrored result
Is if their entire biology, their entire planet, and their entire solar system is constructed out of antimatter.
So if you shake that left hand, you will both instantly annihilate into a blinding flash of gamma rays.
But just wave from a distance.
Yeah, a polite wave is fine.
It is such a profound realization about the fabric of our universe. But, it leaves us with a lingering philosophical puzzle.
Why is nature only almost symmetrical?
Exactly. The strong nuclear force binding atoms is symmetrical. Electromagnetism is perfectly symmetrical. Gravity is symmetrical. But then there is this one tiny, weak nuclear force that just throws the entire architecture slightly off balance.
Feynman shares a really beautiful analogy for this at the end of the chapter. He talks about a famous, incredibly elaborate gate in Nikko, Japan.
Oh, I love this story.
It is covered in intricate wood carvings, dragons, pillars. It is a masterpiece of absolute geometric perfection. But if you look very, very closely at one of the pillars, there is a single small design element that has been purposefully carved upside down.
A deliberate flaw.
Yeah. The story goes that the master carvers did this intentionally, introducing a tiny, deliberate flaw so that the gods wouldn't become jealous of human perfection.
Wow.
And Feynman muses that maybe the underlying architecture of reality was made only nearly symmetrical so that we wouldn't be jealous of perfection.
It is a deeply poetic way to frame a brutally complex dynamical problem. A mathematically perfect circle is easy to explain. But a circle that is fundamentally flawed, just slightly dented on one side,
Hmm.
that requires a massive amount of explanation.
Right.
That tiny flaw in the symmetry of the universe is the thread theoretical physicists are still pulling on today.
And I want to leave you, the listener, with a final thought, to ponder something you can just mull over on your own that builds directly on everything we've unpacked today.
Okay, lay it on us.
We learned that matter and antimatter are the perfect mirror images of each other. But if the universe started perfectly symmetrical, with exactly equal amounts of matter and antimatter, they should have completely annihilated each other in the first fraction of a second after the Big Bang.
Leaving a universe filled with nothing but light.
Exactly. But they didn't. We are here. You are here. We exist solely because of a broken symmetry. Somewhere, deep in the microscopic architecture of reality, the mirror winked with the wrong eye, and the universe produced slightly more matter than antimatter.
Just a tiny imbalance.
Just enough.
Yeah.
So what other invisible microscopic imperfections, what other tiny glitches in the fundamental laws of physics might actually be the very things holding our messy, beautiful reality together right now?